Hello and welcome. I would like to provide a demonstration of solution to our previous challenge, which was to write a program that generates prime numbers. And so again, the whole point of this program was to use an array. You want to learn all about arrays by doing this. So I tried to describe the prime number algorithm before, but to just mention it again, you can check whether or not a prime is a prime number. It basically means that if the prime number, it means that it's not evenly divisible by any other prime number. And so that's the notion algorithm that we're going to go by. And the reason that's why it's a prime number is because if it's any non-prime integer can be expressed as a multiple of prime factors. So for example, 20 has the prime factors 2, 2, and 5. And so by knowing this tells you that prime numbers are not evenly divisible by any other prime number. And so this can help make a very efficient prime number test. And so what you can do is you can check the previously generated prime numbers. And so we can store our previously generated prime numbers in an array, and that's how we can find this information. Also, any non-prime integer n must have as one of its factors an integer that is less than or equal to the square root of n. So this means that it's only necessary to determine if a given integer is prime by testing it for even divisibility against all prime factors up to the square root of the integer. So you can stop right there, and again, it makes it more efficient. This is going to be noticeable in my inner loop when I jump out to determine if I haven't found a prime number. I'm going to jump out if I can't find if I get to the square root of the integer. It's an exit condition essentially. So let's go through, and the way that you can check for that is you just say p divided by primes is greater than prime sub I. And we'll use that in the innermost loop to test whether or not the value of p exceeds the square root of the primes I. So let's go ahead and bring up code blocks and start writing some code. We're going to do the basics here, create a project. We'll name our project called primes. So let's go to new project, and let's go to console application, and we're going to name it primes. Say next. We're not going to use this compiler. We're going to use I was playing around with compilers. I want to make sure I have the right compiler. I'll just use the Sigwin compiler. Say finish. So this generated my main source file, and it's empty. Let's get rid of the printf and start writing some code. So we're going to start off by basically we're going to include a file called standard bool so that we can. I haven't done this yet. I've been creating my booleans as underscores, but we want to be able to just say, I think this should be good. Let's just do a little test. I want to be able to do bool. Yeah, okay, so now we can use bools. So normally in C89, the data type for true or false is underscore bool, but you can actually have a type definition in later versions and in the standard bool file to just use bools, and it also allows you to use true false as values. So we got to create some variables here first. We're going to create our counter, which we're just going to name p. That's going to be our counter for our loop from when we check from p to 100 numbers. That's going to be our outer loop. We're also going to create a variable for our inner loop counter. This is where we check our previous primes. We're going to set that to, actually we won't initialize it here, we'll initialize it in the loop. We're going to create our array, which is going to be an integer of primes, and it's going to be size 50. And we're not going to initialize it to anything but 0 for now. And then we're going to create a prime index, and this will help us skip all of our even numbers. And we're just going to set that to 2. Or this variable is actually going to make sure we start at the correct index, because we're going to hard code the first 2 numbers. So that's what we're going to do first. We're going to hard code our first 2 prime numbers. So this is how we can access the array. We know how to create an array on line 10. You just specify the data type, followed by the name, and then in the square brackets we specify the size. And then we're initializing everything to 0. This is a C99 trait that we can do. And to assign data to an array, I can just say the array name and then the index value. Remember, arrays are 0 based. So I'm going to say prime sub 0, and the first prime is going to be 2. 2 is the first prime number. The second prime number is going to be equal to 3. This way I have some prime numbers that I can previously test to see if, to find additional primes. And now comes our looping. We're going to need a outer for loop that goes through all the numbers from 5 until 100. We know 4 is not a prime number, so I'm just starting at 5. So we can say for p equals 5, p is less than equal to 100, and then we're going to skip even numbers. So we're going to say p equals p plus 2. We don't need to look into any numbers. And that's going to be our outer loop. And again, you should be testing as you're going. Now we're also going to set up a Boolean variable which will tell us whether or not we found a prime number. So here's where I can use bool, and I'm going to just create a local variable Boolean is prime. And I'm going to have that initialized to say is true because I'm only going to set it to false if I've gone through the entire list of previously generated primes, or I've got to the latest prime and make sure it's not the square root. So is prime is going to be equal to true for each iteration from 5 to 100, skipping 2s. Now my inner loop is going to go through all of our prime numbers that we have previously generated, and it's going to go until we see the make sure the square root is not, we haven't gone greater than the square root of the I. So we're going to go through all of the numbers until we get to the square root. That can be our exit condition. We're also going to exit if we found a prime number. So we're going to say if is prime is true, and we've gone through our limit, which is going to be p divided by prime sub I is greater than or equal to primes sub I. And then we're going to plus I as our loop control variable. This is really the key to the algorithm. So we're going to try to find all our primes from 5 to 100, skipping even numbers. And then in our inner loop, we're going to start at 1. We're going to go all the way until we either set is prime to true, or we've reached our exit condition, which is the number p divided by prime sub I is greater than prime sub I. And that's essentially ending to make when we find a square root, because that's another condition of the algorithm. And if either one of those, if that's our loop, inside of our loop, we're going to actually check for primes. The way that you know a number is prime is you divide it by the number, and if it's not divisible, if you don't have a 0, then you're good to go. So you can just do a p mod prime sub I equals 0. And if that is true, then you don't have a prime number. So you can set the Boolean equal to false. And then that's what we do for the entire loop, because all we're doing is we're going to set the Boolean to false. And that will tell us we didn't find a prime number, so we don't want to add p to our primes array. Okay? So the last thing to do is we just check for if the Boolean was set to true. If it was set to true, then we want to fill in our array. We want to add it to the array. So we're adding to the array as we find primes. So we just say primes, and then we say prime index, because remember, this is the one that's really represented by the index for where we want to put into the array, which is we want to start at element 3, which is index 2. So we want to make sure we put it in the right spot in the array, and we just set it to p, because p was the prime number that we found, because remember, this is the outer for loop. That's the prime. We're trying to check if that's a prime number. We start at 5. We say if 5 is going to be prime if we can go to these numbers starting at 1 and then compare against any previous primes, and if it's not divisible by 0, then we're good. And we have to do that for everything. And then the last thing we want to do is we just want to increment that prime index, so the next time we find a prime number, we're in the right index. And that is it. And this is the entire algorithm to find prime numbers. So you want to save that and build it, make sure everything's good to go. We're good. So I like adding the true-false values by including standard bool. Don't forget about that. And then the last thing we have to do is we just have to print out the prime numbers. So we can just have a simple for loop. And we're going to print them all on the same line. So we're not going to add a line feed. So what we're going to do is we're going to reinstantiate our loop control variable to 0, I. We're going to go all the way to our prime index, which is going to be the size of everything in the array, and just print it out in a single line, %I or D, and prime sub I. And then at the very end, we'll add a line feed. Something like that, with a semicolon. But again, things to notice in this program. First, notice the indentation. It's all the blocks are indented. We sometimes use brackets when we have more than one statement inside of our blocks. Sometimes we don't. In this if statement on line 25, we didn't use any brackets. For loops should become somewhat second nature by now. Really what you want to gain from this assignment is the arrays. So we're creating an array called primes, setting it size 50, initializing everything as 0. And then we're setting the first two elements to 2 and 3. And then this whole algorithm from 19 to lines 32 is determining if it's prime by looking at the array in the previous prime numbers, and also jumping out when you're greater than the square root. And so again, you see a lot of square brackets here to access arrays and to assign values to arrays and everything. It's pretty straightforward. So let's build this and see what happens. We have no warnings, no errors. If we run this, what you see as output is all the prime numbers to 100. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and so on. Those are all prime numbers, right? And prime number is something that only has, is only a factor of itself. You can't divide that by any other number and have no remainder. All right, so 97, the only two factors that go into that are 1 and 97. So again, a nice little quick program. I'll provide the solution. You can analyze it. But again, take key takeaways, everything about the arrays, and also the standard bool that I used that allowed us to create Boolean data types without the underscore capital B, and also allows you to use true false values as opposed to 1 and 0. Hope this helps. Thank you. Hello and welcome. In this lecture I want to talk about multi-dimensional arrays. Up until this point, if you've thought of an array, you just said an array is a variable that can store many types of data. It can get more complicated than that. You can have basically many dimensions of an array. So if you just have a linear array, which is what we've discussed so far, that's called a single dimension. And we know it's a single dimension because it just has one brackets with one size. The C language allows arrays of any dimension to be defined. So this is kind of thought of like a nested array, an array of an array. So two-dimensional arrays are the most common, but you can actually do three-dimensional arrays, four-dimensional arrays, five-dimensional arrays. But there's not many use cases for 3, 4, and 5. Really, you're either going to have a single-dimension array that you use in your program or a two-dimensional array. Two-dimensional arrays are common because they essentially represent, for example, like rows and columns in a spreadsheet. That's how you can kind of visualize it. Or a matrix, or a table. That's a two-dimensional array. You have rows and you have columns. So you can store more data than a single-dimensional array by specifying the sizes. But it's very applicable because it looks like a matrix. And there are applications that you may want to write that has this concept of a matrix. Specifically, a mathematical application would be most relevant here. But you can use to do two-dimensional arrays for many different things. One example is a matrix. But again, visualize it as a table. Two-dimensional arrays are declared the same way that a one-dimensional array is. The only difference is you now have another set of brackets. So in this example, we're declaring an array named matrix of type int, which has 4 rows and 5 columns. That means you can store 20 elements inside that two-dimensional array. So you should know how each dimension is specified with its own pair of square brackets. That's how you can easily spot how many dimensions an array has. If you had 3 brackets there, that would be a 3-dimensional array. If you had 4, it'd be 4. This one has 2, so it's 2. And up until the earlier lectures, we only had 1, so we knew that was a single dimension. All right, so look at the brackets. Pay attention to that. Again, 4 rows, 5 columns, total of 20 elements. To initialize a two-dimensional array, it's going to be initialized in the same manner of a one-dimensional array. Same type of syntax, you're just going to add more. So when you list the elements for initialization, the values are going to be listed by row. And the difference here is that when you put the initial values for each row in, you're going to do it between braces, curly brackets. And then you're going to enclose all the rows between braces. So it's going to look something like this. If we create an array of numbers, which is of 2 dimensions, 3 rows and 4 columns, and we want to initialize it, all you have to do is put inside curly brackets the entire array, and then add inner nested curly brackets for each row. So here we're initializing values 0 sub 0 to 10, 0 sub 1 to 20, 0 sub 2 to 30, and 0 sub 3 to 40. And that's how you access multidimensional arrays too. You access them with the row and the column. You just have to remember that it's 0 based. So the upper left hand coordinate there, the upper left hand, which would be row 1, column 1, would be 0, 0, and that'd be equal to 10. Row 1, column 1, column 2, I'm sorry, would be equal to 20. But you would access it as numbers 0 sub 1. So the first element, because the first array contains 3 rows, that when you access it, that's the number you specify for the row number. And then the column number is the next specification for accessing the array. But initialization is pretty simple. Just separate things by commons with the brackets. And accessing them, you would access it just like you access a normal array, except now you're accessing this concept of a row and a column. So the use of the inner pairs of braces is actually optional, but you should use it for readability. If you didn't provide those braces, you could actually just provide 10, 20, 30, 40, 15, 25, 35, all just consecutively. But it's very hard to visualize what you're initializing. As a programmer, readability is very, very important because it increases the quality of the code. It's easier to maintain the code. When I look at this right here, I can easily identify, especially with the comments, what I'm initializing to. What values and what rows are going to initialize to. If I had that as a single line, just consecutive numbers, I would get lost really quick. So although the inner brackets are not necessary, use them. As with a one-dimensional array, it's not required to have the entire array be initialized. You can just initialize certain areas. So in this example, we're creating an array, two-dimensional array, with 4 rows and 5 columns. We're only initializing the first 3 elements of each row. So row 1, column 1 is 10, row 2, column 2 is 5. I'm sorry, row 1, column 2 is 5, and row 1, column 3 is a negative 3. And the same for the second column and so forth, 9, 0, 0, 32, 21, 0, 0, 8. For the ones that we did set, the 4th and 5th values of each row, those are actually going to be set to 0 automatically because we left them out. And in this case, you actually have to provide the curly braces, the inner ones. Because here, if we didn't, the initialization would be all screwed up. Because if you didn't have the curly braces, it would just do it consecutively. So what would happen is, this would actually initialize the first 12 elements. So it would initialize all the elements in the first row, all the elements in the second row, and then the first 2 elements in the third row, and then the rest of the elements in the third row, the rest of the elements in the fourth row would be 0. Again, this is a two-dimensional array of 4 rows and 5 columns. It would just do them consecutively. So don't forget the braces if you only want to specify certain initialization elements. You can also do designated initializers. Remember, this is the C99 concept. That's optional in C11, where you can specify specific indices to be initialized. So you can use subscripts in the initialization list, just like in a single dimensional array. If you want to do a designated initializer, you would just do something like this. So here we're declaring our matrix array of 4 rows and 3 columns, but we're actually specifying that 0, 0 is equal to 1, 1, 1 is equal to 5, and 2, 2 equals to 9. So when we say 2, 2 again, what we're saying is row 2, which is really row 3 because we start at 0, column 2, which is really column 3. Again, visualize this as a table or a spreadsheet, and accessing the elements start at the top left-hand corner. But if you understand that the 4 represents the rows and the 3 represents the columns, it's pretty intuitive after that. So what this is doing is it's initializing the 3 indicated elements of the matrix to specified values. But what you should notice here is the syntax. All the unspecified values here are going to be 0 by default. So this is only going to initialize 3 values. Each set of the values that you do initialize are going to be the elements in a row is between braces. And then the entire initialization goes between another pair of braces. So you see that we have the curly brackets on the outer ones, just like normal initialization. And then we have the brackets to access the array inside. And then we have commas to separate each row. And each set of row values is separated from the next set by a comma. So the values are separated and also the row indices. So notice that. Now, just because we said that we have 2 dimensions and we've been talking about that, you can actually have many other dimensions. Everything I've talked about with 2 dimensions also applies to 3 dimensions, 4 dimensions, 5 dimensions. So if you wanted to declare a 3-dimensional array, you would do it with 3 square brackets. So here's an array named box of type int of 10, 20, and 30. You might want to use a 3-dimensional array maybe if you were, I don't know, maybe if you were storing XYZ values of some sort. You probably won't need to do this. 3-dimensional arrays and up are really not common. But you can visualize a 1-dimensional array as a summary. You can visualize a 1-dimensional array as a row of data, single row. 2-dimensional array as a table, a matrix, or a spreadsheet. And a 3-dimensional array you can visualize as a stack of data tables. So a stack of tables. If you needed that much data, it's going to be really hard to access it and probably confusing. And anybody that's maintaining this program for a 3-dimensional array or above is probably going to get lost trying to figure out what's going on. But you can do it. Again, and if you're ever going to need to iterate through any of these 1, 2, 3-dimensional arrays, you're probably going to use a loop. And the more dimensions you have in the loop, the more nested loops you're going to have. So if you want to process a 3-dimensional array, you're going to have 3 nested loops. And if you want to process a 4-dimensional array, you're going to have 4 nested loops. So as far as initializing an array that's higher than 2 dimensions, again, you're going to apply the same type of thing. You're just going to extend it a bit. So a 3-dimensional array will have 3 levels of nested braces, with the inner level containing a set of initializing values for each row. So it would look like something like this. Here we have a 3-dimensional array, 2, 3, and 4, a stack of data tables essentially. And the first block of 3 rows we're going to initialize, and the second block of 3 rows we're going to initialize. So what this is saying is, again, first block and second block, because we didn't initialize the third and the fourth block, just the first and the second. So we have 4 blocks, and you can think of as each block a stack of data tables, each block having rows and columns. So the first block is going to be initializing just the first 3 rows, which is all we have is 3 rows. And then the second block is going to initialize the next 3 rows. But the third and the fourth blocks are not going to be initialized. If you wanted to initialize the third and the fourth blocks, you'd have more inner braces, curly brackets, and so forth. Same thing applies though for the ones that you do not initialize. They'll be initialized to 0. But again, you can see how it gets very tedious and also very hard to follow. When you want to process the elements in a dimensional array, I mentioned you're going to use nested loops. Again, it's going to correspond directly to the number of dimensions. And each loop is going to iterate over 1 array dimension. So it's going to look something like this. This is an example of a 3-dimensional array. You have an outer loop, and then you have 2 inner loops. The outer loop is going to be the first outer array, and then the second one will, so the outer loop would essentially go through the rows. The second one will go through the columns, and the third one will go through the blocks. Again, what you should be noticing is, wow, this gets really hairy and really tedious really fast. So try to avoid 3-dimensional, 4-dimensional arrays. And I don't even see many use cases for it. 1 and 2 are really all you're going to use. But understand, multi-dimensional arrays are a possibility in C, a way of storing more data and accessing the same name with many data elements. Thank you. Hello and welcome back. I'd like to provide you with another challenge, another assignment. This assignment's going to deal with multi-dimensional arrays. Get a little more familiar with them, mainly a 2D array, as it is something that you should understand. So in this challenge, you're going to create a C program that uses a 2-dimensional array and a weather program. This program will find the total rainfall for each year, the average yearly rainfall, and the average rainfall for each month. So those 3 things are going to be output. The input is going to be a 2-dimensional array with hard-coded values for rainfall amounts for the past 5 years. So what this means is you should create a 2D array that has 5 rows and 12 columns. The rows are going to represent the past 5 years, and then the columns are going to represent the months. So how much rain you got in January, February, March, April for each year. And the rainfall amounts should be floating point numbers. So because you often get, 7.8 inches for rain for a month, they're going to need to be floating points. So you should, when you create this 2-dimensional array, make sure that it's a float. The output for the program is going to look something like this. Here I just kind of formatted it a certain way, but what you should first display as output is everything that's in the 2D array. So you should have just a simple loop that goes through the 2D array, displays the year for the array, and the year is just going to be whether it's the first row, the second row, the third row. You can just create an integer and increment it. And then the rainfall is going to be all of the rainfall for all of the months. So you have to add them as you go. So what you should first do is you should actually have a for loop and an inner for loop and go through it to calculate the total rain for each year. And then have a loop to print it out. And also in that first loop, or actually you probably want to create a second loop with an inner loop that goes through all of the months for each year and calculates the monthly averages. So again, the way that I envision the design for this program is 2D array, floating point numbers. You're going to need to initialize it with all hard-coded data. You're then going to have basically, you're going to have a first loop which is going to go through and it's going to calculate the totals for the entire year. And then it's easy to get the yearly average because you just take the totals and divide it by the number of years, which is 5. So the yearly average you don't have to calculate in a loop, but you will need to calculate the total rainfalls for each year in a loop. And so I would have a loop. You're going to have an inner loop, right? Because every dimensional array you have to have an inner loop. 2 dimensions have one inner loop. So an outer loop and an inner loop, a nested loop, I should say. And you go through your first array, you start at the year. And so let me go through my tips, actually. I think I put this in the tips. But this is the output. You can format it any way you want, but what I'm seeing here again is yearly rainfall, yearly average, and then monthly averages. So you want to initialize your 2D array with hard-coded rainfall amounts. We know how to initialize an array. For a 2D array, you can initialize rows. So you can have brackets inside of the brackets to represent each row. And each row has 12 columns, so you would have 12 values, 12 floating point values. And then you separate each row by commas, and you just create new brackets. We should know how to do that. And then again, just a reminder, to iterate through a two-dimensional array, you're going to have a nested loop, basically one inner loop. If it was a 3D array, you'd have to have 2 inner loops. The key to this solution will be to visualize a 2D array and understand how to iterate through one via nested loop. If you know how to iterate through a nested array or a 2D array, you're going to be fine. As you are iterating, you can keep a running total, which is our first set of loops. An outer loop will iterate by the year, and the inner loop will iterate by the month. And you can keep a running total to get the total rainfall for all years. So your first goal should be to just get that total rainfall for all years. And as you're getting the total rainfall, you can just print out the yearly total as well. Then, after you're out that loop, you can print out the yearly average. Then you're going to need another loop to display the monthly average. And to display the monthly average, you want to have a loop that has the outer loop for each month, and the inner loop goes through each year. All right, and this will give you average. I think this will give you monthly average. I may have missed. This will give you the monthly averages. So the yearly ones can be in that first loop, and the monthly will be in the second. So that should say to get the monthly average rainfalls. So you're going to learn all about initializing arrays. You're going to understand how to iterate through a two-dimensional array. A lot of important concepts here. Good luck, and I'll provide a solution in the next lecture. Thank you. Hello, welcome back. In this lecture demonstration, I want to provide a solution to our weather program that I talked about in our previous challenge. So let's start up code blocks and create a project. I'm going to name this project Weather. And again, just a reminder, this application is going to allow us to get yearly and monthly averages or yearly totals and monthly averages for rainfall amounts. Name this Weather. And there we go. Okay, so right at the top, you want to provide comments telling you what the program is. Again, this program is going to be finding yearly totals, yearly average, and monthly average for several years of rainfall data, 5 years essentially. So right at the top, I'm going to define a couple constants, and we haven't gone over the define preprocessor directive in detail yet, but you're familiar with this. It's not real complicated, so I'm going to include it, and I want to write nice quality code. So I'm just going to define one that's called months, going to be equal to 12, and a constant. You can also use the constant modifier. And I'm going to also define one that's called years equal to 5. That's where we're going to start. And the first thing we really want to do in our main function is we want to create our array, which is a two-dimensional array, and we want to initialize the data. So we're going to initialize rainfall amounts, rainfall data for, say, 2010 to 2015. Or 2011 to 2015 or something. And so we know how to create a two-dimensional array. We just specify the data type name, and I think this should be a float because floats have decimal spots and rainfall amounts can be decimal. So we're going to just say float. We're going to name it rain, and then we're going to specify that we want to have 5 rows and 12 columns. So we're just going to say years, which is our constant, and months. And then we're going to initialize it. We've declared it of that size, and now we want to initialize it. And you can initialize it by having brackets, just like that. And then you can have inside brackets for each row. We could also make this array a constant if we wanted to, but we're not going to. Now I have already done this data, and I don't want to type in, what would this be? This would be 10 times 50, or 12 times 5, that would be 60 elements. I don't want to type in 60 elements right now because it's going to take up time and you're just going to sit there and fall asleep. So I'm going to copy and paste in my initialization and initialize some data. And this is just some dummy data. It might not be correct, but you'll see that we have brackets for each row, and so we have 5 rows. We're separating each row by a comma. And we have these curly braces inside there for each row. And then inside the curly braces, we're separating each monthly value by a comma. So we're separating by rows by commas, and we're separating values inside rows by commas. Here's a bunch of yearly rainfall amounts. So for example, this first row would represent year 2011, and the first column would be January. So in January of 2011, we had 4.3 inches of rain. Down here, if we were to look at let's say look at 6.7, this would be for the year 2012-13. For the month of March, we had 6.7 inches of rain. Right? So you can see how this represents years and months for rainfall. Now that we've initialized all of our data, we can actually initialize or create our other local variables. So we're going to just create a year and a month, because this will help keep our yearly totals or keep our year straight and our month straight. So I'm just going to say year, month. I'm going to create them on the same line. And I'm also going to create a couple floats, subtotal and total. Subtotal will be yearly totals. Total will be the total rainfall so that I can get the yearly average. And we'll also figure out how to get monthly averages. So the first thing I need to do is I need to have a for loop that's going to print out our rainfall for a particular year. So first I'm going to print out on a single line, I'm just going to print out year, and I'm going to add a tab to it to make it better formatted. Let's add 2 tabs. We'll see how this looks once I display it. And then I'm going to put rainfall, and I'm going to put that in inches, and I'm going to add a line feed. And again, you would want to test this to see what it looks like. And then I'm going to go into my loop. So what do I want to do? I want to go, in order to calculate the subtotals for each year and display them, I want to go through all of the rows, all of the years, and then for each year, I want to go through all the months because I need to add the months up. So our outer loop is going to start off with the first year, which is 2011, but it's actually 0 inside the array because arrays are 0 indexed. And I'm going to go all the way, and I'm also going to initialize another local variable inside here. So I wanted to demonstrate how you can, remember for loops are very flexible. You can actually create other variables in the for statement. I didn't need to create a variable that's used outside of the for statement on lines 19 or 20. So here I'm just going to create a variable called total, or initialize my total variable. And then I'm going to go through until my year is less than my years, which is constant. And I'm going to increment my counter loop control variable year. So the year and the month are loop control variables on lines 19. And this is going to represent my outer loop. It's a 2-dimensional array, so I'm going to need an inner loop as well. And my inner loop is going to go through each month. So here I'm going to say month equals 0. Subtotal for each month is also equal to 0. Initialize it. And I'm going to go through until I'm done with all my months. And I'm going to increment my loop control variable. And this will be my inner loop. And so in my inner loop, I can actually determine the subtotals. I don't need to display anything. So all I'm going to do in my inner loop is I'm going to add to my subtotal for each year. My subtotal is my yearly total. And here I'm just going to access the array. My array name is going to be rain. So I can just say rain sub year. So this would be all for 2011 initially because of my outer loop, and then for each month. And I'm adding to it. So I'm saying subtotal equals subtotal plus rain plus the array value. So it's going to go through, in the inner loop, go through all the months for that year, create a subtotal of it. Now I want to display the subtotal outside of the loop because I only want to display the subtotal 5 times for 5 years. So here I can add a little nice little print statement that helps format the data a bit and also helps display it properly. Now I'll probably want to, this will be the year and the subtotal, so we'll probably want to add to the subtotal, I would say a couple tabs, but we'll see what it looks like. So /t/t. And then the only other thing we want to do is we want to add to the total because we need to have the total for all years. So here we can just say total plus equals subtotal. And then you'll notice the subtotal is actually getting reinitialized every time you go into the inner loop, so we don't have to set that back. And here we just want to make sure the indentation is good. Again, notice my indentation for each blocks. And I actually don't need the brackets on 27 and 29 since it's a single statement, but I'm going to leave them there. Now that I've done that, I can actually, after I printed out the yearly rainfall, or the rainfall for each year, I can now display the yearly average because I have enough data. I have the total rainfall and each month rainfall. So here I'm just going to display the yearly average, which is just the total divided by the years. So I'll add another print statement here. Again, another good place to test. So let's go ahead and build this, make sure we don't have any errors since it is a lot of code. And we have an undeclared variable year, even though it's right here. So what's going on? I had an error. I have an error up on line 17. I never ended my initialization. So I had to have a semicolon line 17, which wasn't recognized in the declaration of the variables on line 19. The other thing you'll notice with compiler errors, when you see a compiler error, it's sometimes misrepresentative of what the actual error is. So in this case, it told me I had an error on line 19, but really what was causing the error was the previous statement that didn't have an ending semicolon. Let's run this and see if we can see the yearly rainfall, see how it's formatted. So here we go, year 2010 rainfall in inches. So we probably added too many tabs after when we displayed the subtotals. And then the yearly average is 39.4. So we probably want to fix that by just getting rid of a tab here. Remember, a tab, you can add a tab in your output by using escape sequence /t. So that looks pretty good, at least. Now we have to have another loop that's going to display the monthly averages. So before I display the monthly averages, I want to print everything out on a single line. So I'm just going to print out some information using printf. I'm going to print out my monthly averages and add 2 line feeds so it's formatted better. And then I'm going to print out my other information. I don't need 2 lines for this, I don't think. So we'll just do it all in 1 line for all the months. And we're just going to separate the months by a few spaces and then add a new line. So we're going to do the same when we go through our for loop. Now we need another for loop now to get the monthly averages. So in this for loop, the outer loop is going to start at month. Instead of going by each row, what I'm going to do here is I'm going to go through each column because I need to get the monthly average. So I'm going to start and I'm going to go through each column, which is January, February, March, represent columns. And for each column, I'm going to go through all the years for that column. And that will give me and then I can use the subtotal and the total again variables. So here I'm going to say month equals 0, month is less than months, and month plus plus. And then my inner loop is going to go through the years. So here I'm just going to say for year equals 0. And remember that I also want to reinitialize my subtotal. So here I'm going to say subtotal equals 0 because I want to start at 0 once I get my new year. Go through all of the years and then increment the year. The year leap control variable. And inside here, I want to put in my subtotal, which is just going to be equal to my array for year and months. And so it's important to understand what's going on here is we switched the way that we're iterating through the array. In the first loops, we iterated by going through each row and looking at each column. In this one, we're actually going through each column and looking at that specific row. So because we're calculating monthly averages. So we get the subtotal, and then we just want to print out our subtotal divided by years for that month so that it matches up with our output on line 37. So we're just going to do something like this, and we're going to do it with 4.1 format, subtotal divided by years. And we add a couple spaces so that try to line it up as best we can. Might want to add another space. And then at the end of this, after we've printed everything out, we can just add a line feed for readability, and we're done. And that will give us the monthly averages. Because we got all the subtotals and we divided it by the years. Now let's build this. No errors, and run it. And now we'll see additional output for monthly totals, or monthly averages. So here we see that, monthly averages, and the format doesn't line up real good. So we probably want to, it all depends because of the characters output. We actually probably want to decrease the space. Only add 1 space there. Let's see if that does a better job. Now when we run it, Let's see if it looks better, because you want to be able to tie up each month with the averages. That's a little bit better. We still get a little off because the months are 3 characters and the integers are 2. We mainly got screwed up between October and November because there's only 1 space between. Oh, now I can fix that by just going like that. So that should make the format all nice. But you can see how we're just printing out rainfall amounts for years and monthly averages. I hope this got you familiar with 2-dimensional arrays, how to iterate through them, how to assign arrays, and how to access data. Thank you. Hello and welcome. In this lecture we're going to talk about variable length arrays. What exactly does this mean? Well, this is a new feature that was added, I think for C99. But up to this point, all we know about arrays, besides being multi-dimensions, and also besides being a cool feature where you can store multiple data elements in a single variable essentially, is that they're fixed size. Once you specify that size, you have to use a hard-coded constant when you declare the variable that specifies the size, and it stays the same way. Variable length arrays is a bit misleading. It doesn't mean you're going to change the size of the array dynamically. It's still going to be the same size, but now you can use variables. So the term variable in variable length array does not mean that you can modify the length of the array after you create it. What it does mean is that you now can set a variable to use for that array. So a VLA is still going to keep the same size after creation. The variable length array allows you to specify the size of an array with a variable when creating an array. So you can just use variables. That's all it really means. It seems like it might not be that useful. But actually the only reason it was really added was because it helped with really existing libraries in other languages. So C99 introduced this new feature, and it is used, and that's why I wanted to mention it. I'm only going to mention it briefly. I'm not going to provide a detailed use case of it. I just wanted to tell you that it exists, because sometimes you see this term variable length arrays quite a bit when you're reading up about C. And I wouldn't want you to see it and say, what the heck does this mean, when we studied arrays and we didn't mention the topic. So it was introduced mainly to make C a better language for numerical computing. VLAs, which variable length arrays, make it a lot easier to convert existing libraries of Fortran numerical calculation routines to C. So this is why it was added. So if you're a Fortran programmer, you may want to use this when you're migrating, or if you're converting code. If you're porting your Fortran code, trying to convert it to C, you may want to use this. You cannot initialize a VLA in its declaration. So there's no initialization when you're talking about variable length arrays. Here are some valid sizes that you can apply when declaring an array. Right? So we can declare 2 variables n and m, and then you see at the bottom when we say float A and float A9, we can use those variables when we declare them in the array size. And that was not allowed before C99, but now it is. And that's a VLA, variable length array, specifying a variable to be used inside of an array. It's not changing the size at runtime. There's other examples here of valid declarations of arrays as well that you may want to pay attention to. Perfectly fine if you're setting an array to a specific size like 5. You can use expressions when you assign the size of an array. So in the next example, 5 times 2 plus 1, that's fine. The other thing to notice here is we're using the size of operator. And that's perfectly fine too, because that's going to return an int, right? Size of int is going to either return 4 or 8 depending on the machine you're running on. And then you're adding 1 to it, perfectly fine. Putting a negative number inside the declaration of an array, no, you can't do that. There's no such thing as a negative 4. The size of the array has to be greater than 0. So also 0 will not work. 2.5, putting a float, can't do that either. Doesn't make sense. How can you create an array of size 2.5? However, if you do put 2.5 inside the square brackets and you cast it to an int, that's okay. Again, didn't want to spend a lot of time on variable length arrays. I just want to introduce the concept. If you hear the term, you know what it is. Assigning variables to an array when declaring them for the size. Really just introduced for compatibility with existing Fortran libraries. Thank you. Hello and welcome. We're starting a new section. Our section is based on functions, so we're going to talk about some of the basics of functions first. A function is a self-contained unit of program code designed to accomplish a particular task. That's a high-level definition. Function is going to be basically something that you can invoke that helps you reduce duplication of code. But what it does is it's self-contained inside the code itself, and it has just some task that it's going to accomplish. Syntax rules are going to define the structure of a function and how it can be used. So depending on what programming language you use, functions may be defined differently. For C, we're going to talk about specific rules for C. Most programming languages support this concept of a function. And I'll tell you the advantages and why they're supported. A function in C is the same as subroutines or procedures in other programming languages. So oftentimes you hear these terms subroutines and procedures. Same thing as a function. Self-contained unit that executes some code that you can call. Some functions cause an action to take place. So we're familiar with a couple functions up to this point. We've studied the printf function, which displays output to your screen. That takes an action, does something for you. And then we've also looked at the scanf function, which takes input from the keyboard. Again, it sort of does another action. Other functions, though, can actually just find a value for a program to use. So for example, when we study strings and character arrays, we're going to look at functions for string manipulation and changing things. There's a function in particular called stir length, and that will tell a programmer how long a certain string is. It doesn't perform an action, it just gives information back to you. So functions are going to perform tasks depending on the task and what you need to accomplish in your program. It's either going to cause an action or it's going to modify a program value or return a value or tell you some status information. Advantages of functions. We're going to use functions because they have a ton of advantages. Functions allow for the divide and conquer strategy. So if you were to write down and go and write a medium-sized program or a large program, it's going to be really, really hard to maintain. It's going to be hard to test, debug, and find and fix any errors if you have a single large function. So breaking down and doing this divide and conquer strategy is going to make it a lot easier to find and fix bugs in your code. Couldn't you imagine a single C program that all it had was the main function and there was 5,000 lines in it? We would have no clue how to attack that problem. It's really, really poor organization. You're not having any cohesion, and you're just kind of diving right in there to try to solve a problem. So we're going to use functions. Divide and conquer basically means that tasks can be divided into several independent subtasks. It reduces the overall complexity of the code. You can create separate functions for each subtask. And then you can even create more functions to divide the subtask into smaller subtasks. Each time you create these additional functions, it reduces the complexity. Your goal should be when you're creating these functions and using the divide and conquer strategy is to make your functions as cohesive as possible. And what that means is make sure each function is doing something very, very just one task. Don't have a function do 5 different tasks or 10 different tasks. If you write a function that reads input from the keyboard, have it read input from the keyboard. Don't have it check a string or display output or anything like that. Functions need to be small and they need to be very cohesive. But the divide and conquer strategy is really nice because it reduces that complexity. Instead of having a main function with 5,000 lines of code, you can have many, many functions that are doing specific tasks, and you can identify them very quickly. So functions are going to reduce the duplication of code. And when you reduce duplication of code, it's going to save you time when writing, testing, and debugging that code. It's also going to reduce the size of the source code. And why do functions reduce duplication of code? Because if you have a task, instead of doing that task over and over and over again and writing the same code over and over and over again, you encapsulate that task into a function and you just invoke the function. And the function will do it for you each time. You don't have any duplication there. If you have to do a certain task several times in a program, you only need to write an appropriate function once. Just like I mentioned, you don't need to write that code multiple times. So a program can then use that function whenever needed. And you can also use the same function in different programs. And that's what constitutes a library. We've been doing that. We've been using the printf function, which is from the standard input-output library. And that's only written once. And we invoke it over and over and over. If that function didn't exist, we'd have to take the implementation of that function and put it in our program and just keep repeating it. So functions can save a lot of time and they can reduce your source code. And you can reuse them over and over again. So it's also a software reuse technique. It also helps with readability. When you modularize your program, which is what you're doing when you create these separate functions to perform specific tasks, the program becomes much better organized. Like I mentioned, if you had a main routine, a main function, and it had tons of code in it, it's going to be much harder to follow than a main routine that calls 5 functions, and those functions do specific tasks. So it helps with program organization, it helps with program maintenance. It's much easier to read and easier to change or fix any source code. And remember, the maintenance phase is the most expensive phase of the software lifecycle. This is where you're fixing your bugs, the program has been released, and where you're adding new features. The better organized your program is, the easier it is going to be to maintain. So this organization, this readability, this being able to follow what's going on in your source code, very important, and functions help a ton. The divide and conquer approach also allows parts of the program to be developed, tested, and debugged independently. When you get out there in the real world and you start working on code, you're going to notice that programs are really, really big. And there's many people working on these programs, hundreds, maybe even thousands. When you have all these people work on a program, it's much easier to work on that program if you do this divide and conquer approach. If you have small tasks that people do and it's independent. You're not touching the same source code, and you can go ahead and implement tasks much easier. And when you do this and you have multiple people working on a project, it can reduce the overall development time, which again reduces maintenance costs, reduces development costs. The functions can also be reused, which again will reduce time. And again, we do that with the printf function, reuse that. But when you write your own user-defined functions, you can reuse them over and over and over in the program. So software reuse is a big, big advantage of functions. When you're thinking about these functions, the other nice thing about designing your program around functions is you want to think of it as a black box. What it means when you think of it as a black box, all you're thinking about is the input to the function and the output. And when you focus just on the input and the output, it allows you to look at the design as a whole before you start implementing. And so functions in general will get you in this type of thinking where you can focus on design. And I mentioned design is important. Design is when you start planning out your program, how you're going to organize it, how you're going to write the code. And it's important to do this planning before you even start implementation, which is writing the code. And by thinking about functions and thinking about just inputs and outputs, you can think about how the program is going to be organized and what functions you need to create. So you don't have to worry about just implementation and the details. And this is important because the first thing you want to do before writing code is just to think about design. You don't want to start thinking about implementing. A lot of issues that students have when they write code for the first time is they just start implementation. They don't even think about the problem. They don't think how they're going to solve the problem. They just start writing code. Never a good approach. When you're thinking about writing code and functions, think about it as just inputs and outputs of the function, and it's going to help you with your design. So let's look at some examples. We have used built-in functions such as printf and scanf, as I mentioned. Those are in the standard input-output library provided by the C programming language. So we're familiar somewhat with what a function is because we've used it. But we haven't gone through the fine-grained details of how you define a function or how you actually pass data to a function, nothing like that. But with the printf function, you should have noticed that it does take data. You can pass data to the function. The data is the arguments between the parentheses following the function name. We're going to have a whole other lecture on arguments and parameters to explain them more. But at a high level, understand that you can pass data to a function. And understand that by looking at the printf function. The first argument to the printf function, which is the data that we're passing to it, was a string literal. It was all those characters inside of double quotes. And then we also had arguments, which there could have been 0 or many. They were variable arguments, which were a series of variables or expressions whose values were to be displayed. So remember, if we had any format specifiers in the first argument, we would then have the variables in the subsequent arguments. So we were able to pass data to the printf function. You also should have noticed how you can receive information back from a function. Data can be returned to you. In the scanf function, one of the arguments was how you were going to store the data. And so you would pass it a variable, and that variable would have a value, whatever the user typed in the keyboard. So that's kind of thought of as a return value in a function. So functions are very valuable because they can take data into them, and then they can return data out of them. So a coding example of a function, and this would just be a function that we're going to invoke, but this is the main function. We're familiar with the main function. It's the entry point of the program. But look at how nice this is. We're calling functions read list, sort, and average. We only have 3 lines of code. We have to go and implement those functions, but it makes the program more organized because we immediately know what this program is doing. This program is going to read a list, it's then going to sort a list, it's then going to display the average of the list. And the list contains floats. So it's very readable, it's going to be very easy to maintain. If we have any bugs in the program, we'll immediately know how to find or isolate that bug. If the bug is in sorting, we can go to the sort function. If the bug is in averaging, we can go to the average function. Very easy to isolate errors. So when we implement those functions, in the previous slide we were just calling them. To actually implement functions, you have to write the code inside of the body of the function. You can either utilize functions that are implemented by the C language like printf, or you can create your own user-defined functions. You do not have to implement the printf functions or any of the functions in the library. You only implement your own functions. So in this previous example with the read list, sort, and the average, we would have to go and we would have to implement that function. We would have to provide a function header, a function body that actually does the reading of the list, the sorting of the list, and averaging of the list. And we're not done just by defining functions. We have to implement them. And when you implement the functions, you always want to use descriptive function names to make it clear what the program does and how it is organized. In the previous example, we had a function named readList. Pretty clear what that's doing. Function named sort. We didn't name the function X, Y, or Z. We described that function. It's the same thing when you're describing or creating variables. Meaningful names. And also, if you make these functions where they're generic enough, where they're actually doing something and they're taking generic data, you would actually be able to reuse them in other programs, just like a library function. Again, supporting software reuse. So in these upcoming lectures, we're going to talk about how we can define a function, the specific syntax, how we can invoke and call a function, and how we can pass and return data from them. That's what we're going to focus on in the upcoming lectures. I also wanted to mention that our main routine that we've been seeing over and over in every C program, that's a function, right? The main function is a specially recognized name in the C system. It indicates where the program is to begin execution. All C programs always have a main. The main function can take data when you pass to it, the command line arguments, or it doesn't. It doesn't have to take data. It also has optional data that it can return. You'll notice that we use main functions that return 0. Usually that's used when you want to return error codes. But we've used specific functions already, and the most important function is that main function. And that again helps organize the code. We always know where the program is starting because we just have to find the main. So this is a high-level description of functions, kind of identifying the advantages of functions and what exactly a function is. Now we want to talk about implementation. Thank you. Hello and welcome back. In this lecture I want to talk about defining functions in C. Defining a function. We know the importance of functions. We understand the advantages. We will want to use functions in our programs. So when you create a function in C, you have to specify the function header as the first line of the definition of the function. We're going to talk about defining a function, and we're also going to talk about implementing a function. Implementing a function is just problem solving. It's just regular C code. Defining a function is saying that the function exists. So when you define a function, the first thing you do is you have that function header, and then you follow that with a curly brace that starts the block code for the function. So it's just like when you use a curly brace in an if statement, just like when you use a curly brace in a for loop. Except the curly brace is required for functions. There's no eliminating it. And it always signifies the start of the code for that function. Anything in between the starting and ending curly brace is the code for the function. It's where you're going to implement the task. So in between the braces is called the function body, and the first line of the function is called the function header. The function header defines the name of the function, the parameters of the function. We're going to talk about parameters and arguments in detail, but right now you just need to know that there's something called parameters. And the parameters are going to specify the number and the types of the values that how you can pass data. Parameters have to do with passing data. The type for the value that the function returns. We mentioned that functions can return data. So in that function header, you're going to have the name of the function, the data that you can take can be accepted by the function, and the data that's returned by the function. We're not going to focus right now on the data that can be passed or the data returned. We're just going to talk about creating a simple function. The function body contains just regular code. And that code gets executed when you call or invoke the function. And the function body itself will have access to any values that are passed as arguments. So the data that you pass to it, you can utilize that data inside the function, the body of the function. What it looks like is this, the function header. Function header has the first word in the function header is a keyword representing the type of data that's going to be returned from the function. The next keyword there is the name of the function. And then you have a left parentheses, and then you have parameters separated by commas. That will be the data that's passed to the function. And then you have that right parentheses to end the function header. Then you have the curly brace. That signifies the start of the function implementation. And you have any number of statements to do a task. Like I said, you want to have your functions be small. They want to be cohesive. They don't want to be all over the place. They want to have a single focus. Do something specific. Like I said, if you have a function that gets input, it reads input. It doesn't print out output. It doesn't do any sorting, or it doesn't do anything else. If you have a function named sort, it sorts the data. It doesn't get input. Functions need to be cohesive and small. It's much easier to debug those functions. So make them cohesive. And then you have that right curly brace, which ends the function implementation. That is what a function looks like in C. Now let's focus on the function names, and we'll talk about the parameters and return types later. The first line of the function, again, definition tells the compiler, in order from left to right, 3 things about the function, as I mentioned. The type of the value it returns, the name of the function, and then any data it takes. And this is just to summarize. That's important. As far as function names, you want to choose meaningful function names. It's just as important as choosing meaningful variable names. It greatly affects the program's readability. So do not name functions X or Y. Name the function based on what it's going to do. If it's adding 2 numbers, name it add. If it's subtracting 2 numbers, name it subtract. In this example, here's our simple function. Don't worry about the void. Just worry about the name here. We have a function named printMessage. And then we see that curly brace, which signifies the starting of the function. And then we have some implementation. And this implementation is doing nothing more than displaying a string, a text. And then we have that right curly brace. So this is a very simple function. It doesn't do much. It displays output. In this example for the print message, the first line of the print message tells the compiler that the function returns no value. That's the keyword void. Again, don't need to focus on that, but that's what that's doing. The next is the name, and then after the name is arguments. They're called parameters. And we use the keyword void again if we're not passing any data. The statement in the function body can be absent, but the braces must always be present. So you don't have to actually have any implementation, but you have to have the braces for a function to be there. If there are no statements in the body of a function, the return type has to be void. And again, we'll focus on this later. And the function will not do anything because you have no implementation. If you define a function with an empty body, it can still be useful, even though it's not accomplishing anything. You usually do that during the testing phase of a very large program. And what this allows you to do is you can run the program with only certain functions actually doing something. Helps you test better. Helps you isolate errors. You could even have implementation in the test in the function body, but just comment it out. And then you can do this divide and conquer approach. As you test more and more and more, you can then start putting implementation in the function bodies. It's a step-by-step process of working. You are constantly working in small chunks, adding code, testing that code, and then moving on to the next step. And then eventually the whole implementation will be completed and all functions will be implemented. So there is a use case for having a function body that has no code or commented out. Naming functions. The name of a function can be any legal name. Just like when you're naming a variable, you cannot use reserved words. So these are keywords in the language, such as int or doubles, because they represent data types. Size of is an operator. You wouldn't be able to use it for or if. You could also not have two functions with the same name. And this is also referred to as function overloading, kind of. But you can't have two functions with the same name. Overloading is not supported in C. Lastly, you can have the same name as a function that's in the standard library function. Technically, if you don't include that library include header file, you might be able to have it. But if you ever wanted to actually use that library function, the compiler would complain and say you have two functions with the same name. So don't name your functions the same as standard library functions. A legal name is the same as a variable. A sequence of letters and digits to start off. The first character has to be a letter, and the letter can be an underscore. You can't start off functions with numbers or any kind of weird characters. The name that you choose should be meaningful and relevant to what the function does. I said this already. I'm repeating it for emphasis. Meaningful names are very important. You will often define function names and variable names too that consist of more than one word. So now I want to talk a little bit about just coding style. You've probably noticed when I've written my code that I use camel case. There are 3 different ways you can write the names of your variables and functions. You can separate each of the words in a function name with an underline character. It's one approach. You can capitalize the first letter of each word, or you can capitalize words after the first word. And you still have to string them together. Remember, you can't have spaces in between. This is just an approach for naming because it's important that you follow some convention so that it's easier to read. Just having a long word with 5 different words. So if you had a function that says check for valid input, you wouldn't want to have those all lowercase. It'd be really hard to read and identify where the words were. So camel case is a way to identify where the words are in many words, and it's easy to see what that function is doing. An underscore is another way to separate words. And capitalizing the first letter of each word is another way to separate. It's important to be able to separate the words in a function to make it more readable. I usually use camel case. And when you use one of these conventions, you want to use it for everything. You want to use it for naming variables. You want to use it for your function names. Usually you just follow this common coding convention. It makes things more readable. Function prototypes. We talked about defining a function. What about declaring a function? You may say, why do you need to declare a function? Aren't you declaring it when you define it? But there's also a concept of declaring a function. And it's necessary if you want to use the function before it's implemented, before it's defined. So a function prototype is a statement that defines a function. It tells the compiler essentially all the details of the function. It defines its name, return type, and the type of each of its parameters. So it looks like a function header. It provides all the external specifications of the function. Mainly, you've also probably heard the term signature, function signature. That's what it is. It's specifying the data returned, the data that it takes, and everything about the function itself. You want to write a function prototype the same way as you write the function header. The only difference is that you put a semicolon at the end. And this is just declaring the function. This is saying the function exists. A function prototype enables the compiler to generate the appropriate instructions at each point where you call the function. It also checks that you're using the function correctly in each invocation. The reason that you provide function headers is so that you can invoke the function without a warning or function declaration without it being implemented. So it's really just the order of your code. And I'll give you an example of this in a second. When you include a standard header file in a program, the header file adds the function prototype. Function prototypes usually go in header files if you want to reuse them in many different source files. If you're only using them in a single source file, you can just put them at the top in the source file. But because we're using the printf function, which can be used in many different source files, that header function will be defined in the header, or that function declaration will be defined in the header. And in this case, stdio.h. So they usually appear in source files if only that source file is using that function. Otherwise, you put them in a header file if they're being used by many source files. It allows any of the functions in the file to call any of those functions that are defined regardless of where you have placed the implementation. If you place the implementation of a function after you call it, C is going to complain and say that it doesn't know about it. Because when you compile, you're compiling line by line. If you place the declaration at the top, then you can invoke the function before it's defined, before it's implemented. Parameter names do not have to be the same used in the function definition. You can have different names. And when I say names, those are the identifiers of the data. You can change the name of the parameters in the function prototype. You still have to have the same data types, but you can change the names. It's always good practice to include function declarations for all the functions in your program at the top of the file. It keeps your program more consistent to the design, and it prevents any errors occurring at any stage if you ever want to call that function before implementing it. Here's an example of some function prototypes. At the very top of the file, we have our includes, and then we have some functions that we've declared: average, sum, and get data. You notice it looks just like a function header. It has the return type, has the parameters that are defined in the function, and then it has a semicolon at the end. There's no implementation for these functions. You're just telling the compiler this is the function exists and this is how it's defined. What this allows you to do is now in your main function, you could call the average, you could call the sum, you could call the get data. And the actual implementations can be below where you're calling them. If you didn't have the function headers here, when you tried to call them in the main, if they were defined below the main routine, you would have errors or warnings. So let's take a look at that in code blocks. Here we have our usual main routine. Now let's say that we want to create a function. Or we want to invoke a function. We're going to invoke a function called add, and it's not going to take any parameters. We're calling it in our main function on line 7. We're going to implement it on line 10. We're going to say void add, and we're not even going to do anything. We're just going to keep it empty. When we go to compile this, what you're going to notice is this compiler just gives a warning. It says add has an implicit declaration. Right? You can get rid of that warning by using a function declaration. You can declare the function up top, basically telling the compiler that you're going to use it somewhere, but you don't know where the implementation is. So what you can do is you can say void add right up here and just add the semicolon. Now it will get rid of that warning. In some compilers will actually give you an error. Now when I compile it, I have no warnings and no errors. So that's what a function declaration does. It allows you to put the function anywhere. Now if you didn't have the function declaration at the top and you had the implementation above where you were calling it, then you also won't see the error. Because the compiler is going to know about the function before it actually tries to invoke it. So if we build this, you're also going to see that there's no error. Now I mentioned that you usually want to declare all your functions at the top just for good practice, and I think you do need to do that. So keep doing that. But if you do get out of that habit, you either have to declare your functions before you call them, or you have to provide function prototypes, because you do not want warnings or errors in your program. This is how you can define a function, and this is how you can use function prototypes. In the next lecture, we're going to talk about parameters, how you can pass data to a function. Thank you. Hello and welcome. In this lecture, I want to talk about arguments and parameters. These terms tend to be used interchangeably. What they have to deal with is basically data that you pass to a function. So a parameter is a variable in a function declaration and a function definition implementation. So remember this difference between function declaration, function prototype, and function definition. Function declaration is just the method signature. It's the function header. Function definition is the implementation of the function, the actual code. Right? In both of these terms, declaration, definition, understand those differences. But the parameter is what's in the function declaration and definition. It's in that header. Because both the header is included in the definition and the declaration, right? When a function is called, the arguments are the data you pass to the function parameters. Those are the actual value of a variable that gets passed to the function. So function parameters are defined within the function header, and they're placeholders for the arguments that need to be specified when the function is invoked. So understand the difference here between arguments and parameters. Parameters have to do with the function definition and declaration. Arguments are when you call the function, when you invoke the function, the data that you're passing. So arguments are used when you invoke. You'll say, these are the arguments that are going to my function. And when the function receives that data, they're referred to as, those are the parameters. The parameters for a function are a list of parameter names with their data types. Each parameter is separated by a comma. The entire list of parameters is enclosed in parentheses, following the name of the function. A function can have no parameters, which means there's no data passed to it. And in this case, you just have the left and the right parentheses with a void in between them. Or empty. You can still have it as empty, nothing in between them, but it's good practice to put a void in between them. Void is a special keyword that says nothing, means nothing. It means no parameters or no return data. Parameters provide the means to pass data to a function. Data passed from the calling function to the function that is called. The invokee to the receiving end. The calling end and the receiving end. The names of the parameters are local to the function. We're going to talk about that when we talk about local data. But those parameter names only exist inside the function body. They will assume the values of the arguments that are passed to it. So if you have a function called add, you pass in a variable as an argument, you pass in the value 5, and you have a function with a parameter x, x is going to be equal to 5, anywhere in the function body. The body of the function should use these parameters in its implementation. If it doesn't, then they shouldn't have been passed. If you have a parameter variable defined in your function declaration definition, and you never use that variable inside the function, that's wasteful. Don't include it, because that's just saying you don't need it. Don't send data to a function that's not using it. A function body may have additional locally defined variables that are needed by the function implementation. You may have inside the function body other variables declared, because they're needed for whatever task you're completing. You don't just only operate on data that's passed to it. You can operate on local data inside the function. When passing an array as an argument to a function, you must also pass an additional argument, have another parameter defined, specifying the size of the array. The reason for this is that the function has no way of knowing how many elements are in the array. So even if you declared an array of size 50, you may only be storing 30 elements. And if you're going to use that array inside the function body, you're probably going to need to know how big it is, because you're going to need either iterate through it using a loop, or you're going to need to access elements. And if you're accessing elements or iterating through it, you need to know whether or not when you're out of bounds. And we've talked about the out of bounds error and why that's important. Well, here's an example. When the printf function is called, you always supply one or more values as arguments. The first value is that string inside double quotes. The remaining values are any variables to be displayed. This is actually a function that takes a variable number of arguments, which we're probably not going to talk about since this is beginner class. That's more of an advanced concept. But the printf function is a good example as far as passing data to it, because you're passing multiple sets of data to it, either the string inside the quotes or variables that you want to display. This is why it's so important to be able to pass data to a function. It greatly enhances the usefulness and the flexibility of a function. If functions did not have the capability to accept data, they wouldn't be as useful. In the example that I provided in the last lecture, where we had a function that displayed output, it didn't really do much. It was very static. It did the same thing every time you invoked it. But what if you had a function that took data? Then you can control what's displayed. So just like the printf function. If the printf function didn't have parameters, you wouldn't be able to tell it what to display. If you didn't accept data, you wouldn't be able to say, hey, display this variable or display this string. It wouldn't be very useful. Right? So you want to be able to pass data to a function. It makes it much more useful and flexible. And you'll see that. I mean, if we do multiplication function, you wouldn't want to multiply the same two numbers every time. You would take parameters and data would be passed to it for two numbers. So you could do different calculations based on the data that's passed to it. Very, very important to understand data passing and why it's useful. It's a good idea also to add comments before each of your own function definitions. it helps explain what the function is going to do and how the arguments are to be used. You'll typically see this. You'll see this in my examples. You have the function declaration at the top of the file. You have the function definition. Function definition includes the function header. Right above the function header, you have comments, usually multi-line comments. So you have the slash asterisk. And there you say the name of the function, the purpose of the function, and then also describe any data that's being passed to the function. This again is for maintenance and be able to find and fix errors much quicker. Usually you want to have a good name for the function. That will tell you something, but with additional comments, it will tell you even more. Here's an example that is a function that multiplies two numbers. That's getting data passed to it. We have our multiply two numbers. We know it's a function because it has the parameters essentially. It has the parentheses. That's one way you can identify functions when you see parentheses. I mean, we could also identify it because it has a return type, but there's multiple things that tell us it's a function. But the main thing is the parentheses, and then also you see the brackets. The curly brackets that signify the starting and the ending of the block. This multiply two numbers function though, remember that the function parameters are defined in between the parentheses. So here, and then they're separated by commas. Here we have two parameters. We have a parameter named x and a parameter named y. For each parameter, you have to identify the data type that's coming in. So here we have two ints. This is the standard way to pass data and how to do it. In between the parentheses, data type, then a name for the variable. The name for the variable became anything that's valid in C for the name of a variable. You could call that X, Y, Z, whatever you want. You just can't start it with a $ symbol. And then you separate those by commas. Become accustomed to this convention. Parameters inside parentheses. If you had no parameters, no data that's passed to the function, what you would see in between those parentheses is void. Or you would see nothing in between the parentheses. This function, all it's going to do is it's going to take the data that's passed to it, which are two variables now named x and y. And it's going to multiply them together and store them in a variable named result. Or in this case, it looks like I misspelled it, t. And then what it does is it prints data. It prints out the data that is multiplied. But again, see the flexibility and usefulness of the function because it takes data. It can have different, displaying different data based on what you pass it. When we invoke the function in the main routine here, we say multiply two numbers and we pass in the arguments. We pass in the value 10 and 20. We could pass in variable names here as well. But in this example, we're just saying 10 and 20. This is going to call the function multiply two numbers and it's going to pass in data 10 for the first parameter, 20 for the second. So x is going to be equal to 10, y is going to be equal to 20. So when we do our multiplication, x times y, it's going to be 10 times 20. The result is going to store 200, and then it's going to display that result, along with the variables that are being passed to it, x, y, and z. So it's going to display 10, 20, and then 200. Also notice that we can now reuse this function. We're calling it again with different data. Data values 20 and 30 in our second line here in the main function. And then we call it again a third time to multiply 50 by 2. Very useful to be able to do this, to create a function that takes different data, makes it reusable, makes it flexible. And the syntax is very easy to follow, right? It's just two variables inside of the parentheses separated by commas. And then to call it's even easier. You just space a name and you have the two data, whatever data is separated by comma inside parentheses and then ending with a semicolon. You can pass any kind of data type into a function. You can pass in arrays. We're also going to talk about how you can pass in other data types. We have simple examples here, but you can also pass in pointers, which we haven't talked about yet. You can pass in structures. Again, another concept we haven't talked about, but it becomes really meaningful and useful when you pass data here. This is a simple example. Notice the syntax, study this, and we'll provide a good challenge for you where you write a number of different functions. Thank you. Hello and welcome. In this lecture, I want to talk about returning data from functions. Up till this point, we know what a function is, we know why it's useful, we know how to define functions, we know how to pass data to functions. Now we want to talk about how we can return data from functions, which is also very useful. In our prior example, when we multiplied two numbers, a multiply function displayed the results of the calculation at the terminal. Remember we had that printf statement in there? Also, we had an example where we were just a simple function earlier. We just printed out data inside the function. Well, wouldn't it be nice instead of printing it out there, because it's actually doing more than one thing, it actually printed it out, the data was returned and it printed out the data in the main function? You might not always want to have the results of your calculations displayed. The function becomes more flexible, more generic, and, which in turn allows it to be used more if you can return data. So functions can return data using specific syntax in C. We should be familiar with this a little bit because remember our main function? Our main function at the very end, we were returning data quite a bit in a lot of the examples. So we've been exposed to this a bit, we just haven't really understood what it means. Let's take another look at the general form of a function. Remember this function header? We had a return type, which was the word that was first defined, and then we had the name, and then we had the parameters separated by commas inside parentheses. We already know the name and the parameters. That first thing is the return type. The return type specifies the data type of the value returned by the function. Functions can return any kind of data. You just have to let the compiler know what kind of data you're returning. If it's an int, a float, a double, whatever it is, you have to specify that in your function header. The return type. The return type we saw right here, and you can specify that type of value to be returned by a function as long as it's a legal type in C. I mentioned the main ones, double, float, and so forth, but you can also return enumerations and pointers. We haven't discussed pointers, but it makes it very, very flexible when you can return pointers. The return type can also be a void type. You often see this keyword void. We now understand what it means. Void means that no data is going to be returned. If you see void before the name of the function, you're not returning any data. If you see void inside the parameters list, you're not passing any data. Void is just a general keyword that for return types and for parameters. You also notice you can use void as a pointer as well, but we'll get to that when we get to that. But void is a way of saying nothing. And the reason you include void as opposed to just not including anything is because it makes the program more readable. You can have actually, when you pass data to a function and you have no data that's being passed, you can have it just be empty parentheses. But you don't, it's easier to read if you have void in there. Same with a return type. Except the return type, you have to have void. You can't have it just be empty. Void means no data is going to be returned. The return statement. We've talked about how you can identify what data is going to be returned, but how do you actually return the data? Inside the body of the function, you have to have a statement where you can say what you're going to return. Because remember, the body of a function can have a lot of data. It can have local variables, it can have anything. You know, the function could be doing a specific calculation, be doing multiple calculations. What do you want to return? Luckily, there's this statement with the keyword return. If you provide the return with no variable name after or expression, that means you're just exiting the function. It's similar to a break in a loop. You're just returning from the function. And you can provide this in functions that are defined as void. It makes it clear when you're exiting the function. You should really only have the return in one spot at the bottom of the function. We'll get to that later. But you can have it anywhere in a function. If you see it anywhere in a function, it means you're jumping out of that function. The reason why it's good to have it at the bottom is it's very clear when you're exiting the function. If you have multiple returns, even if you're returning data all throughout your function, it's hard to say when you're returning. So what I like to do in my functions is create variables and only return once at the bottom. If I need to return something in a function, or in a specific if statement in a function or something, I'll set the variable and then return it at the bottom. So if you have return and you have nothing after it, that just means you're exiting the function with no data returned. This is really not used as much. You only use it in the void function. Doesn't return a value. The more general form of the return statement is returning some variable or some expression. X plus Y or returning X. This form of the return statement has to be used with the return type that's specified in the function header. If you're returning an int, whatever that variable or expression you're returning has to be an int. It has to evaluate to an int if you're returning an int. Now, if you're returning a double, it has to evaluate to a double. Remember, you can have many different types of data returned. The value that is returned to the calling program is the value that results when the expression is evaluated. So if you have x plus y, it's returning the result of that expression. And it has to be the same type as the function declaration, as I mentioned. A function that has statements in the function body but does not return a value must have the return type as void. Have to. You cannot not have that. If you do not have that and you're not returning any data, you're going to get an error message when you compile. When you compile the program and it contains a function with a void return type that tries to return a value, compiler error. Void means no return data. Don't return a variable or an expression. If a function does not have a void return type and it has a valid return type, you're going to get an error message if the compiler tries to return a different type than is specified, or if they just have return by with nothing after it. So pay attention to this. Those keywords in the beginning of the functional declaration are important. It directly affects the implementation of the function. And the compiler is going to tell you if you screw up and you don't return the right data, or if you don't return any data, or if you do return data when you're not supposed to return data. If the expression results in a value that's a different type than the return type in the function header, C will try to convert it. The compiler will try to convert it if it can. So for example, if you're returning a float and your expression is I plus X with 2 ints, it's going to just convert it to a float. If you're returning an int and you have an expression that's doing float calculation, it will convert it to an int. You're going to lose data in that case, but it will do conversion. It's not always possible to do the conversion. In cases where it's not possible, you're going to have an error that's produced by the compiler. If you're trying to return an int when you're supposed to return a string, or when you're trying to return an int when you're supposed to return an enum, it's going to complain, the compiler. You can also have more than one return statement in a function. I mentioned this briefly and why you don't want to do it, but you can do it. You can have multiple returns throughout the function. It just makes the code harder to follow because you're jumping out of the function all over the place. When you do return and you do have multiple return values, just make sure, again, if you have a function that's returning something, you have an expression or a value of that type, or it can be converted. Now that we've talked about passing data and returning data, we know how to invoke a function, but I want to say a couple of other things about invocation. You call a function by just using the function name followed by the arguments that you pass that are in between the parentheses. We know that. That far we know, but I want to formally state it. That's how you can invoke a function. When you call the function, the values of the arguments that you specify in between the parentheses are going to be assigned to parameters inside the function. The parameters are representative variables with a data type. You can then use that variable inside in the function body. When the function exits or executes certain code, it will use those values supplied as arguments, as I mentioned. Sorry, I misspoke there. Executes. The arguments you specify when you call a function should agree in type, number, and sequence when the parameters in the function header. Order also matters. I didn't emphasize that. But if it says int x double y, you first have to pass in the int, then the double. You can't pass in the double and int. The order is very, very specific. So make sure you pass the data as an argument when you invoke the function the same way as the function is declared in the function header in the parameter list. Pass in the right types as that as well. Invoking a function and assigning the data returned. If a function is returning data, the function can assign that data just by using the equals operator and after the return as well. Or you can store it in a local variable if you want. It will also work with an expression. So you can say return x plus y. You can say return x. You can say return a constant. This example here is after you invoke the call, when you want to assign the data that's returned. Right? So you can say int x equals my function call. Whatever that function returns is going to be assigned to x. And if my function call returns x plus y, the result of x plus y is going to be assigned to x. So you can assign the data that's returned from a function call by just having a variable on the left-hand side of the equals and the function invocation on the right-hand side of the equals. The calling function doesn't have to recognize or process the value returned from a called function. You don't need to have that assignment there. If a function is returning data and you don't care about that data, you don't have to have the equals at all. You can just invoke the function. It wouldn't really make sense because if it's returning data, it means that you probably need to look at it. But you don't have to do it. The compiler is not going to complain if you just invoke a function and don't handle the data. It's up to you how you want to use the data that's returned from function calls. Here's an example of invoking a function and also returning data from a function. In this example, multiply two numbers. This was just like the example we had previously, but the previous example didn't return any data. The previous example displayed output. In this example, we're not displaying any output. We're returning the data and then we're displaying the output in the main function. Here our multiply two numbers takes two integers as parameters. We multiply those two integers, and then instead of printing the amount or the value, we're using the return keyword and we're then specifying a variable named result. Yeah, it's misspelled, but don't worry about that. And then we have the semicolon to end it. When you see that return keyword inside the function body, you're returning that data. And remember, you can have that in multiple places. But you only can have it return one value. You can't return multiple values. So if you have the return keyword in multiple places, it has to be inside an if statement. You can't, or a loop, because you're jumping out right then. If you have a return followed by another return, it will give you an error because it would say you have two returns in both cases. You're always returning two results. You can't do that. But the return keyword's important. You're returning a variable, and then you see in the main function that the data that's being returned is being assigned to another local variable called result. You'll notice we're using the same names here. This has to do with function scope, which we're going to talk about in the next lecture. Local variables versus global variables. All you need to pay attention in this lecture is the fact that this function multiply two numbers is returning data. How you return it using the return keyword followed by the variable or the expression. You also notice that the multiply two numbers specifies the return type at the top of the function header. It's returning an int. So we have to return an int. You also notice that when we assign the data in the main function, we're assigning it to an int. Assigning, though, is very easy. We just have the equals operator. If we didn't care about the data, we could just call multiply two numbers and then do nothing with it. But after we get the data returned from the function, we then print it out using a printf function. This makes the function more cohesive that it takes data. We're not actually displaying the results inside the function. There are times when we don't want to display the results. We just want to multiply two numbers, and then we may want to divide the product. Flexibility with data being passed and data being returned is a big deal. This is a simple example. You're going to get exposed to this more in our next challenge. Hello, welcome back. In this lecture, I want to talk about local and global variables. This is really the concept of function scope, or in general, program scope. It has to do with when you can use variables and when you cannot use them. We know what functions are, so now I want to talk about local variables. Local variables really have to do with more than just functions, though. Local variables have to do with anything that has a block of code. So variables defined inside of a function are known as automatic local variables. So in that function body, in between those starting and ending brackets, if you declare a variable, that variable is a local variable. It will automatically be created each time the function is called. Also, any values in the access to that variable is only local to the function. You can't access that variable outside of that function. So the variable cannot be accessed in other functions if it's local to a specific function. It's only accessible from where it's defined. If an initial value is given to a variable inside of a function, that initial value is assigned to the variable each time the function is called. If you want to retain a value in a variable every subsequent call, there's actually a way you can do that in C. It's referred to as a static variable inside of a function. That's, again, more of an advanced concept, not in a beginner class, but it is a way that you can actually have the same data, or different data every time you invoke the function. So if you wanted to, for example, keep a counter of how many times a function was called, you would declare a local variable inside that function named static, with a static keyword. But without, just regular local variables are going to have new values each time. You can use the auto keyword before the data type, but it's not necessary. It does make it a little bit more precise. The compiler is going to add it by default if you don't include it, but if you do include it, it's just going to make it more precise. It's not necessary. So it's called an automatic local variable. There is a keyword named auto in C, but you don't need to provide it. It's provided by default. And that's why you don't see it in a lot of examples where variables are being defined and declared inside of a function. Local variables are also applicable to any code where the variable is created in a block, loops or if statements. Again, if you have an if statement, and what's a block for an if statement? It's just where the brackets start. That's referred to as a block. Blocks can be in functions, blocks can be in if statements, blocks can be in loops. Blocks can be anywhere that there's brackets, essentially. Anywhere there's brackets and you create that variable. Creation of the variable is declaring it and maybe assigning values to it. But if you declare that variable, you create that variable inside of a block, you can only use that variable inside the block. If you try to access that variable outside the block, it's not going to be used. So if you have an if statement, inside the if statement you declare a variable, you can't access that variable outside of the if statement block. Same with loops. It's very important to understand this. The compiler is going to complain and give you an error if you try to access it somewhere else. And what this means is the values in the data is only applicable to that block. You're not sharing any data. Global variables is the opposite of a local variable. Global variables can be accessed by any function in the program. The way that you create a global variable is you just put it at the top outside any function. So global variables are declared outside of the function and they do not belong to any function. And remember, the main keyword, the main is a function. So any variables defined in the main function are only accessible in the main function. So the variables in the main function are not accessible in any other functions. If you want a variable that's used by all functions, you put the variable outside of a function, usually at the top of the source file, and usually mark it as saying this is a global variable. The global variable is alive for the entirety of the program. From when the program starts to when it stops, that global variable is going to be located in memory. Any function in the program can change the value of that global variable. Because they have access to it, they can modify it. Right? And so you should start thinking about, well, wow, that seems kind of dangerous. Because now you have code that can access the same data anywhere. But we'll get to that. If there is a local variable declared in a function with the same name as a global variable, then that function will use the local variable. It will mask the global variable. So if you have a global variable named x and you have a local variable named x inside of a function, the local variable is going to take precedence. It's not going to modify the global variable's data. If you assign to that variable, it's only going to modify the local variable. So the global variable is not accessible when you have the same name. And it will actually not be accessed within that local function. So don't use the same names basically because it's just going to be confusing. For people that have programmed a lot and advanced programmers, they'll immediately notice this. They'll say, hey, it's just modifying the local variable, even if they see a global variable with the same name. But for beginners, it's not always very clear. Let me give you an example. Here in this example, we're creating a global variable at the very top before the main function. And the way you want to organize your program, usually you have your include statements at the top, after some comments maybe, and then you may have some defined constants, and then you would have your global variables. Global variables look just like normal variables. It's just where they're actually declared. If they're declared outside of a function, then they're global. So in this example, we have a global variable called myGlobal. We're initializing it to 0. We can also initialize these global variables anywhere. We can initialize them when we declare them, or we can initialize them in any function. It's an integer. We also have two functions, the main function and a function called myFunction. Inside there, we have local variables, which are only accessible inside those functions. In the main function, we have a myLocalMain. You can only access myLocalMain inside the main function. But because myGlobal is a variable that's global, you can also access that in the main function. So the main can access two variables, the local and the global. And myFunction has a local variable named x because it's declared inside the brackets of the function body. And we can actually access the global variable, which is myGlobal. We can also access x, but we cannot access myLocalMain, I should say. Because myLocalMain is only inside the main function. We don't have access to that. If we try to write or read myLocalMain variable inside the myFunction function, the compiler is going to give you an error. You need to understand this concept of local versus global. Local are inside blocks of code. When they're declared, you can only use them in the block. If a variable is outside of a block and it's just in a function, or it's just in the program itself, you can access it in any function. Global variables should be avoided. Global variables are sort of a bad thing. The reason for global variables being bad and why you should avoid them is because it promotes coupling between functions. What does coupling mean? Coupling means dependencies. If you have a global variable and it's being used by 4 functions, that means each one of those functions could be dependent on the other function. What's wrong with dependency? Dependency causes a program to be much harder to debug and find errors. If you have a bug in your program and you're using a global variable and the global variable is causing the bug, now that bug could be anywhere in any function that's using that global variable. It complicates things when you have global data. You have a global variable, it could be modified in function 1, function 2, function 3, function 4. You're not restricting access to that. It's also very hard, once you find the error and you isolate it, it might be very hard to fix it. Because now when you fix it, you may cause problems in other functions because of these dependencies. Global variables should be avoided as much as possible because of this coupling, because of these dependencies. There are times when you may need to use it, but you should avoid it. And to keep in mind, most modern languages and most object-oriented languages like C++ and Java don't even have the concept of a global variable. They have static variables, which can be class variables, but they're still encapsulated inside of a class. So because global data is such a bad thing, new languages actually try to prohibit it. And you should try to avoid it because it just complicates your program and makes it harder to find and debug errors. Instead of using global data, pass data to functions. If a function needs access to some data, pass it to it. Okay. If it's a lot of data and you don't want to have a lot of parameters, in theory you should never really have more than 5 parameters. There's a great book out there called Clean Code that talks about the quality of code and things to avoid like global variables. It also talks about how many parameters you should have in your functions. And if a function has 20 parameters, it's an indication that something's wrong. Mainly because that function is probably doing too much. But a function can have access to data by just passing the data to it, and you can restrict the use of global data. And for a function that takes a lot of data, you can use something called a struct, which we haven't talked about, but that's another way to do that. So don't use global data as much as possible, only when necessary. Make sure you understand the code, and make sure you document it really, really well, so that somebody else looking at the code immediately knows that you're using global data and knows how everything works. This is the concept of function scope. You need to understand this, so pay attention to all these slides, and also we'll be using some global data and some local data in our next challenge. Thank you. Hello and welcome. We pretty much talked about the most basic concepts of functions, the basics of them. There are some more advanced concepts related to functions like function pointers and static and automatic static variables, recursion, but those things are going to be discussed in an advanced class. Now that we know the basics of functions, I want to provide you with a challenge so that you get familiar with creating and using functions. So you're going to actually write a number of different functions. We need to start getting some practice writing these different functions. And why do we want to write functions? Because it makes our code more organized, more modular, and you can avoid duplication. We went through all the advantages. So the purpose of this assignment is to get you familiar with functions, understand these advantages. So you're going to write 3 functions, and you can have all these functions defined in a single program. I want you to write a function which finds the greatest common divisor of 2 non-negative integer values and returns the result. So you can create a function name called GDC. The function should take 2 integers as parameters. The algorithm to find the greatest common divisor is pretty simple. You can look online or find any math book. What you should be noticing in these challenges is that they're getting more and more difficult, right? I'm not going to provide you with every single hint. You have to come up with the GDC algorithm. It's very easy though and very common. It's a common function. Have this function take data and have it return data. 2 non-negative integer values it accepts. You can either check for negative integers if you want, or you don't have to. It's up to you. I also want you to write a function to calculate the absolute value of a number. The absolute value of a number is positive, the positive value. So if you have a number -5, the absolute value of that is 5. If you have a positive number 5, the absolute value is 5. It's a very simple function. Actually, the implementation of this function, all you're going to need to do is really check if it's less than 0, and if it is, just make sure it's positive. If it's a variable, you just say x equals -x. You'll want to test this function with ints and floats to make sure it works. To make the absolute value function more usable, I would have it take a parameter as a float and return a float. That way you can actually use it with an int and you won't lose any precision. If you pass an int in there, it's automatically going to convert it to a float. And if you had an int have the parameter as an int and returned an int, if you tried to use a float, you would lose data. So make it take floats. The third function that you're going to write is going to compute the square root of a number. Don't use any helper or any standard library functions. Do the square root with an algorithm that you create. I also want you to check the parameters passed to this method. If you have any values passed to the function and the values are negative, I want you to display a message and I want you to return a -1. What this means is you can actually use the other function you created, absolute value, as a helper function. That's what you usually, when one function uses another function, it sometimes is referred to as a helper function. So the square root function, I want you to invoke the absolute value function. You can use that to test whether or not the arguments are negative. You can also actually use it when you do your computation of the square root. Even though you're returning a negative number, you still want to call the absolute value function when you're performing the square root itself. So these are the 3 functions I want you to write. You're going to be exposed to creating, declaring your functions. I want you to have function prototypes at the top of the file because remember, that's good convention. I want you to return the correct data. I want you to pass data to these functions. So you're going to have to understand the whole entire function signature. And then you're going to invoke these functions. When you actually go and start testing the program, make sure you have a lot of test cases. Call the GDC function with multiple values. Call it with negative numbers. Call the absolute value function with many different values. You can test all of this by just invoking the functions in the main function. And then you can also have normal output of this. I'll show you my solution in the next lecture, but think about this, get a little planning out of the way, try to figure out what functions are going to return, even though I gave you a lot of hints here, what they're going to return and how they're going to take the data, understand function declarations and so forth. Good luck. Hello and welcome back. In this lecture, I want to go through a solution demonstration of our previous challenge, which was to create some functions, mainly the GCD function and a couple function helper, absolute value function and a square root function. I'm going to create a project, and I'm just probably going to name the project functions. I'm going to close my existing project here. It's going to be another console application. We haven't really got into libraries or any kind of graphical programming. This is going to be, how about just some functions? Usually you want to have a good name there, but this is just for learning purposes, so we're kind of just providing generic functions. If it was a GCD program, I'd write greatest common divisor, but first thing we're going to do is we're going to implement our greatest common divisor program. This is going to be a function that finds the greatest common divisor between 2 non-negative integer values and then returns the results. We should be providing function prototypes as well so that we can call them and we can place them anywhere in the function. So let's do that. For the first function, this is a function declaration. Why do we make a function declaration? So that we can invoke it anywhere in the program. We don't have to actually implement this function above the main function when we call it. And it's just good practice. It's very easy and clear to see what's going on in the program with all the function declarations at the top. This is going to return an int. So remember, functions, the function header, the first thing you do is you specify the type of data that's going to be returned. GCD is going to return an int. And it's just going to then name the function, which is GCD. And then inside the parentheses are data that's being passed to the GCD. And this is going to be also be an int. We're going to pass 2 items of data. So we separate those by commas. We specify the data type for each one and the variable name. I'm just going to say int u and v. And then I have the semicolon to end the definition of the function. Now I can define my function below the main, and I can still invoke it and not going to have any problems. So now when you want to actually define the function, implement it, you do the same function header, int return value, GCD, has to match up with the declaration in terms of types. You could name it something else, like int x for the names, but we're going to be consistent and we're just going to say int v. We know it's the function definition because there's brackets that define the body. This is the implementation code. The actual algorithm for the GCD is quite simple. All you have to do is write a loop and go through the loop and look at temp values based on remainders. So I'm going to create a local variable inside my GCD function. How do we know it's local? Because it's inside the brackets for 12 to 14. This variable is not accessible inside the main function. It's only local to this block. Here I'm just going to call it temp since it's local. I'm also going to now create my loop. I'm going to use a while loop. And my while loop is just going to go until v, which would be our greatest common divisor. Remember, the greatest common divisor takes 2 parameters. It would take a parameter, and based on both those parameters, it has an algorithm to find the greatest common divisor. So if we're trying to find the divisor, we have to make sure that v is not equal to 0, our second parameter. This is just standard parts of the algorithm. While the v is not equal to 0, we're going to put brackets for the loop. What we're going to do is we're going to first assign the temp to the module's value of u mod v. We're then going to set u equal to v, and we're going to set v equal to temp. Whoops. Just like that. And then we want to return data from this function. So how do we return data from a function? We use the return keyword. And we just return the data that we want to return. In this case, we want to return u. Now remember that if this function didn't return any data, we would have to change the type to void. And then we could just have a return with no data. But this is returning data, so we have to match up. And here's where we would say return, again, u. Also, if we were not passing data to this function, we could put void as the parameters. Or we could keep them empty. And that would say that the function takes no data. But we are passing 2 variables. And these variables, u and v, are local variables to the GCD function. We can use them inside the function. And that's what we're doing. These are all traits of a function. The return value, the data that you're passing in, using local variables, and then returning data. All those things pay attention to. In the syntax, with the brackets, and then also with the declaration at the top. Now we want to try to test this function. So we want to test it for all sorts of different things. Let's go ahead and remember that this function returns data, so we probably want to create a local variable in our main. We'll just call it result. We can initialize it to 0. And then we want to basically call the function. How do we invoke a function? We just specify the function name followed by the data that's being passed to it. And because this function returns data, I'm going to have, say, result equals, and then the function name. The function name is GCD, and I'm going to pass it 150 for my first test and 35. And I'm going to do 2 other tests to just pass different numbers. But what I want to do is I want to print out the data that's being returned, the result. So I'm going to say printf, and I'm going to say the GCD of 150 and 35 is %d line feed and then result. Right? So line 10 is important. We're getting data back from GCD, so we're assigning it to a variable. And we can call the function passing in 2 constants here, 150 and 35. We could also pass variables. The way that we invoke the function with data passed to it is inside the parentheses, we put the value separated by commas. And then the semicolon is at the end there. I want to do multiple tests, so I'm going to copy lines 10 and 11 and just put in some other data. I'm going to put in, let's see, 1026 and 405. And then also 83. And actually, you know what we could do is instead of returning the variable, we could actually just put the call of the function inside the printf and print it out right there. We don't even have to save it. So we could just say GCD 83, 240. We would have to change what we're printing out in terms of the hard-coded values here. So 1026, 405, and then also 240 and 83. So let's go ahead and compile that. Let's make sure we get no errors or warnings. We have no errors or warnings, so let's run it. When we run it, we should see the greatest common divisor 3 times for certain numbers. So we see the GCD of 150 and 35 is 5. The GCD of 1026 and 405 is 27. And the GCD of 83 and 240 is 1. Greatest common divisor means the factors that go into those two numbers. What's the highest factor? So 5 goes into 35 and 5 goes into 150, and that's the highest one. 27 also goes into 405 and 1026. That's the highest one between the two. So it looks like it's working. And we covered the basics of passing data and returning data. Now we want to practice a couple other things in terms of just algorithms and problem solving. Let's create another function called absolute value. The absolute value function is going to return a float and take a float. It's going to be a very simple function. So we're going to declare the function up on line 5. We're going to say float absolute value, that's a name, followed by the parameters, and we're just going to say float x, and then we're going to end a semicolon. Again, notice the function declaration, the return value, the parameters, specifies with data types, and then the name of the function. We can then go ahead and define this function below the GCD function, and it's going to be very simple. We define the function with the type that's going to be returned, the name, and then the parameter, just like the declaration, except that now we have brackets to start the block of code. This is easy because all we have to do is check the parameter that's passing and check if it's less than 0. If it's less than 0, then we're just going to assign it the inverse, which would be a minus x. So if it's a minus value, it's going to multiply by a minus, return a positive. And we want to return that data, so we're going to say return x. Okay. Now, one thing I mentioned in the lectures that I didn't get to provide an example for was what if you return data all throughout? Because we could eventually have a bunch of if statements, and we could be returning in each if statement, right? And so your function can, in theory, have many return statements if they're inside ifs or loops. And then you could have one at the bottom. The issue with this is it's really hard to follow. If you need to return at different parts of your code, basically just store the data in a variable and return it at the bottom. But here, this is a simple function. We're just returning a value. Let's go ahead and try to use this function. And it's really nice that it takes floats, so we can use it with integers and floats. So I'm going to create a couple variables here that we're going to pass, and I'm also going to create an integer. I'm going to do that at the top of my main. I'm going to create a float for f1, f2, f3, and I'm going to create an integer I1. And then I'm going to create another variable that stores the result, but it has to be a float, so I'm going to have to create another variable. And this is just going to say absolute value result. And I'll initialize that to 0.0. Now I'm going to invoke the function and print out the results. So I'm going to copy and paste some code here. I can invoke the function and store the data that's returned, or I can just pass it to the printf function. Probably want to do some code, some comments here. Testing absolute value function. And when you use the asterisk on a single line, it kind of highlights it a bit. So here I pasted in just a bunch of calls to the absolute value function and then displayed some results. So here in 24, I'm calling absolute value with f1. Remember, f1 is a float. It's equal to negative 15.5. I'm going to format the result and print it out. And then I'm also going to print out f1. So we're going to see if the result changes by calling the function than the original. So I'm going to print out the result of the calling the function and then the original value. This will tell us if it changed at all. If it was negative originally and changed to positive. Doing that on multiple lines for multiple tests. And then in line 37, the only difference here is that instead of storing the value in a variable, I'm going to just print it. So I have to change the results here to the right variable. So let's do that. And so down here, I want to do that. When I originally wrote the program, I wrote them as separate. So hopefully I make no errors here. And change all the ones I need to change. And that should do it. The other ones actually aren't printing the results of all the variables, only the ones on line 26. Otherwise, we're just showing the results. The first one just shows that it changed because F1 is a negative value. Well, let's build this. We have no errors or no warnings. The output that we want to pay attention to is just the absolute value output. So it might be better to actually add some line feeds. After we display our last one, let's add a couple line feeds. Easier to read. And run this. So now we see result is 15.5, so it actually changed it from a negative to a positive because F1 was originally 15.5, and all the other results are also positive values. The last print statement didn't print out the result, it just printed the value returned from the function. Looks like it's working. The last function that I wanted to define was a square root function. This will be a function that computes the square root of a number, and if a negative argument is passed, a message will be displayed and -1 will be returned. So let's define the declaration of this function as float square root, and it takes a float with any name. And square root is actually going to use the absolute value function, so we can define it above it and still use it because of the function declaration. So let's define it. And it will take, say, float. Okay, so we're getting pretty handy at defining these functions. Data type for return, parameters, brackets. We're going to create a couple local variables in here. These can only be accessed inside the block. This is just going to help with our square root algorithm. You'll notice here on lines 59 I created a constant variable. We haven't talked about that, but that's just a way to create a constant as opposed to using a define. We created a float variable named epsilon. It's 0.001. It helps with our square root calculation to make sure it's within a given range. We have a guess, which is 1.1, and an absolute value declaration here. We don't actually need to provide the declaration here because we defined it at top, so I can get rid of that. Now, remember that we have to check the parameters. We want to do parameter validation. If the parameter is less than 0, we want to print out a comment and return a negative value. So if x is less than 0, print out negative argument to square root and return a -1. Here's where we're going to have multiple return values, and I'll show you how you can return once and just put it at the bottom. Otherwise, we have our algorithm for square root. I'm not going to explain the algorithm because it's not pertinent to what we're learning. But basically, to find the square root of a number, we can get the absolute value of it by multiplying it and then minusing the x. So the guess is we're going to guess. So originally we're going to guess and then check if it's, this is the algorithm, check if it's graded, if it's within a certain range. And if it is, then we're going to set our guess to something and divide it by 2, and that's going to be the guess that we return. So at the very bottom we would say return guess. And so we're using the absolute value function. It's defined below us, but we have our declaration at the top, so that's good. One thing here is we have multiple return statements. This is perfectly legal, but it should be avoided because it helps. It's harder to figure out the what's going on. So what I would do here is I would probably store this -1 in a variable other than guess, but let's see here how we can do this. So what I would do is guess is initialized to 1.0 and we're returning a -1. I would probably just create another variable called float return value. We can set this to 0.0. And then before returning it here, because this is jumping out of the math function, I can just say return value equals -1.0. instead of having the return. Then I can check and I can say if return value is not equal to a negative 1.0. Because I don't want to execute this if I already have my non-valid number. And I could wrap this in an if statement. And then what I could do is I could just say, and then inside the while statement, I can say return value equals guess. That way I'm returning the correct thing if it was a valid entry. And then instead of returning guess, what I do is I return the return value. And this code is a bit cleaner because it only returns once at the bottom. And it's clear. It's easier to follow. So return value is either -1 if it's an invalid argument, or it's going to be the actual square root if it's not an invalid argument. And we could also even make this simple by just actually not even checking the return value here. It would probably be easier to just say else and make the else part of the original if. So if it's a positive number, that would even make it cleaner. That way you don't have that if statement. Now we need to test it. Let's go ahead and test this. We'll just call the function a bunch of times. We'll say testing square root. Not going to do any fancy printing here. I'll just make sure that I can add a bunch of line feeds so that it's easier to read. Whoops, hit the insert button there. Alright, so now I'll just do a bunch of printfs where I'll send in some good and valid data and some invalid data, and I'll format it the same way. Let's see. Let's just say the first call will be square root of, what's some good valid square roots? Well, first we'll check it with a negative number, so we'll just say -3. That should print out an error. Otherwise, we'll test it with some valid numbers. So we'll say the square root of 16, and we'll just pass an int. They'll be converted. I might get some warnings. Well, I don't want to get any warnings. And we'll do 165. Now let's run this and test it. Hopefully it will compile. I do have a misspelling with float. Now when I run it, hopefully we'll get good square root output. So here we have a -1, and we actually printed out negative argument square root, so that's good. And then the other ones are the correct, I believe the correct square roots, so it looks like the function works pretty good. We did square root of 16, which is 4, 25, which is 5, 9, which is 3, 165 is 12.85. So I did some miscalculation there. I was trying to think of 15 times 15, which is 225, right? 15. Yeah, 225. So if I put 225 in here, it would come back as 15 as a square root. I'm going to provide this source code for you so you can analyze it, but understand function declarations. Understand how to define a function with the return type and the parameters, passing data. Understand local variables. Understand how to return only once at the bottom. The algorithms themselves, not that important. I hope this helped. Thank you. Hello and welcome back. In this lecture, I want to give you another challenge. It's related to functions, but this challenge is going to be more about divide and conquer. It's going to be more about organizing your program around modules. It's going to be more about problem solving. What I want you to do is I want you to write a tic-tac-toe game. This is going to help you just become a better problem solver, and it's going to help you organize your program around functions. You're also going to utilize an array. You're going to have to figure out how to format certain data. But it's going to be a simulation of a tic-tac-toe game. We're not going to write a computer. It's going to be player 1 versus player 2. So I want you to write a program that plays tic-tac-toe. Hopefully everybody is familiar with this program. or this game, I should say. It's just a game that's played on a 3x3 grid with 2 players. You take turns, X's and O's. Hopefully that rings a bell. I didn't want to have to go and explain this game, but hopefully you're familiar with tic-tac-toe. I'm going to provide a little demonstration of how it works and how I would expect the output to play out. But it's a basic tic-tac-toe game. What I want to do is you're going to probably need to create an array to represent the actual board, the 3x3 grid. I think you can get away with just creating a single dimension array. You could actually create a 2D array as well to represent the rows and the columns. 2D would probably be more intuitive, but it might be easier, it might be a bit harder to visualize in your code. But either way works. The good thing about programming is there's many solutions to a problem. I'm going to show you one of my solutions and my design approach, but feel free to change the design. As long as you're using the C constructs correctly, that's all I care about. I want you to learn how to use C. As long as your program is modularized and it's organized and it's easy to maintain and there's quality code, that's what I'm worried about. So one way to implement, only one way, is representing the board as a single dimensional array with 10 elements. The reason I have 10 elements here is I don't want you to use 0. These 10 elements are going to represent the board, but they're also going to represent the coordinates on the board. So I'm going to demo this and show you how I'm thinking it working, but the way that you're going to actually pick the box that you want to draw in is going to be based on the element number. In addition to creating an array for the board, you have to try to think of how you're going to break this problem down, how you're going to organize it. I'm thinking at the very minimum that you're going to need at least 3 functions, probably more. But you need to at least have one function that checks for winners. This will basically just see if a person has won the game. Or it may also even check for a draw. You should have a function that draws the board, because you're going to be drawing the board after every player's turn. And you're going to reuse this. Another function for marking the board, this happens when the user actually wants to put X or an O in a certain box. You need a function to set that box as an X or an O. What will happen is you'll probably be populating the array with that X or O. And that way you can look at the array to see if you won or lost. So you can, and in the mark board, it would also allow you to check for an invalid selection. So if valid selections were 1 through 9 and the user entered 10, you would say, hey, you can't do that, try again. The game should be user-friendly, should be intuitive to use as far as a user perspective, and it should be organized as far as a programming perspective. Really think about this one. Get some planning out, do some planning, get some paper out, start writing some design out, how you're going to attack this problem and what functions you're going to need to use. The way that I'm thinking of this is going to run, let me show you a little demo. I'm not going to show you any source code, but this is what I envision the game will look like when we run it. Maybe a little title that says, hey, the game. And then also a little information about the player. Player 1 is going to be X, player 2 is going to be O. And remember, this does not have to be playing the computer. You can just put in each turn. So you'd have to play this game if a friend was sitting next to you and they would have to tell you where to put the number. If you're getting really ambitious, you can write the game to play against a computer. But you'll notice that the 3x3 grid has numbers in it initially. You can use these numbers to enter. So if player 1 wants to take their turn and they represent X, depending on what number they enter, that's where the X is going to be placed. So we print the grid, we display the board, and then we also tell the user whose turn it is. And we tell them to enter a number. So in this case, I'm going to go ahead and enter number 2 and hit return. And what will happen after I hit 2 and return, it's going to actually see if somebody won. It's going to clear the screen and it's going to redraw the board. So after I hit 2 and entered, you'll notice that I still have the title, I still have player 1 and player 2, but now in box 2 I have an X. So what else I should have done there is I should have checked before I displayed the board whether or not we had a winner or a draw. And obviously that's the first entry, so we have neither. Since we don't have a winner or a draw, I'm now going to ask player to enter a number. And then they can pick any number here. Now if I entered an invalid number, like 10, it should tell me it's invalid. And it should allow me to maybe make another move. If I would enter 2, 2 should also be invalid. So if I enter 2, it also says invalid because 2 is already taken by X. So the program is allowing me to try again. You could just get rid of their turn, but that's not really fair. So now I'm just going to say, where do I want to place the O? I'm going to say 5. I'm going to put in a valid move. It's going to redraw the board, and there's an O and 5. And now it says player 1. And you keep doing this until you have a winner or a draw. I'm just going to say 9. Now I have an X there. Valid entries are 1, 3, 4, 6, 7, and 8. I'm going to say 3. And let's actually try to get X to win. So now X is going to go into 8. And I'll put O and 6 just to show you that the game works with a winner. And then I put 7 for X. The game should now be over. I hit return. It says player 1 wins, and it even played a little sound for me. I did a little fancy stuff there. So the game is over. Player 1 win. And it should also happen if player 2 wins or if there's a draw. So think about how you want to attack this problem. Nice little program. I'll go through a solution and provide the source code in the next lecture. Thank you. Hello and welcome. I would like to provide a solution for the tic-tac-toe challenge. Now remember, there's many solutions to a given problem. This is just going to be my solution. If your solution is different, as long as you follow good programming practice and you use the C programming language the correct way, then that's fine. I'm just providing my solution. I'm sure it can be improved. So let's get started. I'm going to create a new project. It's called tic-tac-toe, obviously. And we're going to start trying to modulize it. I tried breaking it down like I did in the description in the lecture. I'm going to create only a few modules, or I should say a few functions. Hopefully this will be okay and work good for you. Say tic-tac-toe. And you see I'm using camel case for all my naming conventions, just what I'm used to. We could actually even separate this into multiple source files as well if we wanted. So we have our main. Let's get rid of this printf. I am going to include an additional include. This will allow me to basically do some clearing of our system and a couple nice things. Allow me also to, I think, remove a char. So in addition to these two libraries, let's include conio.h. And what I want to do, and I want to attack this problem, I want to try to module as much as I can. I mentioned that I'm going to use a single dimensional array. A two-dimensional array might even work better. But I'm going to implement this using a single dimensional array that represents our game board, our tic-tac-toe board. I'm going to create this as a global variable. I'm using a global variable here because I haven't demonstrated the concept of passing data by reference in C. I don't want to confuse you. I would not have to use global data here, and I could pass the data to functions, but I would need to use pass by reference. I would have to pass around pointers. And we haven't discussed any of that yet. So I'm going to use global data. Forgive me. Remember, I said global data is usually not a good thing to do. But because, again, we're trying to demonstrate learning, divide and conquer, and we're trying to demonstrate how to utilize functions, I need to use global data because we haven't talked about pointers yet. So my global data here that I'm going to use is my square that represents my grid, my tic-tac-toe board. This is going to be a single dimensional array of 10 elements, mainly because I don't want to use the 0 element. I'm going to use this array to pick numbers to play the game. It's going to also allow for me to have my coordinates. I'm going to initialize this with just values 1 through 9. And this is going to be a character array because I need to put X's and O's in it. All right, we haven't talked about character arrays yet, but this will allow me to put single characters. It's just like the array concept of ints, except it contains characters. Characters, remember, have single quotes around them. So 1, 2, 3 to 9, the 0 there, the O, I'm just going to skip. I'm not even going to use. But because I want to use the ones to, it makes programming a bit easier. I can use the value that the user enters as an index, as a valid index. I'm also going to have to create two global variables for choice in the player turn. So choice is going to be what they entered via the keyboard, either a 1 through 9, depending on where they want to place their X or O. Player is going to just represent whose player's turn it is, player 1 or player 2. I don't need any other global data. I just need my function declarations here. I'm going to start off with creating 3 functions. So I'm going to have 3 function declarations. I'm going to have one for checking for a win. It's not going to take any data. It's going to return an int. I'm going to have one that doesn't return any data, that just displays the board with the correct characters. It also doesn't take any data. And I'm also going to have a function that just marks the board. This will take the user input, and depending on what they entered, it will place an X or an O in the correct spot in the array and then display that array using display board. So here we're just going to say mark board, and that's going to actually take a mark with an X or an O. So I can reuse this. I can reuse this for player 1 or player 2. 3 function declarations so that I can place my functions anywhere in the program. I've declared them up top. And you'll notice that 2 of these functions aren't returning any data, and only one is taking a parameter. Now we can actually start invoking or creating these. Let's implement these functions before we implement the gameplay. So first, let's implement check for win. This function is basically going to work where it's going to check the board to see if there's any wins. So it's going to contain a lot of if statements. I could probably improve this code quite a bit. But I'm going to put some comments in here because we should always have comments at the top of our function. These are pretty simplified. We should have the function name. This is basically saying that the function is going to return a game status of 1 if the game is over, tell you if you won. A result of -1 if the game is in progress, and 0 if the game is over and it was a draw. That's why, so this function, check for win, is returning an int. So I'm going to go ahead and define this, and all this is going to do is it's going to look at the array and see if there's any spots in there. If 3x's match. So there's a lot of different if statements. So how do we know if a player has won? Well, we know if a player has won if they either match in a row, diagonal, or a column. So we have to check each one of those situations. And we know the rows and the columns based on the array. So if my square 1 is equal to square 2 and square 2 is equal to square 3, that means we have a match in our first row, right? So I'm also going to create a return value here. At the top, I'm just going to say return value. Initialize this to 0. Actually, we'll initialize this to 0 for game over. And if we have a match in the first row, I'm going to return 1. Game's over. We then have to have a series of other else ifs to match. And actually, I don't want to return 1. I want to set my return value. Because it's, we could return, but it makes the program harder to follow. Otherwise, we're going to check all of our other rows. So I'm going to copy and paste some code in here because it's a lot of redundant code. The only thing that's interesting is if we have a draw. So let me put in all the else ifs for winners. All right. And then I'm also going to return different values. And I could actually have, instead of having a bunch of else ifs, I could have ampersands, but that's even harder to read. So if we have a match in the first row, and let's make sure our indentation is correct. If we have a match in our second row, that's what the second one's doing. If we have a match in our third row, return 1, add some new lines for readability. Don't need any brackets because they're single statements. On line 37, it looks like we're matching 1, 4, and 7, so this looks like a diagonal match. Return 1. 40, we're matching 2, 5, and 8. That looks like a match of the center going down, so the second column. 3, 6, you can see the other matches as well. We have to basically catch all matches for rows, columns, and diagonals. And that's what we've done with all these statements, looking in the array. Now, the one thing that tells us if we don't have a match, or we have a draw, is we have to compare all of them and basically just make sure they're not the numbers that were initialized. So if we have our array square and it doesn't contain 1, 2, 3, 4, 5, 6, 8, or 9 for any of the values, that means we have a draw because they contain a 0 or an X. So we can write another else if that basically says it's a draw, and we can set the return value to 0. Return value equal to 0. And again, this is just basically checking this last else if the numbers are the same as they were initialized. If they're all different, then that means we can return 0. Let's put that up 1. Otherwise, if we don't have a draw and we don't have a winner, that means we're not done. So a final else statement can just say return value equals a -1. Because remember, the function is returning -1 for game in progress, 1 for game is over, and 0 for game with no result. And then the last thing I want to do is I want to return the return value. So here I'm just going to say return value. And this will complete the function. And what do you notice when we're doing this? We're dividing and conquering. All we're focusing on right now is checking the board to see if there's a win. We would work in small chunks, just like this, and we would constantly test. This allows us to focus on our design and also allows us to reduce or isolate our errors easier. Now that we're done with the game board, we want to go ahead and implement the display board. The display board is just going to show the board. So all this really needs to do is draw the array in a specific format. Right? So we're going to write a function called display board. It's not going to return any data. It's not going to take any parameters. The reason it's a function, number one, is because we're going to need to draw the board many times. And also, it's just better because it's doing a specific task. Now this one is just going to have a bunch of printf functions in it. And it's going to have a bunch of formatting. So I'm going to copy and paste it in. The thing that's unique here is I'm clearing the screen each time. In that con.io, actually I don't think it's in the con.io, I think it's in another include. But if you say system and Windows and you say CLS, that's going to clear the screen. That just makes it cleaner. We're then going to just do a bunch of printfs. We're going to print out the title of the game. We're going to print out the player, 1 and 0. And then we're going to print out the board. The board is going to be nicely formatted with some parallel bars. And then we're going to print out the values of all the values in the array. And if the value is X or 0, it's going to display. If it's not, it's going to display a number so we can use that number to select our option to draw. And that's it. That's it. That's all this function does. Now that we're done with displaying the board, we now want to create our last function, which is marking the board. Right? So mark board is going to set the array with a particular value. And it's going to take a mark in either an X or an O. So it's going to take a character. What this is going to do is it's going to have a bunch of other else if statements. Right? So here in our mark board, we're going to want to basically give some comments and say that this is going to set the board with the correct character. X or O in the correct spot in the array. Okay, so hopefully that makes sense. As you see the code, I got to end my comment. I want to format it nice, so it's 2 lines here. And all this is going to do is it's going to check to see what the user entered. So remember, we have 2 global data values for what the user entered. We also have a value for the current player. So choice is going to be basically what is entered via the keyboard. We haven't implemented this yet because we're going to implement that in the main function. Player is going to be the current player. We're going to need both of these to make our marks. So what we're going to do is we're going to have a bunch of else statements, if-else statements. We're going to check the choice, which is what's input by the user. And if the choice is equal to 1, we want to draw something in that square. We also want to make sure that that square is available. So if it's equal to 1 and it's not currently equal to 1, that means that basically somebody already put an X or an O there and we can't use it. If it's equal to a 1 and they entered 1, that means we can set the array to a specific value. We're going to set the array to what was passed in, either the O or the X. And we're going to repeat to do this for each choice, if its choice is 2, 3, 4, 5, 6, 8, or 9. Right? So a bunch of else ifs that do the same thing. If the user entered choice 2, we're going to make sure the indentation's good, and square 2 is available, we're going to mark square 2 with whatever we passed in here. And depending on what player's turn it is, we're going to pass in an O or an X. Now, the last thing we need to do in this function is we have to validate. If they passed in anything other than 1 through 9, then that's an invalid move. So our last else statement should basically last else statement here will print out a message saying invalid move. It will mark the player down 1 because remember, players are either 1 or 2. And we're going to mark the player back, and then we're going to increment it in our loop in our main function. And then this last thing, getChar, is just pausing the program so that the user has to hit return after invalid move. Otherwise, invalid move would be displayed, and then it would immediately be erased because we'd redraw the board again. So getChar pauses it. It forces you to hit the enter button to go on to enter another value. And these are our three functions. Remember, this function doesn't return anything, so we can keep it at the bottom. Now we have to actually implement the gameplay. The gameplay goes in the main function, which is, where? I gotta find it. There it is. It's empty. And so for the gameplay, this is where we're going to ask the user to enter a number. We're going to draw the board. We're going to check for win. So we're going to create two local variables here, and we're going to initialize our player. Here we're going to create our integer I. This is going to be used for our loop. And our mark is going to be either X or O, depending on whose turn it is. Yeah, mark is going to be X or O, I believe. I'm trying to remember if mark is... No, yeah, mark is going to be X or O. And choice is going to be what the user enters via the keyboard. So two local variables. We're also going to set our player, which is a global variable. Initially, it's just going to be player 1 to start the game. Then we're going to have a loop. We're going to have basically a loop until we're done playing. I'm going to use a do while loop here because I want it to execute at least once. I want to display the board at least once. So I'm going to display the board and play the game until I get a draw, basically, or a win. So I'm going to do it as long as I is equal to a -1. What does a -1 represent? It represents the game is in progress. I is going to be the return value for checking for win. And you'll see that in a second. But basically, we're going to have a loop that keeps doing the same thing over and over until the game is over. And the game is going to be over if it's not a -1. So what do we have to do first? First thing we have to do is we have to display the board. So I can just call the function display board. Then we have to calculate the player. And the player starts off player 1. What we're going to do here is we're going to use a ternary operator. And we're going to say if the player mod 2, then the player equals 1, else it equals 2. This is a way to determine the right player. Each iteration of the loop, it's going to change from 1 to 2 or 2 to 1. When it starts out as player 1, it's going to say player mod 2, I'm misspelling there, 1 divided by 2, or the remainder of 1 divided by 2 is what? 1. So if it's 1, you're going to be player 1. And then when you go back for the next iteration, player is going to be equal to 2, because we're going to increment it. 2 mod 2 is 0. So if it's not equal to 1, then player is going to be equal to player 2. It's only going to set it to player 1 if player mod 2 is 1. Remember that ternary operator, hopefully. The next thing I need to do is I need to get the input from the user. So here I'm going to say, I'm going to ask the user to input a number. I'm going to say player %d, either player 1 or 2, enter a number. And then I'm going to put the player to print out, player 1 or 2. Then I'm going to read the input from the user using scanf. And that's going to be an integer. That's going to represent a spot on the board, 1 through 9. And I'm going to store that in my choice variable. Choice is an int, so I have to pass in the address. And I have to say choice. Only if it's a string, I would not pass in the address. Then I can basically determine whether or not what the mark is. I have to determine if the mark is an X or an O based on the player. So I'm going to use the ternary operator again. And I'm going to assign to mark either an X or O. If the player is equal to 1, I'm going to assign to mark the X, capital X. Otherwise, I'm going to assign it an O, capital O. So this ternary operator is very useful when you have to assign variables based on a condition. Again, what this is saying is if the player is equal to 1, mark is going to be equal to X. Else, it's going to be equal to O. The question mark represents if the Boolean evaluation is true. The colon represents if it's false. Now that I got the correct letter, I can call my function for marking the board by just saying mark board and passing in the X or the O. After I mark the board and they made their selection, I have to check if there's a winner. I have my variable I, which really probably should be a better name. Let's name it status check. game check. How about that? Or game status. Game status. And game status is going to be equal to a 1, a -1, or a 0. Game status is going to be equal to whatever is returned from check for win. Because remember, this function will return a 1, a 0, or a -1. A 1 if you win. Well, actually, let me remember. Check for win returns a 1 if the game is over with a result. -1 if the game is in progress. 0 if it's over with no result. So now that we stored game status, we'll also want to change the exit condition of the loop. So if the game status is equal to -1, we'll jump out of the loop. Otherwise, all we need to do is change the player's turn. How do we change the player's turn? We just increment the player by 1. That way, the next time it will go up and it will be 2, and player will be equal to 2, and we'll go back down. When they make invalid attempts, what happens in the invalid attempt is it decrements the player count. When you decrement the player count, you go back to the correct player. So if it's 1, you decrement it to 0. The next turn is going to be 1. It's essentially your same turn again. That's why we increment it. Now, if it's player 2, we increment it by 1. And what happens is 2 divided by 2 is 0, so it actually sets the player back to 1. That's how that works. But this is all the logic. We did a lot here. You should not write all this code and test at once. You should have been working with the divide and conquer, constantly testing as you're running the code. Now, I'm going to provide this solution, but let's run it and test it. It's going to work just like it did in the demo from the challenge lecture. But again, study this code and make sure you understand what's going on. The use of arrays and the divide and conquer approach. But look how nice this main method looks. It's very easy to know what's going on in the main method. Display board, change player, and you probably want to put in comments here. You know, change turns. And then also here, get input, right? And then set the correct letter, set the correct character based on player turn. You know, and you don't even really need these comments because the functions are so descriptive. Mark board, set the board based on the user choice. Based on user choice. Or invalid choice. And then the game status, check for win. Pretty self-explanatory. And then we jump out if the game is over. Let's build this. Hopefully get no errors, no warnings. We don't, which is nice. Now let's run it, and you're going to see it works just like in our demo. First thing it does is it's going to display the screen, and it's going to allow us to put in an enter. And it has our grid, 1, 2, 3, 4, 5, 6, 7, 8, 9, our array. So it tells me player 1 to enter something, and I'm going to enter something valid. And it draws it. And it clears the screen. So it looks like nice. And now there's an X in 3. Now it's player 2's turn. Let's do something invalid. It says invalid moves. It pauses. I hit return. I get to go again, player 2. Now I hit 1, redraws with the O in the 1 spot. And I continue this until we have a winner or a loser. So let's cause a winner for O. So now X is going to be 2. O is going to be 5. X is going to be 6. And O is going to be 9. Game over. Because we just drew 3 O's. Actually, I forgot one thing. It doesn't tell you if you won. So the one thing I forgot was after the while loop to display the congratulations you won. And all we have to do there is we have to check the game status. If the game status is equal to 1, that means a player won. And it would be the last player that wins. So we would print out player %D wins. Otherwise, we're going to just print out a draw. Because if we got out of our loop and the status was a -1, we know the game was over and had a result. It just might. So we have to have that last if statement to display the results. So now let's run it again as a winner. And now we'll actually see somebody win. So I'm just going to put in valid numbers here. Cause a quick win for X. And actually I have to do it in this program because that one goes away. There it goes. Player 1 wins, and it played in a little nice sound there. So this was a long lecture. I apologize for the long lecture. Study this code. I'll provide it as a source file. Hopefully you learned a lot about methods in divide and conquer. Thank you. Hello and welcome back. We are in a new section. In this section we're going to talk about character strings. You've probably heard me say the word string quite a bit throughout the class, and you may have been a little confused. A string is really just a word. It's something enclosed in double quotes. We're going to talk about how we can store strings in character arrays. So up until this point, we're pretty familiar with a single character, the char data type, or the char data type, however you want to pronounce it. We know what that is, but we haven't really learned about words. To assign a single character to a char variable, the character is enclosed with a pair of single quotation marks. All right, we're familiar with this. We've learned all about this. In this example, plus sign equals plus inside single quotes. The important thing there is the single quotes. You've also learned that there is a distinction made between single quotes and double quotes. So if you put plus sign variable and you assign it something in double quotes, and plus sign is of type char, that's not going to work because you can only assign single characters to the char data type. A string constant or a string literal is a sequence of characters or symbols between a pair of double quotes. So now double quotes are going to come into play. Anything between these double quotes is interpreted by the compiler as a string. And so really it's just, it can be alphanumeric characters, it can be special characters, but they usually make up words. You can kind of think of it as text. You can have spaces, but anything in double quotes is a string literal. Every time you have displayed a message using the printf function, we have defined the message as a string constant. Remember printf, the first argument, we put some text inside there and we have some format specifiers. That is a string constant. You also hear the term string literal. It's the same thing. So when we say printf, this is a string, everything in between that, those double quotes, is a string constant. And we can put it on 1 or 2 lines. You also notice that you can have print statements that have escape sequences, \n. Now this third one's pretty cool, which I'll explain in a second. But the main point is you have to understand the difference between single quotes and double quotes, right? And what's inside there. With the double quotes, you have strings. With the single quotes, you have characters. There are 2 types of constants. For this third example, this printf where we have the 4 and then we have a backslash and then a single quote, if you want to actually display a single quote as output, you have to escape it. And you can escape special characters by using the backslash. So in the third example, it's actually going to print out 4, double quote, you write, and then another double quote. So the compiler interprets an explicit double quote without a preceding backslash as a string delimiter, right? Every other time you use a double quote, it's beginning and ending of a string. But what if you wanted to display it? Then you have to just put the backslash in front of it. And it will tell the compiler, hey, this is not actually ending the string. It's something that we want to display or something we want to use as that character. Also, you have to use the escape sequence if you want to do the backslash as well, because the backslash is an escape sequence. So when you see the backslash, you're actually displaying that backslash in a printf function. If you see it anywhere else, you're assigning the backslash to a variable or however it's used. But a backslash itself, followed by another backslash, will escape the backslash string. And again, a backslash in a string always signals the start of an escape sequence. So one by itself is not going to display. These are special characters. So when you're in double quotes, you may see the backslashes to escape special characters and even the backslash itself. Here's how a string is in memory. A string in memory is each single character is represented by a bit here. And so if you have a string called this is a string, you're going to see it where the space has something in memory. And also you should notice at the end that \0. That's the null terminator, which we're going to talk about. But for the second string, again, you see everything that's in memory. Even the \n, which represents a new line, is in memory. And then for you write, you'll notice the quote is in memory. But the backslash isn't, because the backslash is delimiting the quote. It's escaping the quote. So this is how it looks in memory. And you should notice that the string in memory always has at least one more byte for that \0, which is the null character. Also, it looks like the diagram on the bottom is incorrect. You'll notice the U is not shown here. So after the quotation double quote, you don't see the U there. The U should be there somewhere. And it kind of implies it's there somewhere. They are really just showing it. These are the ASCII values underneath. And so then it's just showing, not showing it, but U would be right before the right. And that's what I want to talk about, is this null character. It's a special character with the code value 0. It's added to the end of each string so that the compiler knows where it ends, and also when you run it. This character is known as the null character, and you don't just put a 0 in it, you can put a \0. And that's what was in this previous slide, right, at the very end. And it can be anywhere actually in memory, and depending on where it is in memory, a function is going to go and look until it sees that \0, and it may display it or may manipulate it if you're using different string functions. It's very important, that null character. A string is always terminated by a null character. So the length of a string is always 1 greater than the number of characters in the string. And this is going to become very important when we use character arrays and we specify the size of the array. The array size is always going to have to be 1 more than how many characters you want to store because of this null character. We also have a concept of null that we haven't really talked about in too much detail. It usually comes into play when we talk about pointers. But do not confuse the null character with the null keyword. So there's a null keyword in one of the include headers that you can use. And this is a symbol that represents a memory address that doesn't reference anything. So you use it when you use pointers. A null character is just a string terminator. We'll talk more about null when we talk about pointers. But make sure you understand the distinction between null character and the null keyword. You can add a \0 character to the end of a string explicitly, and this will create 2 strings. And I'll show you how to do this when we talk about defining character arrays. Here's an example with the null terminator. We have a printf here, and we say the character and then the \0, which terminates a string. So what's going to happen is if you compile and run this program, the output that you're going to get is the first line is going to be the character, and then the \O, there's going to be it's going to end it, and only the first part of the string is going to be displayed. There's going to be no more output because print thinks that it's the end of the string. So it just prints out the character. Output is going to end after those first 2 words because the function stops outputting once it reaches the null character. So the second \0 if at the end of the string, so even though you don't see a \0 here right before the ending double quote, right after string dot, there's still one there, but it never gets reached. So there's an implicit null terminator at the end of the string in the printf, so it knows where to end. And if you add another one, it's only going to display up to that first one. So the first null terminator that's found in the character sequence always marks the end of the string. So understand these null characters. This was just a quick overview to describe what a string is and understand that strings are in double quotes. And I also want to describe the null character. In the next lecture, we'll understand what character strings are in terms of how you can create this one type of variable to store strings. Thank you. Hello and welcome back. In this lecture, I want to talk about creating a string, specifically how you can do it in C using a character array. I tend to use the terms string and character strings interchangeably, but really a character string is the char array that we're going to talk about. It's a very important concept. We're going to be able to now utilize words and text in our program to do all sorts of things. Now, C itself doesn't have any data type that represents a string. There's nothing there. Many languages support either an object or a data type of type string. Now, because there is no data type C in string, you can't use any of the operators on the string. So what we'll end up doing is we're going to end up using this standard library, and there's all sorts of string functions that we're going to talk about. We have 3 lectures dedicated to the various string functions that you can employ. And this will help us manipulate the strings, get information about the strings. But you cannot utilize operators on strings. No plussing or minusing strings, nothing like that. Strings in C are stored in an array of type char. We know what an array is. We know what a char is. A type char is a single character. An array, you can just store multiple elements in the same name. So it makes sense that a string would be inside of a character array because a string is many, many characters. So characters of a string are stored in adjacent memory cells, one character per cell. You can access it just like you access an array as well. But how you would actually declare a string in C is you would simply use the char type and then the brackets to indicate the size, just like a normal array if you were to create it of a different type. Char, and then whatever your name is, and then the size of the character array inside square brackets. That's how you can declare a string in C. Now, when you do declare the string in C like this, there's no actual data associated with it. You're just specifying the size. That's the simplest way. So the variable can accommodate a string that contains up to 19 characters. Remember this null character. If you say that your string size is going to be 20, that means only 19 characters can actually be stored because you have to have that one extra character for the null. Keep that in mind. Declaring a character array as 20 means 19 characters can be stored there. When you specify the dimension of an array that you intend to use before a string, to store a string, it must be at least one greater than the number of characters in the string that you want to store. The compiler will automatically add the null terminator to the end of every string constant. So what you should really do is when you create these character strings, you should be initializing them. Okay? So you can initialize a string variable just like you can initialize an array. You put each character inside of these brackets. Right. So this looks very similar to if you were to initialize elements in an integer array. But if you say char word and then inside the squiggly brackets, you put in each single character, that would create a character array. So it's the same as any other array initialization. In the absence of putting the size, the C compiler automatically computes the number of elements in the array and then adds 1 for the null terminator. So it's based on the number of initializers you have in between the brackets, curly braces. This statement is going to reserve space and memory for exactly 7 characters. HELLO, exclamation point, and then the null terminator. And this little diagram on the right shows you that. Automatically adding that null terminator. Now, it'd be really kind of a pain in the butt if you always had to initialize your character arrays with single quotes followed by commas. So what you can do is even shorthand notation is you can just put double quotes around that. So you can either specify the string explicitly, like in that first example, and then you would have to actually use a string function to apply data to it, or you can let the compiler do it for you. The problem with doing it explicitly is you always have to remember to add that extra character for the null. So what you should really do is you should be letting the compiler figure it out for you. So don't put any numbers inside those brackets for the size. Because if the size specified is too small, the compiler cannot fit the terminating null character at the end of the array. And it doesn't put one there. And it's not going to tell you that it didn't put one there. So you're going to have a bug in your program and you're not even going to know it. Best practice is when you're using a string literal and you're initializing a string to just let the compiler figure out the size for you. You know, do something like make it a larger size or something and then just put it in there and it will figure out the size for you. So do not specify the size. Let the compiler figure it out. This way you can be sure that it's going to be correct. Just leave those brackets as empty brackets and assign it with the assignment operator, and then inside double quotes you can just put it. You don't even need the square brackets. This is the best practice. We'll go through an example. You can also initialize just part of an array of elements of type char with a string. So if you actually created a size that was really large and you only assigned a couple characters, that's fine as well too. You're only initializing some of the characters. All the other characters are just going to be empty. So what will happen here is the compiler will initialize the first 5 elements. Stir 0 to stir 4, all of those characters are string constant, and then string sub 5 will contain the null character. Space is still going to be allocated for all 40 elements in the array, but only 5 of those are going to be used. 4 plus the null character. So again, your best practice, don't actually specify a number inside the size. Just assign it a string literal with using double quotes. That's what you're going to end up seeing. Now, if you didn't initialize and you just created the character array with a size, how do you put data in it? Well, because it's array, you can't just assign data. Right? We know that if we had an integer array, we can't just assign an integer array the number 5. It doesn't make sense. You have to specify the actual elements. You have to specify the indices. So you can't do something like declare a character array with 100 characters and then say s equals hello. That is not going to work. Because again, s is an array. Even though it's a string inside double quotes, it's still an array in memory. So if you're performing an assignment operation, you cannot assign one array of characters to another array of characters like the above. If you want to assign data to a character array after you've declared it and after you've initialized it, you have to use a special function called stir copy. And we're going to talk about that in another lecture. So up until this point, when you create your strings, they're going to be string literals. They're going to be inside double quotes, and you're never going to modify them. So this is perfectly valid as well. You could actually just access each character or each element in the array by the index and specify each character. So s sub 0, s sub 1, and then put a single character in a single quotes. You could assign it that way, but imagine if you had a string that was 100 bytes. This is going to take a lot of lines of code. So you don't want to do that. What you're going to want to do is initialize it when you declare it with no size, and then specify, if you ever want to modify it, use stir copy. As far as displaying a string as output, we're still going to use that printf function. When you want to refer to a string anywhere in your program, you just use the array name by itself. You don't have to specify indices, because indices inside the array is going to specify a single character. If you want the entire string, you just use the array name. So if you're using the printf function to display output, you would just do the following. Inside the double quotes, you would use a %s as your format specifier, and then just the name of the character array. So you don't treat it like other arrays when you want to access it. When you want to access it, just the name, no actual indices or brackets. And the %s format specifier is for outputting a null terminated string. Remember before we used %d for integers. We've used, you can use %c for characters. For strings, you use %s. And those are character arrays. And the null terminated it expects a null terminated string. So however you initialize the string, if you did it with no size and null terminator was automatically added, or if you created it with a specific size and you added it, or if you added it explicitly, it doesn't matter. It just has to be null terminated. The printf function assumes when it encounters the %s format specifier that the corresponding argument is a character string that is terminated by a null character. That's what it expects, so it has to be that way. To input a string, we know how to input other sets of data via the keyboard using scanf. We're going to do the same thing for inputting strings. We're going to use the scanf function. With the scanf function, it's going to be the same way, except you're going to use a different format specifier. So for strings, you're going to use a %s as input, and that's used for inputting a string. The other thing to notice here is there's no ampersand for the variable name because it's a character. Remember we mentioned you only have to provide the ampersand, the address of operator, on strings. The reason being is when we talk about pointers, it will be more clear, but char input, even though it's a character array, it's a pointer. And scanf, as its second argument, takes a pointer. So that's why you don't have to do it. When you declare integers and doubles, those are not pointers. And so if you want to read input from the keyboard using scanf, the second argument expects a pointer, you have to pass in an address. Now with the scanf, when you do a string, scanf is only going to read up until space. So if you do scanf and you type in Jason is a instructor, the only thing that's going to be stored in input is Jason, because once it hits that space, it's not going to read the rest of the string. So there's other functions that you can use to read the entire string. Some of the examples we're going to use will probably do that. You can do things like fgetS, which is another way to read input from the keyboard, and that will read the entire string regardless of spaces. But there's another one, I think it's called get_s for C11. But we'll talk about that more, but that's just one thing to remember when you're reading input for strings. It's only going to read all the way up until the space. How about testing if two strings are equal? Well, up until this point, we have tested all variables to see if they're equal. We just use equals equals, right? But with strings, this is not going to work. The equality operator, remember we said that strings are character arrays, so you can't use operators on them. And the equality operator can only be applied to ints and doubles, or floats, or characters. It does not work on structures or arrays. You can't compare two arrays. So it's not going to work with strings. If you want to determine if two strings are equal, you have to explicitly compare the two character strings character by character. So you'd have to look at each element in the array index by index. However, that's really a big problem because that would be really tedious. So we're going to talk about how you can do it very easily using a stir compare function from the standard library. But you cannot use the equals equals. Remember that. And again, just as a reminder, I've said it a couple times, I want to say it again. The string constant x inside double quotes is not the same as the character constant x inside single quotes. X inside single quotes is a basic type. It's just char or char. X inside double quotes is a derived type. It's an array of type char. X inside double quotes really consists of two characters, the x and the null terminator, the null character. So keep that in mind. Here is an example of how we can create strings, either declaring them with a size or initializing them on the same line. Now this is best practice. If you're going to use string literals, what I would do is I would do what it says right here. Create the character array, do not specify a size, and then to the right of the assignment operator, have double quotes. The compiler will automatically create the right string and add a null terminator to it. If you specify a size and then you don't have enough characters, it's not going to store it. All right, so just create character string literals by using the char data type, the name of the variable, and then empty brackets. This program, let's see, this program is going to, I think, count the characters in an array. So it's essentially going to get the length of the string. What we're doing here is we're creating a variable named count in two character arrays with two different strings, to be or not to be, and then comma, that is the question. Char stir1 is going to have a null terminator after b, and stir2 is going to have a null terminator after question. So we have a loop here that's going to go through the first array from count equals 0 all the way until we see a null terminator. And we can use the not equals in this case because we're comparing a character, right? Null terminator is a character. It's perfectly fine to compare characters. So our while loop is going to go all the way until we see a null terminator. Once we see a null terminator, we're going to jump out. Count is going to be equal to the number of characters in that string. So it's the length of that string. We do it for both strings, and you're going to notice that basically both strings will have the correct length because we're just going through each one. To be or not to be is going to be something like 18 characters. I had to quickly count them. Sorry about that. Now, you're never going to really need to do anything like this because we have a nice helper function with stir length to find lengths of strings. But again, what this is demonstrating is that the fact that it is an array, and if you want to compare or find the length of a string, you can use the not equals and look at the character, the null terminator. I hope this was helpful. This is how we're going to define and initialize string literals. Thank you. Hello and welcome back. In this lecture, I want to talk about constant strings. We know that string literals or a string constant is inside double quotes, but what about the variable itself? How can you make sure that the variable can never change that value? This is referred to as a constant. So a constant string is sometimes necessary in your program where you do not want your values of your variables to ever change. So for example, if we were creating a circumference of some calculation, we would do 3.14159 times diameter. 3.14159 is a constant. It never changes. It represents pi. So it would be really nice if instead of using that magic number, we could use a variable and make sure that that variable never changes. So there are good reasons to use a symbolic constant instead of just typing in the number every time. First off, a name tells you a lot more than a number does. Ode equals 0.015 times house value is much less meaningful than ode equals tax rate times house value. So we want to have variable names that represent numbers that never change. If you read through a long program, the meaning of the second version is a lot plainer. It's a lot easier to look at that code and understand that 0.015 represents the tax rate. Suppose you have used a constant in several places and it becomes necessary to change its value. You would have to go and change that value everywhere in the program, as opposed to just changing it in one spot where you define that constant. I talked about this earlier when I used the term magic numbers. That's what this is referred to. Whenever you see a number used in a program, it's not stored in a variable. It's usually best to create that number and put it in a constant. Because then, if you use it multiple times and that changes, that variable changes, all you have to do is change it once. You don't have to change it everywhere you use it. So avoid magic numbers, use constants. One way you can define a constant in C is you can use the define preprocessor directive. So this preprocessor directive lets you define constants, and I actually used it in a couple programs. I'm now trying to help explain it. So if you wanted to do a tax rate and it was a constant, you could say define with the pound sign before it. We know it's a preprocessor directive because of the pound sign, and then we would say the name and then the value. When your program is compiled, the value 0.015 is going to be substituted everywhere you have used tax rate. Just like a variable, but it's actually not a variable. You cannot assign any other values to that. If it was a variable, you'd be able to assign data to it. But not in this case because it's a preprocessor. So the preprocessor directive says you can't assign data, and you specify that with the define. So notice the syntax for this. You have the pound symbol followed by define keyword, and then after that you have your name. We're not using any assignment operators. We just have our name and then the space and then the value. So to assign a value to that define, all you need is a space. There's no semicolon at the end. It's not a statement. It's very specific. So what's happening here is there are compile time substitution happening for these preprocessors. The preprocessor runs before the compiler, remember, right? The preprocessor is going to run and it's going to see these define keywords, and then everywhere it sees a tax rate, it's just going to put in 0.015 for the compiler. Define statements can appear anywhere in the program. There's no such thing as a local define. Once you have a define, anybody can use it. Now, best practice or convention is usually to put the define statements at the beginning of the program or inside a include file if you want to share it in more than one source file, but you don't have to do that. Because it's running at the preprocessor, it doesn't have any scope. It doesn't have any local or global. You can just put it anywhere, and anywhere in the program you can see it, even if it's being used before it's defined. Define statements are also really good because they help make your programs more portable. Sometimes you can use a define statement and relate it to a particular computer you're running on when the program is running, and it will get that right value. The define statement can also be used for characters and string constants, not just for numbers. So if we wanted to do something like this, perfectly valid. You just enclose the single characters inside a single quote, and if you want to actually put in an entire string, literal, you just put it in double quotes. And that's what this oops is doing. Another way you can create constants in C is a more recent mechanism. C90 added basically another way, which is providing the constant modifier. You can use the constant keyword to convert a declaration for a variable into a declaration for a constant. And this will allow you never to be able to change that variable. So all you do is you say const, and then the name, the data type, and then the name of the variable. And what this does in this example, it's going to now make months a symbolic constant for 12. We're not calling it a variable because a variable can change, right? That's why it's called variable. You have constants or variables. And constant in months is not a variable. It does not change. Constant makes months into a read-only value. You can display months and use it in calculations. You cannot alter the value of months. Right? And so constants are important if you do not want data to change, and also they can replace magic numbers. Const is a newer approach and is more flexible than using define. It lets you declare a type. It's also has better control over which parts of a program can use the constant. So you should be using constant whenever you can, but you'll see a lot of programs using defined because it was the first mechanism. Also, there's a third way you can create a constant, and that's using the enum. Remember we talked about enums. Enums are a way to create your own type of variable and only have certain data associated with it. you can't change the value of enums, right? Once you define an enum, it has to have those values. It can have different values, but it still is sort of a way to create a symbolic constant. Not a complete way, but a sort of a way. Also with const, you can initialize a character array and declare it as a constant. That's a good way of handling standard messages. So if you say const char message equals the end of the world is nigh, that will declare the message as a constant, and it's protected from ever being modified explicitly within your program. Any attempt to try to modify message by doing a stir copy will result in an error message from the compiler. And now you can use this for a standard message that may be displayed as output in various parts of the program. The technique for defining standard messages is particularly useful if they are used in many places, like I mentioned. Prevents accidental modification of such constants in other parts of the program, just like magic numbers. So constants, you want to use them in your program. Two ways to employ them, essentially, using the define and using the constant keyword. Please pay attention to this. You might see it in some upcoming examples. Thank you. Hello and welcome back. Here we have another challenge. So I hope you guys are getting familiar with strings, character arrays. Very important concept with C. This idea of storing these string literals in variables, character arrays. Understand that it's an array and how you can access different elements. This challenge is going to be focused on that. We're going to have another challenge that helps you understand how to use some of the string functions, because we cover a lot of those. But this one really is for you guys to get familiar with this concept of a character string and a character array. So the requirements for this assignment are you're going to write a program that tests your understanding of character arrays. So what I want you to do is I want you to write a number of functions. I want you to first write a function that counts the number of characters in a string. It will be similar to the stir length, but you're going to actually implement it yourself without using that function. So you cannot use the stir ling library function. The function should take a character array as a parameter and should return an int. Okay, so you can just have a character array as the parameter. You don't have to worry about pointers at all in this assignment. This is just going to take maybe a parameter constant because it's not going to change. And all you're going to do is you're going to need to iterate through the array. So even though you have a string, you still can access individual characters because it's an array. So if you can access the individual characters, you can just keep a count and then display it. This function should return an integer, which is the length. The next function I want you to write is I want you to implement the concatenate function, where you can concatenate two strings. Again, I don't want you to use only library functions. Don't use stircat. This function should take three parameters, the result, and then the two characters that you want to concatenate, the two strings that you want to concatenate. So those can be constants because you're not going to change those. The result is just going to be the character string that you store in. Right? So pretty simple. Again, you don't have to deal with pointers. You're going to have to go have a couple loops, go through each one of the arrays and assign to the result array. And what you should return for this function is nothing. You don't have to return anything because you're passing in the result array. We could modify this and return a pointer and stuff like that, but we're not going to do that for this assignment. So this is going to manually concatenate two strings. Third function I want you to write is to compare two strings to see if they're equal. Again, I don't want you to use the library function. I want you to understand how these character arrays work. This function should take two constant character arrays as parameters, and it should return a Boolean, either true or false. True if they're equal, false otherwise. So what are you going to have to do? You're going to have to iterate through the arrays and compare each character. Right? And you should probably look for the null terminator for the equal strings, because the null terminator is going to determine when you want to stop. Because you don't have the sizes of these arrays, so you're going to have to look for null terminator to determine when the second string. And you should actually compare the second string to the first. Right? So you have to figure out how to do this, but here's three functions to get you familiar with creating a character array and manipulating it or accessing it to determine its length, concatenating it, and checking if it's equal. Good luck. I'll provide a solution in the next lecture. Thank you. Hello and welcome back. I would like to provide a demonstration, a solution to our previous challenge which had to do with understanding character arrays. Mainly we're going to write functions to get the length of a string, a function to concatenate a string, and a function to check if two strings are equal. So I'm going to create a project. I'm just going to name it understanding character strings. And the first thing we'll do is we'll implement this length function. We're going to create 3 function declarations at the top. We're going to name the first one string length. We're going to use camel case for our naming. This is just going to take a constant character string. Right, so how do we know it's a string? Because it's a character array. And then we're going to put a semicolon. That'll be the first one we create, so we'll just stop there for now. And we're going to create this function, define it down below. So you should understand that nice keyword const. Right? Const means that it's a character string that cannot change, can't be modified. The reason we're using const here is because we don't want to modify the string inside the function. We just want to basically parse it and then return the length, return an integer. This function is actually pretty easy to implement because we're just going through an array. So we can actually say int count equals 0. This is a local variable. It can only be used inside this function. Now you may ask yourself, why can't we use the size of operator? Because the size of operator is just going to tell us the size of the string. It's not going to tell us how many characters are inside that string. But all we need to do is create a loop and go through the array until we hit the null terminator. So we can look at our string and we can say, while the string count is not equal to the null terminator. The null terminator is represented inside a single character as \0. Right, and we can use the not equals operator because we're comparing against characters. And we only have one thing in the body of this while statement, plus count, just incrementing count. And then when we want to return it, we just say return count. And that's it. That's the entire string length function. It's pretty easy because the character string is inside of an array. And the string ends with a null terminator. So to test this, we can go inside our main method and we can create some constant chars. We'll just say word1 JSON. Right, so this is how you create a character array in C. You don't have to have the constant there, but this isn't being modified. Use the char keyword, char data type, the identifier, and then the brackets. It's better to not specify the size inside the brackets because the C compiler will automatically add a null terminator. And then you just, after the assignment operator, you put in your string literal inside the double quotes. We'll create a couple here to just make sure it's working. And word 3 will just be whatever. And we can display character strings very easily because we can just use the %s symbol, right? Except what we really want to display here are the lengths. So we're going to use %d. So we're going to just print out the lengths of these 3 strings, %d, and we'll just have some spaces in between, and then add a line feed. And this is just going to call the string length function for each word. Pretty simple here. And that is it. So now we can build and test and see if this actually works. What we should see as output is we should see the length of JSON, which is 5, the length of OK, which is 2, and the length of whatever, which looks to be about 8. We build this. We want to make sure we have correct spelling, because it won't build if you misspell. And again, I do not know how to spell. Typing too quick for my own good. All right, let's run this. So here we have 5, 2, and 8, which looks right. So that's how you can write a string length. Let's move on to the concatenation function. The concatenation function is just going to take 3 strings, 2 constants. And this is not going to return anything. It's just going to add to the, put the resulting string in the first parameter. So we're going to call it concat. We're going to have a result. And we're going to have 2 strings, one that we want to concatenate to, and then one that we want to just have a single string. So we'll name them string 1 and string 2. And there we go. And that's our function declaration, so we can use it anywhere before it's defined. Make sure I put a semicolon after it. Yep. This one is going to have to go through the array as well. It's just going to have to go through 2 arrays. And as we go through each, add to the resulting string. We're going to create a couple local variables which we can only use inside this function. Int I and j. And then we're going to use a for loop to go through the array. We're going to say for I equals 0, str sub 1, or sub I I should say, is not equal to the null terminator. And then also increment I. All right, we're familiar with our nice for loop syntax where we have the loop identifier as the first thing before the first semicolon, the condition where we jump out before the second semicolon, and then modifying the loop control variable to make sure we don't have an infinite loop. All we do here is we say result sub I equals stir1 sub I. Remember, these are characters, so it's perfectly fine to use the equals in assignment here. We can't do this in character arrays because character arrays, you can't assign an array to an array. We would have to use a stir copy. So that's copying the first string, and now we want to concatenate the second string to result. So we would do something very, very similar, except we're going to look in the second array, and we're going to make sure we put it in the right spot in result. So we would do something like this. We would go from j to 0, stir2 j is not equal to the null terminator, plus plus j. And you'll see result is just saying I plus j. So whatever I ended with, if I added 10 characters, it will now start at that 10th character because it's 0 based, and it will just add j to it. So 10 plus 0, 10 plus 1, and so forth. And that's it. And then, well, that's one last thing you got to do that's really important is you have to add that null terminator. So we want to say result I plus j, and then add in a single character, the null terminator, which is \0 inside a single quote. And that is our function. We don't have to return anything from this function because we're just copying in stir1 to stir, and I got to make sure I type correctly, stir1 to stir2. So let's test this. What I would expect to be able to do on this one is test it with a couple characters. So here let's create a couple. We'll use the existing characters that we have, and we're just going to concatenate a couple. So we need to create another result one. So we'll just say result, just declare it. And in here we're going to say, we will have to specify a size though for that first one. And so we're going to just specify a size of 50. We're going to limit it. So these constant characters should work. Now we're just going to say printf. We're going to print out a string. So we're going to say %s, and then we're going to say concat, which is what we named it. We're going to pass in the result, and then word 1 and word 2. So what this should display as output, and we'll make sure we put it on a couple new lines. This should display as output JSON OK. And we want to make sure that so concat doesn't actually return any data, so I can't put it directly in the printf. What I have to do is call it and then display result. Simple mistake. So there we call concat, everything gets put in the result, and we display the result. So again, when we run this, we should see JSON OK, and we do. Third function that we want to implement is a comparison function to check if two strings are equal. This function should return a Boolean. So we want to include our standard bool. I think that's the name of it, hopefully. So we can use Boolean and true and false values. And this will actually be defined as equal strings. This is going to take a constant character array, S1, and a constant, another one, to check if two strings are equal. And just to make sure I included the right header, I'm going to try to build that. And I think I did. So now I'm able to use the bool keyword because I included this. And I can also use true or false. So let's implement this equal strings. This is going to be much of the same, really, just going through the array and checking each character. So we're going to create a couple local variables, I equals 0 for our loop, initialize at 0, and a Boolean that just tells us if they're equal, because this is what we're going to return. Something like is equals. And we could actually initialize this to false. And our while loop is just going to go ahead and compare. What we want to do first, actually, is we want to get the count. We want to see how big both of these are. So we can have a while loop because we need the count in order to look at the size. Basically to just check for that null termination. So we're going to assume that the strings we pass in are the same size. So we can write a simple while loop. You could write if statements as well. I kind of incorporated everything into a while loop, or my comparisons, by using the logical operators. You don't have to use the logical operators. You could use an if statement and just go through the entirety of a second string. But here what I did is I said while s1 sub I is equal to s2 sub I, and they're not equal to null terminators. Because if they're equal to null terminators, we want to jump out if either one's a null terminator. So now we say plus plus I, and then the last thing we have to do is just check if those are null terminators. And if they are, you can set your Boolean variable to return the right data. So here we can say if s1 sub I is equal to a null terminator and s2 sub I is equal to a null terminator, set our Boolean variable is equals, and then we want to return that. And then just say return is equals. And to test this, we'll have to test a good string and a bad string. So let's go ahead and say equal strings. I'm going to print out just the integer value of the Boolean, so %d, and we're going to say equal strings. Here this returns something, so we can put this in the print expression. Equals string, I just want to make sure I equal strings. Thought I had that wrong. Equal strings, and then we'll pass in JSON, comma, JSON. And we'll call it again. Make sure we add a line feed. And this time we'll say JSONs. And the first one should return 1, second to return 0. 1 represents true, 0 represents false. When we run this, we see 1 and 0. 1 for true and 0 for false, except it's tough to read because we don't have a line feed, so let's add a line feed. And just to show you again, now we see 1, 0. True, false. JSON, JSON is equal to each other. JSON is not equal. So these are some quick functions that you can learn from. Learn basically about the character arrays and how strings are represented with this concept. Thank you. I'm also going to provide the source file so you can look at it in more detail. Hopefully this helped with your assignment. Hello and welcome back. In this lecture I want to start talking about string functions. I mentioned earlier that strings, character arrays, are not a variable type, a data type in C. So you can't use any of the operators, but you're still going to need to be able to do a lot of things on strings. You're going to be able to manipulate them. You're going to want to get the length. You want to compare them, all sorts of things, probably convert them. So luckily, the standard library comes with a bunch of functions that you can use to perform these type of operations. I'm going to first start talking about some of the most common ones, and then we'll move into some more specific ones in other lectures. So we already know that a character string is a char array terminated by a null character. Character strings are commonly used in C programs. C luckily provides many functions specifically designed to work with strings. The ones that we're going to discuss are the most common ones that you'll use. First, getting the length of a string using the stir length function. Copying one character string to another. Remember I told you earlier that you can't use the assignment operator to assign a string. So what you do is you use stir copy or stern copy. Also combining two character strings together, concatenation. There's a stir cat and a stern cat. And determining if two character strings are equal. Again, the equals equals operator is not going to work for comparing strings because they are arrays. So if you want to compare strings, you have to use special functions provided by the C library, stir compare and stern compare. First, let's talk about the length. All of these functions are defined in the string.h header file, so you have to include that when you call or invoke one of these functions. Getting the length of a string. Stir length is a function that finds the length of the string. It's pretty straightforward. It's returned as a size t variable. You can pretty much use the size t variable interchangeably with an int. But first you'll have to include that string header file if you want to use stir length. And this is how you use it. You basically create a string literal inside double quotes and you assign it to a character array. You don't specify the size of the character array. The compiler will do that for you and it will add the null terminator. Once you have my string defined and with a string constant, you can then call stir length and just pass in that character. Pretty nice. It's one of the most often used ones because you often want to get this length of a string when you do validation checks or anything, really. If you want to make sure there's no buffer overflows, you can do that as well. This function does change the string, so the function header does not use constant in declaring the formal parameter string. If you were to go and look at string.h inside user include in your directory, you would see that it's not defined as a constant. Copying strings. Copying strings are either modifying an existing string, modifying an existing character array that has some data in it, or if it doesn't have anything in it, you want to put something in there. Since you cannot assign arrays in C, you cannot assign strings either. I mentioned this earlier. Declaring a character array and then using the equals assignment operator does not work. So what you have to do is you have to use the stir copy function to copy a string to an existing string. It's the equivalent of an operator for strings, assignment operator. If we declare two character arrays, source and destination, all we need to do is say stir copy, source, and then whatever the source is there, we can put in the string, and the same with the destination. You can also put variables in there as well if you wanted to copy those. But what we're doing here is the first parameter is where you're copying to. The second parameter is the string that you're copying. So source would have this is source inside of it after stir copy. Destination or dest would have this is destination inside of it after the stir copy call. The stir copy function does not check to see whether the source string actually fits in the target string. So what would happen if you had a big string? So in this previous example, what would happen if destination had 100 characters in it, and instead of having this is destination, it had 100 characters. This is destination, destination. And you tried copying it into source that only had 50 characters. There would be a problem. The destination string would be larger than the source string that you're copying. Right? So if we tried to copy stir copy into source, instead of copying this is source, we put in this is source 5 times or 10 times or whatever it is, and it went over 50, there would be an error. And I'll demonstrate that. So a safer way to do copying strings is to use stern copy. You'll notice that N in between the stern copy. Stern copy takes a third argument, the maximum number of characters to copy. So here you actually specify how much you want to copy. So if you have a source of 40 and a destination of 12 sizes, you can first do an mset, which is just setting the size of the data inside a destination to null terminators. That way when you add something, it will automatically be there. Don't worry about that. The stir copy is going to copy hello, how are you doing to source. And it's not going to check if hello, how are you doing is larger than source. But if you do a stern copy and you copy in a destination, it's going to copy source and it's only going to copy the first 10 characters. So that third argument should correspond to the size of the destination. Dest. So let's go into code blocks and look at stir length and look at copying strings to see exactly how these work. So here we have our main. And to get the string length string is really easy. We're going to create our character array. We know how to create a character array. We don't want to specify the size, but we got to put the name first and then the brackets. And then we can initialize it with whatever we want. Say inside double quotes. Double quotes represent string literals. So I can just say, my name is Jason. The end result of this is S is going to be an array of size 1, 2, 3, 4, 5, 6, 17 characters. All of these characters plus the null terminator. The null terminator is the \0. You don't have to put that in there because it automatically gets added by the compiler. That's how we can initialize and create a string in a character array. Then to print it, all we have to do is say printf and say the length is. And then we put the %s as the format specifier to display a string. And then all we do is we say the name of the string. And to not get confused, let's just say my string. And we don't have to use the ampersand like we did previous examples. We can just say my string. If we compile and run this, we also may have to make sure we include the string header. When we compile and run this, you're going to see the length of the string. So the length is, and I didn't call the string length function, so you have to actually call the function if you want to display it, the length. So you just do something like that. You put the string inside stir length. And now when you run it, you'd actually see the length of the string. Got to make sure, okay. And I forgot a parentheses. And this is now complaining about, this has to not be a string, but an actual. So that's how I would display the string. If I want to display the length of the string, I do %d in the call the function. Now when I run it, you'll notice that it actually prints out 16, which is the length. So it's a pretty easy function to use stir length. If you want to copy strings, you use stir compare. And you want to use stir and compare to actually specify the bytes. Right. So here if we have my name is Jason, and then we create another string, actually we'll just keep it that we won't even have to specify. And what we're going to do is we're going to say create another string called temp, and that's going to be equal to stir and compare. We're going to pass in what we want to copy to. So actually let's do this. Just create an empty character array, and we're going to just make it of size 50. And what we're going to do here is we're going to say stir and compare. Stir and copy, CPY. The first parameter is where we want to copy to. We're going to say temp. The second parameter is what we want to copy, which is my string. And then we don't want to pass in more than 50 bytes. So we can actually say size of temp to say we don't want to pass in more than 50 bytes. And you probably want to do -1 for the null terminator. And this way, that third parameter is really important because we're never going to have buffer overflows. You should always use stir and compare and not stir, or stir and copy and not stir copy. And then here we can just display our string to see if it was copied. We can say temp, change it to a %s. And when we build this, we should see
not the length, we should see the string is, something like that, and end it with a semicolon. There we go. Now we should compile, we do. So now we run it, we should just see our string that was copied in. Oops. And so we see my name is Jason, and that is stored inside of temp because we printed out temp. But always use str copy, don't use stir copy. That will make sure that you don't have buffer overflows. And the third parameter should always be the source, right? Not the, I'm sorry, the destination. Not the source, the destination. It would be pointless to say copy this entire string because if this is smaller, you're going to have problems. So always say the size of this. And you see that you can use the size of operator to see how many bytes are inside of character. All right? Let's talk about some more functions. So we know how to get the length, we know how to copy strings. How about concatenating strings? The stircat function takes two strings as arguments, and it copies the second string at the end of the first. The second string is not altered, only the first. It will return the value of its first argument, the address of the first character of the string to which the second string is appended. So it returns something telling you where you actually appended it if you ever needed to use that. So here's an example. We create a character string of my string, and it just contains my string with a null terminator. We create a character string of input, which is 80, it's empty. We say enter a string to be concatenated. We read it in, and then we concatenate it. We print out the original string followed by the concatenated string, and then the input. So if after this, whatever you entered would be put at the end of my string. So if you entered Jason, it would be my space string Jason. That's what my string would be equal to. Because you do a stir cat on it. Right, so the one thing we didn't do here was, here it is right here. First we print out the string and then we call stir cat on it. Input is actually going to be equal to whatever was input, my string followed by whatever was input. We'll go through this example in a sec. Now just like stir copy, stir cat also has a stir and end cat. So the combined version becomes the new first string. Oh, my slides keep getting messed up. I double check them and they still have, I got to become better at PowerPoint. Anyways, so just like string concatenation with the stir cat, there's a stern cat. Stir cat has the same problem as stir copy. It can have a buffer overflow. It doesn't actually make sure that the second string will fit in the first array. So if you don't have enough space in that first array, you can run into buffer overflow problems. So what you want to use is stern cat. The second argument indicates the maximum number of characters to add. So for example, if you do a stern cat and two strings, bugs and add-on, it's only going to add the first 13 characters of add-on to bugs. Depends which comes first. If add-on is less than 13, then it will only add till you see the null terminator. So in this example, we're creating two strings. This is the source, this is the destination. We're doing a stern cat. We're only copying 15 characters into destination at the end. So if whatever the size of destination will be size of destination plus 15. And then we print it out. So let's look at this in code blocks again. So here we are. Here's our example. And we're going to create two character strings array, one size 50, the other size 50. We're going to do two stir copies to set them to data. This is the source, this is the destination. And then on line 12, we do the stern cat. And destination is going to be what we concatenate to. So the source is going to be what we're going to concatenate. And we're only going to assign 15 characters. So if source was bigger than 15, we wouldn't copy all of them. So when we build this and run it, you're just going to see that it now says this is source followed by this is it's going to say this is destination followed by this is source. So it says this is destination, this is source. It concatenated that onto the end of destination. So you always want to use stern cat for concatenation, so you don't have buffer overflows. Let's talk about stir compare, which I keep accidentally saying instead of stir copy. Stir compare. So for comparing strings, we have to also use a function. If you want to compare one string to another, you can't use double equals. That only checks for references, whether or not you have the same address. So what you need to use is stir compare. This is going to compare the string contents. It does not compare the arrays, so it can be used to compare strings stored in arrays of different sizes. It does not compare characters. You can use arguments such as apples and a in double quotes, but you cannot use character arguments such as a single character, a. This function does for strings what relational operators do for numbers. Right? So the compare function is going to return a value that tells you whether or not the string is equal, whether it's larger, or whether it's less than. If it's equal, it's going to return 0. If it's less than, it's going to return less than 0. If stir1 is less than stir2. And if stir2 is less than stir1, it's going to return greater than 0. And so what exactly does this mean? Well, let me provide you with an example of how this works. Let's put this into code blocks and run it. But here we're doing a bunch of stir compares, and we're going to tell you what the values are, whether they're less than or greater than, because it's not very clear. So let's take this and look at it in code blocks. Okay, so here's our example. And we're comparing a bunch of strings and then just displaying the results of stir compare, whether it's a 0, 1, or whatever. So if you compare two strings, A and A, they have to be in double quotes. And what you see here, what we're doing is we're printing out what we're calling. So we're delimiting the quotes. We're putting the backslash so that we actually print out a quote character, and it doesn't end the string. But if we compare A and A, this should return 0, because 0 means strings are equal. If we compare A and B, stir compare should return less than, because A is less than B. BA, it should return a greater than 0. But let's go through this to make sure I don't make any mistakes, and we'll actually see it in the output. So when we run this, and this helps you remember what numbers are going to be returned. So when you compare A and A, you actually get 0. If you compare A and B, B is less than A, so it's a negative 1. Something less than 0. I might have said the opposite. See, even I still get them confused. Because A is greater than B. A is greater than B, negative 1. B is less than A, so you get something greater than 0, which is a 1. C is greater than A, so you get 1. Right? Just like when B was greater than A. And then you're comparing uppercase and lowercase. When you compare uppercase and lowercase, it does the inverse. Z is actually less than lowercase a. So capital is always less than lowercase. If you try to compare apples and apple, it's going to be 1 because apple is less than apples. And that's how the comparisons works. It's important to understand the 0, greater than 1, or less than 1. Again, less than 0 is going to say that the first string is less than the second string. And greater than 0 is going to say the first string is greater than the second string. This function is very easy to use. You don't have to worry about any kind of strn compare because it doesn't matter the size of the arrays that you're comparing. The stir compare function compares strings until it finds corresponding characters that differ. So it could be all the way to the end of one of the strings. Stir and compare function compares the strings until they differ or until it has compared a number of characters specified by the third argument. So in this case, you don't need to use stir and compare for buffer overflows. It exists, but you only would use it if you only want to compare a certain number of characters. It's used differently than the stir copy or the stern copy or the stern cat. The stir and compare just says I only want to display so many characters. So it would be useful if you're only looking for a prefix. So if you wanted to search for strings that begin with astro, you could limit the search to the first 5 characters. And you would use stir and compare this way. So this example would actually, and you see that we say equals equals 0. You often see an if statement like this when you're using stir compare. You see stir compare inside of an if statement and the equals equals 0 to say that it's equal. So if stir and compare uses the first 5 characters, compares astro to the first 5 characters of astronomy, it's going to say that it found it. It's going to be equal to 0 and it's going to say found astronomy. If you do the same thing but comparing it to a different string called astounding, it's not going to find it. It's going to actually going to display. It's going to say that astounding is greater than estro, so it's going to display something greater than 0, which is a 1, and it's not going to display any data. So use stir compare when you're comparing strings for all the contents. Use stern compare when you only want to compare a prefix to a string. Same type of syntax for stern compare, just that third argument. Okay, so we talked a lot about some really important functions that we're going to use, mainly stir length, stern copy, stern cat, and stern compare. We're going to have a challenge where you have to utilize these functions. It will get you familiar with it, but you're going to become really familiar with this because you're going to end up using them over and over and over again. Thank you.
Hello and welcome. I'd like to go through another challenge for you. Mainly has to do with string functions, getting you familiar with stir length and stir compare, which are two of the most common functions available. Also, I think string copy you're going to use for these. So I want you to write a challenge that's going to reverse the string, and also a challenge for using stir compare. So write a program that displays a string in reverse order. You should read input from the keyboard, and you need to use the stir length string function because you need to find the size of the string. Once you have the size of the string, you can then start reversing characters. I'd also like you to write a program that sorts the strings of an array using a bubble sort. You'll need to use stir compare and stir copy functions to get this to work. If you don't know what a bubble sort is, you're going to have to look it up or do some research. It's a really easy sorting algorithm for anything, integers, strings, whatever. In this case, strings. Here's what it will look like, the program, if you run it. You'll ask the user to input a number of strings. They'll say 3. They can input the string 3 times. So they say 0, 1, or 2. So you could have a loop here with scanf. The expected output would be 1, 2, 3. 1, 2, 0, sorry. OTZ. And that's all the information I'm going to give you. Pretty basic. You're going to need to understand the arguments and parameters that go to the stir compare, the stir copy, and the stir length, and what they return. And you don't really have to understand much about pointers for this. Really just the basics. These are two pretty straight assignments. I mean, one assignment with really, you could even have multiple functions or create multiple programs. It's up to you. Good luck, and I'll provide a solution for this in the next lecture. Thank you. Hello and welcome. In this lecture, I'm going to provide a demonstration of a solution for our previous challenge. I'm going to go through how we can reverse the characters in a string using the stir length function, and also go through sorting strings using stir compare and also stir copy, as well as using the bubble sort algorithm. Let's bring up code blocks, and I'm going to just create a single program, I think, for this. I mentioned in the challenge that you create 2 programs, but for simplicity and demonstration wise, I'm just going to create a single one. Create a project, and I'm just going to name it string functions or some variation of that. Let's see. Let's call it common string functions. Example. So let's start with the reverse. The reverse can go in its own function, or we can just put it in the main. I'm just going to put it in the main. So first thing I want to do is I want to create first thing I want to do actually is I want to include the correct header file so that I can use these string functions, which is my include string.h. This is where it contains all the nice string functions. Now I'm going to create a character array. I'm going to make it a size 100. It's just arbitrary. Won't be able to store things greater than 100. I'm going to create a couple local variables that will help me with my parsing. And what I want to do is I want to display some output first to the user. So I'm just going to say a couple line feeds. Print individual individual characters of string in reverse order. That'll tell the user what's going on. And then also print out, just to make it more apparent, just print out something like that so it's easier to read. I'm going to say input the string. I'm going to read in the string. And then I'm going to store the string. So I'm going to say scanf %s, and I'm going to say stir. And I don't have to pass the ampersand to read it in. Then I'm going to get the string length, and I'm going to put that in my L local variable. So I can call stir length by just saying stir length, passing in the string, and it returns how many characters in that string. Very, very easy. And then I'm going to print out something to tell them that the characters in reverse order. So the characters of the string in reverse are \n. And then I'm going to write a nice little for loop that goes through my array and according to the length and just reverses them. So I'm going to say for I equals L, remember I, so I'm going to be going backwards in the actual string array. I'm going to start off at the end and go forward. I'm going to say I is greater than or equal to 0 and I minus minus. And you notice I don't have to look at any null termination characters when I do it this way. Then I'm just going to print out each character as I encounter it. To print out a character in C, you just do the %C. And just do that and say stir sub I. And that is basically it. And then I'll just print out a new line. And actually I'll print out a bunch of things just to end it. And a bunch of dashes. Let's see if that works. Very easy, this one actually. As it should be. To get the length should not be difficult. And I forgot a line feed, so let's fix that. Okay, so here it says print individual characters of string in reverse order, enter the string. Now scanf, it's only going to read in, so if I enter JSON space fedden, scanf is only going to read up to JSON in the space. You'd want to use another function like fgetS if you wanted to read the entire thing. So what this is going to do, it's just going to reverse JSON, print out NOSAJ, which it does. The characters of the string in reverse are NOSAJ. That's pretty simple. Not a very complicated function or implementation. Now let's try it with sorting a string. And so now I'm going to do something, and I'm going to do it in the main, I guess, just for now. Probably should be putting these in actual functions, but we're not demonstrating functions in this lecture. We're demonstrating strings. So let's create a couple more local variables that we're going to need. Mainly, we're going to create a name. And in this case, we're going to create, I don't know if I should do it this way. I was going to create an array of strings. Yeah, we'll create an array of strings and we'll use fgetS. I'm going to create an array of strings. So this looks like a two-dimensional array. So what we're doing here is we're creating 25 strings of size 50. And then I'm also going to create another one of just 25. This will contain each string. And then I'm going to add two more variables. I'm going to add an N and a J. And so after we do our reverse, I'm going to print out another message to say what we're doing. Sorts the strings of an array using bubble sort. I'm not going to explain bubble sort to you because again that's just an algorithm that it's not relevant to what we're doing really. It's just a way to sort. It's one of the easiest sorts actually because you just swap essentially.
But what we want to do is we first want to get how many strings they're going to enter. So we're going to say printf input number of strings. And then we're going to say scanf. Scanf can be used here because it's just a number. We're going to say %d, and we're going to store that in our local variable n. Again, I know I'm not using great names here, but I'm demonstrating something. Since it's an int, we have to pass in the ampersand. Then I'm going to ask them to enter the strings. So here I'm going to say input string 1, 2, or 3, followed by line feet. This will just be what number they have to enter. String 1, string 2, or string 3. Then I'll actually have a loop that goes through and gets the input. So here I'll say for I equals 0, I is less than equal to n for how many strings they want to enter, in I++ or plus I. Here I'm going to actually read the string, and I'm going to use a different way to read strings because I want to ignore, well, actually I shouldn't need to. Yeah, it's okay. I'll just use scanf again. I was thinking of using fgetS so that you could enter in a string that had spaces, but I don't think we need to do it. We do scanf, and we're going to read into scanf into our names array. Remember, we have name, and this is a string of strings, essentially, of each 50 characters, or 25 characters. 25 rows, 50 columns. So 50 characters, 25 words. No, the opposite. Sorry. The 50 characters, 25 words. So the max number of words you could enter is 25. So we're going to store this in our name array. So we're just going to say scanf. We're going to read in a string, and we're going to put it in name sub I. Okay. And so we stored our arrays. We can only store up to 25. Now we're done with our loop, and now we can just write our bubble sort. And so our bubble sort, I'm not going to explain to you. I'm just going to tell you that it's a pretty simple algorithm that has an inner loop. So you have a for loop that goes through I is equal to 1 through all the strings. And then in your inner loop, you go from 0 to all the strings minus 1. And you compare that first string to all the other strings. And you essentially bubble them down. But what's important here is the stir compare function. Let me just try to get this indentation correctly. And the stir copy functions. This is really what's important. You'll notice I don't have any ending brackets for either for because they have single statements. Even though this if has something in its if body, this is only one statement. So we're comparing each word to every other word, essentially, after we've compared one previously. So then we say if stir compare name sub j is and name sub j sub 1. So stir compare takes two arguments, two character arrays, character pointers really. And if they're equal, it's going to return 0. If the first parameter is less than the second parameter, it's going to return less than 0. And if the first parameter is greater than the second parameter, it's going to return greater than 0, 1. So what this is saying is if the first string is greater than the second string, then we want to swap everything. And that's why we have that temp. Temp is actually storing a temporary string. So we put in the temp name sub j, and then we swap name sub j with name sub j plus 1. That's how the bubble sort works. Again, what's important here is stir compare and stir copy. All right, and if you're being safe, you'd want to use stir and compare. And when you do stir and compare, well, actually stir and compare you don't care about because that's only if you want to compare a prefix. For stir copy, you actually want to use stir and copy. And that third parameter is what's important. So stir and copy, you only want to make sure you don't copy in more than the size of temp, minus 1. Because otherwise you have a buffer overflow. So you would add all of these. You could also use, if it wasn't a character buffer, you'd probably want to use stir length if it was a pointer. But size of will work fine for this. And again, this will eliminate any buffer overruns. So it's always safer to use stir and copy. Right, and -1 because we have our null terminator that needs to go at the end. So here, it's just source destination for stir and copy. We're copying name sub j into temp. And the same with name sub j plus 1 and name sub j. And then lastly, temp into name sub j plus 1. And I'm actually have to update these variables because they're wrong, because they always have to be the source. So name here would be name sub j. And then the last one would be name sub j plus 1. J plus 1. So that's stir and copy and stir compare. Very easy to use functions. After we've sorted them, we just want to print them out. So we want to say the strings appears. The strings appear after sorting. Put it in line feed. And then go through a loop to print out all the strings in our array. So we say for I equals 0. I is less than or equal to n, because the n represents how many strings we sorted and entered in. Then we just want to go through our string of string arrays. So we want to say printf %s line feed and name sub I. So name sub I is actually our sorted array. That's why, so we had names, name sub I, even though we don't have the second one, because that represents the size of each character. 25 characters max of, 25 words of 50 max. So let's see if this works. Build it. Got a couple messages because I don't know how to spell. And if we run this, we're first going to run our reverse function so you can see that again, because we included it in the same program. So let's just say JSON, or well, let's do something different since that's what we did before. Let's say fedin NIDEF, that's good. Input the number of strings we want to sort, let's say 5. Let's say ZZZZ, just so it's clear, F. Something like that. And actually, what I do 5, 1, 2, 3, 4, it did 6. So I messed up a little there. But it looks like it sorted it A, B, D, F, R, Z. So it works. I do have one bug though, because input string %d, I input the number of strings in n, and then I say less than equal. I should just say less than. So let's run it again just to demonstrate it. But I have to build it. Don't forget to build after you've changed things. Again, we'll just say anything here. And then number of strings, let's just do 4. And well, let's do something. So then they alphabetize them and say D, E, L, Z. So it looks good. So you can definitely improve on this code where you could want to put everything in functions and make it more modular. But what I'm trying to get through with this assignment is how you use stir compare, how you use stir and copy, and how you can use stir length. You should also play around with the stir cat, the stern cat, and the that's the other real common function. You may want to play around with stir stir and stir char for searching. Those are really, really good. Or the is up or is lower for checking characters. Or the A2I and A2F conversion functions. Thank you. I hope this was helpful.
Hello and welcome back. Another exciting lecture. In this lecture, we're going to talk more about strings and string functions. mainly the ability to search, tokenize, and analyze strings. So let's discuss some more string functions. Hooray! Searching a string. All these functions are going to be in the string header. There's some string searching functions that are particular use, where you can find a specific character or a substring. The name of those functions are stir, chr, and stir stir, finding a single character or substring inside of a string. We'll provide some examples of that. There's also some capabilities for tokenizing a string. You may say, what is tokenizing a string? First, you have to define what a token is. A token is a sequence of characters within a string that's bounded by a delimiter. A delimiter is something that is in the string that you notice that has special meaning. So a token would be, if you had a complete string, this is JSON, and it was separated by spaces, one token could be this, another could be is, another could be JSON. It's a way of taking an entire string and breaking it apart in certain boundaries based on a delimiter. And you want to make sure that your delimiter is not something that is valid in the actual string. So you also use delimiters when you read from files. Same type of concept. Where you break a sentence into words, that's called tokenizing. We're going to use a function called stirTok. I also want to talk about some analyzing strings. There's a ton of these, many different ones to check whether or not characters are lowercase characters or uppercase characters, or alphanumeric or digits. These are mainly done on characters, but characters inside strings, and you can also apply them to entire strings. Now, we're getting into some more details about strings, and in order to understand some of these functions, we have to talk a little bit about pointers. Pointers are a huge concept in C. We're going to have an entire section devoted to pointers, probably the next one or the one after. And it's a lot of discussion. It's probably the most confusing topic of the language. I don't want to go over that in detail right now because it's not relevant. I only want to touch on it, just give you a little sneak peek about what a pointer is so that you can understand some of these functions that we're going to use. That's the only purpose of this. So if you don't fully understand pointers at this point, after this couple slides, do not worry. So the concept of a pointer, again, we're going to discuss in detail later, but in order to understand some of these string functions, I want to give you a quick peek. C provides a remarkable, useful type of variable. It's called a pointer. I've been talking about it. It has to do with memory and memory allocation. Some languages, if you've programmed before and you're not entirely new to programming, some languages will automatically manage memory for you. They'll allocate memory for you and delete it. A language like Java does this. It's called the garbage collector. A language like C does not do this. So whenever you create memory for using pointers, you have to delete that memory. But what a pointer is, it's very useful, and what it is, it's a variable that stores an address. An address, remember, is something in memory. It's usually hexadecimal. So it's the value in the address is in another location in memory. The pointer just points to an address. That address contains a value. And we've actually used addresses in the past with the scanf function. Remember that ampersand symbol that we've used? That's the address of operator. Scanf function, as its second parameter, would have to take in a variable that you wanted to store the data. That variable, it has to be a pointer. And so the scanf function expected a pointer. If you declare an integer by itself, it's not a pointer. But if you get the address of it, it now becomes a pointer. So we're using the ampersand to get the address of a primitive data type. So you're a little familiar with the address concept. Remember from now with pointers, you create a number, int number, and that's not a pointer, and it's equal to 25. But if you get the ampersand of it, which is the address of it, you can then assign it to a pointer. A pointer has special syntax in C. The asterisk represents a pointer. So we declared a variable number with the value 25, and then we declared a pointer using the asterisk named pNumber, which contains the address of number. And again, the asterisk is used to declare the pointer. That's how you know it's a pointer, data type. To get the value of the variable pNumber, because pNumber is what? It's a pointer. It's pointing to an address in memory. If you just try to look at the value of pNumber, it's going to give you the address. If you want to get the value of what the address is pointing to, you have to dereference it. So there's special syntax that C uses. It's called the asterisk in the name of the variable that's how you can actually access the memory location that contains the value. So if you want to assign data to that memory location, you have to say star P number. Again, the effect is it accesses the data stored at the address specified by the pointer. So it becomes very confusing when we talk about pointers because you're not used to this concept. You think a variable has a value, that's it. But a variable can have an address, and the address can then have a value. This slide tries to illustrate what I just mentioned. I found this in a book that I've read. It's a slide that shows you the concept of a pointer in memory and how things work with addresses. So I'm kind of reiterating what I just mentioned, but the value of ampersand number is the address where number is located. So if you have two variables, number and p number is a pointer, number is an int, you also, by the way, have to specify the type of the pointer. Even though pointer is an address, you still specify the type of where the address is pointing to. So int star p number is going to be equal to the address of number. Number is in memory, and it points to an address of 1000, for example, and it has a value of 25. P number has a address of 105 for that actual P number, but the value of that address is 1000 address. In order to get the value of P number, you would have to dereference the 1000, which will give you 25. All right, and the reason I mention all of this thing about pointers is because a lot of the string functions are going to return pointers. It's not going to really matter that much. It's only important when you want to understand how you're getting a certain character inside of an array. But I did want to briefly mention them. It's okay if the concept doesn't sink in right now because we're going to cover it in a ton of detail in a later section. But understand that these string functions now that we're going to use are going to return pointers. And then you're going to maybe use that return to do something useful. In the past, when we used the stir copies and the stir compares, we passed in pointers, but it never returned pointers. We never had to use that pointer. Now that we have to use the pointer, I want to just give a little description of what that means. Pointer is just going to point to an address. And then you can use that address to do parsing or whatever you need to do. So hopefully this didn't overwhelm you. Again, don't worry if you don't fully understand it. We'll go through some examples now of analyzing, tokenizing, and searching strings. To search for a string, we mentioned you're going to use the stir car or the stir. The stir car searches a given string for a single character. The first argument to the function is the string to be searched, which will be the address of a character array. The second argument is the character that you are looking for. We'll provide an example in a second. So the function is going to search the string starting at the beginning and return a pointer to the first position in the string where the character is found. This is why pointer is important now, because we're not returning an entire value. We're returning a pointer to a character inside of a string. And that address represents the index of an array, essentially. So the address of this position in memory, it's of type character star, and is described as a pointer to a car, which is really just a single element, a single character in memory. To store the value that's returned, you must create a variable that can store the address of a character, so you have to create a pointer. If the character is now found, the function returns a special value, which is null. Null means that the pointer doesn't point to anything. We use null when we talk about pointers. And null is just saying it didn't find anything, so it's not pointing to anything. When it points to something, it points to the address of where you found that character. And then you can start parsing from there. Because remember from the earlier lectures, when you create a character array in memory, you just have each character represented as a byte. And if you're parsing a string and you want to see where a particular character starts in that string, you return that byte. And then you can start looking from there. So stir car, how you use it is this. You create a string, character string, and we initialize it here with the quick brown fox. We then create a single character, and we initialize that with Q. Then we create a pointer, because we have to create a pointer because that's what's returned from the stir car. That's what allows us to see where in that string we found a character. We're going to initialize our pointer to null, because right now it's not going to point to anything. Then we're going to call stir car. We're going to pass in our string, which is the quick brown fox, and we're going to pass in our single character, which is Q. What's going to happen is it's going to look inside the quick brown fox, and the first time it finds a Q, it's going to return the address of that queue. So p.char is really going to be pointing to, let's see, it's going to be pointing to the fourth index of stir. Because T is sub 0, H is sub 1, E is sub 2, space is sub 3, Q is sub 4. So p.char is going to point to Q in the quick brown fox. And so you can see exactly where that character starts in that string. So the first argument to stir car is the address of the first location to be searched. That's the search string. Second argument is the character that is sought, the character that you want to look for, a single character. It expects the second argument to be of type int. So technically, stir car, the second argument takes int, but C compiler will automatically convert the char to an int. It will get the ASCII value essentially. So you could actually define the queue, single character, instead of a single car, you could define it as an int. That's just more of a technicality that I wanted you to know about. But p.char is going to point to the value quick brown fox because it's going to start at Q and then it's going to go to the null terminator if you try to print it out. So it's actually going to be quick brown fox when you run this example. This is how you can search for a single character in an entire string. Use stir car, then use the pointer, and then display the pointer. And how do you display that pointer? The same way you display other characters. Use printf %s. So this is a nice mechanism to search for characters in an entire string. If you want to search for a string inside of a string, which would be a substring, you use stir. This is probably the most useful of all searching functions. It searches one string for the occurrence of a substring. And it returns a pointer to the position in the first string where the substring is found. Very similar to stir car, but it searches an entire string. If it didn't find any match, it returns null. The first argument is the string that is to be searched, just like stir car. The second is the substring you're looking for, another string. So here's an example. It looks very similar to the other one, except instead of looking for a single character, we're looking for a word, a string. So we have word, which is equal to dog, and we have text, which is every dog has his day. We create our pointer again because it has to be, this is what the function returns. When we call stir, we pass in the text, the string that we want to look at, and then the second argument is the word that we want to look inside that string. Right? So it's going to search for the text, the first occurrence of the string stored in word. The string dog appears at the 7th character in text. Right? If you look at text sub 6 is going to be equal to dog. And that's where it starts. So the pointer is going to point to the address of text plus 6, dog, and it's going to start there, and then it's going to go to the null terminator. So pfound is going to be dog has his day. And also be careful because the search is case sensitive. If you actually provided a capital DOG, you're not going to find anything. It's only going to look for the correct case. But this is used to find substrings and strings. Very useful because a lot of times in a program you're going to say, does this string inside this string? Because you're doing like, it's almost similar to like a grep, if you've ever used grep on Linux. All right, I hope this makes sense. Tokenizing a string. A token is a sequence of characters within a string that is bound by a delimiter. We know this. A delimiter can be anything, but it should be something unique to that string. Don't have a delimiter as A, because now it's going to find in that string something valid in a word. Make it something unique, like a space or a comma. This, again, is used as a boundary for usually words in a single string. So it breaks a sentence into words. It's called tokenizing. The stir toke function is used for tokenizing a string. It requires 2 arguments. The string to be tokenized, which is the entire string that has the spaces and has the delimiters. And then the string containing all the positive delimiter characters. You can specify what you want to set as the boundary. So here's an example. We're creating a character array, 80. It says, hello, how are you? You are dash, my name is dash Jason. We then create a constant string that represents the delimiter, which is the minus, the dash. It looks a little different, but it's still the minus the dash. They're both dashes. And then we create our pointer, which is token. Because stir toke is going to return our each token. So if we call stir toke and we pass in string and we pass in our delimiter as s, token is going to be equal to the first thing that it finds. So the first time you call stir toke, it's going to be equal to hello, how are you, space. And then it finds the match with the dash. And if you call for a second time, it's going to print out my name is. If you call it a third time, it's going to print out Jason because it's going through the dashes. So that's why we have a while loop here. We say while the token is not equal to null, print out the token. And then we call token, we get the next token by calling stir token. And we say null as our first parameter and s as our second parameter. And then we display it. So let's look at this in code blocks, since it will make it more understandable. So let's build this. We just went through this example. I want to show you what the output is so it's clear what's going on here. Whenever I copy and paste from PowerPoint, the characters get messed up, so I have to fix that. All right. And so here, you'll see that it says, it prints out the first token, which is hello, how are you? Well, the first thing it does is it finds the first token, prints it out, hello, how are you? My name is, and then Jason. Let's format this output a little better, because I have the dash. I want to make sure they're the right ones. There was another problem from copying and pasting. So now we have hello, how are you? Finds the first dash, prints it out. My name is, finds the next token. Then the third one is Jason. But you have to call the token 3 times to get each token. The first one's going to tokenize on the stir. See, the next one you can pass in null because you don't want to look again. You just want to get the next token. And so you pass in null the second one and you just pass in S. It will give you the next token of the stir it already toked. So that's how you can use stir toke. Separating, it helps a lot with parsing. You can parse something and get certain word boundaries out. The last functions I want to talk about are these analyzing string functions. Is lower, there's a ton of them, so I just provided a little table here. Is lower, is upper. It does exactly what you think it would do. It tests to see if a character is lowercase or uppercase. So we're testing certain characters, but they're used inside strings. And so the argument to each of these functions is the character that you want to look for. And then all these functions return a non-zero value of type int if the character is within the set that's being tested. Right, so we're going to pass in characters inside, looking for inside words. If we have an uppercase letter inside of a word, it will tell us. And we can use it for parsing individual elements in a character way as well. So the return values will convert to true or false, so you can use them as booleans as well, which is nice. So is lower will return true if a word or a character has a lowercase letter. Well, here's a nice example I wanted to run through, which will count the number of letters, digits in an entire string. So let's run this because this will be clearer. But what you should notice is we're creating a buffer, our input buffer, and then we're creating 3 integers to count. We're telling the reader, the user, to input a string of less than so many characters. We then read it in. We're then going to look at that string to see if it contains certain characters. And so we're going to iterate through that string by looking at each index in the array. So here's our example. Again, buffer is our character array that's going to store inputs. We're going to use scanf to populate that. We have to type in our string with no spaces because it's a single string. We're going to run through it, go through each element in the buffer, and then call the isAlpha, isDigit, or isPunct functions to see if those characters are in there. And then it will increment them based on that, whether or not that returns true or false. And then it will display out how many letters, digits, and punctuation characters are inside that string. Let's run this. I'm just going to enter something with a bunch of uppercase, maybe some digits. Whoops. I got to get rid of this virus thing. So now, yeah. And then when I hit return, it's going to count everything. So it says, my string contained 24 letters, 4 digits, and 1 punctuation character. The colon. Nice little, neat little program that utilizes those sort of character functions, but are useful with analyzing a string. Because that's what you're doing, is you're analyzing the string, but you're just going it through character by character. Thank you. Hello and welcome. In this lecture I want to talk about converting strings, some more string functions. It's very common to convert character case specifically if you want to make your string all lower or all uppercase characters. Luckily there's a toUpper function that converts from lowercase to uppercase and a toLower function that converts from uppercase to lowercase. So lowercase to upper, upper to lower. Both functions return either the converted character or the same character for characters that are already in the correct case, or are not convertible, such as punctuation characters, if you can't convert them. So this is how you can convert a string to uppercase. Remember, these are actually utilized on character by character basis. So if you had a buffer that was a character array, you would have to go through each element in the buffer and then do a toUpper on that character. So here we're going through each element in our buffer character array and we're passing it to the toUpper method. And that's going to return a character that's in uppercase and we're going to assign it to our buff sub I. We're going to do that until we hit the null character. So this is a for statement that just has one line. This converts the entire string in a buff array to uppercase by stepping through the string one character at a time. The loop stops when it reaches the string termination character, \0. The cast to the type char is there because toUpper returns of type int, which is the ASCII value, and it just converts it. And you would do the same thing if you wanted to convert it to lowercase. Very simple to use the case conversion functions. All right, so you can use the function toUpper in combination with the stir function to find out whether one string occurs in another, ignoring the case. So let's look at this example that does exactly that. Here we have two character arrays, text and substring. Text is 100, size 100, substring is size 40. We ask the user to enter a string to be searched, less than 100 characters. We get that, we store it in text, and then we enter the string that they want to find using the stir, so then the substring. So they enter some other substring. We then print the first string and then we print the second string. We then convert both the strings to uppercase. And then we can actually say the second string found the first string. So when we call stir, it can ignore case, because remember, one of the limitations of stir was that it was case sensitive. And so now we can use stir on text and substring because they're all uppercase characters. And again, this is a way to find whether a substring is an entire string, ignoring case. First, we just convert everything to uppercase, and now we're comparing uppercase. And that's what this program does. It's often the case that you'll want to convert strings to numbers. So there's specific functions that start with an A. They're like A2F, A2I, A2L, and A2LL. It's not ATOF, A2F. A2I is very common, converting a string to an int. So A2F is going to convert a string, and it's like ASCII to F. It's going to convert a string to a data type. So an A2F is an ASCII to a float, or double to a float. And you may have certain return values if it's not found or can't do. So sometimes you can't convert strings to integers, especially if you have a string that just had words, right? Usually you use this function when you have, in the example, if you have a character string that has 98.4. That can be represented as a double. So you can do an A2F on it. If you have a character string of JSON, you can't convert that to a float or an integer. So nothing's going to happen. So when you have character strings that have numbers, you can convert them using these ASCII2 functions. And this is all included in the standard lib header file. You'll also see the opposite for creating integers to strings. You'll see things like I2A, which is int to ASCII. So if you had a number 98, and you want to convert it to a string, you'd say I2A. Right? There's also some newer functions, I think, that do some more. These ones are specifically for string to double as opposed to A to F. You can use these stir to Ds or store to F or string to LD. And they each just convert to either long doubles, floats, or floats doubles. But either one of them is fine. The ASCII ones are the traditional ones. I think the other stir to Ds and stir to Fs were added in later standards of C. So here's an example of doing some conversions. It's very, very basic. Here we have a stir character array, 3.5 space 2.5 space 1.26. We have a couple pointers, and we're going through until we jump out as if we can't convert it. So we say stir to D, we pass in our address of our PTR, our pointer, and we pass in our P string, which is our string, 3.5 to 2.5. Now you may say, why are you passing in the P stir as opposed to just the stir? And you don't have to. But here we want to actually check if there was no conversion. So because we're checking for no conversion, we have to look at both pointers. You can't compare the PTR to the stir because the stir is an array. So we're going to use P stir to just represent our character array so we can compare. And if we compare those two, it means P stir stored no conversion. And so we're done. We weren't able to actually convert that value. Otherwise, if we were able to convert the value, we're just going to print it out. And we're then going to go for the next conversion. P stir is going to equal to pointer. So you can run this and you can see that it's going to end up converting everything in the string array to specific values, doubles, double values. I usually use A to I, A to F, but either one of these will work. These are the conversion functions. Thank you.
Hello and welcome. In this video I'm going to walk you through setting up the debugger in CodeLight for Windows, setting up the configuration. Now it's pretty straightforward as far as the settings go, but the issue is that CodeLight is definitely somewhat buggy when it comes to the Cygwin GDB debugger. We're going to try a couple things. First, we're going to try to use a particular version of GDB through Cygwin. Sometimes that has worked for some students, and other times it hasn't. You can also try using the latest version of the Cygwin GDB debugger, and sometimes that will work. But if all else fails, we're going to have to revert and use the MinGW debugger for CodeLight. And that's perfectly fine. We just may have to make sure we use the compiler, the Cygwin compiler for CodeLight, because we're using advanced features of C and the MinGW doesn't have those advanced features. But using the debugger for MinGW is perfectly fine. So the first thing you should do is you should go to your browser and you should go to cygwin.com. Remember, we installed Cygwin earlier in the course. If you go to the home page, you'll want to go to install Cygwin. This is just a setup file that allows you to update packages, change versions, and all those things. So if you download setup x86-64 for Windows, you can download that anywhere on your device. I'm just going to download it to my desktop. And when I download that to my desktop, it may take a couple minutes, but it's basically just going to install the setup for Cygwin so that we can change the version of our GDB to use a particular version. So here it is on my desktop. If you double click this and run it, again, you can actually pick what version of GDB to install. So this is the first thing we're going to try. We're going to try reverting to an older version of GDB, particularly the 9.2 version. And so you just want to make sure that you install where you've already installed Cygwin. So you just want to pick that same directory, hit next, and keep going until you actually get up the setup screen. So you can just select whatever mirrors and so forth. Again, we've done this already. We just want to revert our GDB. So once you see this screen, you can actually go to the view and you can just say full, and you can search for GDB. At this point, you should see that you have GDB installed. So I have GDB installed and I have the latest version. But the latest version isn't working with CodeLight. I keep getting strange errors. So there are some versions of CodeLight that will work with 9.2-1. So if you go down to the drop down, you select 9-2-1, and you select next, you'll see that it's going to uninstall GDB, the latest version, and it's going to then go ahead and install 9.2.1. So you can go ahead and select next and install that. It may take a couple minutes. And you can go ahead and click finish once it's done. And then once that's complete, you want to bring up CodeLight. and you want to try to set the debugger settings to use that particular version of GDB. So I'm going to go ahead and create a new project. Just say new project, and we'll just call this project debugger test. And we're going to actually not use the template. You can always add this to your template later, but we're just going to do a console app. The type is going to be simple executable GCC, and we're going to specify the debugger to be GNU GDB debugger. So I'm going to hit OK. And now there's a couple ways to set your debugger settings. You can go up to settings, and you go to GDB settings, and for your debugger path under general, you can point to the version of Cygwin that we just downloaded, GDB. But that's not always necessary. These are supposed to be the global settings, but I don't think they necessarily get inherited for every project. So your best bet is to click on the project, go to settings, and select the debugger on the left-hand side. And it says select the debugger path. You want to point it to your Cygwin bin folder. So if you select the ... and you go to C, Cygwin 64, wherever you downloaded it, bin, and then GDB. And so here we go to GDB, and we select that. And so you see that path there, and you say apply, and you say OK. Now in our debugger test, one way to test to see if the debugger is actually working, you can go to your main.c file, and on the margin where the line numbers are, you can just select inside of the main function, maybe on line 5, you can select it, and you'll see this red circle appear. This is called the breakpoint. We're going to talk about these in a lot more detail later. But this will essentially stop the execution of your program at this line of code if you run the debugger. And so to test to see if the debugger worked, we're going to go up to the debugger, and we're going to say start continue debugger. And we're going to say build and debug. And at this point, you should try to run the debugger. And you'll notice that nothing happened for me. It just came up and it closed. And so it didn't catch that breakpoint. So unfortunately, 9-2.1 is not working for me for the Cygwin debugger. If this doesn't work for you, you could try installing the latest version of GDB, just like I did a minute ago, where you bring up the Cygwin setup and you select GDB and then you select the latest version, and then you could point the path to that. That's another option. But again, I haven't been able to get those to work. It's been really confusing. I posted in the CodeLight forums. I've asked questions. It seems like it's a common problem, a common bug. So if all else fails, what I would suggest you do is install the min-GW debugger. And so at this point, let's walk through that. If you bring up your browser, so you want to navigate to basically the download page of WinLibs. So you want to go to WinLibs right at the top here, winlibs.com/#download-release. And once you select that, you'll see that it says released versions, and you'll want to select the one for Windows. I would suggest selecting it for Win64, and I usually select the zip archive. That's GCC. The current time of this recording of this video, it's 12.2.0, but you can just grab the latest version. So if you select zip archive, it's going to ask you to save that. You can save it wherever you want. It's going to be a zip file. It will go ahead and download that, and it's not too big, but it may take a little bit. It's about 308 megabytes. Once that's downloaded, you will have to extract it somewhere. I would suggest extracting it right where you extracted your Cygwin folder, maybe in C. I actually extracted it to C min-GW. So once that's done, you'll see that it's downloaded. I downloaded it to my desktop. You can right-click on it. You'll need a WinZip application or WinRAR to extract it, but you can right-click on it and say extract, and then extract it wherever you want. Again, I've already downloaded it and extracted it. I've downloaded it to my C drive. So if I go to my C drive, you'll see that I have min-GW64. That's where I extracted. And inside there's a bin folder with your GDB executable. And that's the one we want to point to in CodeLight. So now that I've downloaded it and I've extracted it, I'm going to go back to CodeLight. I'm going to have my example project here. And in my project settings, I can select my project, right-click, and I can say Settings. And now, instead of pointing the path to Cygwin, I'm going to point the path to my min-GW bin folder. So if I hit the ... I can go to C, min-GW64, the one you just downloaded, remember, bin, and then GDB, gdb.exe, and I can go ahead and select that. And you'll see that path placed inside there. So that I can hit apply, and I can hit OK. And now again, to test this, you'll want to set a breakpoint and run the debugger to see if it actually hits that breakpoint. So you can go up to like line 5, make sure you have the right file selected for the right project, you can select line 5, add that circle for that breakpoint, go up to your debugger, you can say start continue debugger, build and debug, and then it should hit that breakpoint. And that's what happens, right? You see the program stop execution, there's a little green arrow next to the 5, and then the debugger window comes up, right? And that means that the debugger is working. And so you were able to successfully install and configure the debugger, the MinGW debugger for CodeLight. Now we're going to talk about how you can run through the debugger and do all the options and how it's useful for finding errors in your code. But right now we just want to make sure that we were able to successfully configure and install the debugger. To stop the debugger, you can just hit the stop, the red rectangle right there. Now there are also settings right at the top, GDB settings. I've noticed that this doesn't need to be set if it's set in the project. I've also noticed that when I do set it, so if I go ahead and I set this to GDB, that it doesn't necessarily apply to every single project. So if I set the CMinGW64 bin, it doesn't actually work when you create new projects. So you always have to set it in the project settings. I'm not sure why setting it here should set it up for all projects, and maybe it does later, but right now I'm just setting it in my project settings. So if it's in your project settings, and you might as well just keep it in here set anyways, and you can see there's some other options. Usually all the default options are perfectly fine. Now, since that's a project setting, you definitely may want to add it to a new template. Create a new template and then make sure that you have all your settings correctly, right? So you can go to project settings, right? And for debugging, you always want to make sure that the compiler is compiling for debugging and opting for optimizations for debugging. By default, it already does that. But you should see for the C compiler, gdwarf2-00 and so forth. Those always have to be set. And you also have to make sure that when you build for a debug release, right? So remember up here, we talked about this before, debug and release. If you're built for release, you're not going to have debugging information. You won't be able to set breakpoints. So you always want to make sure that debug is selected. And that's about it, right? You can play around with other settings, but really all you need to do is set that path to the correct GDB executable. And because CodeLight is somewhat buggy with the Cygwin GDB, and I don't know why, again, you can try to use the latest version of Cygwin GDB. You can use an older version. Maybe you'll get it working. But if all else fails, just set the project settings to the MinGW64 debugger, and you can use that while debugging on Windows in CodeLight. If you have any questions in the forum, let me know. Thank you. Hello and welcome. In this video, I'm going to show you how you can configure the LLDB debugger for the Mac OS so that it works in CodeLight. Now, the first thing you probably need to do is you need to bring up a terminal. And you can bring up a terminal. Remember, just go to the Finder and you go to Utilities and bring up a terminal. Once you have a terminal window, you can actually type in which LLDB. And that will show you the path to the LLDB debugger. And you want to use the LLDB debugger. It works a little bit better than GDB if you're on a Mac OS. You could try using the GDB debugger. So the LLD debugger is installed in user bin LLDB. You might need that information later. At this point, you would just want to bring up CodeLight, and you can go to your application finder and go to applications and double click on CodeLight to bring that up. I already have that up, so I'm going to go ahead and bring up CodeLight. And at this point, I'm going to create a new project and make sure I select the LLD debugger and then see if the configuration works. So I have this workspace as an older workspace. I'm going to right click. I'm going to say new project. I'm going to make sure that I'm going to call this project debugger test. And I'm going to select the categories console, simple executable GCC, compiler GCC, but the debugger I'm going to select is LLDB debugger. And then keep the build system as default. And I'm going to go ahead and say OK. So now I have this new project debugger test, and I have a new template source file, main.c. And we're going to see if the LLD debugger works. So what we can do is we can select in the margin here where the line numbers are. We can just select in here, right by the 5, and try to add a breakpoint right in there. And you'll see that circle red. Breakpoint basically stops the execution of the program at that line of code. And so to see if the configuration of our LLD debugger worked, we set that breakpoint, and then we can go up and we can say debugger, and we can say start continue debugger. At this point it says, would you like to build? You can just say build and debug. And the project comes up and it starts to run. and you'll notice it stops right on line 5. You can see that little red circle, but also you can see that green arrow. That means the program has stopped execution. So that means we're good to go. Our debugger is working on the Mac OS, and we can step through the code. We're going to go through all these details in later lectures, but you'll also see that the debugger window came up. You can make that bigger. Again, we'll walk through that later. But we just want to confirm that our configuration is working for the LLD debugger. So at this point, we can just hit the red rectangle. We can stop the debugger, and our program will stop execution. And you should notice too, when you select the debugger test, you can check the project settings for the debugger and so forth. And you should see that you don't actually need to set the debugger path. If you do have any issues, you might need to go and set it to the path that we just looked at, user bin LLDB, if you have any issues. But it doesn't need to be set if you're actually selecting, when you create your project, and selecting LLDB. But if you do have issues, you may want to look there. The other thing is up in the settings, you can also see settings for LLDB settings. Again, usually these are all good by just keeping default, but if you have any issues, you may have to, look at some of this information. But I don't have any issues. It's as simple as basically just selecting LLDB as the option and then setting breakpoints, and everything works. A couple things to notice: you do want to make sure that when you compile and when you run, that your project is set as debug. It should not be set as release. It should be set as debug. And then one other thing is you want to make sure when you have your project settings that you're actually compiling for debugging. So you want to make sure, and we've gone through this already, but you just want to make sure under the compiler that for the C compiler option that you have the -O for optimization and the -G. And so you can, produce debugging information as -G, and you want to make sure that is selected, and then also optimize for debugging. But if you have all those settings set, you should have no problem running the debugger and CodeLight on a Mac OS. Thank you. Hello and welcome. In this lecture, I'm going to show you how you can set up the GDB debugger inside CodeLight on Ubuntu Linux. The first thing you're going to need to do is you're going to need to bring up a terminal. Remember, you can go to a terminal just by selecting the ... and typing in terminal. I already have a terminal up, so what I want to do is I just want to type in which GDB, and that's going to show me the path of the GDB debugger. That may be important later, it may not be, but you should know where GDB is installed, which is user bin GDB. Now you want to bring up CodeLight. Again, you can bring up CodeLight by going to the Show Applications, searching for CodeLight. I already have CodeLight up, so here it is. I'm going to go ahead and I'm going to create a new project. So I just have an older workspace here. I'm going to right-click on the workspace. I'm going to say New Project. I'm going to name this project Debugger Test. Debugger Test. And I'm going to select the category. You can select the template, but the template should have the GDB settings in it. So I'm just going to select the category as console, the type as simple executable GCC, compiler GCC, whatever version, and then what's really important is the debugger, GNU GDB debugger, and then build system by default. I'm going to go ahead and hit OK. Now later, if you want to add a new template to make sure you have the GDB debugger set, you can also do that. So once I hit OK, you'll notice that my project was created, debugger test, and I now have main.c. I double click main.c. I'll see my templated source code for Hello World. Now, to see if the debugger configuration already works by just selecting that, and when I created the project, I can go on the margin here where the line numbers are, and I can select on line 5, I can just right click on it, and that will show me a red circle. This red circle indicates that it's a breakpoint. We're going to talk about breakpoints in a lot more detail, but what this is saying is we're going to stop execution of the program on line 5. And that will allow us to look at different information and so forth. But right now we're just setting a breakpoint. This is going to test to see if our debugger configuration is set up correctly. After we set the breakpoint, we can go up to the debugger and we can say start continue debugger. We can say build and debug, and this will build and start up the debugger. And so you'll see that this terminal window came up, and what you want to actually do is you want to move this, and you want to make sure that the debugger was hit. So if you look on line 5, you'll see the red circle, but you'll also see a green arrow, and that indicates that the program has stopped. And you also don't see any printf statements, so you know the program has stopped right there. So at this point, you know that your configuration is working, that GDB is all set up correctly for CodeLight. Now, if you want to stop the debugger, another thing you should notice actually before you stop it is that a window does come up, a debugger window, where you can now actually start doing things. But again, we're going to talk about this in subsequent videos in much more detail, how to use the debugger. So now we can just stop the debugger. We can hit the red rectangle to stop the program, and we're all set. A couple things to notice, right? If you select the debugger test project, you right click and you say settings, and you go to the debugger tab here on the left, you'll notice that the debugger path is not set. As long as you create the project and you select GDB, you should be good to go. But if you have any issues, you may have to set this path to what we had earlier, right? User bin GDB, when you type in which GDB at the terminal. You can just do that by going to ... and setting up that path. But it doesn't look like it's necessary, only if you have issues. There's also the settings up here on the main menu where you can go to GDB settings. And again, you can set up the debugger path if you have any issues. I thought this was a global setting that would set for all projects, but it doesn't seem to do that. There are also settings in here that you can look at if you're interested in. All the default settings should be fine. But these are where the configuration happens for GDB. If you look at your project, you see this drop down where it says debug. It's really important to have debug selected and not release. Make sure debug is selected because that will build debugging information and allow you to run and debug. And then the last thing, again, if you select your settings and you go to your compiler, you want to make sure that your C compiler options are building for debugging. So -G dwarf 2 and -00, those are options for debug information, right? We went through this earlier. It builds the executable to have debugging information in it, optimized for debugging in gdwarf 2. So if you have all these settings set, you should be ready to go to debug your program. Just remember that the paths and so forth, if you have any issues, you may want to set that. And make sure that wherever you do set your breakpoint, that it's in the right file for the right project that you're actually running, your active project. Okay, happy debugging. If you have any questions, please ask them in the Q&A forum. Thank you.
Hello and welcome. In this lecture, I'd like to talk about debugging. This is a very important concept that you need to understand. Specifically, you need to understand some of the tools and some of the methods that you can employ to find and fix bugs. So debugging is the process of finding and fixing errors in a program, usually logic errors. And I'm going to tell you the difference between logic and syntax errors. But it can also include compiler syntax errors. It's the entire process. For syntax errors, debugging is understanding what the compiler is telling you. You always want to focus on fixing the first problem detected. I want to go through some of the common compiler errors and warnings that you may get, but one of the things you always want to know about the compiler is that the compiler may give you a number of errors. You always want to focus on the first error because that first error may result in other errors, so it can be very misleading. If you see 5 errors in a program that the compiler is telling you, you might only have 1 error, and that first error might be causing the other errors. So it's important to always look at that first top error and fix that one first.
In this very simplistic example, we have multiple errors in this code. Right? We don't have a beginning left bracket, curly brace. We don't have a semicolon. We're returning a string. And so when we save this and we go to compile it, and you actually see some red errors, when we go to compile it, it actually tells us we have 3 errors. You never want to just select the last error on line 7. Even though in this case it's an actual error, you always want to just fix the first error. So you see the first error listed here and you fix that first error, and then you recompile and you run it again. But the reason to do this is only to fix that top level error is because that error may cause other problems. So always focus on fixing that first error.
Debugging and the process of finding and fixing bugs can be very complex, from finding simple errors to collecting large amounts of data for analysis. It all depends. Sometimes you don't have any information provided with you except logging. And in that case, you have to analyze things. Sometimes you'll have bugs that aren't repeatable. You can't reproduce it because it happens in such a rare occasion. That's usually when you have to analyze logs or some variation of that. The ability to debug by a programmer is an essential skill. It's really a problem-solving skill. that can save you tremendous amounts of time and money. So it's an important skill to learn. It's an important skill to develop. It takes practice. It's not just going to come to you. There are certain techniques that you can apply and methods that you can apply to make you better at debugging. I know quite a few number of developers that are really good at writing software, writing code. They understand the language very well, but their debugging skills are very poor. They may get a bug, and their first inclination to solving that bug is really kind of off track. And again, this comes with practice. You'll get better and better at debugging and understanding how to find and fix problems. But it is something you have to learn as well. The maintenance phase is the most expensive phase of the software lifecycle. The maintenance phase is after you release your product and you now have to maintain it. Maintain it means fixing any new bugs that come in and also adding new features. So for example, when Windows releases a new operating system such as Windows 10, they're not done producing that software. It's going to be out in the field for probably 10 years. And it's still Microsoft's responsibility when any new bugs come in or they find new bugs for that software to fix it. And that's why they push auto updates and they do things like that. And then they'll also notice that the operating system will come out with new features as the market changes and as technology changes. So maintenance is very important. And as a result, finding and fixing your bugs is very important. Understand, though, that bugs are unavoidable. All software have bugs. Nobody can write perfect code. And it's not even necessarily about writing perfect code. It's just things change over time, so that may result in bugs as well. You have to understand that just because software has bugs does not mean it's poorly written code. It's kind of unavoidable. So it's okay to have bugs, and when you find and fix them, it's even greater because you actually feel like you're accomplishing something. Common problems, and we're going to talk more about specific problems related to C, but common problems when you're trying to debug are logic errors. Logic errors have to do with with the opposite of kind of syntax errors. Your code actually compiles, it works, but it doesn't do what it's intended to do. So there's some kind of logic or intended functionality that's incorrect. Maybe you have an if statement and you're jumping into that if statement on the wrong condition. Maybe you have a loop and the loop is not executing the right number of times, or you're not sorting correctly. Functionality is broken, but the compiler says, hey, everything looks good.
Here's an example of a logic error. A logic error is where the syntax is correct, but the desired results are not correct due to some kind of logic problem. So in this code, you see the for loop has a semicolon at the end. That is syntactically correct, but you're expecting this for loop to run 5 times, but it's not. It's only going to run runtime. So if we say build and we build this project, we do see a warning, which is nice, and you should always fix all your warnings, but it did compile successfully. So when we run this project, you're going to notice that it actually only runs one time and prints out hello world once. So this is an example of a logic error.
Syntax errors are directly related to the compiler. These are things not following the rules of the language. You don't have a semicolon at the end of a statement. You don't have a ending right parentheses with a left parentheses. You're missing a bracket. You're not using the right keyword. Things like that. Syntax errors are usually caught by the compiler. Logic errors are going to be caught by the programmer during the testing phase. Memory corruption is also a common problem, especially in C. If you're not freeing your memory after allocating it correctly, you can have things like dangling references, and you can also have memory issues related to memory that's not being used. You can have memory leaks.
Here's an example of a memory error. In this particular code, we actually have a memory leak. So we haven't talked about pointers yet. We haven't talked about dynamic memory allocation. But in C, you can allocate memory while your program is running. You can use a malloc function. And so here we're allocating memory, but we're never freeing it. So we can build this code, and we can run it, and everything's good to go, but we're not actually freeing this error. So what we'd have to actually do to correct this memory error is we'd have to say free, and then we have to say free in X to free that pointer. But whenever you allocate memory, you don't free it. That's a memory leak. And then another example would be if we don't allocate the memory. If we create a pointer and then we try to assign it, we're going to have memory corruption because that memory doesn't have any allocation for it, and we're trying to assign a value to it. So just a little tidbit of some examples for memory corruption.
Performance and scalability. This could be a problem where your functionality is intended as it is, and your code syntactically is correct, but it's not very efficient, or you don't have the hardware to support it. So if you're running a server and you don't have enough hardware to support all the requests, it's going to run really, really slow. Or if you wrote your program to work with 10 users, but when it gets a lot of users, maybe it's not as fast because the database gets bogged down, or whatever the case may be. Code works, but it's not designed correctly to handle many amounts of users, or whatever the case may be. Lack of cohesion. This can be a problem in your code that reduces quality related to your code is doing too much, or a function is doing too much. It's not a single focus. Or even an application has too much functionality, has features that are never used. Right? And so this would probably require a redesign.
Here's an example of a program that would be not modularized, right? That's not cohesive. You have one big function that's doing way too many things. Hundreds of lines of code, thousands of lines of code. You want to break a function down into helper functions, separate modules. That makes your program much more cohesive, easier to maintain. So instead of having like a big main method that does initialization, reading input, find sum, find difference, find product, find quotient, you could create all of this code and put it in helper modules and separate the code. And so the separation can help find and fix your bugs much easier. Cohesiveness is always important in C, and it usually is resolved where you have high cohesion by providing helper methods.
Tight coupling. This also has to do with quality of code. This is where you have a lot of dependencies. Coupling is different than cohesion. Cohesion is your single focus. Coupling is where you have dependencies between maybe functions or between objects. We talked about coupling. We talked about global variables. If a global variable is being used in a lot of different functions, it can cause dependencies between those functions. So what you want to strive for when you write code and you're writing high quality code is you want to have very high cohesion and very low coupling. The debugging process, the first thing you have to do before you can find and fix any error is you have to understand the problem. This is relatable to don't just dive in and start looking at the code. Sit down with the tester, understand the requirements, understanding what's going on. Because if you don't understand what's going on, you're not even going to be able to, you shouldn't even attempt to try to solve it. Once you understand the bug, try to reproduce it, because reproducing the bug can help you gather more information. It's not always possible to reproduce bugs because they may occur in really rare circumstances. So for example, bugs that have are race conditions or even memory corruption may only happen in very specific use cases. And they may be intermittent problems. And if that's the case and you can't reproduce it, it's going to become harder and harder to debug. If you're able to reproduce it, you can usually gather enough information to fix it. Most problems are fixable. Also, you can have problems with not being able to reproduce a problem if you're a multi-threaded environment, parallel processes, or threading problems. Those are also very hard to debug. But definitely try to reproduce it once you've figured out what the problem actually is, in terms of you're able to understand it. Once you're able to reproduce it, or if you're not, then you want to try to apply some kind of divide and conquer. You want to try to isolate the bug, simplify the problem. Because being able to reduce is going to give you information back, but it might not necessarily tell you what part of the code the bug is in. So what you can do to try to simplify the problem is remove parts of the original test case so that you're not testing too much. You can isolate the problem even smaller by saying, oh, it only happens in this specific situation. You can also comment out code. We talked about functions just having stubs and not having any implementation. Sometimes that's employed in testing so that it can limit the problem set. Also, if you comment out code, you're going to have less code where the bug can actually happen. So as you're commenting out code or backing out changes, the bug may go away. And if the bug goes away, that tells you that the code that you commented out may have been causing it. What you essentially want to do, though, is turn a large program into a lot of small programs, either via testing or commenting out. Another common technique is to have unit tests surround your code. If a unit test fails, that can tell you exactly where the logic or the problem might be in your code. Once you isolate the bug, you can, and that will help you find the origin of the problem in the code, the specific code that's causing the problem. Sometimes this will employ using debugging tools, such as a debugger. We're going to talk about a debugger in specifics, but usually, depending on what IDE, integrated development, you use, there's debuggers that come with the IDE. There's also debuggers that can land standalone. The big important debugger that we're going to use for C programming is called GDB. It's the GNU debugger. So it's a nice tool that's actually a graphical where you can stop the execution of your program and add in breakpoints. And then as you stop the execution, you can go line by line in your code and look at the value of variables. So you can see exactly what's going on in your code while it's running. It's an invaluable tool. It's so useful. We're going to run through the debugs. I'll show you how to add breakpoints. I'll show you how to set up a watch so you can look at variables as they change, and also then step through the code. After you've identified the origin of the problem, you then have to fix it. This takes a lot of experience and practice. Just because you found the origin of the problem, you still might not be able to fix it just based on your experience. This sometimes includes redesign or refactoring of other code that especially with scalability problems or performance problems, you may have to redesign to allow your software to be more scalable. So it's not always easy just finding the problem and then fixing it. The problems sometimes, especially even harder problems like threading or parallel processing, those are even more difficult to fix. But as you write more and more code, this is going to become easier to do. And then lastly, you got to test like crazy. Always test. Test many different boundaries, good cases, bad cases, in-between cases, to verify that you have indeed fixed the problem. Some of the techniques and tools that are available. One common and very used tool is to use print statements. You can use print statements to basically trace your code. So in C, you can use the printf statement, and you can put it at multiple lines in your code to signify where you are. This is also very useful when your program crashes. It can help identify where it crashed. As you're adding these print statements, tracing through your code, you can add output in the print statements to see the value of variables, because the value of variables may be affecting state and may be causing logic issues. So just adding print statements is very useful. It can show the flow of execution, and it can help isolate the error. Debuggers, as I mentioned, one in the GDB, those can monitor the execution of the program. You can stop it. You can run line by line, restart it, set breakpoints, watch variables in memory. Very helpful when trying to diagnose where a problem resides. Log files. Log files are also very useful, especially for bugs that cannot be recreated. You can analyze them at a later date to see exactly what was going on when the bug happened. So this means that you have to provide good logging statements in your code itself in order for this to be useful. So you may create your own log file and then write to that log as the program is running, so that if you do have an error, you can send those logs out to developers. We employ this quite a bit at Xerox, because when we encounter issues, we can't always reproduce them, or they may be encountered in the field. We need to be able to access those logs to see what was happening when that bug happened. Monitoring software. There's software that can monitor and have runtime analysis of memory usage, network traffic, thread and object information. This can tell you if maybe you're allocating too much memory and not deleting it if you have a tool for memory usage. Network traffic, that can tell you whether or not you're sending too many packets out or whether or not your software is scalable. If you have an increase in network traffic and you see that your response time is degrading. You can also monitor threads and objects information for parallel processing to see what's going on in certain threads and what's going on in another thread. That will help you diagnose any thread kind of problems. Some other common debugging tools that you can employ to find and fix your errors. You can use exception handling. Many programming languages have exception handling. Unfortunately, C does not. An exception handler will actually prevent crashes and do a lot of things at runtime. It doesn't apply to C, but it's still a good thing to understand. Try catch blocks, things like that. Static analyzers. There are many static analyzers available for C. Static analyzers analyze the source code without the actual executable running. The program doesn't need to run it. It goes line by line and looks at the source code, and as it's parsing the source code, it looks for any known problems. So it can check semantics. It can make sure that you don't have any uninitialized variables. If you're allocating new memory, that you delete it. If you have any dead code where code's not actually being executed, you can delete that code. It also analyzes things like race conditions and deadlocks. We employ a couple static analyzers. Where I work, we have one called Coverity, which is pretty popular, And there's a code sonar tool that we use as well. And we'll run this on our entire baseline, our entire source set. And whenever we introduce new files and new code, that tool will be run on that code, and we'll be able to identify immediate issues with the code as far as uninitialized variables, memory leaks, and so forth. It does not analyze syntax. That is what the compiler is for. There's also a number of test suites that run a separate set of comprehensive system end-to-end tests that you can run on your software. Testing is always important, but if you can automate it somehow to run certain tests every time you do a new build, for example, that can be very helpful. And this can actually prevent errors, but it also helps diagnose errors as well. Debugging the program after it has crashed, we're going to talk about something called the call stack. This is a very useful mechanism to see, especially in a language like C, where you have a crash and the only information that you get is something like segmentation fault. When you have that crash, what happens a lot of time, depending on how it crashed, a core file will get generated. And you can analyze the core file to look at the call stack to see exactly where that program died. It will tell you the line of code where the program died. And so we're going to learn about the call stack. And as far as analyzing core files, that's more of an advanced technique. But in C, a core file can be generated and you can analyze it. That's a little more advanced technique. But that's another way you can do debugging on your software. What about preventing errors? We know that debugging is finding and fixing errors, but if you can prevent errors, that's even better. One of the ways that you can prevent errors is you can write high quality code. This is really not a focus on many software engineers. A lot of software engineers write the code, and as long as it works, that's all they're concerned about. Or as long as the output is correct, then they consider themselves done. But there is such a thing as poor quality code. And you don't want to write that. I've demonstrated some of this during the lectures, but things like using meaningful variable names, very important. Or if you write inefficient code where you're using loops maybe more than you need to, or using an if statement where you don't need to do that. All of these types of things constitute poor quality code. If you have a function that's doing 100 other things and it's not cohesive, if you have 5,000 lines in a function, if your code is not organized in a module fashion, or if you have many dependencies between functions, again, all of this is poor quality code, and you want to strive not to do this. You want to employ techniques where your program is organized, it's easy to maintain, it's highly cohesive, it has low coupling, and you use meaningful variable names. Very, very important. Again, it's very important also because the maintenance phase is so expensive. If you write poor quality code, it becomes much harder to maintain. It's harder to isolate errors, and it's harder to add new features. So employ good, high-quality techniques when writing your code. Unit tests. Unit tests help prevent errors tremendously. Unit tests are executed usually automatically when you compile. Unit tests can help void regression. That's one of the most important factors. Regression is when you write new code and you introduce a bug on something that was previously working. You broke old code. You don't want to do that. If some software is working and then something new that you did broke it, you want to immediately be notified. And unit tests can help do that because unit tests will run on that old code and will say, hey, this was working, now it's failing. It also can find errors in new code before it's delivered. Because again, they run after you build, and it will immediately tell you if something's wrong. There's a concept of test-driven development, which is getting really, really popular. This is where you write your tests first, and then you develop your code after. And the goal here is when you write your first test, your test is failing. And then you write the code to get it to pass. There's a lot of advantages to TDD, and it's kind of a reverse way of thinking. Normally people, when they write code, they write the code first and then they write the test after. But with TDD, it actually gives you a different way of thinking so that you're working in really small chunks and you tend to write very cohesive code, and the code doesn't have a lot of dependencies. Because guess what? If you're able to test code, it means that the code doesn't have as many dependencies. If your unit test is really, really large and you're mocking out all these different things, it's usually a big indicator that your code is very, very dependent on other things. So by employing TDD, it forces you to write very loosely coupled code that doesn't have dependencies, and it forces you to have your functions be very cohesive. There are a lot of advantages of TDD. You also want to provide good documentation, and you want to do proper planning. Don't just dive into code and start implementing. Write down your design on paper. Utilize pseudocode. All right. Plan your code. If you plan your code, you understand the requirements, and you have a good, thoughtful design, you can prevent many, many errors. And I've mentioned this throughout the course, but it's very, very important to have a divide and conquer type approach, work in small steps, and constantly test after each step. Do not write 1,000 lines of code and then say, okay, compile and test. That is not a good approach. Avoid too many changes at once. When making changes, apply them incrementally. Add one change, then test thoroughly before starting the next step. This can help reduce all sorts of bugs, and it also limits your problem set. So if you do have a bug, you immediately know where it is in the code because you just compiled and you just added that line or number of lines. Again, I cannot emphasize the importance of debugging, writing high quality code, and preventing errors. These problem solving techniques will save you a ton of time and make you much better programmer, top tier programmer. So in the next few lectures, I want to talk about some of the common errors that we see in C programming language. Also, I want to talk a little about the call stack. I want to go through the debugger that introduce you to the menu options and how you can stop and run watches and so forth. And I also want to help identify some common compiler errors that you see, how to interpret the compiler warnings and errors. What does it mean if the compiler says this? What does it mean if the compiler gives you this warning? Thank you. Hello and welcome. In this lecture, I want to talk a little bit about the call stack, what exactly it is, and how you can read it to further help debug your program. A stack trace, which is essentially what the call stack is generated whenever your app crashes because of a fatal error. The reason the term stack is used is because it's referring to a data structure that's common in programming. Stack is a data structure that's known as a LIFO, last in, first out. And that's how the data is stored. The last data element that's added is the first one that you retrieve back out. You can kind of think of it if you're eating a stack of pancakes. The first pancake is at the bottom that you add. The last pancake is at the top. When you go to eat them, you eat the last one that was added. And so a stack trace is very useful when your program crashes because it contains information that helps you debug it. So a stack trace shows a list of the function calls that lead to the error. And what will happen is in a program, when you call your main function, that's the entry point. The main function is going to call other functions. Those functions are going to call other functions. And all those functions that get implemented or get called will be put on the stack. And so what you can do is when a program crashes, the call stack will tell you that with the last function that was invoked and the specific line of code that caused the error. So the call stack contains a lot of good information. It will include the file name and the line numbers of the code that causes the exception or the fatal error to occur. The top of the stack contains the last call that caused the error, and there could be nested calls. The bottom of the stack contains the first call that started the chain of calls to call the error. So if you usually in C, that will be at the main routine. You invoke the main invokes another function, which invokes another function, so forth, and then that last line is detailed. It's very, very helpful when app crashes. And so when a C program crashes, it may generate a segmentation fault, and that doesn't tell you a lot of information. It just means something bad happened. That will also generate a core file. You can analyze the core file, which contains the call stack, which will tell you the exact line of code that caused the problem for your crash. So you need to find the call in your application that's causing the crash, and the call stack is probably the best way to do this. And you don't always need to look at that core file. You can also analyze the call stack using GDB with a debugger. And I want to show you what this looks like. A programmer is also able to dump the stack trace at any time. So if you do catch an error or you recognize that a fatal error might happen, you can dump the call stack to see what's going on. If you don't actually know when the error is going to happen, you can still dump the call stack to see the current traces that led up to a particular call. When using GDB, the call stack is going to look something like this. You can access the call stack via the menu when you're running the debugger in GDB, and I'm going to show you how to do this. But this is what it looks like. And what you'll see here is it has a number, an address, and then the function. This particular call stack here has a lot of different calls. So it must have been doing a lot of different nesting and a lot of different function calls. But at the very bottom of the stack in line 22, it says GT key main. That means it executed the main function. And then on lines 21, it looks like it executed maybe a statement that says main loop run. And then it looks like it called a function called gmain context iterate. And inside that function, there was another call to a IA gmain context dispatch function. So there was an iterate function, then a dispatch function. And then the question marks on line 18 mean that there's no debugging information. It doesn't know what happened there. And that's why when you build your program, you can either build it for release or you build it with debugging information. When you build it with debugging information, it contains extra information when you compile so that when you run, you can look at call stacks. When you release it, build something for release, the executable is a lot smaller and may not contain this information. It may contain more question marks. But this will also tell you if you invoked any libraries, any additional programs, it will call those and will tell you the call stack from there. But what this is showing again is the different nested events for the call. At the very top is what's important because that will signify what caused the crash. So it looks like in this particular call stack, the iter refresh was causing a problem. And you can see that from line 22 to line 0 that there are many different invocations of different code, but the eventual program crashed in line 0. Call stacks, you can also look at call stacks while the program is running to just see information so you can trace it back. So if you put a breakpoint inside of a function, you run the debugger on that, the debugger is going to stop at that breakpoint. You can then bring up the call stack and it will tell you how you got to that line of code. This function was invoked, followed before this function. And again, it usually will start with the main function. You can also switch to different frames. If you're familiar with the stack and the concept, how it's in memory, you can look at different frames. But this is a very useful tool to find mainly crashes in C. And it's very easy to read. If you just look at the top and you don't understand a lot about the call stack, you can look at the top and say, oh, that's a source, that's a line of code that caused the crash.
Here's a nice example I found on the web, scs.gm.edu, that illustrates function call stack examples. So if we look at an example in CodeLite, we'll see we just have some simple code. The calculations don't really matter. We're basically just calling some functions. So we have this mogrify function and this truly have function. And the main is going to call a mogrify function, and then it's going to call truly have, and then it's going to mogrify. So we can illustrate the call stack and what it looks like on these calls by basically just setting a simple breakpoint in main and then looking at the call stack as we progress and make calls. So again, we're going to get more familiar with breakpoints and information like that, but I just want to demonstrate the call stack real quick, and we'll actually give a more detailed example of the call stack later. So here I set a breakpoint. I can go ahead and build and compile this, and I can start the debugger, and it will hit that breakpoint. And what you'll notice now, you can see all the debugger menu over here on the right hand side in the bottom, and you'll see the call stack. Let's make this a little bit bigger. But right when it stops at line 14 here, it just has some assignment statements, and you'll see that the call stack shows main. If we step over that and go to the next line, we can actually see that it just goes to line 15 before it calls mogrify. Right? And so you see the call stack stays with main. If we step into, you'll now see that the call stack shows mogrify. So we're actually inside this function. We can step over that. So it executes the first line, and then it's going to return temp. It still stays in that function, and then it returns where it does the printf on line 16. You see how the call stack is changing. We then go to line 18. Call stack still is in main, and we step into the truly have function, and now you see the call stack change where it shows truly have. The function at the top is always the function that was last called. Again, we step over, and you see we're still in truly have. We go back to main. We print something out on line 19. We go to line 21. We again jump into the mogrify function, which again you see on the call stack. We jump over, and eventually we print out the final result on line 23 and return from the program. But the call stack again shows us the order of the functions that are being invoked from one function to the next. So if you have nested functions, it can be more and more complicated. The advantage of the call stack is if you have a line of code that crashes, say on line 4, you'll have a call stack that contains at the very top where the line crashed. And so you can actually see by going through the call stack what line of code was the last one that was invoked, and that will tell you what line of code was crashed.
But you will want to use this tool when your program crashes. Thank you. Hello and welcome back. In this lecture, I want to go through a demonstration of how you can use the debugger. So I want to run through the graphical user interface, show you how you can start up a program in debugging mode, how you can set breakpoints, how you can look at the call stack, and how you can view different variables using the watch window. Just a simple program that's determining an average. I'm going to use this as my demonstration. All it does is it reads in 3 integers and stores them and then computes their average.
Now, one thing I want to mention, before you're actually using the debugger, you have to make sure that your configuration is set up correctly. And I have talked about this in a prior video, basically configuring CodeLight for using the debugger. But just to refresh your memory, you can select the project here. You can right click and you go to settings. You want to make sure, again, depending on what platform you're on, you want to make sure that the debugger settings here on the left have the right path to GDB. Now, if you're on Windows, that may entail using gdb.exe from Cygwin, or it may be using the MinGDW64, whatever you got working. If you're on Unix and Linux, this path doesn't even necessarily need to be set. The other important thing is in the compiler options, you want to make sure that you're compiling for debugging. So that -G dwarf is on, -O for optimization, again in Windows. Those things have to be set in order to have debugging information along with your executable. You also have to make sure that you're building for debug mode. So you got to make sure that debug is selected and not release. Once you have all those things configured correctly, you should be able to use the debugger in CodeLight. If you have any issues with that, please go back to my video for configuring on your platform the debugger in CodeLight. The most important concept concerning the debugger is the idea of a breakpoint. And so a breakpoint is something that you can set in your program where it will stop execution of your code. You can essentially say, hey, I want to stop at this line, and your program, when you run the debugger, will stop at that line. That allows you to look at variables, the values of variables. It allows you to step through your code one line at a time to try to diagnose and fix any problems you that may have. Normally, when you run your program, if you try to run it in the debugger and you don't have a breakpoint set, nothing's going to happen. So normally when you build, you can go and you can build your project just like any other project. Go to build project. When you build it and run it in debug mode, you have to go up to the debugger menu option and you have to go to start continue debugger. And when you execute that, again, if you have a breakpoint set, it will hit it. If you don't have a breakpoint set, it will just run. So if we try to execute this program in debug mode, it just comes up and asks for enter because it stops right at the numbers, and then you just hit some numbers in and it just closes down. It doesn't even actually print out the information. Right? So it's very important if you want to use the debugger that you have at least one breakpoint set. The easiest way to set a breakpoint is to simply click inside the margin by the line numbers on the line number that you want to set the breakpoint. And again, a breakpoint is going to stop execution on that line number. So if we set a breakpoint right by the printf function on line 10, we just double click, you'll see that a red circle gets placed. This is telling the debugger, hey, stop at line 10. So again, the way that we start the debugger is we go up to debugger and we say start continue. Right? Everything else is kind of grayed out. Right? So let's just start the debugger just to hit that breakpoint. So let's go start continue to debugger and we'll say build and debug. And you'll notice that the program stops at line 10. You see that green arrow. You also see that the debugger pane came up. So if you go to view, you can actually bring up the debugger pane manually, or it can automatically come up when you go into debug mode. And the debugger pane has many different tabs for information that can be seen. You can also get through it to the debugger. You go to GDB windows, you can see all the ones that are checked. There are many debugger windows that you can look at. So locals usually has to do with your local variables. Watches, you can put a watch on a variable, so whenever the variable changes, it will pop up. Output is used for different debugging options and output. Threads, you can actually look at the threads that are running your program, more advanced C concept. Call stack, is what we focus on. We basically look at the call stack and the locals. Those are the two most important ones that help you with debugging. And then memory, and then also breakpoints. You can see where the breakpoints are set. So a lot of different options. We're currently stopped at line 10. We can look at the call stack. The call stack shows us that the main function is called. If we look at locals, it shows us 3 variables, 0, 1, and 0. We haven't actually entered any information in. Those are initialized 0, 1, and 0. The watches you can actually add by hitting the plus sign to add a watch on a particular variable. And then the other important thing to notice is when you run a debug mode, you now have the toolbar for the debugger, right? The play button will just continue. So it will go, if I hit play, it will just exit the program, right? It will just start running the program, actually. It will ask for input. So I hit play, I go back to the console application, and it says enter. So I hit my 3 numbers, and the program runs. Right? You still didn't see the print function. The window just went away. So again, we run in debug mode, and it goes to the breakpoint. Again, the debugger pane comes up, it stops at line 10. Now, the toolbar is important because this is how you can actually step through your code. And you can actually use the toolbar, or you can go up to debugger, and you can look at all the options up here. So you can say step into instruction, next instruction, step out. Step into will go inside of a function if a function is being called on that line. Step into instruction goes more to the assembly language type stuff. Next will jump over that line of code. Next and next instruction are kind of the same thing. Step out tries to jump out of a function if you're already in one. And jump to the caret line actually I think goes to the cursor, the same with run to the caret line. You can turn breakpoints on and off, disable them all that stuff. So you can access this through the menu or again the toolbar. Usually I use the toolbar because it's already up. And then if you look at the different windows, again locals, call stack, and breakpoints are really those important ones. This says I have a breakpoint at line 10. And then I think one just says the cursor. So now I've stopped here at printf, enter on line 10. I can go to the next instruction, and this will go to line 11. Scanf is actually a blocking function that asks for input. So if I try to go next here, it actually just kind of pauses. You might actually have to hit next multiple times. What I usually do when the program is asking for input, and I want it, it's already blocked, it's already stopped, and I want it to go to the next, I'll just put a breakpoint on that next line and hit the play button. So now I hit the play button, and nothing's happened because it's waiting for input in the program. It says enter. So here I can hit 5, 6, 7, hit the enter button, and now it hits my breakpoint. So now we're at the print button where we can actually jump into the print function, and actually first it will jump to the average function. So if we say step into, we go to the average function. And what you'll notice is if you look at your variables, you can kind of see your variables changing. So if you go next, you go to the next line on 27, then 28, and then keep hitting next, you actually jump out and you're actually at the end of the function. So then you can hit play, and you can see that your program is now completed and the window went away. But you can look at your variables, you can look at everything else. And so again, you can also put a breakpoint inside the print function right here. And if we run to that, we can see, again, that the print function will stop execution instead of the average. And then we can kind of see what's going on in the actual, if we step over and we go to the application, you can see that the information was printed out. Right? When you continue and you run to the end, you get the return statement and the program will exit. So it's important if you do want to see the output of the program that you place a breakpoint before that return and you don't hit the continue. You can stop the debugger by hitting that red rectangle, pause the debugger by hitting the 2 parallel bars, restart the debugger with that option. And the call stack, again, yeah, it's easier to see here if you get inside of a function and you run the debugger. We'll run the debugger again, say debugger, start, continue. And when we hit that breakpoint after entering information inside of a function, you'll see the call stack has the main and the print, just like we showed before. And so you can see the last function that was invoked.
Now with a program that has many functions and so forth, the call stack can get much larger than this. The only other thing that may be important is the breakpoints. If you want to see what breakpoints you set, it will show you all the breakpoints in your entire program, where they're located. But you'll have to play around with this, get familiar with it, get comfortable with it, and use it quite often for problems that you can't figure out with basic debugging techniques. Or if programs crash, go line by line, and as you go line by line, you can actually see the program exit once it crashes, and you will know what line that occurred on. Again, this is a small program, but you should get a basic understanding of how debugging works. Again, I hope this was helpful. The best way to learn this stuff is to start playing around with it and start using it. Bring up one of the programs that you worked on in your previous challenge, add a breakpoint. Very simple. Just click right inside the thing to add breakpoints. Start it up in debug mode and step through each line and see how the variables change and how the call stack increases if you have bigger functions. Thank you. Hello and welcome back. In this lecture I want to talk about some common mistakes that you'll make while programming in C. Some of these you might be familiar with from your previous challenges and you've already actually encountered these errors, but these are the most common types of mistakes. First one is very, very obvious. It's missing a semicolon. Remember that all statements in C will end in a semicolon. If you don't have it there, the compiler is going to complain. So either misplacing a semicolon or missing a semicolon entirely is a really common error. In this case, we're misplacing a semicolon. We have an if statement. We put a semicolon at the end of the if statement. And this actually causes the behavior of the program to be completely different. This will actually compile. When you miss a semicolon and don't even have it included, it will not compile. But in this case, the value of j is always going to be set to 0 because the semicolon on the if statement was placed. So the semicolon is perfectly valid to have it after the if statement. It actually represents the null statement, and therefore you don't have an error by the compiler, but this will cause a problem because j will never ever be set to 0. And this type of mistake can be common in looping as well. When you have a loop and you put the semicolon at the end of the for loop, and then you may have a bracket, it's gonna, or you don't have the bracket because you'll have an error if you have the bracket. Very common. Another one is confusing the equals operator with the equals equals operator. Specifically mention that the equals equals operator is not actually it's not comparing strings. So if you use equals equals when you're comparing strings, that's not valid. It's just going to compare the references. But if you actually mean to assign a variable to a value to a variable, and instead you use the equals equals, you're going to have a compiler error. Now, if you try to compare two items, like two integers, inside of an if statement, and instead you use the assignment operator, you actually won't have a compiler error, but you're not going to that expression is always going to evaluate to true. So when you use the equals and you don't use the equals equals, this is usually made in if while do statement inside the Boolean expression. And this is valid, except it has the effect of assigning to something as opposed to executing something. So in this example, if we have if a equals 2, it's assigning 2 to a. It always is set to true because that's a true statement because you never fail when it's doing assignment. And so printf is always going to run. What you really meant to do here is say if a equals equals 2. So it's very common using the equals as opposed to the equals equals and then not have a compiler error. If you use the equals equals in the wrong situation, you may have unexpected behavior as well, but you will have a compiler error if you're using it incorrectly for assignment. But be careful of this with the equals instead of the equals equals. Omitting prototype declarations. I mentioned that it's really important to always declare your functions at the top of the file before you use them. However, this doesn't always happen, and it's a very common mistake. And usually what will happen is you'll get an implicit declaration error in the compiler. In this example, if you have square root defined later in the program than where you're invoking it, or in another file, and you didn't explicitly declare it, you're going to have some warnings. The compiler is going to assume that the function returns an int. It's always safest to include that prototype declaration at the top for all the functions that you call, either explicitly or implicitly by including the correct header file in your program. But when you don't include that, those prototype declarations, you can have errors. Failing to include the header file that includes the definition for a C programming library function being used in the program. So in this case, you want to reuse some code. Maybe you have the printf function, you want to display some output, but you do not include the standard lib header file. That's a mistake. And that will be usually told you by the compiler. There will be an implicit, there will be a linking problem with that function. So in this case, we have double answer equals square root value 1. If this program doesn't include the math.header file, this will generate an error that square root is undefined. It will go try to link the object files. It won't have a math.o, and it will say, hey, you're calling the square root, but there's no implementation for it. So make sure you include the correct headers for all of your invocations of functions, especially from the standard library. Confusing a character constant and a character string. So here, if we have text equals A inside single quotes, that's a single character that's assigned to a text. If we have a variable named text and we assign it in double quotes, that's a pointer to the character string. Right? That is not valid for a single character. And this actually, we talked about string constants and assigning them to character arrays, and how you can't do that with the equals, and you have to actually do them with the stir copy. In this case, when we say text equals A, it's assigning a pointer. And this actually isn't valid either in C. What you would have to do is you'd have to do the star text equals A, or the star copy if you don't want to assign it directly like that. But you get the gist. Using an A inside of single quotes versus a character inside double quotes, completely different. Character versus string. In the first case, text is normally declared to be a char variable, and in the second case, it should be declared to be type pointer to a char. And if you want to assign a value to that pointer, other than the pointer itself, you'd have to dereference it. This is actually incorrect because if it's a pointer, instead of assigning an address, you're assigning it a string. So that doesn't make sense. Using the wrong bounds for an array out of bounds exception. Here we're declaring an integer array of 100 size, and then a couple variables I and sum, with only sum being initialized. And we go through our loop, and we say for I equals 1, I is less than equal to 100. That's incorrect, because the size of 100 means that there's 100 elements in the array. But arrays are zero-based, so the first element is 0. The max index that you can assign or access in the A array is 99. This is going to less than equals. So you're going to have an out-of-bounds mistake here. This is not a valid subscript. All right, because this loop is going to go all the way to 100. It's also probably incorrect because you're starting at 1. If you really wanted the first element of this array, you would start at 0. Forgetting to reserve an extra location in an array for the terminating null character of a string is also a common problem. When declaring your character arrays, they need to be large enough to contain the terminating null character. This is why I would suggest to you, you don't put a size in an array when you create it, if you're initializing it. You would only put the size in there if you're not initializing it. If you're creating and initializing on the same line, let C do the work for you. It will automatically put the right size, and it will include that null terminator. So, for example, if you have a character string called hello, this is more than 5 memory locations. It's 6 because of that null terminator at the end. Don't forget about the sizes of your arrays. This is a common problem with pointers, which we haven't discussed a ton about, but I did want to just mention it because it's very common. In pointers, when you want to access, or even in a struct, when you want to access something by a pointer, you have to use the dash greater than symbol. That's used when you're accessing a pointer element. All right, so if you have a pointer that's pointing to a structure, that's how you access it. If you have a structure that's not pointing, it's not a pointer, then you access it using a dot, the dot operator. A lot of times this dot operator and this dash then greater than is used incorrectly. Dot for non-pointers, pointers dash greater than. This will become clear in more of our examples. Omitting the ampersand before non-pointer variables in a scanf call. So remember, our scanf call expects a pointer as a second argument, and that means an address. When we declare a data type, a variable of type int, that's not a pointer. So in order to allow scanf to store that data in our int variable, we have to pass it the ampersand to say it's an address. So this is incorrect. Not having the ampersand before number in scanf as the second argument is not valid. The only time you do not have the ampersand is if you're using a pointer, like a character array. All arguments appearing after the format string in scanf must be pointers. Using a pointer variable before it's initialized. So here's an example of creating a pointer and then trying to assign to it. And this is the correct assignment where you're assigning a value, you dereference it. But what we haven't done here is we haven't initialized a pointer to actually have any memory allocated for it. And you can't do this in C. You can only apply the indirection operator, which is the asterisk before, to a pointer variable after you have set the variable pointing somewhere. So it has to be pointing somewhere. Right now it's null. It's not pointing anywhere because you didn't allocate any memory. So the char pointer is never set to point to anything, so the assignment is not meaningful. This would actually cause a segmentation fault. Another common error is omitting the break statement at the end of a case in a switch statement. If break is not included at the end of a case, then execution is continued to the next case. Right, so this is what I mentioned where you have a case, it gets evaluated, and if you don't have that break in there, it goes right to the next case and will execute the code inside that next case. So you always want to have breaks inside your case statements. There are times when you want to have a fall through case to another case and they do the exact same thing. In that case, you wouldn't have anything inside the case statement. Inserting a semicolon at the end of a preprocessor definition. Preprocessor definitions, remember, start with the number, the pound symbol. The preprocessor is run before the compiler, usually for optimization. And so the correct syntax for preprocessor definitions are not to include a semicolon. However, in C, you get into the habit of always putting a semicolon after everything. But you got to remember that if you define some constant data, that you don't need the semicolon. This is incorrect. This will lead to a syntax error if it's used in expression like that. So if you actually try to use that define, it's going to be okay to have that semicolon at the end, but when the preprocessor runs, it's going to insert exactly what is in that define. So it's going to insert into end of data 999:. This is what the compiler is going to see it. And it's going to actually cause an error. That would be a syntax error. Omitting a closing parentheses or closing quotation marks on any statement. Very common. This is also directly related to brackets too. Having a starting curly brace and then not ending the curly brace. Same thing with parentheses. In this case, we have 2 starting left parentheses, or 3, but we only have 2 ending parentheses. We're missing an ending right parentheses. That would be a syntax error that the compiler would find. So when you're using embed in parentheses to set apart each portion of an equation, it makes for a more readable line of code. You want to use parentheses. However, you want to make sure they all match. You start a parentheses, you have to have an ending closing parentheses. The same with curly braces. You start a curly brace, it has to have an ending curly brace. So either you have too many or you have too little, but the compiler is going to complain, and this is very, very common. So the second line here is missing a closing quotation mark as well, this print statement. We don't have an ending quote. The compiler will complain about that. Both of these will generate a compiler error. Sometimes, though, the compiler error is very misleading because it doesn't actually know where the error occurs. It thinks the error might have occurred on a subsequent line. So the line that it tells you the error might be misleading. So depending on whether the compiler uses a parentheses or a quotation mark on a subsequent line, it will actually complete that expression. So it will move the error down into another line. And that's where it will complain and say that's where the error is. But the actual error is higher up above where you meant to place it. These are some common mistakes that I see a lot of C programmers making. And they're easy to fix. And if you understand them and study this, you'll know not to make them. It's okay to make them as a beginner, but as you code more and more and get more practice, you'll realize, hey, I forgot a parentheses, I forgot a bracket, I didn't use the equals and the equals correctly. I'm using pointers incorrectly. I didn't allocate any memory. All these things will come more second nature. Thank you. Hello and welcome back. In this lecture, I just want to go over some common compiler errors and warnings. We talked about some of the common C problems, but sometimes you don't even know you have those errors in your program when the compiler is trying to tell you that. Compiler errors and warnings tend to be really cryptic to new programmers. You know, they may be telling you that you're missing a semicolon, but it says unreachable end of statement. And for somebody new, they might not even know what that means. So it takes a lot of practice in writing a lot of code and to decipher some of these compiler warnings over time. But I'd like to give you a heads up before that. So some of the common problems that you saw in the previous lecture, I'm going to actually describe some of the compiler warnings and errors and what it will actually say. It's very, very important to tell you to understand what the compiler is telling you. If the compiler is telling you there's errors, but you don't understand that error, it's going to take you much longer to fix that code. But if you see the error and you know exactly what it's saying, you can then go and fix it in no time. I remember I would be in the lab when I first started programming, and I would be missing a semicolon, something very common. And the compiler would be telling me I'm missing a semicolon, but I wouldn't know that. It would just say unreachable end of statement, and I would be like, what does that mean? What is a statement? I would be very confused. So that's why I wanted to give you some tips on what the compiler is actually trying to tell you. So it's very hard to understand what the compiler is complaining about. To decipher these messages are sometimes very confusing. So you need to understand these compiler errors in order to fix them. Pretty basic. And the compiler is doing half the job for you. It's checking the syntax, telling you exactly what's wrong. So you should use that to your advantage. But sometimes it's difficult to understand exactly what it's saying, especially if you're new and you don't understand some of the terminology. The compiler makes decisions about how to translate your code that the programmer has not written in the code. This is convenient for the program and the compiler so that it can be written more succinctly. And only expert programmers take advantage of this feature. So what I'm telling you is when you compile, you should always use the -wall option. This is going to turn on everything. So sometimes a more advanced feature is you'll actually take some stuff out, have the translation a little bit more efficient. But when you add that, you cause the program to be compiled differently, and as a result, you may have warnings in your code that you don't know about. So the reason I tell you that is you always want to compile with a certain option, which is the -wall option. And you actually, by default, that's turned on in code blocks. And this will notify you of all cases where the compiler is doing things that you don't know about. It also will turn on all warnings, give you a lot of information. It's a very useful compiler option. Once you have that option on, then you can try to help you better understand some of what the compiler is telling you. So the compiler is going to show you two types of errors. Or two types of problems. One is an error. This will actually prevent the creation of the program, right? You have a syntax error and the program cannot be compiled. No executable will be created. And usually, I mentioned this earlier, but usually when you see errors from the compiler, you always want to focus on that first error. That's the most reliable error because some of the other errors may be a result of that first error. So always focus on that first error. Fix the errors at the top first and then compile again and see if the other errors go away. Warnings are messages that the compiler shows about for special situations in which some type of anomaly has been detected. They're non-fatal errors, so the executable will be created, but it's still something that you should fix. A warning is there for a reason. You're either doing something incorrectly or it could cause a problem in the future. So you want to always fix all of your warnings. And by compiling with the -wall option, you do not consider the program correct until all warnings have been eliminated. So the compilation will not fail. This is why I tell you to use this option, as well as seeing everything that's going on by the compiler. So some of the most common compiler messages that you'll encounter, and this will be directly related to some of the most common C problems that we mentioned earlier. If a variable is undeclared, you'll see this message, variable undeclared, first used in this function. This is one of the most common and usually easier to detect. And then it will also display the symbol before this message. It will basically say that you're trying to use this variable, but you never actually declared it. We know that when you declare a variable, you specify the data type. You can't just start assigning data to variables that don't exist. A warning, implicit declaration of function. This is related to the function declarations. It's when you're trying to call a function but the function doesn't have any implementation associated with it. You didn't include the header or you didn't declare it. So it doesn't know where it is, and it doesn't know how the function is declared. It doesn't know the arguments. It doesn't know the return value. It has no information about the function itself. To solve this, always declare a function prototype at the top. Another warning, which is, it will say warning, control reaches end of non-void function. This will happen when a function has been defined as returning a result. It's non-void, but there's no return statement included in the function. So you forgot to return the data. Either the function is incorrectly defined, where you have to remove the data type before the function declaration, or you forgot to add that return statement. One or the other has to be changed in order to fix this warning. But you see how this is a warning. You can still compile it, but man, that could really cause problems in your program if you're expecting a function to return something and it doesn't. So you want to fix your warnings. Unused variable, another common warning. This is printed by the compiler when a variable is declared, but it's never used. You shouldn't be declaring a variable if you don't use it. So remove that declaration. I tend to get these quite a bit when I do some of my demos because I leave in variables that I never use. Or when I was demonstrating how to declare a variable and then I compiled it to show you that I compiled, I would get a warning saying it was never used. So that's okay because I was demonstrating something, but you remove your variables if they're not being used. No need to declare. Undefined reference to. This happens in the linking phase. So remember the compiler or the compilation phase, it will compile. First, it will run the preprocessor, then it will compile, it will generate the object files, and then it will take those object files and link them together to make a complete program. So during the linking phase, it needs to resolve any external dependencies, or specifically any functions that you're calling, they need to be implemented somewhere. So if it doesn't have that object file, it's going to give you this problem. You're trying to invoke a function, but we don't have the code for it. So you have to either make sure you link to this file. Usually the link will happen for you, but in GCC you can just do the -L option to add the linking file. So if you're using a function in the math header file, but you're not linking to the math object file, you're going to get this error. And it also happens if you have user-defined functions and you didn't include a C source file. So you have multiple C source files. One of the C source files is implementing this function. Another C source file is including the header and calling it, but you never compiled the other C source file that has the implementation. You'll see this error. So make sure you bring in that source file. Make sure you bring in any standard library source files if you need to explicitly. Usually you don't have to do that. Another common error, this is when conflicting types. This is when you actually have defined or declared a function prototype, and then when you went to implement it, it wasn't the same as how you declared it. So for example, the prototype has a result type, a name, a parentheses for the parameters, and then a semicolon. And then when you define the implementation, you have a different actual function header. You have a different return type, or you have a different number of parameters. And this is saying, well, hey, you have this one function declaration, and then when you go to implement it down below, it's completely different. So there's a mismatch. And this will actually show you on the line that the conflict appears in the previous definition that caused the contradiction. So in the implementation is usually where it shows you the line, because usually you declare your functions at the top. Runtime errors. Runtime errors are problems in your code that happen when you run the program, not when you compile it. So these are usually crashes or they're the non-fatal errors where you're array out of bounds or something like that. It's when the program is running, you have some kind of logic error. So the execution of C programs may terminate abruptly with a crash when a runtime error is detected, something it can't handle. There's a memory corruption, like I mentioned. Out of bounds errors usually cause programs to crash. Usually what you'll see is segmentation fault, and segmentation fault doesn't really tell you anything. So typically what you want to do to further diagnose this problem is look at the call stack, as I mentioned, or run a debugger and see what line of call before the program crashes, stepping line by line to see what line is causing the crash. You can get the call stack if there's a core file, which I mentioned earlier, and then from the call stack you can see what line is crashing. Or better yet, run the debugger, step line by line, and then when you execute a line, you'll see the program crash and you can identify it that way. So these are just, again, some more tips on compiler errors and warnings and messages and how to interpret them. There's actually links online, or if you do a Google, it will tell you every single compiler error and warning that can be produced. And it will actually give a definition of why this was produced it is, and why it was, what was the problem essentially. Because again, those compiler errors can be very cryptic. And if, even the one where it said unreachable control, you never know from that description necessarily, unless you had experience, that means, oh, you never return something from a function. But if you do, one of the best ways to find and fix problems in your program when you have compiler errors and you don't understand that compiler, Google it. And typically what will happen is you'll go to Stack Overflow and it will tell you, hey, this is your error, this is how you solve it. I do that to this day. I've been programming in C for 15 years, but there are still times when I encounter things and I'm like, what exactly does this mean? And I'll Google it. I'll actually take the compiler error, put it in quotes, and it will tell me exactly what's happening. Stack Overflow is a really, really good website. And it can really help save a lot of time in the debugging process. Don't just try to guess when you see compiler errors or warnings. That compiler is trying to tell you something, and it will pinpoint exactly what's going on. So if you understand it, you're going to be able to fix your problem much, much quicker. And if it's not something you're familiar with, go to Stack Overflow or go to a website that describes all of them, and you can decipher it that way. I hope this was helpful. Thank you. Hello and welcome back. We are in a new section. This section is named Pointers. This is probably the most important section of the course. It's also probably the most difficult section of the course. The concept of pointers in C is a tricky concept. But we're going to go through it really slow. We're going to provide a lot of lectures and go step by step. We're going to start at the highest level and then go into more and more detail. You have to understand pointers if you want to take full advantage of the C language. So it's very important. So let's start at the top and talk about this concept of indirection, which is essentially the same concept as a pointer. So pointers are very similar to the concept of indirection. You employ indirection in your everyday life. So for example, if I'm describing what indirection means, it would be like if you had to buy something new, a new product at your company. So for example, say you had to buy a new ink cartridge for your printer. If you were working at a large company, what you would probably do is you would have to go through a certain department to buy any new purchases. So you would probably go to the purchasing department. You would probably call somebody up in purchasing and ask them to order the new cartridge for you. It would be their job to then find a local store that provides the actual item that you want to order, okay? And what this means is you're not going and ordering that item directly by yourself. You're asking somebody to do it for you, and then through their expertise and their knowledge of who has that product in inventory, they get it back to you. So this is a level of indirection concerning you. You don't go ahead and just go down to the store and buy it. You go to the purchasing department. The purchasing department has the knowledge that it goes and does everything for you. This is the same concept of a pointer in programming. In programming languages, indirection is the ability to reference something using a name, a reference, or a container instead of the value itself. We use a form of indirection by using variable names. We do not use the memory address to access data. We use a variable name. The most common form of indirection is the act of manipulating a value through its memory address. So in addition to a really small description of indirection using a variable name to represent a memory address, you also manipulate a value through its memory address using the address itself. So a pointer provides an indirect means of accessing the value of a particular data item. It's a variable whose value is a memory address. And this is vital to understand. We have learned variables up to this point that contain certain types of data, numbers, characters, doubles, floats, with rational numbers. Now we're going to have a variable that doesn't store any of this type of data. The type of data it stores is a memory address. The memory address is going to be represented as an integer, a hexadecimal number, but it's still going to be a memory address. So it's going to be the value of an address in another location in memory if it's an existing variable, or a new location that you dynamically allocate. So just as there are reasons why it makes sense to go through the purchasing department to order new cartridges, You don't have to know which particular store the cartridges are being ordered from, for example. There are also good reasons why it makes sense to use pointers in C, to use these variables that represent an address, a memory address. We talked about memory addresses in the very beginning of the course, and how whenever you run a program and you create variables, those are stored in memory. And that memory has a particular address. You have to know the address to get that data back. Just like you need to know the address of a house if you're driving somewhere, or an address of a location. So using pointers in your program is one of the most powerful tools available in the C language. That's why it's important to understand. Any program in C that is substantive is going to use pointers. So you have to understand this concept. And for programmers out there that have programmed in more modern languages like Java or C Sharp, you don't necessarily have to worry about this because all the memory allocation and there's no real concept of pointers. Even though under the hood, Java uses pointers because they have copies of references. It's the same kind of concept, but in C you explicitly have a variable that represents an address. Pointers are also one of the most confusing concepts of the C language. They tend to be abused. They tend to not be fully understood, especially by new programmers. So it's important that you get this concept figured out at the beginning and have a clear idea of what is happening as you go into more and more advanced C and more advanced pointers concept. So if you don't understand this in the beginning, study. Practice writing code with pointers. The compiler has to know the type of data stored in the variable to which it points. So it's just like a regular variable, and that you have to specify the data type when you create the pointer. The reason the compiler needs to know this is the same reason for variables. It needs to know how much data to allocate, even if you're pointing to some data. Every pointer is going to be associated with a specific variable type. It can be used only to point to variables of that type. We'll give an example of this when we talk about defining a pointer. So for example, pointers of type pointer to int can only point to variables of type int. Again, a variable has a value of an address. That's a pointer. That address may contain a value somewhere in memory. Pointers of type pointer to float can only point to variables of type float. So here's an illustrative idea that gives you the concept of a pointer. Don't worry about the syntax here. We briefly discussed it in previous lectures, this ampersand and this asterisk. You don't have to necessarily worry about that. What I want you to pay attention here is how a pointer has an address. And that address can contain a value, but be somewhere else in memory. So in this example, we're creating a regular number. We've created 1,000,000 times. Then you see this syntax with the asterisk. That signifies that it's a pointer. We're going to go through that in details. You also see the ampersand, which signifies it's an address. So in this example, when we create this pointer of type int, p number, we're assigning an address. Because remember, pointers can only store addresses. And how this is actually laid out in memory is you have a variable named number. And number has a value of 99. Number also has an address in memory. That address in memory is the value of the pointer. So P number is a pointer that's pointing to address 1008. 1008 has a value of 99. It contains the variable number as well. So this is really what we're getting at. If this is not clear, you need to look at this for an hour and make sure you understand it. Again, the point is a pointer has a value to an address. That's what it stores. And then you can actually access the value in that address using certain syntax. So why use pointers? Why even broach this concept? Why can't we just use existing data types that we use and use the character array when we want to use strings? Well, accessing data by means of only variables is very limiting. With pointers, you can access any location. You can treat any position of memory as a variable, for example. And then you can perform arithmetic with pointers as well, which makes things easier. Pointers in C make it easier to use arrays and strings, and we're going to go through that as well. That's another advantage to use pointers. Pointers allow you to refer to the same space in memory with multiple locations. So what this means is you can update memory in one location, and then the change can be seen from another location in your program. It's a way of sort of using global data, but still having it encapsulated inside functions. You can also save a lot of memory space by being able to share components in your data structures. So remember, when C was invented in the 70s. The idea of C was to be very efficient and to be low level. The idea of accessing memory directly via pointers is very efficient. And it's also very fast. Pointers also allow functions to modify data passed to them as variables. This is passed by reference. We're going to have a lecture on this. This is where you can pass arguments to a function, which are pointers, and then inside the function, when you change that data, the change will be reflected outside that function. So we no longer have to use global data. We can use data inside of a function, pass that data as a pointer, and then that data outside that function will be allocated. So it's still it's not having the disadvantage of using global variables where everything is tightly coupled. You can limit that to only only the functions that need to know that data. As I mentioned, you can also be used to optimize the program to run faster and use less memory than it would otherwise, which is an important concept, especially in embedded and real-time programs. Pointers also allow us to get multiple values from a function. We've talked about functions and how you can pass data to functions. We've also talked about how you can return data, right? We know that right now you can only return one value from a function. But if you use pointers, you can actually return multiple values from a function. And we're going to talk about that. That's a big advantage. We're also going to talk about dynamic memory allocation. Right now, when we create memory for a program, it's done implicitly by the compiler when you declare a variable. If you declare an int variable, it automatically creates 4 bytes for that variable, for example. When you're using arrays and you specify the size of an array, that size is allocated at compile time. So if you're trying to store more data than that, you're screwed. Your program's not going to work. But if you had the ability to actually create as much memory as you needed at runtime, that would be huge. And pointers allow you to do this. They allow you to create memory at runtime, dynamic memory allocation. We're going to be talking all about this as well. Pointers allow us to design and develop more complex data structures. A data structure is something that stores data. Examples of data structures are stack, a queue, or a linked list. And we can create those much easier using pointers. Pointers provide direct memory access. Again, efficient, fast. So pointers are going to be a big concept. We're going to have a lot of lectures on pointers. I want you guys to focus and I want you to pay attention when I talk about all these concepts because it's important and vital to understanding the C programming language. So good luck and let's get started. Thank you. Hello and welcome back. In this lecture I want to talk about defining pointers, mainly the syntax for declaring a pointer and then using the address of operator to assign a memory address to a pointer. So up until this point, we should have it drilled in our head that a pointer is nothing more than a variable that points to a memory address or contains a memory address as its value. Okay? So declaring a pointer, it's not the same as creating a normal pointer. All right? So you can't do something like pointer. That's not the way to declare a pointer. The syntax is slightly different. You use an asterisk. So it's not enough to say that a variable is a pointer. You also have to specify the kind of variable to which the pointer points. Different variable types take up different amounts of storage. Some pointer operations require knowledge of that storage size. So just like a regular variable, when you specify a data type, when you create a variable of a pointer data type, you also have to specify that data type. You can declare a pointer to a variable of type int by doing the following. Int star or asterisk p number. That is going to tell you that that's a pointer. The int looks the same, but after that is the asterisk. The asterisk signifies that a pointer, and then you have to specify the type of the pointer itself. This is an int pointer. The type of the variable with the name p number is int star. It can store the address of any variable of type int. Right? A pointer stores addresses. So if you're going to store the address of another variable, that variable has to be defined as an integer type. So here, pi is pointing to int, to an integer variable. Char star pc, that's pointing to a character variable. Float star pf star pg, those are pointers to float variables. That's how you're defining them. Types matter. The space between the asterisk and the pointer name is optional. You don't have to put a space there. You can have no space. What ends up happening, and we're going to talk about dereferencing a variable, is you usually use a space in the declaration, and then when you're dereferencing, you don't use it. So all these declarations should contain a space by convention. The value of a pointer is an address. So it has to be represented internally as an unsigned integer on most systems. So it still has to store something. It just so happens that it stores a hexadecimal number. And even though it's storing it as it looks like an integer, don't think of it as an integer type. The same things that you can do with integers, you can't necessarily do with pointers, and vice versa. So even though if you try to print it out, it's going to look like a number, a hexadecimal number, it doesn't mean you can treat it like an integer. You can multiply one integer by another, for example, but you cannot multiply one pointer by another. A pointer really is a new type. It's not an integer type. The %p represents the format specifier for pointers. I'm going to go through displaying the different data for a pointer, and we'll see how that's used. The previous declarations creates the variable, but there is no initialization. There's no assignment there. You always want to assign a value to a pointer. It's very dangerous if you do not initialize that. So you want to initialize a pointer when you declare it. If you don't know what to initialize it to, if it's not another variable's address or you didn't allocate memory dynamically for it, you can use a null pointer. So you can initialize a pointer so that it does not point to anything. You do this using null. You say int star p number equals null for a pointer to an int. Null is a constant that is defined by the standard library. It's the equivalent of a 0 for a pointer. It means that it doesn't point to anything. It's guaranteed not to point to any location in memory. So this is good. You want to do this because what it means is you're not going to make any mistakes by accidentally doing any buffer overflow or writing to memory that you're not supposed to write to. By initializing it to this, it actually limits some mistakes that you can make. We talked about null a bit previously. We talked about the null character. That concept is different from the null pointer. A null pointer means it's not pointing to anything, and it should be initialized with that. You need to add an include directive for standard def.h if you want to use the null definition here. The address of operator. If you want to assign your pointer to some address, you can use the address of operator of an existing variable. So if you want to initialize your variable with the address of variable you have already declared, you use the address of operator, the ampersand. We've seen this when we've discussed the scanf function. Here we're assigning an integer value variable 99. We're creating a pointer of type int, and we're assigning it the address of number. We can do this because number is an int, and the pointer that we created is also pointing to an int. So all we have to do after the equals operator is use the ampersand. And so now p number is going to contain the address of number. The initial value of p number is the address of the variable number. The declaration of number must precede the declaration of the pointer that stores its address. Because you cannot assign to a pointer something that doesn't have memory allocated. If you try to assign to that pointer number, number doesn't exist unless you do it after. In order to assign an address to a pointer, that address has to have memory allocated for it. Otherwise, the compiler is going to complain. Be careful though, because there's nothing special about the declaration of a pointer. You can declare regular variables and pointers in the same statement. So you could say double value, p value, fnum. In this statement here, this is only the second variable, p val, is a pointer. The other two are just doubles. That's a little bit more explicit, a little more obvious in that declaration, but what if you say int star pq? This implies that they're both pointers, and they're not. We only have one int pointer here, that's p. The variable q is just of type int. It's a common mistake to think that both p and q are pointers. So be careful when you're declaring a pointer on many variables on the same line. It's also a good idea to use names beginning with p as pointer names. This will tell you that that variable is a pointer by just looking at it. So usually you do all your declarations of variables at the top of a program, usually inside the main function. And if you want to look at those variables, when you see those variables used later in the program, you can easily identify the different data types or the different pointer types because they have P as a prefix. So this lecture just went over how you can define, declare a pointer, and then assign an address of an existing variable to a pointer. Now there are cases when you don't want to necessarily assign an existing variable a value of a pointer. Maybe you want to allocate new memory. We're going to talk about those in the subsequent lecture. But right now we're going to keep it simple. We're going to focus on using pointers of type ints and different easy types like doubles or floats. And we're going to concentrate on assigning existing variables the address of and see how that works. So let's move forward. Thank you. Hello and welcome back. In this lecture I want to talk about accessing the value that a pointer is pointing to. So remember, pointers, they store memory addresses. That memory address actually contains a value of somewhere. And so pointers point to that memory address. I want to get the value of what it's pointing to. Because if I were to just print out the value of a pointer, that would be an address. But I want to get the address. I want to get the value of the address. So you can access the value of an address that a pointer is pointing to using the indirection operator. The indirection operator is the asterisk. So we learned how to use the asterisk to declare a pointer. We're also going to use the asterisk to find the value that a pointer is pointing to. So it's also referred to as the dereference operator because you use it to dereference a pointer. So for example, if you have a number it's equal to 15, you declare a pointer of type int pointing to an int, and you assign it the address of number using the ampersand. Now how do you get the value of what pointer is pointing to? Right? You can dereference it. You can basically, what the value that the pointer is pointing to is the value is 15, right? Because it's pointing to the address of number, which is 15. So the pointer variable contains the address of the variable number. You can use this in an expression to calculate a new value for the result. So say we wanted to do result equals the value that the pointer is pointing to plus 5. You would use the asterisk for it, right before the name of the pointer. And so what this would do is it would basically say, what is pointer variable pointing to? It's pointing to 15, add 5 to it. It's the address that the pointer is pointing to. What is the value of that address? So the indirection operator, asterisk, you should have noticed, is also the symbol that's used for multiplication, and it's also used when you declare pointer types, right? So this can get very confusing. How do you know necessarily what's going on, or how does the compiler work? Well, it's all about context. It depends on when you use that asterisk and where you use it. If you use the asterisk when you declare a pointer, right after the type of the pointer, then it's obviously using a declaration. If you use the asterisk in between two numbers, then it's being used for multiplication. And if it's used right before the pointer name on the right-hand side, for example, or the left-hand side, it's going to be assigning a value or accessing a value. So it's all about context when you use this indirection operator. Okay, and that's how it works. So that's how the compiler is going to interpret it. Whenever you see it in this example, star pointer, and you don't have a data type before it, or you don't have two numbers on each side, then you know it's an indirection pointer, a dereferencing. So let's go through an example. Here's another example where we're going to create an integer count equal to 10. We're also going to create an integer of type named x, another variable. We're initializing count to 10. X is initialized to nothing. We then create an int pointer. We know it's an int pointer because we have the asterisk after the data type. And then we named it int pointer. We're now going to assign to that int pointer the address of count. Because remember, pointers only contain addresses as their values. But they also are pointing to something. So we can then assign the variable x whatever int pointer is pointing to. What is the value of the address that is contained in int pointer? So x is going to actually display 10. So if we go ahead and display that, saying count %d IRD, x %IRD, count is equal to 10, x is going to equal to 10. That's how you can dereference a pointer and get the value that it's pointing to. If you want to display the pointer's values, because remember, a pointer has a value in memory. It's just an address. So what if you want to display the pointer's value, which represented by a hexadecimal number, an integer, or an address? Well, you can use the format specifier for %p. We talked about this before. This will output a pointer value as a memory address in hexadecimal form. So if we were to do something like this, where we declare our number, we declare our pointer, we initialize it to null, because that's good practice. We want to always do that. Whenever you're not assigning something in a declaration to the pointer, make sure you initialize it to null. We then assign our number variable 10, and then we assign our pointer to the address of number. So the value of p number is actually going to be an address. So if we were to try to print it out, we would use %p, and that would be the value of the address. If we wanted to print out what it's pointing to, we'd have to dereference it using the indirection operator. But when you print out the address, what it does is it prints it out in hexadecimal. And pointers occupy 8 bytes in memory, and addresses have 16 hexadecimal digits. So how does that work? Well, it depends on whether or not your machine supports 64-bit or 32-bit addresses. If your machine has 64-bit operating system, then you're going to see 16 hexadecimal digits. If your machine or your OS only has 32-bit addressing, then you'll see the hexadecimal represented as 8 hexadecimal digits. Now, what if you want to display an address? Right? And you may say, well, what's the difference? Because the pointer has a value, right? But you can also display the address with the address of operator. So in this example, we want to display the address of number. Number is not a pointer, right? Number is just an integer. If we want to get the address of that, we use the ampersand. If we want to display the address of that, you just use %p again. You just apply the ampersand. Right? So if we supplied the ampersand with the pointer variable, we would actually display the address of that pointer, not the value of the pointer. Remember, the address of the pointer is some address in memory. The pointer value is an address that it's pointing to, and the value that it's pointing to is somewhere else in memory. So remember that illustration where we showed how pointers work. A pointer, when you declare it, it creates memory for that pointer, 8 bytes. The value of that pointer is an address. And then whatever that pointer is pointing to is a value, usually of the type that you provided. But remember that there's really 3 parts of it. If you want to print out the p number's address, you again would use the ampersand. That would be the address of the actual pointer, and you would have to use the void star to get around a warning. So remember, a pointer itself has an address, just like any other variable. It gets allocated when you declare it. You use %p as the conversion specifier to display addresses. You use the ampersand, the address of operator, to reference the address that the p number variable occupies. Right? That's the address of the pointer. And then again, the pointer has a value of an address. The cast to void is to prevent a warning from the compiler. Specifically, the %p specification expects the value to be some kind of pointer type, but the type of ampersand number is a pointer to a pointer of int. And so you have to cast it. Displaying the number of bytes a pointer is using. Another way to get information about a pointer. Here you can use the size of operator. We've learned about the size of operator to display different data types, bytes. You can do the same thing with a pointer. On a machine that I'm running, this will occupy 8 bytes, and the machine address has 64 bits because it's a 64-bit operating system. And you can you may get a compiler warning when using size of this way. Size t is an implementation defined integer type. To prevent the warning, you could cast the argument to a type int like this. So what you would do is you would say p number size %d bytes, and you would say int, cast it to an int, size of p number. That's going to give you the size of the pointer in memory. Size of pointer of that address, which again is 8 bytes on most systems, because that's just containing an address. Another example here, this is going to display a number of things, and we'll run this example to show the output. But just before we run it, I want to describe a little what's going on here. We have a number that's declared. We have a pointer that's initialized to null. We set the value of number to 10. And then what we want to do is we want to print out the address of the integer number, and we want to print out the value of number. Very simple. Using the address of operator and then just the variable. When we do the address of operator, we do %p. We're then going to assign the address of number to our pointer. We're then going to print out some pointer information. We want to output the address of the pointer itself. We can just use %p, void star, ampersand number. We want to see how many bytes that pointer has in memory. We can say size of. We want to see the actual value of the pointer, which is an address. We can just say p number without any kind of extra information. And then we use %p. If we want to see the value that the pointer is pointing to, the value at the address, then we do star p number. We use the indirection operator. And we know that p number is pointing to an int, so we can say %d. So let's take a look at this example in code blocks to see how it's actually displayed. What we're going to see is some hexadecimal numbers for addresses whenever we display addresses, and we're going to see values in other cases. Okay, so this should look familiar. This is just a program that is showing you how to access different parts of a pointer. So again, we have a regular number data type int, and we have our pointer. We initialize it to null. We're first going to display our number, which is 10. So this is going to display the address of number. And then it's going to display the value of number on lines 10 and 11. We're then going to assign our pointer the address of number. If we want to see the actual address of our pointer, we just use the ampersand, the address of operator, and we cast it to a void star. We use %p. If we want to see how many bytes the pointer is in memory, we do %d, size of. If we want to see the address, the value of the pointer, we do %p and we just say p number, because p number is an address. If we want to see what the pointer is pointing to, where the value of the address that's in the value of pointer, we just say asterisk p number. We dereference it, the indirection operator. So let's run this. When I run this, hopefully we can see both. You'll see the first two things that are printed out, the number's address, which is on line 6, and that's some hexadecimal number, 0060FF0C. Right? And this is actually running a 32-bit program, so you see it's only 8 bits. We then print the value of the number variable, which is 10. We then print out the address of the actual pointer. It's allocated in memory. It's a different address than number, because this is the address allocated for the pointer. The pointer number size is 4 bytes, and that means it's a 32-bit addressing. The pointer's value, which is the address of number, it should be the same, and it is 0060FF0C. Right? And you see that you can actually get the number address by just using the name of the pointer with %p. Right? And we saw size of operator 4 bytes. If you want to get the value that p number is pointing to, which is 10, you have to dereference it using the indirection operator, and you see that it's printed 10. But you see you use %p whenever you're displaying addresses. You use the %d when you're displaying values of the integer pointer or the number of bytes. So this is the basic syntax of accessing pointer values. Address of pointer, ampersand, value that the pointer is pointing to, just the name of the variable, and so the value of the pointer itself is just the name of the variable. Then the value that the pointer is pointing to, use the indirection operator. Thank you. Hope this helps. Study this, run this through. Hello and welcome back. We have our first challenge for our section on pointers. This is going to be a challenge that gets you acquainted with the pointer syntax. Mainly you're going to create, initialize a pointer, assign an address to a pointer, and then display some of the pointer's values. So in this challenge, you're going to learn how to create, initialize, assign, and access a pointer. Creating the pointer is just declaring it. Initializing it will be you initialize it to null because it's not going to point to anything, and that's what you can do. Assigning it, you'll assign it the address of another variable, and then accessing a pointer is using the indirection operator, the dereference operator. So write a program that creates an integer variable with a hard-coded value. That's pretty easy. We know how to do that. And the reason you have to create the integer first is because that's going to have a memory location that you're pointing to. And once you have that integer variable created, you then want to create a pointer, initialize it to null, and then assign the address of the int to the pointer using the address of operator. Pretty straightforward. I want you to display as output the address of the pointer. The address of the pointer is just when you declare the pointer, the pointer has an address in memory. You'll need to use the address of operator to display the address of the pointer itself. Then I want you to display the value of the pointer. The value of the pointer is going to be another address. It's going to be the address of your integer variable. And then lastly, I want you to display the value of what the pointer is pointing to. Okay, the value of what the pointer is pointing to, you'll have to use the dereference operator, the indirection operator. These are the three things that a pointer can be equal to. You also have to understand what format specifier to use in each case. Typically, you'll use a certain format specifier for addresses, and then you'll use a different format specifier for whatever the pointer is pointing to. So this is a basic assignment to get you familiar with the syntax of a pointer and also understand the different values that a pointer can store. Again, mainly the address of the pointer itself, the pointer's value, which is an address to some other location, and then the pointer's value of what's pointing to from that address, which would be the value using the indirection operator. So good luck. I'll provide a solution to get you familiar with the simple syntax. Hopefully this won't take you too long, but it's a good little exercise to help you become familiar with pointer syntax. Thank you. Hello and welcome back. In this lecture, I want to provide a demonstration or solution of our previous challenge, which got you familiar with pointer syntax, the concept of a pointer, assigning an address to a pointer, and then displaying some output for a pointer. So let's bring up code blocks, and we're going to create a new project, a new C project that will just be called Pointer Basics, because it's going to do the basics of pointers. So we know how to do all of this. We're going to select console application, go, make sure we have C, and just call this Pointer Basics. This pointer concept is really, really important. So we're starting off slow and going on from there. So here we go. Here we have our main. Now all we want to do is we want to create one integer variable and then one pointer variable, and we want to initialize both. So the first thing I'm going to do is I'm going to create an integer variable, and I'm just going to name it number or num. And I'm going to initialize this, let's say, to 150. To create a pointer variable, we have to, and it's going to store an int, so it has to be the same type. To create a pointer, all you have to do is do the data type and then the asterisk in the declaration. And then we'll just call this pnum for pointer number. Usually you want to start your variables that are pointers with a p prefix. And it's a good idea to always, when you create your pointers, initialize them to null. Null is a special keyword that is saying that the pointer does not point to anything. Once we have both of our variables initialized, our num integer and our num integer pointer, we then want to assign something to our pointer, because right now our pointer is not pointing to anything in memory. And you want to make sure whatever you assign your pointer to, that actually has memory location for it, memory allocated. So in this case, if we're going to assign it num is an integer on line 6 that has memory allocated for it. C will automatically allocate memory for any variable declaration. Even this pointer on line 7 has memory allocated just to store a pointer. It doesn't necessarily mean it has memory allocated for what it's pointing to. But so to assign pnum a value of an address, all we have to do is say pnum equals ampersand, which is the address of operator, and we want to assign that the address of num. Num has memory already allocated for it when we declared it. So line 9 is just assigning the address of num to a pointer. It's as simple as that. Now, when you create a pointer and you assign an address to it, you could also create your own dynamic memory and assign that, but that's for another exercise. In this case, we already have our variable created. We're going to point to that variable's value. We need to assign the address of num. Now, after we've printed out, or we've done our assignments, we've initialized everything, now we just want to print out some information. So we're going to use the printf, and I'm just going to say, first I want to print out the value of pnum address. Not what the pnum value is for the address, but the pnum address. And here we can actually say the address of a pointer, so we're going to say p, and then all we have to do is put in here, we have to put in the address of our pointer. So here we would say address of pnum. And what is this going to give us? This is going to give us the address of the pointer that was allocated to memory. It's not the value of the pointer. The value of the pointer is also going to be an address. It's going to be the address of num. So here, let's first print out num as well then. So here we're just going to print out num address is, and again, we want to print out an address. So we're going to say %p, and then we're going to say the address of num. And the address of num should also match the value of pnum. The address of pnum will be different because that's the pointer in memory. So we're going to print out the value of pnum, or I should say the address of pnum. And then we're also going to print out the value of the pnum variable. And this is also going to be an address. And this is just going to be pnum. And then the last thing we want to display is we want to display what the value that pnum is pointing to. So the value of what pnum is pointing to. And this is actually going to be the type that what it's pointing to is an integer. So this would be %d. And let's actually add some line feeds so we can read this. And what it's actually pointing to, the way you get that value is the indirection operator. So you do the asterisk and then the pointer name. And that's going to tell you what the value is pointing to, which should be 150. Okay, so just to reiterate here, on line 11, we're printing out the address of num. That's going to be some number or hexadecimal number. Then on line 12, we're printing out the address of pnum, which was just allocated on line 7, because you have to store the pnum pointer somewhere. Then we print out the value of the pointer, which is just the address of num. Right? And when we print out the address of pnum, we have to use the ampersand. And then we print out the value of what pnum is pointing to, which is dereferencing using the indirection operator. So now let's go ahead and build this and run it, and we should see all these values. So the num address, just this number in memory, is 0060FF0C. The address of pnum is going to be something different, 0060FF08. The value of pnum, which is the address of num, should match the first line, and it does, FFOC. And then the value of what pnum is pointing to, which is 150. So a pointer really can have three values. Its address, the value of the pointer, which is another address, and then the value of what that address is pointing to. Right? And again, ampersand always gives you the address in memory. Pnum contains an address. You can print that out just by saying the name of the pointer. And then to get the value that it's pointing to, you use the indirection operator, the asterisk, and that will give you that value, which is 150. So these are the basics of pointers, getting you familiar with the syntax, when to use the address of operator and when to use the indirection operator, and then trying to explain just this concept of a pointer and how a pointer contains a value of an address. A pointer's value is an address. So play around with this, understand this syntax. Pointers are a really important concept. Thank you. Hello and welcome back. In this lecture I want to talk about the use case for pointers, when we're going to use them, how we're going to use them. We know how to create them, declare them, and define them. We know how to assign an existing variable's address to them using the address of operator. And we know how to dereference them, how to get the value that the pointer is pointing to. Now, how do we actually start using them? So C offers several basic operations that you can perform on pointers. You can assign an address to a pointer, which we've learned about already. This is an existing variable where the variable has an address, and you just look at that variable's address by using the address of operator, and we have it pointed to it. We could also assign an existing pointer to another pointer. That's two ways you can assign an address to a pointer. So it can be an array name by itself. We haven't talked about arrays yet, but when you assign arrays to a pointer, all you have to do is specify the name. You don't even have to use the address of operator. So far, we've just focused on using an existing variable and passing in the address of the variable itself. But the three ways you can do it are mentioned there. You can also dereference a pointer. We just learned about that. That's where you use the asterisk, the indirection operator. This will give you the value that's stored in the pointer to the pointer. the pointer's value, which is an address, what the pointer is pointing to. Just use that. You can also take a pointer address. This is the actual address of the pointer when you create the pointer, where the pointer itself is stored. You can use the address of operator on that pointer as well. And you can also perform pointer arithmetic. We're going to have a separate lecture on this. This is where you can use the plus and the minus operators to either add integers to a pointer or subtract integers from a pointer. And this allows you to have specific notation. It allows you to jump around in memory quicker, especially if you're using arrays. So what you typically do is when you add an integer to a pointer using the plus operator, it's going to just set the address of that pointer up so many bytes. If you subtract a number from a pointer, it's going to set that address and minus it a certain number of bytes. You can also increment and decrement by 1. And you'll see this is very common when we use it in arrays. So when you're in an array and you want to move to the next element, instead of using the index, you can use a pointer and just increment it by 1. If you want to move to the previous element, instead of using an index, you can just decrement a pointer by 1. So pointer arithmetic we're going to talk about exclusively, but that is something that you can do with pointers. And again, it's particular notation that allows you to move around quickly in memory, be more efficient. You can also find the difference between two pointers. So if you have two pointers and the elements are in the same array, you maybe want to find out how far apart they are. The elements, you can minus them. This would be the difference of two pointers. And so if you were index 5 and then you had a pointer pointing to index 5, you had another pointing to index 15, you could minus them and that would give you how many elements they're away, because it would be the hexadecimal address minus the other hexadecimal address. Assuming the array is in contiguous memory, which it is, it will display how far apart they are. You can use relational operators to compare the values of two pointers. Pointers have to be the same type. So if they're both pointing to integers, they both have to be the same type. This is just going to tell you whether or not the addresses are greater than or less than. Again, you could identify how far, which part of the array you're in. There are also two forms of subtraction. So I just talked about subtraction, where you can actually take one pointer and subtract it from another one, which you'll get a pointer. Or you can subtract one pointer from an integer, which will give you a pointer. Right? So subtract one pointer from another to get an integer, or to subtract an integer from a pointer to get a pointer. Those are the two cases. So we'll keep in that mind. We'll go through some more examples. Be careful when you use the incrementation or decrementation of pointers in causing an array out of bounds. So most of this stuff that you do with pointer arithmetic is when you're operating on arrays. Because again, it allows you to move quickly. It's simple syntax. But remember that arrays have an out of bounds error. So if you increment too far, you're going to go out of bounds in the array. If you decrement too far, you're going to have an under bounds. You go into a negative number. The computer itself is not going to keep track of whether a pointer still points to an array element. So using the pointer arithmetic on arrays, you got to be careful. If you want to pointers used in expressions, you can also do that. So we talked about this a little earlier, and we dereferenced the pointer and we added 15 to it. I think we got 20. So the value referenced by a pointer can be used in arithmetic expressions. So if a variable is defined to be of type pointer to integer, then it is evaluated using the rules of integer arithmetic. And we showed that with the dereference. So if you have a variable and you have a pointer, you initialize it to null, you then sign your pointer that variable's address, you then can just say star p number plus equals 25. Remember, star p number is getting the value that's pointing to. So what this is doing is it's saying the value of p number equals the value of p number plus 25. Right? So the value is going to be equal to 35. This is not changing what it's pointing to because we're using asterisk. So it's not changing the address that we're pointing to. It's not changing the address itself because we don't have the address of operator. We're changing the value that it's pointing to. So incrementing the value of the number variable by 25, the star indicates that you're accessing the contents to which the variable called p number is pointing to. If a pointer points to a variable x, that pointer has been defined to be a pointer to the same data type as x, right? So if you create an int pointer, a float pointer, you can only have an address of a data type that is float or int, depending on which one you declared. So the use of the indirection operator in an expression is identical to the use of the x in the same expression. And that's all it's saying is if you use a float or you have an int and you use the indirection operator, you dereference it, you can do whatever you can if you had a float or an int, whatever it's pointing to. A variable defined as a pointer to an int can store the address of any variable of type int. We know that. So here, int value equals 999. We can assign that int to p number as long as p number is a pointer to an int. And then we can add to it. This statement will operate with the new variable value. That's the new variable value, and the new constant's value will be 1024. Right? P number is pointing to value, the address of value. So if you change the pointer is what it's pointing to value, you're going to change the value of this variable value. So just remember that. This is the concept of changing a variable in one spot, the pointer, and you're changing it in multiple variables. A pointer can contain the address of any variable of the appropriate type. So you can use one pointer variable to change the values of many different variables if they're ints, or doubles, or floats, as long as they are of the type compatible with the pointer type. You can change that value. You can't change p number's value if p number is pointing to a float and the value is an integer. You wouldn't be able to do that. You would have a compiler error. Another example here. Here we're going to show you how to get the address of some variables. So here in this main, we're doing some pointer arithmetic on the actual expressions. So we're not doing anything on array, so we're not incrementing or decrementing pointers necessarily, we're decrementing values. So we have two long types, num1 and num2, and then we have a pointer of type long. We initialize it to null. We assign the address of num1 to our pointer, pnum, and then we assign the value of pnum 2l. So that means num1 is now going to be 2l. If we increment num2, now num2 we're not actually, haven't done anything to yet. So pnum, value of pnum is 2l, that means the value of num1 is 2l. L is just a suffix to signify that it's a long. If we now increment the long num2 value, it's 0l, it's going to be 1l. If we say num2 plus equals star pnum, pnum is 2l, so it's going to be 1l plus 2l, num2 is now going to be equal to 3l. And then if we assign the address of num2 to pnum, pnum is now going to be equal to the address of num2. So if we increment pnum, what we're pointing to, we're now going to have 4l. Right, and we'll look at this inside of code blocks, but I'm walking you through it. Num1 is going to be equal to, I think, 2l. Num2 is going to be equal to, it's pointing to pnum. Pnum's 3l, so I think it's going to be 3l. Pnum is going to be 3l, and then pnum plus num2 is going to be 6l. So let's see if I'm right. Let's go through this in code blocks. So here we are in code blocks. Tried to go through this by hand, but now we want to see if we're right. And we could actually use let's use the debugger. We'll put this right here and we'll see as we go through the program how values are changing. So let's build this and let's debug it. This is going to start up and it's going to stop at line 10. And if we bring up our watch window, which we can do by going to debug in Windows watches, we can see the values as they're going. So right now, num1 is 0, num2 is 0, pnum is pointing to null. That's why it's 0x0, because we know that null represents 0 in pnum, and we can use that when we compare it in if statements. So after we execute line 10, pnum should now have the address of num1. So let's just step over. Now pnum has an actual address, 0x60ff08. After we execute line 11, we're going to say the value of pnum is equal to 2l. And we're not going to be actually see anything in the watch window for that, but let's go ahead and execute it. Pnum still has the same address. Num1 is now changed though, because pnum had the address of num1 and we changed it. So now num1 is 2. Now in lines 12, we're going to increment num2. So num2 is just going to become 1L. Right? It's going to be 1. The address of pnum is still the same. Now we're going to add to num2 whatever pnum was. Pnum, remember, is pointing to num1, so it should be, num2 should be 3. Now we go to 14, num2 is 3, num1 is still 2. Now in line 15, we're going to assign pnum a new address of num2, so after this, we're no longer going to be 0x60ff08, we're going to be 060ff04. So now if we increment the value that pnum is pointing to, which is number 2, and number 2 is 3, number 2 should now be 4. And we see it's 4. Now we're going to print out all these values, and you're going to see the value of num1 should be 2. The value of num2 should be 4. Pnum is pointing to num2, so that should be 4 still. And then we're going to say the value of pnum, which is 4, plus num2, which is 4, should be 8. So I might have actually been off with 6. So now we won't be able to see that in the watch window, so let's just play it and see the output as printf statements. We should see 2, 4, 4, 8. So let's run this now in non-debug mode. And we see 2, 4, 4, 8. So there we go. I hope that made sense. Let's go back and continue our discussion. So how about when we receive input? How can we use pointers in that way? So far when we've used scanf to input values, we have to use the ampersand operator whenever we have an int or a float data type. The only time we haven't is when we had a character array. And the reason for that is because the character array actually is a character pointer, which we're going to talk about. But if we use scanf to input values and we use them on normal data types that aren't character arrays, we've always had to use this address of operator. Right? And the reason for that is scanf's second argument is a pointer. So we have to send it an address. Pointers only have values of addresses, right? So when you have a pointer that already contains an address, you can use the pointer name as an argument for scanf. So now you don't have to use the ampersand operator if you're actually created a pointer, because the second argument to the scanf is a pointer. And so you can just say the pointer name. So here, in the past, we've always, if we want to store a value in value, we would have to say ampersand value in the scanf second argument. But if we have a pointer that we create and it already points to an address, as it does in this example, then when we use scanf, all we have to say is the name of the value, the name of the pointer. So here's a case when we have an integer, but we don't have to use ampersand because we have a pointer to an integer. We just say %d, p-value. So there are other times when you can pass in regular names of variables to scanf besides character arrays, if you have a pointer. You can also print out what they entered afterwards, and you will notice that value is actually going to be changed to whatever they entered because we're pointing to that address. Testing for null. There's one rule that you have to burn into your memory. This is very, very important. We talked about dereferencing, but what happens if you dereference an uninitialized pointer, a pointer that's pointing to nothing, or a pointer that doesn't have memory allocated for it? So what if we do something like this? We declare a pointer, but we've never actually initialized it, and then we try to assign to it. We dereference it and assign to it. That's a big mistake. So the second line basically means that you want to store the value 5 in the location to which PT points to, but PT doesn't point to anything because it hasn't been initialized. So PT is now going to have a random value. So there's no knowing where 5 will be placed. It could be placed anywhere in memory. This might be harmless. It might overwrite existing data or existing state variables in your program. It might cause the program to crash. It's very problematic. So when you create a pointer and you allocate memory to store the pointer itself, it does not allocate memory to store the data. Right? So by saying int star PT, that allocated memory for the pointer, but it didn't allocate any memory for the value of the pointer, the address. Remember, pointers contain addresses. It created the pointer, but it didn't create any memory for what it's pointing to. Right? So you can't dereference it. So it does not allocate memory to store the data. Before you use a pointer, it should be assigned a memory location that has already been allocated. Right? Or you have to use dynamic memory allocation using malloc, which we'll talk about. So you either assign the address of an existing variable to the pointer, or you use malloc, which is dynamic memory allocation. But keep that in mind. Whenever you use a pointer, if you created it and it was null, you want to check it for null beforehand. We'll talk about that in a second. But if you created a pointer and wasn't initialized, do not assign anything to it unless it's either pointing to another variable initialized that way or having memory allocated. So this is where null comes into play. You can actually test for null to make sure you don't have a dereferencer or make sure your program doesn't crash. So we already know that null basically points to nothing, and we should initialize all of our variables, our pointers, to null. So we should always do something like this. Null is a special symbol in C that represents the pointer equivalent to 0 with ordinary numbers. The below also sets a pointer to null using 0. So we can also, if we don't want to pass it or assign it to null, we can just say 0, and that's the equivalent of saying pointing to nothing. So because null is the equivalent of 0, if you want to test whether p-value is null, you can do something like using an explicit test. You can say pointer equals null. And if pointer is equal to null, meaning it's 0, then you can actually do something. So if it's not 0 or not null, it's 1, true, or any other value, that's a way to check against having crashes. You make sure before you actually try to dereference something that this will tell you whether or not it has memory allocated. So you want to check for null before you dereference a pointer. And you often do this in functions, because functions will take pointers as parameters. And if the caller is passing in bad data or passing in a pointer that doesn't have any memory allocated, it could crash your code. So what you want to do is you want to make sure that the caller has a valid address so you can check it for null. Basically what this means, always to have these if checks to say not p-value or not pointer. And if it's not pointer, then you can dereference it. We're talking a lot about pointers. We've discussed quite a bit. I'm sure it's getting a little overwhelming. You may want to take a break and go through the previous lectures. Try to really sink this concept into your head. Pointers just contain addresses, but there's 3 parts to it, so it can get problematic. But stay positive. Keep with me. And I know it's confusing. You know, we've talked about working with addresses. We've talked about working with values. We've talked about working with the pointer itself. And we've talked about working with variables that point to pointers. So there's all this stuff you got to remember. And it can be very, very overwhelming and frustrating. And it's always hard to try to figure out what's going on, and it's going to take a lot of practice. The best way to understand this concept and everything we've talked to up until now is to practice. Write short programs that use all the concepts I've mentioned. So write a program that gets the values using a pointer. You know, this would be maybe using the indirection operator, dereferencing. Write a program that changes values using pointers. So this would be dereferencing. Getting the values using pointers would just being the name of the pointer, which would be the address. Printing addresses. We've looked through all of that syntax. Practice this stuff over and over and over again. That's how you're going to get good at it. You have to get your confidence up, and you have to study these concepts in detail to master them. We still have a lot more to talk about pointers, but this may be a time to just step away and go over what we've talked about so far so that it's drilled in your head. Thank you. Hello and welcome back. In this lecture I want to talk about the const modifier and how we use it with pointers. We've learned about const in previous lectures. It just means you can't change the value of a variable, but what does it mean when we apply it to a pointer? So when we use the const modifier in a variable or an array, it tells the compiler that the contents of the variable array will not be changed by the program. Right? We can also remember the alternative was to create define statements by the preprocessor, but const is usually a more efficient, better way to do it. With pointers, we have to consider 2 things when using the const modifier. Are we actually saying that the pointer cannot be changed, or are we saying the value that the pointer points to cannot be changed? Right? Because remember, a pointer contains a value of an address. And we may not want to change that address ever. Or we may not want to change the value that the pointer is pointing to. In either case, we have to be specific in our syntax. So you can use the const keyword when you declare a pointer to indicate that the value pointed to must not be changed. The way that you provide this, and again, so the pointer is a value, as a value has an address. What it's pointing to is the value of that address. If you want to have that not change, you would do something like this. You would say, when you declare the pointer, you would put the asterisk in the constant modifier before the type. So you would say constant, whatever the type of your pointer is, asterisk pointer. So this is actually defining a pointer to a constant. We're not going to be able to change 999L. So we declared that the value pointed to by the p-value to be constant. The compiler will check for any statements that attempt to modify the value pointed to by the p-value. And if there's anybody that does in the program, it's going to throw an error. So this is the syntax. Again, to know what you want to notice here is the constant is the first word. And it's before the type. So that's saying that the value pointing to cannot change. So if you try to do something like this on p-value, you try assigning a value to what's pointing to. You see the indirection operator there. That means we're assigning a value to what we're pointing to. If we try to do that, it's going to give an error because we can't change that value. We can't change 999L to 888L. So now what about pointers to constants? And in the previous declaration, we created the pointer that the pointer is pointing to cannot change, but we can still change the actual value of the variable that we declared, right? So we would still be able to change long value. We just can't change star p-value. But long value is defined, it's not defined as a constant, it's just defined as long value. So we can still modify the value integer pointer because it didn't have constant applied. We only applied constant to the pointer. So we can say value equals 777L. The value pointed to is changed, but you did not use the pointer to make the change. The pointer itself is also not a constant. The pointer, remember, it contains an address. We didn't declare the pointer to be a constant. We declared the pointer, what the pointer is pointing to be constant. So we can still change that as well. So if we declared a new variable called number, we can say p-value equals the address of that number. That's perfectly fine because we're changing the address of the value of the pointer. We're not changing the value of what the pointer was pointing to. So understand this distinction. Either changing the value of the pointer, which is just an address, or changing what the pointer is pointing to. If you don't want to change what the pointer is pointing to, const has to be that first keyword in the declaration of the pointer itself. So again, in this example, we're going to change the address stored in p-value to point to a number. We still cannot use the pointer to change the value that is stored because that was declared as, we can't change that value. You can change the address stored in the pointer as much as you like, just like we did. Using the pointer to change the value pointed to is not allowed even after you have changed the address stored in the pointer. So even though we just changed it to long number, the pointer still had constant as the keyword. So we can't change the value to no matter what the pointer is pointing to. What about not allowing the address of the pointer to change? The value that's in the pointer. So you also may want to ensure that the address stored in the pointer cannot be changed. You can do this by using the constant keyword in the declaration of the pointer the same way, but it's slightly different. Instead of having const as the first keyword, you put it after the data type and after the asterisk. This is saying that the pointer itself cannot change its value. If you put it before the int, you're saying the value pointed to by the pointer cannot change. So when you do this, it ensures that the pointer always points to the same thing. The address will never change. The compiler will check that you not inadvertently attempt to change the pointer elsewhere in your code. You can't change this address. So if you tried to say pcount equals and item, you would get an error because that can only ever point to the count address. It's all about where you place the constant keyword if you want to change, if you do not want to allow the pointer to the pointer to change, or if you do not allow the address of the pointer to change. Constant as the first keyword doesn't allow the value that the pointer is pointing to be changed. If you put the constant after the data type and the star, that's saying the pointer address can't change. So that's a lot to take, and that's very confusing, so study what I just said. Understand that syntax. It's very important. And it's very tricky. It can be easily make that mistake, so understand the difference. You can still change the value that pcount points to using pcount. just like we could in the previous one, because pcount is even though we can't assign it a new address, we can still change the value that's pointing to. So we can dereference it and change it that way. We can say star pcount equals 345. That's fine. References the value stored in count through the pointer and changes the value to 345. You can create a constant pointer that points to a value that is also a constant. So you could do something like this, constant int star constant p item. And that's saying that the pointer itself, what the value is pointing to is constant, and the pointer itself is a constant. So p item is a constant pointer to a constant, so everything is fixed. You cannot change the address stored in p item, and you cannot use p item to modify what it points to. However, you could still change the item. Item is not a constant, so you could change item. You can change the value directly. If you wanted to make sure nothing was changed, you'd have to actually create the item int variable as a constant as well. And then that would say it's never going to ever change. But remember the difference here between constant pointers and constant values that the pointer is pointing to. You can use both. You can use one or the other. If you wanted to ensure that everything's constant, make sure what you're pointing to, that variable is constant as well. Thank you. Hello and welcome back. I want to talk a little bit about void pointers in this lecture. We know what void is because we've used this keyword when we've talked about functions. Mainly if we don't want to return any data from a function, we use the void as part of the function signature. But what about when we use a void pointer? What does this mean? Well, the type name void means absence of any type. So a pointer of type void star can contain the address of a data item of any type. So it has a lot of flexibility. If you don't know what you're going to store as a pointer, you can say void star. Pretty nifty. It's usually used in functions for function parameters. So void star is often used as a parameter type or a return type with functions that deal with data in a type independent way. So you can allow your function to be more flexible if it takes void star pointers. It basically means that your function can take more than one type of variable, except it's not completely flexible because you have to cast it some way when you dereference it. So any kind of pointer can be passed around as a value of type void. Any type. The void pointer does not know what type of object it is pointing to, so you cannot dereference it directly. And that's where the real hiccup comes along with the void star. It's great for allowing flexibility for different data types, but you can only use it if you know the data type. So you have to provide an explicit cast to the pointer when you dereference it. The address of a variable of type int can be stored in a pointer variable of type void, because void star means that any type of data can be stored inside there. So when you want to access the inner value at the address stored in the void star pointer, you have to first cast it to a pointer of type int. Okay, so what in this example here is we're going to see how you use the void star pointer. We have three variables we defined, an integer and a float and a character. We're now going to create a void star pointer. Because the pointer is of type void, we can assign it the address of I, which is an int. We can assign it the address of f, which is a float. And we can assign it the address of character, or ch, which is a character. The only problem is when you dereference it, you have to know that type. But you still see the advantage here. The advantage here is we only have to create one variable type, and we can store multiple different addresses in it. But whenever you want to use it, you have to use that int star. And you'll see here when we're printing out the data that the int star is casting the pointer, and then we're dereferencing it. The star outside the int parentheses is dereferencing. So that's going to print out the value that v pointer is pointing to. But first, it's going to cast it to the right type. So in all three of these v pointers, it's going to print out for the int, it's going to print out 10. For the float, it's going to print out 2.34. And for the ch char, it's going to print out k. We'll see the void pointer used more in function parameters, like I said, in return types. And that's really the value when it comes into it, as well as only using a void star pointer in one declaration and assigning many different data types. Thank you. Hello and welcome back. In this lecture, I want to talk about the relationship between pointers and arrays. There is a strong relationship, And we need to understand this relationship before we can actually talk about pointer arithmetic. So let's get started. An array is a collection of objects of the same type that you can refer to using a single name. We know that. We're pretty good at arrays by now. We've been using the character array for a few sections now. It's an array you can access by using an index or a subscript inside those brackets. We remember that. We know that arrays are zero-based. They start at 0. But again, it's just a way to hold multiple elements with the same variable name. A pointer is a variable that has its value, a memory address, as its value. And it can reference another variable or constant of a given type. We also should at this point be pretty clear on what a pointer is. It just holds a memory address. You can use a pointer to hold the address of different variables at different times, but you have to have the same type. An int pointer has to point to or store the address of an int type. Arrays and pointers seem quite different, but they are very closely related and can sometimes be used interchangeably, especially with the character array. You can actually create a character array, remember, which is a string, and you can create a character pointer, which are essentially the same thing. There's only slight differences, whether or not you allocate memory and free it with a character pointer. With a character array, you don't have to do that. But a character array is also fixed size. So if you create a character array string with 20 as its size, you can only store 19 characters. With a character pointer, you can use dynamic memory management, and you can have the size increase or decrease. It can be more efficient concerning memory. But one of the most common uses of pointers in C is as pointers to arrays. This is when you really most often use pointers, especially to characters. A character pointer is the same as a character array. The main reasons for using pointers to arrays are ones of notational convenience and of program efficiency. So you can use either one, an array or a pointer in many cases, except when you're talking about dynamic memory management. But in most cases you can, and really the only difference is its syntax. It's the notation. It's whether or not you use a subscript to access an element or whether or not you use pointer arithmetic, whether or not you use the character pointer to point to the specific address of that element. It's also more efficient to use character pointers as well. Pointers to arrays generally result in code that uses less memory and executes faster. So you want to use a pointer for characters as much as possible, and a pointer to other data types as well, because it is faster and less memory. Use pointers over arrays for the most part. If you have an array of 100 integers, we know what this means. You just say int values 100. 100 is the size. That means you can store 100 integers in that array. You can also define a pointer. We're going to name it values pointer since it's pointing to the values array. And it can be used to access the integers contained in this array. So we just say int star values pointer. We know how to declare a pointer at this point. When you define a pointer that is used to point to elements of an array, you do not designate the pointer as type pointer to array. Right? Up until this point, all we've ever heard about is pointer to int, pointer to double. Right? But when you're using arrays, you don't say pointer to array. That actual pointer is pointing to a specific element contained in the array. So keep that in mind. It's not actually an entire array when you declare a pointer with the address of values. So to set the values pointer to point to the first element in the values array, all you have to do is say values pointer equals values. You don't have to put the address there or anything because values array is a pointer. That's what you have to drive in your head, is all these arrays are pointers underneath the hood. So if you want to assign the first element of an array to a pointer, all you have to do is specify the array on the right hand side of the equals operator, and on the left hand side you just have the values pointer. This is going to point to the first address in the array, or the first element. The address operator is not used. Notice that. The C compiler treats the appearance of an array name without a subscript as a pointer to the array. So specifying values without a subscript has the effect of producing a pointer to the first element of values. And so what this means is you can now point to subsequent values in the array by just incrementing the pointer to go to the next address. And that's what we're going to talk about in the next few lectures when we talk about pointer arithmetic. And it's really just a notation thing, and it's also an efficiency thing. So an equivalent way of producing a pointer to the start of values is to also apply the address of operator to the first element of the array. So you can do it two ways. Either way is fine, but you could also do this. You could say values pointer, address of, value sub 0. That will set the values pointer to the first element in the array. So you can use this one, or you can just say values pointer equals value. Obviously, without the ampersand and without the subscript, it's a little more less code or easier to write. This may be a little more clear because you don't necessarily know that values is an array unless you look at the declaration. But again, either way is fine. Values pointer equals values, or values pointer equals address of value sub 0. It's a matter of programmer preference, and again, it's a notational thing. So just to reiterate, when you have two expressions, AR sub I and asterisk AR sub plus I, those are equivalent in meaning. Right? So we just want to make sure that you understand this. Both work if AR is the name of an array. You can use the pointer and you can dereference it. And both work if it is a pointer variable. Use an expression such as AR++ only works if AR is a pointer variable. So you can't increment an array by saying plus plus and expect it to go to the next element. You can only do that on array pointers or pointers. So if we have AR that's a pointer pointing to array and we want to go to the next element, we can just increment it every time. But if you say AR sub I, because AR sub I is an array and an array is a pointer, you can dereference it by saying AR, which is AR is a pointer, we've assigned, AR plus I. It's the same thing. So in the next few lectures, we're going to talk about pointer arithmetic, and this strongly relates to the relationship between arrays and pointers. Pointers can be arrays. It's not a pointer or array, it's an element. So you can use the address of a pointer to navigate through an array, iterate through an array. Thank you. Hello and welcome back. In this lecture I want to talk about a concept called pass by reference. When we first started talking about pointers, I mentioned one of the advantages is you don't have to use global variables as much, because when you pass a pointer to a function, the function can use that parameter, and when it modifies that parameter, the data will be modified outside the function. Right? So this is a valuable concept. We're going to talk about this. This is more of a concept. C actually doesn't employ this, and I'm going to show you how and give you some examples, basically how this works. So there's this concept of pass by value. This has to do with functions. We talked about passing data to a function, but how is it actually passed in terms of the language and the compiler? So there's a concept of pass by value, and this is what we've been talking about up until now. Whenever we call the function, besides the scanf function, but every other time we've called the function, we haven't been when you modify that data inside the function, it didn't get modified outside the function. Right? So we talked about local variables. That's kind of a different concept. But when you pass data to a function, there's two ways you can pass it. You can pass it by value. You can pass it by reference. Okay. C does exclusively passing by references, or passing by value. I'm sorry. And so does Java, all by pass by value. But it simulates pass by reference because you copy addresses. And so even though this concept of pass by reference is not specifically employed by C, it simulates it. And so to understand what pass by reference means and why that's important, we're going to talk about that. But pass by value is when a function copies the actual value of an argument into the formal parameter of the function. And this is why if you have an integer, a float, or a double, and you pass that in as an argument to a function, that actual variable doesn't get modified outside the function because it's copied. So changes made to the parameter inside the function have no effect on the argument. The argument being passed in, does not get modified. Right? So it almost acts like a local variable because it's a copy. How it's actually happening under the hood is it's being copied and passed to the function. C programming uses call by value to pass arguments. Everything is call by value, pass by value. These are used interchangeably, these terms. So again, this means the code within a function cannot alter the arguments used to call the function. There are no changes in the values, though they had been changed inside the function. It seems like they're local variables. And that's why earlier up until this point, when you created global, you got to create global data if you wanted to share the data from one function to the next. Right? And this is how C works. But what happens when you actually pass in a copy of an address? Well, then it can mimic pass by reference. But here's an example of how we've been using pass by value. It's demonstrated very nice here. This swap routine is an often used case to demonstrate pass by value because what it does is it creates a temp and it swaps the parameters, the arguments that are being passed. So if we have a function called swap that takes two integers, we create a local variable temp. If we assign to the parameter x to temp, temp is going to be equal to x. If we say x is equal to y, y is now going to be equal to x. If we say y equals to temp, y is going to be equal to temp. Right? But when we actually call this, when we call this function, passing those values, x and y is going to be local to this function. Those variables are not going to be modified outside this function. And this function demonstrates it very useful because we're assigning to y and we're assigning to x. And x and y is local to this function because we're passing by value. They do not get modified outside this function. And that's why we have to use global variables. But they're integers. They're two integers, x and y. They're not addresses. They're integers. And that's significant. So if we call swap and we see what this is looking like, you're going to notice that the values do not change. So if we create a variable called A100, B200, and we print out the variables before we swap, 100 and 200, then we call swap, the variables are not going to be changed after we print them out again. So let's look at this in code blocks, and this will demonstrate pass by value. Okay, so here's our example. We have our swap routine. We're swapping values of data that's passed, x and y. We're calling it with 100 and 200. We're going to print out before we call the function. We're going to print out after. And what you'll notice is the variables a and b never change. And the reason for this is because we're doing pass by value. So if I run this program, we can see that before swap the value of a was 100, after swap the value of a was 100, and the same for b, 200 and 200. And the reason for this is because we pass by value. If we pass by reference, those variables a and b would change after the call to swap. Now how about if we employ this same technique, pass by value, but we copy pointers? What do you think is going to happen? So pointers and functions get along quite well together. You can pass a pointer as an argument to a function, and you can also have a function return a pointer as its result. And we're going to show how to do that as well. But pass by reference copies the address of an argument into the formal parameter. The address is used to access the actual argument used in the call. So what this means is the changes made to the parameter inside the function affect the argument, the variable that's in the call. And so even though it's not technically under the hood pass by reference, it mimics or simulates pass by reference. We're copying the address. If you copy the address, you have a new address in memory for that value, the address. But if you try to assign to that address, it's going to assign to the address. Okay, so even though it's passed by value, it's copying. And if you're copying a regular integer, you don't make changes. If you're copying an address, the address is in memory, so when you make changes, you're going to make changes to that address. So to pass a value by reference, argument pointers are passed to the functions just like any other value. You need to declare the function parameters as pointer types with the asterisk. Changes inside the function are reflected outside the function as well. You don't have to use global variables as much. Unlike a call by value where the changes do not reflect outside the function. We're still copying, we're still passing by value, it's just the value of a copy of the address. Okay, so this is an important concept to understand. Now, when we create our swap function, we're going to create it with the declaration inside the function as asterisks, star and star. That's saying that this function takes pointers. Now, when we assign inside this function, we have to actually use the indirection operator to dereference because we want to assign the values. We're going to assign the value of x that x points to temp. We're going to assign the value that x points to the value that y points to, and then we're going to assign the value that y points to temp. Temp is an integer, so we don't have to dereference it. Now, when we invoke it with A100 and B200, by passing in A and B are not pointers, so we have to pass in the address. right? Because the function takes pointers. Whenever you have a function that takes pointers and you don't declare a pointer, you have to use the address of operator. And it's the same thing as how we use scanf. But now you're going to notice when we invoke this, after the call to swap, the variables A and B are going to be changed. They're going to be swapped. A is going to be 200, B is going to be 100. So now let's look at this example with our swap method changed to pointers in code blocks. Okay, we're in code blocks. We modified the swap function to take pointers. So we have to dereference them when we assign them. We also now pass in the address of A and B because these are now integers, and the swap now takes pointers. So when we run this, we're going to see that the call and after is now going to be changed. So now before we call swap, A is equal to 100. After we call swap, A is 200. Before we call swap for B, it's 200. Afterwards, it's 100. So we're able to change the values of variables inside the function because we're making a copy of the address. Very, very important. And one of the big advantages of pointers. So let's summarize the syntax. I kind of already did, but let's go through it in more detail. You can communicate two kinds of information about a variable to a function. You can transmit the value of x, and the function must be declared with the same type as x. Right? We know that. Whenever we pass data to a function, we have to have the same types when we call it. And here we have int function1 to invoke it, and it's defined as an int num. So when we transmit the value of x in the function, they have to be declared with the same type. And then if you want to actually invoke an address of x, it requires the function definition to include a pointer to the correct type. So whenever you use pointers, you have to make sure that if you're passing in data and that data is not a pointer, you have to get the address of it. Again, what this is summarizing is if you define a function that doesn't take a pointer, you can just call it and pass in the data. Make sure it's not a pointer. If you have a function that does take a pointer, int asterisk pointer, when you invoke it, you have to invoke it with the address of operator. You have to pass the address in. That's the syntax. Now you can also qualify a function parameter using the constant keyword. This indicates that the function will treat the argument that is passed in for this parameter as a constant. It's only useful when the parameter is a pointer, right? Because if you're passing by value and you're not passing in pointers, it doesn't matter because you change it, it's not going to affect the change on the outside the function. So why would you make it a constant? Who cares if you change it? The only reason you make a pointer a constant is because you don't want to have outside the function values changing. And so you can apply the constant keyword to a parameter that is a pointer to specify that the function will not change the value to which the argument points. Very important. So in this example, we have a send message function. It takes a p message pointer. We put the constant keyword before the char star. So this type of parameter, p message, is a pointer to a constant character. It is the character value that's constant, not its address. So in this case, what we're doing is the pointer that's being pointed to cannot change. We can change the address, but we can't change what it's pointing to, the value. The syntax is similar to when we create constants on other pointers. The constant keyword is it's the first thing showing, then you can't change the value. Now you could specify the pointer itself as constant, but this makes little sense because the address is passed by value. You cannot change the original pointer in the calling function. So this is just like if you tried to make it so that the address couldn't be changed, well, what's the point? Because it's passed by value. So you're actually making a new memory location to hold that specific address. So if you change it, who cares? It's not going to change it on the outside. You only want to be able to make the parameter a constant so that you don't change the value of what it's pointing to. You can't change the original pointer in the calling function anyways because it's passed by value, passed by copy. The compiler knows that an argument that is a pointer to constant data will be safe. So there are advantages to this. You can't accidentally modify what the value is pointing to. So you might do this again if you don't want the changes to be reflected on the outside of the function. If you pass a pointer to constant data as the argument for a parameter, then the parameter must be used like in the above. Right? So if you actually, when you invoke the function and you pass it in a constant, then you have to have the function declaration also take a constant character pointer. Just like normal other pointers that are constants. They have to be defined, and the defines have to match the prototype. Returning pointers from a function. Returning a pointer from a function is a particular powerful capability. It provides a way for you to return not just a single value, but a whole set of values. So again, one of the other advantages I mentioned about pointers is that you can now return more data from a function. In the past, you could only return one value. But with a pointer, because a pointer could be pointing to a structure that which we haven't talked about yet, or even other things, you can return multiple values. So we know how to pass pointers to functions. Now we want to talk about returning pointers. You'd have to declare a function returning a pointer. So the function declaration has to match up. It's very easy to do that. You just say use the asterisk when you declare the function or define it, and have the return type for that pointer what it's pointing to. So be careful though, there are specific hazards relating to returning a pointer. Use local variables to avoid interfering with the variable that the argument points to. It is somewhat problematic when you're returning pointers, because if you modify that pointer inside the function and then return it, it could be something that you don't intend it to do. So always use local variables if you do not want to affect a variable that your argument points to. And so this lecture described how you can pass pointers to functions and how you can return pointers from functions. And by using this mechanisms of passing pointers to a function, it demonstrates or mimics pass by reference, because you're copying in an address. And when you copy an address, if you write to that address, you're going to update whatever is pointing to that address, which effectively means that you're changing the value of the data inside the function. It's going to be reflected outside the function. We use the swap routine to demonstrate that. This is a very powerful concept, and you want to mimic pass by reference. You can use pointers to do that, and you'll want to do that when you want to change things outside the function. Thank you. Hello and welcome back. Another challenge for you. Again, it's going to be on pointers. What I want to try to help you learn in this challenge is the concept of pass by reference. So even though C is doing everything pass by value, it's actually making a copy of an address when you use pointers. So it mimics pass by reference. And the big advantage of pass by reference is that when you change a pointer's value or variable inside of a function, you're going to see the change reflected outside the function. So we don't have to use global variables as much. And it's a big advantage to be able to pass in data to a function as a pointer that mimics pass by reference. So in this challenge, you're going to write a program that tests your understanding of pass by reference and how to use pointers to do this. I want you to write a function that squares a number by itself. The implementation of the function is going to be quite simple. It's just going to square the number that you pass in. So the function should define as a parameter an int pointer. In your function declaration, it takes an int star, which is a pointer, and then inside your function implementation, all you're going to do is you're going to need to dereference the value of the pointer and multiply it by itself. You don't have to return any data from this function. I just want to let you understand the concept of passing in by reference or passing in a pointer. The last thing that this program should do is it should print out the value of the variable, the value of the pointer that you pass to the function. So you don't even need to create a pointer to pass in. You can use a regular primitive data type integer float. It's just when you pass that integer or float in, it has to be the address, because the function for square only accepts a pointer. But again, what you're going to notice here is that the value or the variable outside the function, the one that's being passed in to the function, is going to change because you're using the address, and this is going to mimic pass by reference. So good luck on this. It's pretty straightforward. Again, going to get you familiar with pointer syntax as well as this concept of pass by reference. Thank you. Hello and welcome back. In this lecture, I want to provide a demonstration for our previous challenge, which was understanding pass by reference. Having a parameter inside of a function take a pointer. So let's create a new project. We'll call this one pointer pass by reference, because that's what it's demonstrating. Basic stuff here. New project, console application, C. Pretty straightforward here. Let's just call this pointer underscore pass by reference. Again, demonstrating how we can use parameters inside of a function to pass data and how that data will then be modified outside of the function. So the first thing we're going to do is we're going to create our function declaration, our function prototype. This is always nice to do so that you can call it anywhere in your program. We're just going to call it square. Main thing in this function declaration is it's going to take a pointer. So it's just going to take an int pointer, so we're just going to say int star, and then you can give it whatever name you want. And you end it with the semicolon. In our main function, first we're going to do is we're just going to create a regular integer variable. And we'll just say int num, and we'll just say hard-code it to 9. And what we're going to do is we're going to call our square function. Our square function is not going to return any data. It's going to be void. We have to pass it an address now, though, because our square function on line 4 is taking a pointer. So we can't pass in num. We would have to actually pass in the address of num. Right? And then we would end it with a semicolon. So we call the function using the function name and then passing the address of the variable. Because the variable here in line 8 is not a pointer. Then we can just basically print out the value of num. And again, what you'll notice here is because we're passing in the address, if we change the data in the function itself for that variable, it's going to change outside of it. So here we're just going to say the square of the given number is, and it's just say %d. I'll add a line feed, and we're just going to print out num. And num is not going to be 9, I'll tell you that much. And then we'll just return 0 for our regular functions. Now we have to actually implement the function, define it. To define it, I'm just going to say void square. We know it takes an integer pointer, so I'm going to say int star x. And now we want to just multiply it by itself. But we want to make sure that we don't change the address. Right? So what we could do here is we could make this a constant. But you'd want to put the constant after the data type because we don't want to change the address of what x is, the value of what x is, or the address of what it's pointing to. So we could say int constant. If we didn't want to change the value of x, we'd say constant int, but we do want to change the value of x. We're going to square it by itself. So to square it by itself, first off, what we want to change is the ultimate value of x. So we have to use the indirection operator. We have to dereference it with the asterisk. And then we're just going to say equals. We don't want to do x times x because that's just going to multiply the addresses, right? X is a pointer. We don't want to just get the value of x. We want to get the value of what x is pointing to. So again, we have to dereference it. And then we're going to multiply it by itself. We're going to dereference it twice. It might be a good idea to put this in parentheses just so it's very easily understood what's going on here. You're dereferencing the pointer, getting the value of it, and then multiplying by its value. And then you just add the semicolon. And that's it. That's all you have to do. So when we run this program, it's going to print out 81. It's going to print out the value of num. Num is going to change inside square because we're passing the address there. We're not able to actually change, though, the pointer's value. So we have the constant after the type. So here we say build, and it looks like we didn't change the declaration. I forgot to put the constant. And now we just want to make sure that everything else is correct. I did make a little mistake. If you want to have the pointer be constant, you have to put it after the asterisk. So int star, that means int star constant means that you can't change the value of x, which is the address of num. Right? If we put const before the int or after the int but before the asterisk, it means that you can't change the value of what the pointer is pointing to. So now when we run this, we should see as output 81. And again, what this tells us is, which we do, what this tells us is that we modified the data. This variable, this local variable num was modified inside the function and its value changed. That's not normal. We have not learned that concept up until now. That's passed by reference. But in C, what's happening is you're passing in a copy of the address. And that's why it's really redundant. We don't even need the constant because even if we were to change the pointer's value, it's a copy of the pointer's value. So you don't really need to do that. Now, if we didn't want to use an existing number, we could create a pointer. We just have to allocate memory for it. So what we would have to do here is we could create an int star num. But what we'd have to do is first we'd have to cast the malloc because malloc comes back with a void pointer. But we can allocate memory dynamically. And in here we'd have to say, really just because we're creating one integer, we could just say the size of int. And that would allocate memory for us. And then all we'd have to do is pass into square num. And then when we build this, it would do the same thing, but now we're actually, we don't have a value for num either. So it wouldn't actually know what to compute. So you'd have to actually assign to the value of num, we'll say here 4. You dereference it. And then now when you build it and run it, you should get 16. Now the only thing here is we want to print out the value, so we want to say num. And then when we run it, we should see 16. And it's really just the same type of behavior. And we see 16. The only thing difference here was we were allocating memory for what the pointer is pointing to, as opposed to just pointing to an existing memory location with ampersand. Again, important things to note here. This number is changing outside of the function. This is passed by reference. Understand where we're using the dereference operator, the indirection operator, to get the value of what the pointer is pointing to. Okay. Understand that if the function takes a pointer and we have a pointer, we can just send in the name. If it's not taking a pointer and it's actually a value, then we have to dereference it. And this is just like the scanf. So here we'd have to say the ampersand, and then also when we print it out, we wouldn't have to dereference anything because it's not a pointer. And then that would be the same thing here. And then understand const too. Const before the int star is saying that the value that the pointer is pointing to cannot change. The const after the int star is saying that the address of the pointer can't change, the pointer's value. Hope this was helpful. Again, play around with this, change some syntax, mess around like I did. It will help you learn a lot. Thank you. Hello and welcome back. In this lecture I want to talk about pointer arithmetic. Now that we understand the relationship between arrays and pointers, this concept is going to be easier to understand. We say arithmetic, but we don't really, all it really means is you can do either plus or minus or incrementation or decrementation on a pointer itself. So the real power of using pointers to arrays comes into play when you want to sequence through the elements of an array. You want to go from the first element to the end. You want to iterate through them. This is the real power of pointers. Because pointers use addresses, an array, each element in an array is just another address. So you can just do plus plus on pointers and you can go to the next address. So here, values pointer can be used to access the first integer of the values array. It can be used to access value sub 0. So if you remember, values pointer is a pointer that's pointing to an integer array. And we assigned it to the first element in the array by just assigning the pointer to the array name. We could also use the address of operator sub 0 if we wanted to. But when we dereference values pointer, because it's pointing to the first element in the array, it's going to give you the first integer in the value sub 0 array. If you wanted to reference value sub 3 via the pointer variable, all you have to do is add 3 to the values pointer and then apply the indirection operator to dereference it. So you could just do something like this. You can say values pointer plus 3 and then dereference it with the asterisk, and you usually put the asterisk outside of quotes to make it clear. But what this is doing is it's saying values pointer, which is an address of the first element in the array, it's adding 3 to it. And so it's going to actually add for each bytes for integers, it's going to multiply the bytes times the integers. But this is essentially going to point to the third sub 3, the fourth element in the array. So in the expression asterisk values pointer plus I, that can be used to access any value contained in a values array. So if you understand this expression, you can add anything to I and it will point you to a specific element in the array. So if you want to set value sub 10 to 27, all you have to do is, if you're using a pointer, is say values pointer plus 10 and then dereference it and say equal 27. So you see the different syntax here. Again, it's notational convenience, but it's also more efficient in terms of the program itself. So pointers, because they're so closely related to arrays, you can easily access elements by just incrementing, decrementing pointers, or adding values or subtracting values from a pointer. Very, very useful. To set values pointer to point to the second element of the values array, you can apply the address operator to value sub 1 and assign the results to values pointer. We saw this. This is just another way to do the same thing I mentioned earlier, if you want to use the address of operator. You can always do this if you want, but it's much more convenient to do pointer arithmetic. If values pointer points to value sub 0, you can set it to point to value sub 1 by simply adding 1 to the value of values pointer. And this is really what we're getting at with pointer arithmetic. All you have to do is say values pointer plus equals 1, and now values pointer is pointing to the second element in the array, or the first index. Very, very nice notation, very easy to do. So this is a perfectly valid expression in C and can be used for pointers to any data type, whether it's an integer, a character, or anything. And you probably should be thinking about how useful this can be in characters. If you have a character pointer, you can now access each element, each character in a string by just doing a plus plus on a pointer. The increment and decrement operators, plus plus and minus minus, are particularly useful when dealing with these pointers because you will usually want to go from one element to the next and so forth. It's not as common to add 20 to it or minus 20 because you're usually going in sequence. So using the increment operator in a pointer has the same effect as adding 1 to the pointer. Using the decrement operator has the same effect as subtracting 1 from the pointer. So saying plus plus values pointer is going to set the values pointer pointing to the next integer in the values array. Minus minus should be values pointer is going to set the values pointer pointing to the previous integer in the values array. But you want to be careful when you do the minus minus because you want to make sure that you're at least in the array and you're not at 0. And the same goes for plus plus. If you're at the end of the array, you don't want to have any out of bounds errors. So make sure that values pointer, if you're decrementing it, it was not pointing to the beginning of the values array initially. Another example here where we're actually going to sum all the elements in an array. You see that we have an array sum function, and the function takes an array, and it also takes a constant integer as parameters. Inside the function, we're going to create an integer. We're going to initialize that integer sum to 0, and we're going to create an integer pointer, a pointer to of type int. We're also going to create a pointer that's constant. So what that means is you can't change the address of it. It's always going to be array plus n, and it's going to be named array end. We're doing this because it makes our loop more efficient if we set it up to go to the array end and just look at the pointer. So array end is pointing to the address of the end of the array. We can say array, which is what's passed in, and then n is the size of the array. Now the for loop is going to initialize the loop control variable pointer, which is a pointer to the array. So it's going to, and all you have to do is if you want to assign an array to the first element of, or assign a pointer to the first element of an array, all you have to do is say pointer equals array. And then our loop exit condition is if the pointer is less than the array end. Remember, a pointer is an address, and array end is also an address. So we're saying if the address at pointer is less than pointer end, then we want to execute the body of the loop. Right? Pointer is just an integer. It's a hexadecimal address. Each time we increment it, it goes to the next address. We have the ending address, so we can say go through the loop until we hit the end. And then we're incrementing the pointer itself, which is going to increment the address to go to the next element in the array, essentially, because that's what we're pointing to. Then we have inside the body of our loop, we say sum plus equals pointer. We're dereferencing the pointer to get the value, because remember, we want to get the value. We don't want to get the address of the pointer, or the pointer, or the address of the pointer is pointing to. And then at the very end, we return the sum. So this is going to sum all the elements in an array. You'll notice in the main, we also did a declaration of the function in there as opposed to the top of the file. I usually like to put them at the top of the file. But in the main, we create an array of 10 elements, 3, 7, negative 9, and so forth. We then pass in the array to array sum, and we specify the size as 10. And what you're going to notice is it returns the value, which is the sum of the array. So it's very, very nice to use this pointer arithmetic to iterate through an array. We can just plus to the next address and also look at the ending address to jump out. This is more efficient with the pointer looking at the ending address as opposed to a counter looking at less than n. And you also notice we created them as constants because the constants don't change, and that's more efficient with the compiler. The array here is a constant pointer, meaning that the address can't change. You also should have noticed in this example that To pass an array to a function, you simply specify the name of the array. Right? So we know how to pass arrays to function. And to produce a pointer to an array, you only need to specify the name of the array. Right? We saw that when we assigned the first element of the array to a pointer. So what this implies is that the call to the array sum function, what was passed to the function, was actually a pointer to the array values. And this really is telling you that arrays and pointers are very, very closely related. That an array is nothing more than a pointer. And this explains why you're able to change the elements of an array from within a function. Right? Because up until this point, when you pass in data to a function, that data does not get changed outside of that function unless it's a pointer. Right? Because that's why we have to pass in the address for the scanf. The only way that elements get changed outside of a function is if you're passing pointers to a function. And because the elements are modified inside that function, this implies that you're passing a pointer. And this is just, again, proving that that arrays and pointers are very, very similar and that arrays are indeed pointers, just using different syntax. We're going to talk about how we can pass by reference, or really passing a copy of a reference, which will allow you to change data in a function outside of that function. If you remember from one of our previous challenges, whenever we wanted to change data in a function, we had to use a global variable, right? Because we didn't understand the concept of passing by reference, and we didn't understand the concept of pointers. But I mentioned earlier too, one of the advantages of pointers are that you can now change data inside of a function and it will get reflected outside of that function. But that's another lecture. But that concept in itself, because of the previous example, is demonstrating how arrays are essentially pointers. So you might wonder why the formal parameter inside the function is not declared to be a pointer. Well, it could be. We could just do something like this: int array sum, int star array. We don't need to declare that as a array. It's perfectly valid, because arrays and pointers are the same, that we can say int star array. We mentioned they're really closely related. So you can declare an array type to be a type of array of ints inside the array sum function, or you can declare it as a pointer to int. And that's why you see many functions that accept arrays as parameters or as arguments, where the parameters are actually pointers. So if you're going to be using index numbers to reference the elements of an array that is passed to a function, then declare the parameter as an array. Again, notational convenience. It's just a different way of the notation, either using the brackets and the subscript or using a pointer. The array itself is usually easier to read in terms of maintenance of the program and more correctly reflects the use of the array by the function, but the pointer is easier to use. And if you're using an argument as a pointer to the array, declare it to be of type pointer in the formal parameter. So here's an example with the pointer notation of the function, where the previous example was using an array notation. Here we just say int star array, and what you'll notice is the function immediately becomes a lot smaller, right? Because we don't have to assign the pointer to the array, to the first element like we did. The loop also becomes a lot smaller because we don't need to do that assignment in the first statement. We can just say until the array is less than array end, and we can increment the array. So it's a little less code. It's still very clear what's going on, hopefully, if you understand arrays and pointers. We're passing in an int star array, and we don't have to initialize that array anymore because we're passing it in, the pointer. We don't have to initialize the pointer anymore. And then we're actually setting the address of the end of the array to a constant pointer, array end. We use that to jump out of the loop. And we just say sum plus equals star array, using the indirection operator to dereference the array again, returning the sum. And then the main function is exactly the same, except the declaration is now a pointer as opposed to an array. So here are two examples using different notation, but providing the same functionality. And that's why you see a lot of pointers as parameters inside of a function parameter. So to summarize, here are some things that are valid when you use pointers and things that are not valid. So if we declare some variables here, we declare an array called earn, and it's contained 3 elements, and then we declare 2 pointers. Now, on those pointers, we can do arithmetic. We can say pointer 1 plus plus. We can say pointer 2 equals pointer 1 plus 2. We can even say pointer 2 equals earn plus 1. It's perfectly valid to do that because you have pointers and you're modifying the pointers by the address, so you can do pointer arithmetic. You can't do pointer arithmetic on arrays, so you cannot say earn plus plus. you can now say pointer 2 equals pointer 2 plus pointer 1, right? Because those are addresses, and you're not actually pointing to anything inside of an array. And you can't multiply earn times pointer 1 to get pointer 2. Right? Those are invalid. So pay attention to the correct syntax for pointer arithmetic, and also understand that pointer arithmetic can only be applied to pointers, not arrays. Okay? Also, functions that process arrays actually use pointers as arguments. You have a choice between array notation and pointer notation for writing array processing functions. So if you're going to process an array function, it's perfectly fine to use a pointer as a parameter. You can choose which one you want to use. But using pointers is usually less code and more efficient. Using array notation makes it more obvious that the function is working with arrays. And array notation has a more familiar look to programmers that have some programming background in certain languages. So if you programmed before in Fortran and Pascal and so forth, you may use the array notation. Other programmers might be more accustomed to working with pointers and might find the pointer notation more natural. Just makes more sense. It's closer to machine language using the pointer arithmetic and the pointer notation. And with some compilers, it leads to more efficient code. Another reason to use it. So let's take a look at these examples inside code blocks. So here's our example from the slides. We have our function declaration up on line 3. It's an array sum. And in this example, we're going to use array notation. So we're going to use the brackets, we're going to use indexes. And we're going to call it passing in the values array and passing in the size. So the array sum function takes a integer array. First thing you have to do is you have to assign on line 15. Well, first thing you have to do is you have to create the pointer that you want to use for pointer arithmetic on line 14. And then you have to assign the end of the array to the address array plus the size. That's the end of the array, which you can now use to exit the loop. But we have to assign the pointer to the array. We know that we can assign arrays to pointers to point to the first element by just using the name of the array. We don't have to use the address of operator. We could if we wanted. We could actually do something like this. And this is fine as well. And then we plus the pointer. We're incrementing the pointer because all that's doing is incrementing to the next address. It's pointing to the next element in the array. And then on line 18, we're dereferencing the pointer to calculate the sum. Sum equals sum plus the value of the pointer that it's pointing to. So if we build this, we do have one warning, which is main is not an int. We want to change this because it's good to return error values from the main and just say return 0. You could return, if there was an error in main, you would return a -1. Now when we run this, you'll see that it just performs the sum of the values in the array, which is 3 plus 7 plus -9 and so forth. Not even sure what that is, but it looks like it's 21. Now we can easily modify this array parameter to take a pointer by just declaring the asterisk before the pointer. We call it the same way. We just modify, we don't need to declare the pointer anymore. We probably want to change the name to make it easier, but we don't need to declare this pointer anymore. We still want to get the end of the array, and we don't need to assign it anymore either. We can just have an empty thing there, and it might actually be more useful to have a while loop here. But if we have no assignment, we can just put the semicolon there. And now we're good. We still want to dereference it, and we still want to return it. But if we build this, we want to make sure that we define the function declaration as a pointer, since we changed it. And this can be any name, but we'll just be consistent. Now when we build, we want to make sure that we're, again, using all the variables that we changed. So now we finally build successfully and run it, and you see you get the same result, which is 21. So understand this difference between using pointers as formal parameters and arrays. You can use them interchangeably. It's just a notational convenience, but you have less code usually when you use a pointer, and you can manipulate it more and you can do more powerful things. It's usually more efficient too based on the compiler. Thank you. Hello and welcome back. Because pointer arithmetic is kind of a difficult concept to understand and grasp, I wanted to go through one last example that really demonstrates this concept. It does a good job, and if you understand this example, you're going to have no problem with pointer arithmetic. So the first example that I want to show you is the effect of adding an integer value to a pointer. So when we do pointer arithmetic with addition, we can actually see how it works in terms of the addresses. So here in this program, all I'm doing is creating a string, a character array. It's called a string. And then I'm creating a character pointer called p. I'm going through the entire length of the string, which is multiple. So I'm going through the entire array. Just basic for loop, string length of multiple, size of multiple. And then I'm printing out each actual string or character inside that array. And also while I'm doing that, I'm displaying the address and then the address with the actual number, the I, added to it. So let's look at just the output of this, because the output demonstrates a really good example of pointer arithmetic. So let's go to code blocks and run this. So here we are in code blocks. I cleaned up the code a little bit. I used stir length instead of string length because it's an extra include. And I want to just run this. So when I run this, what you'll notice is it's showing you what memory looks like. And it's showing you the values doing the pointer arithmetic. So if you say multiple sub 0, remember multiple just contains a string. But if we look at this and we say look at the array contents, multiple sub 0 is a, multiple sub 1 is a space, and then the rest are string. That's the array. Right next to this is the same as adding 0 to the pointer and dereferencing it, adding 1 and adding 2. And it shows you how you can do pointer arithmetic by dereferencing the pointer itself and adding numbers to it. So the pointer plus 7, dereferencing that, you get G. Then in the third column, I'm showing you the actual addresses as we increment. So the addresses of each element in the array, using the ampersand just on the character array, we see the addresses 060, FE, FF for element 0 and so forth. And then we look at the addresses if we just add to the pointer itself without dereferencing it. And you'll see the addresses line up. And so then we can look at the syntax to see what's going on here in terms of the first thing that we actually display is the index in the array, which is just a counter. And then we display a %C, which is the character at the array. The next thing we're displaying is dereferencing the pointer plus I. So here what we're doing is we're displaying I, and then we're displaying the dereference of pointer plus I, the actual value. So we display as the D, just the actual counter, and then point C is our dereferencing. So P is our pointer, right? P is our pointer. We're just saying P plus I, pointer arithmetic, and then we're dereferencing it. And then to get the addresses, all we need to do to get the array address is say ampersand multiple and then the index. To get the first get the address of the pointer, right here we just say P plus I. To get the actual counter, which is showing you how we're incrementing that P, we just do a P plus %D. But it does a good job of demonstrating the various ways that the memory that we're pointing to, the addresses, are actually displayed and how they're equivalent to the different indexes in an array and the actual pointers. I thought this did a good job. I want to look at one more example that does another good job concerning pointer arithmetic with longs. Because here, these are integers, so all we have to do is add 1 and it automatically goes up to the next byte and so forth. Let's look at what we do. We do longs. So in this example, I wanted to also just demonstrate how you can do the same thing with a long and a long pointer. With the character pointer, it was just a string character array. But even for long arrays, which are different sizes, we can still iterate through them using a pointer, and you can see how the number of bytes actually changes. So even though we say we have a long pointer and we add 1 to it, we're actually adding 4 bytes to it because a long is a little bit bigger. And we'll see that in this example. So now let's run this example in code blocks. So here's our example. Again, we have an integer counter, a loop counter. We have a long array, 15L. We're specifying L. By putting the suffix on there, we specify their L's, their longs. We have a long pointer that's pointing to multiple. Again, because it's an array, we don't have to use the address of operator. We're going to go through the entire long. Here we can't use stir length. We have to use size of. And we actually have to divide it by each spot in the array. So the total size divided by the single spot in the array. That's when we want to jump out, because these, remember, are addresses that are incrementing by 4 bytes each. And again, what we're doing here is we're just displaying both the pointer versus the array and showing you how they're related. And then we're displaying the actual total number of bytes that the long is on our system. And so this again just demonstrates how arrays are related to pointers. So if we run this, we're going to see similar output, but what's a little different here is the address size going up by 4 bytes. So we're going to print out the address and the pointer. So for the address and the pointer plus 0, that's going to be equal to the array sub 0, which is address 6356728. And to dereference the pointer, we'll get the value 15. So p plus 0 is still going to be equal to the array sub 0. And then again, we do the same for p plus 1, p plus 2, and p plus 3, all equivalent to the correct spots in the array for the index. The addresses are going up by 4 bytes, but we can still just add 1, 2, and 3, and we see that the values are the same. And then it tells us this long occupies 4 bytes, and that's why the addresses are going up by 4. But what's significant here is we can still add 1 to it, and the compiler knows to go to the next address. So if whether we have a long or a character or whatever that particular data type is inside of the system, adding 1 or 2 is going to add the correct number of bytes. So just another cool example I wanted to show you, because this pointer arithmetic is really important and it's really useful when iterating or traversing an array. It makes it much cleaner and much more efficient. So I hope this helped. Thank you. Hello and welcome back. Now that we understand pointers a little bit more detail, I want to talk about character pointers, mainly how you can use character pointers to represent strings. Strings are character arrays, multiple characters, words. So we now know how arrays relate to pointers and the concept of pointer arithmetic. Very, very useful concept. These concepts can be very useful when applied to character arrays, strings, because now we can easily traverse a string character by character. One of the most common applications of using a pointer to an array is as a pointer to a character string. The reasons are one of notational convenience and efficiency. So using a variable of type pointer to char or char to reference a string gives you a lot of flexibility. So you're going to try to use character pointers as much as you can over character arrays. Specifically using character pointers to pass data to a function, all sorts of nice things like that. So let's look at an example that uses an array to copy a string. In this example, our array parameter is going to be a character array. You'll see that right in the function declaration. I want to compare this to a function that takes a character pointer and show you how the character pointer function is a lot more efficient. So in this example, we have two functions, one that takes an array and one that takes pointers. In the first function, copy string, we can go through the entire array using a for loop, I equals 0, from sub I, and we go all the way until we see the null character string, and then we increment our loop control variable. And then all you have to do is say to sub I equals from sub I. We're doing a direct assignment there. And then at the very end, after we've gone all the way until we see the null character, we add a null character to the end of our to array. Pretty basic. Now let's see how we do it when we use pointers. First, we declare two pointers as the function declaration in the copy string by just saying char star to char star from. In our for loop, we don't have to actually declare any variables because we have pointers and we just want to iterate until the from hits the null terminator. And then we can increment both the from and the to pointers, because here we're doing pointer arithmetic, right? We're just adding 1 to the pointer, which is increasing its address by 1, which is getting the next character. And the next for loop line, we just dereference both the to and the from because we want to assign the actual value that the pointer is pointing to, the actual character, to the to pointer. And then at the very end, we add the null character to wherever the to pointer is pointing to, which would be at the end of the last address of the string for from, but now pointing in the to address. All right, it doesn't look too bad. I mean, you have a for loop, you basically have the same amount of lines of code, but you see the difference in syntax. You can see how you don't use subscripts, right? And you use pointers, use the asterisk. Again, really an issue of notational convenience. You don't see a big advantage here. But you can actually optimize this more to even get down to less code for when you use the pointers. So if you have a char array as a pointer, if you have an array of characters called text, you could similarly define a pointer to it and use the elements in the text. So here we could say char start text pointer. That's how you define a character pointer. If the text pointer is set pointing to the beginning of the array of chars called text, then you can just increment it by 1 using these incrementation, pre and post incrementation and decrementation operators. So this above, this plus plus text pointer is going to set the text pointer pointing to the next character in the text, which is text sub 1. So if we want to look in the next array, just like for integers, all we have to do is add 1 to it and we can get the next character. It's much more useful though in character arrays because you can easily manipulate characters 1 by 1. If you do a minus minus text pointer, which is the decrementation operator, that will set the pointer to the previous character in the text, assuming that the text pointer was not pointing to the beginning of the text. Because if it was, you'll have these under bounds errors. If it was doing a plus plus to the end of the string, you'd have an out of bounds error. You always have to be careful, just like in integer arithmetic, to not go past the bounds for an array. But very simple. It relates very closely to when you do integer pointer arithmetic. Character pointer arithmetic is the same thing. It's just even more useful because now you can actually look at individual characters without using a subscript. So if we look at that previous example, and we can actually optimize it a bit more using pointers to make it even less lines of code. So now in our copy string, we do this functional declaration is the same as before. Create a couple pointers using the asterisk. But we don't use a for loop anymore because it was kind of pointless to use a for loop in the previous example because we didn't actually need to initialize a loop control variable. All we needed to do was exit a loop on a condition, and then we were actually using the incrementation and decrementation operators in the for loop, but we don't even need to do that. It actually becomes even much simpler here because if we use a while loop, all we have to do is look at the while loop and it will jump out if it's pointing to a null character because the null character is actually equal to 0. And the while loop, remember that Booleans in C are represented by integers. 1 is true and then 0 is false, or really 0 is false and then anything else is true. In this case, null character is 0, which is false, it's going to jump out. So all you have to do for the exit condition in the while loop is put an asterisk from. Right? What is that doing? That's dereferencing from to see what the value of that character is. So when we're to the end of the string that we want to copy from, we jump out. Otherwise, we just actually put our modification of our pointers right in there, to plus plus from plus plus. Now, this is a post incrementation operator. So what this means is the plus plus is on the right hand side of the variable. And when you do this, it means that the plus plus actually you don't add 1 to it until after the statement is done. So what this is going to do, it's going to say star2 equals star from, and then after that statement is done, it's going to add to 1, and it's going to add to from 1. If you had the plus plus before the variable name, it would add to that variable before it executes that statement. And that would be a problem because we'd miss essentially the first element being copied in the string. But we don't need any more lines of code. We're doing an actual incrementation, pointer arithmetic, and assignment in the same statement. So we reduce the code by 1. So it's very, again, the notation is very simple. We're doing an integer arithmetic and assignment very easily. And then at the end, after we're done copying all the strings, we just add to the end the null character to the pointer, which we dereference, right? Because the 2 is actually, while it goes through the loop, it'll be pointing to the last character. So it's just a little cleaned up a bit here. It shows you the power of pointers and how you can use pointers and arithmetic in the same lines. And with these incrementation and decrementation operators, these plus plus and minus minuses, it makes it even quicker and easier. So it's more efficient as well. If we wanted to use these copy string functions, we could just create 2 character arrays. We can pass the character arrays directly to the copy string because the character arrays are pointers, right? They are pointers, so we don't have to actually dereference them or add in addresses or anything. We could just say string 2, string 1. And so what this is going to do is it's going to copy a string to be copied to the string 2 character array and then print it out using printf. I wanted to go through, an example of how you can use character pointers instead of character arrays and why they are sometimes preferred. We mentioned that it's sometimes programmer preference, where if you've programmed in previous languages like Fortran, you may be used to arrays, but if you haven't, you'll see the benefits of using pointers. Hope this was helpful. Thank you. Hello and welcome back. We have another challenge for you. In this challenge, I want you to learn all about pointer arithmetic. Remember, pointer arithmetic is a really neat concept. It's a notational concept, but it really illustrates how arrays are related to pointers. You can traverse an array very easily with a very simple syntax. It reduces your line of code, and it's a really neat concept. So you're going to learn all about pointer arithmetic. We're also going to learn more about the constant modifier. So in this challenge, I want you to write a program that tests your understanding of pointer arithmetic and the constant modifier. We've learned about both of these concepts in previous lectures. So I want you to write a function that calculates the length of the string. The requirements are the function should take as a parameter a constant char pointer. A constant char pointer means that you cannot change the value of what the pointer is pointing to. And you're not going to do that with the length. The function can only determine the length of the string using pointer arithmetic. I do not want you to use the stir length function. I want you to use pointer arithmetic. And the way that I'm envisioning this function to be implemented is that you're going to get the address of the end of the pointer. Okay, that would be the length of the pointer essentially. But the way that you can get the address of the last string in the pointer is you can write a while loop. The while loop can go all the way to the null terminator character, right? Or the null terminator character, remember, that's represented as int. So the null terminator is actually a 0. So you could write a while loop, and all the while loop has to include in its condition is dereferencing the pointer. Because if the value of the dereferenced pointer is 0, jump out of the loop, and that would be the null terminator. So I want you to go through the entire pointer, and when you get to, and while you're going through it, keep incrementing that pointer. So now you have a pointer that's pointing to the end of the string. Then, to actually calculate the length, all you have to do is minus 2 pointers. The pointer that was passed in, which is the beginning of the string, and then the pointer that you created in the function, which is pointing to the end of the string. If you minus the end of the string pointer from the beginning of the string pointer, you'll have the length of the string. So you'll be doing pointer arithmetic by incrementing the pointer one by one to get to the ending address, and then you'll be using pointer arithmetic to multiply or to subtract each pointer. This is really probably the most valid way to use pointer arithmetic for subtraction. You usually don't add 2 pointers because why would you add 2 addresses? You may subtract 2 addresses to get the how far away 2 elements are in an array. That would make sense, but adding would not. So just to reiterate, the function can only determine the length of the string using pointer arithmetic. Create a local pointer in your function, increment that pointer each time to get to the end until you see a null terminator, a simple while loop. And then once you have the ending address, you already have the beginning address, subtract those 2 pointers, that will give you the length. You should return that length as an int from the function. And then you can just print out the actual length itself. So this assignment is getting you familiar with pointer arithmetic and also how to use the constant modifier, because you don't want to change the actual value that it's pointing to, and subtracting 2 pointers as well, and also using a while loop where you can look at the pointer's value itself to determine the null character. Good luck. I'll provide a solution in the next lecture. Thank you. Hello and welcome back. In this lecture, I want to provide a demonstration of our challenge for pointer arithmetic and using the constant modifier. Let's bring up code blocks. I'm going to create a new project. We're going to name this one pointer arithmetic example. Okay, so what we're going to do here is we're going to actually determine the length of a string by using pointer arithmetic. So the first thing I want to do is I want to create my function declaration. This is going to return the length of the string, so it's going to have int as the return type. I'm going to call it string length, and this is just going to take a pointer, but it's going to be a constant pointer. We don't want to change the value of what's pointing to. So that means we would use the constant as the first keyword, and then we would specify the type, which is a character, and we would say star, and we can name it whatever we want, string. Now again, just to reiterate, if we would have put the constant here instead, this would say that the address of the pointer's value cannot change. But again, it's kind of redundant and it doesn't really need to be done because we're doing pass by value, pass by copy. So you have a copy of the address anyway, so it doesn't matter if you change it in there. But it is important to change what you're pointing to. If you do not want the value of what you're pointing to change, you definitely want to do constant here. And that's important. So now all we have to do is we're going to create our main. All we're going to do in our main is we're going to call string length function with different strings. So let's print out, and remember it returns an integer, so we can say %d, and we're just going to print out the length of a couple strings that we pass. So we're going to call string length, and we're just going to pass in some constant strings. So we can just put things in double quotes here. We don't even have to create pointers. You could create a pointer and assign it and then pass it in, but you just have to make sure it's a constant. But since it's easier and less code, we can just say string length test. Again, that's a constant literal string, right? We'll test it with some more. We'll say, we'll put a space after it. Let's actually, instead, let's add some line feeds. Here we'll call string length, and actually let's call it with the empty string. Make sure it returns 0. And then our third one, we'll say string length, and we'll just say JSON. Now incidentally, when you create these and pass these string length things, they automatically get the null terminator added to them, right? We learned that when we declare pointers. That's one of the advantages. If you're going to create a pointer and it's going to be a literal, you don't want to specify the size. You know, you'd want to do something like character, if it's an array, because an array is a pointer. But if we wouldn't want to specify the size, we could say character P, and then inside here we could just say JSON, right? Remember that lesson where if we don't specify the size for character arrays, it will automatically add a null terminator and create the size for you. That way you don't make any mistakes. If you put the size inside the array, you might not have enough with the null terminator. It's the same thing when we pass the literal to the string length. The null terminator gets added to the end of it. So we could have created these variables, initially and done something like this and then passed in each one. But I didn't want to waste time creating variables. So I'm just going to do that. Now what's really important for this code is the function. So we're going to create our string length. Remember again, it returns an integer. And it's going to be a constant, so we can just say constant char star string. And you also notice that the function declaration variable name doesn't have to match. I could put this as strings, and that's fine as well. Now, inside this function, we have to create a local pointer because the local pointer is going to point to the end of the string. And then once we have the address for the end of the string, we can minus the address for the beginning of the string. The address for the beginning of the string is what's passed in. String is automatically going to be pointing to the first element in the array, or the first address of the array. So if we create a local pointer, and we'll just want to, again, create another constant char star, and we'll just say last address, how about? And this is going to be equal to the beginning address of string, and then we're going to increment it each time in our loop. So now we have last address. Again, this is a local variable that's going to store the address right before the null terminator. So now we can write our while loop. And our while loop is going to exit when we see the null terminator. Now we could do this two different ways. We could say, we could compare characters. So we could say something like while star last address, because we have to dereference it, is not equal to \0. Could do something like that. But that's kind of a lot of code. All we really need to do is just to say while star at last address. Because if you dereference a null terminator, it's going to be equal to 0. And 0 is equal to false, right? We know that Booleans have 1 is true, 0 is false. So if it's false, it's going to jump out. So all you need to do is inside your while condition is put star last address. Again, this is going to dereference the pointer. And once it's pointing to the last address, it's going to be pointing to the null terminator. Now we have to make sure that we modify last address so that it eventually points to the null terminator. Here, all we can do is we can say ++ last address. So each iteration of this while loop is going to increment the address until it sees a 0. A 0 represents the null terminator. So the end result of after this while loop is done executing, last address is going to be pointing to the address of the null terminator. We can then subtract the address of the null terminator from the address that was passed in, our string. And that's going to give us our length. So that's all we have to do on the next line. We can just say return our last address. And we actually want to minus the address, so we don't need to dereference anything or use the indirection operator. Last address minus string. Right? So string is passed in. We don't modify it at all. That's pointing to the first character. That would be pointing to J. That would be the address, or for the first time we call in line 8, that would be the address of S. Last address is going to be pointing to the address of this last T. Actually, one more than that, the null terminator. If we say last address minus S, the address of S, it's going to give us the length. And that's what we're going to return. So I hope that makes sense. Again, on line 17, we're creating a local variable because we need to keep track of the last address, the address of the null terminator. After this while loop is done running, last address is going to point to after the T, the null terminator. Then we can just subtract the last address from the string. The string's address is pointing to S is when it comes in, and we don't modify that. So let's see what this, if this gives us back the correct length. When we run this, we should see the length for those strings we passed in. So we see 17, 0, and 5. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You got to count the space. 14, 15, 16, 17. That's right. We put in double quotes, which is empty, so that should be 0. And then Jason should be 5. So 17, 0, and 5. That's correct. So what we did here was we used pointer arithmetic to get the last address, ++, the incrementation operator, and then pointer arithmetic to get the length by minusing the last address minus the string. Pretty neat. I'm trying to demonstrate the power of pointer arithmetic, the notational convenience of it. How you can easily increment, decrement to get to various spots in a character array and get the characters out. In this case, we're just getting the addresses and then using the addresses to minus each other to get the length. So I hope this was helpful, and I hope make sure you understand everything I just mentioned. Again, the concept of a constant, the concept of ++, the concept of the condition. If you dereference an address and that's pointing to a null terminator, it's a 0, so it jumps out then. And then this concept of minusing two addresses. Thank you. Hello and welcome back. In this lecture, I want to talk about dynamic memory allocation. This is directly related to pointers. You can only employ this on pointers. So let's get started. So whenever you define a variable in C, the compiler automatically allocates the correct amount of storage for you based on the data type. We've seen this throughout. When we create integers, floats, doubles, we don't have to allocate any memory. The compiler does it for you. It actually allocates some memory. Same goes for pointers, by the way. When you create a pointer, memory is allocated for you so that it stores a pointer type, an address. Now, that doesn't mean that memory is allocated for that address. Up until this point, whenever we have assigned data to a pointer, we've always assigned an existing variable, right? So if we wanted to assign data to a pointer, we've used the ampersand address of operator. On a variable, that variable already had memory allocated for it. But what if you wanted to create a pointer and you didn't want to assign it the address of operator? You wanted to dynamically allocate memory. That's what this whole entire lecture is about. So it's frequently desirable to be able to dynamically allocate storage while a program is running. Allocate memory as you need it. If you have a program that is designed to read in a set of data from a file into an array in memory, you have three choices. You can define the array to contain the maximum number of possible elements at compile time. It's a fixed size. If you define the array that has 50 elements, it's only going to contain 50 elements. The compiler determines that it's 50, and it's going to allocate that much memory when it runs. You can use a variable length array to the dimension, the size of the array at runtime. We talked a little bit about these variable length arrays. They're not supported until C11. They're actually taken out in C11. They're added in C99. This is where you can put in variables. But these are still sort of fixed size because all that means variable length arrays, all it means is you can pass in variables for sizes. But they're still static. Or the best choice is you can allocate the array dynamically as you need it. And there's different C functions that you can call to do this. So it's going to be very useful to be able to dynamically allocate memory. So with the first approach, right, which we've been doing all the way up until now, whether it's an array or whether it's a data type, it's a fixed size. You have to define your array to contain the maximum number of elements that will be read into an array. So you would do something like this, int data array 1000. What this means though is the data file cannot contain more than 1000 elements. If it does, your program's going to break. So you just have to hope that whatever file you're reading in doesn't have a lot of data. Your program will not work with large sets of files or large files. And if you do want it to work with large files, you have to go back and you have to make the array larger. You have to change the size, but then you have to recompile it on all that stuff. It's compile time. No matter what value you select, you always have the chance of running into the same problem again in the future because it's a fixed size. This size is determined when you compile the code. It doesn't adjust when you run the program. It doesn't dynamically change. Using dynamic memory allocation functions, you can get storage as you need it. This approach enables you to allocate memory as the program is executing. So think of the advantages of this, right? First of all, you don't create a ton of memory that you might not use. You're only going to create as much as you need. And if you do need more, you can allocate more. You don't have to go back and recompile and change the size. So dynamic memory allocation is the way to go. It depends on the concept of a pointer, and it provides a strong incentive to use pointers in your code. So we talked about the advantages of pointers, and you may have thought to yourself, well, okay, they're a cool concept, but why do we need to use them? This is one of the big reasons, so that you can allocate memory dynamically. And again, what is this? C is all about being efficient language and not using a ton of memory. So C runs on embedded systems, real-time programming, and this is one of the reasons why. Because you can limit how much memory you use based on the need. So dynamic memory allocation allows memory for storing data to be allocated dynamically when the program executes. Allocating memory dynamically is only possible because you have pointers available. Because you have an address and you can change how much the pointer is pointing to, you can readjust the memory. The majority of production programs will use dynamic memory allocation. If you're writing code in C, you're going to use this. Even if you're a beginner, you're going to use dynamic memory allocation. Most useful programs will employ this concept. Allocating data dynamically allows you to create pointers at runtime that are just large enough to hold the amount of data you require for the task. So you're not wasting memory. Vital. We also have to talk about the heap versus the stack. There are two ways that you can store memory in a program. Two different data structures. You can store data on the stack or you can store data on the heap. Dynamic memory allocation reserves everything on the heap. We're not going to go into detail of how these are organized, but essentially heap allows the heap, when you store data on the heap, it allows for more change. You can arbitrarily change the size of data objects, and it sticks around a lot longer when you allocate memory in a heap. It sticks around the entirety of your program. When you use a stack, it's more limiting. The stack is used for everything from function arguments and local variables. That's where those are stored. And that's why when we talked about the call stack, it looked at methods, right, and functions. Functions, I should say. I use methods every now and then, but methods is really an object-oriented term, so functions. Everything related to functions are created on the stack. So what that means is when you execute a function, it gets put on the stack. The local variables get put on the stack. When you exit the function, everything gets deleted. So memory located on the stack does not stick around for very long. That's one of the reasons when you dynamically allocate memory, it's on the heap, because you're going to use it. You control when you use it and when you don't use it. You allocate it and you delete it. Stuff on the stack, you don't control. It automatically gets deleted, automatically gets allocated. So local variables inside functions like the main, those are created on the stack, and so forth. The memory on the heap is different. It's controlled by you, the programmer. When you allocate memory on the heap, it's up to you to keep track of when the memory you have allocated is no longer required. So you have to delete the memory. You have to free the space when it's no longer used by you. And this is important because memory is very, very a scarce resource, right? Today we have a lot of memory that you can run on a computer, 12 gigs, 16 gigs, whatever it is. But for programs that are embedded running on devices, you don't have that much memory necessarily. And so you want to control how much memory you use, and you also want to release the memory when you're done using it so other applications can use it. Again, more important in low-level embedded type systems. But this is a freedom that many languages don't have, this ability to control and manage your memory by the programmer. And it can make the program much more efficient and much faster. So in the next lecture, we're going to talk about how you can actually do this, what functions you can invoke. Obviously, there are different functions that you can call to allocate memory and to free memory up. Thank you. Hello and welcome. Now that we understand dynamic memory allocation, we have to implement it. We have to actually know how to do it in C code. So we're going to talk about three really important functions: malloc, calloc, and realloc. And you see that they sort of have names where memory allocation, calloc, and reallocation. The simplest and most common way to allocate memory is through the standard library function named malloc. This is allocating dynamic memory at runtime. In order to call this function, you need to include the standard lib header file. You specify the number of bytes of memory that you want allocated as its argument. What's returned from this function is the address of the first byte of memory that is allocated. Because you get an address returned, a pointer is the only place to put it. Right? So this is why dynamic memory allocation is only possible via this concept of a pointer, because it returns addresses. You can only put an address in a pointer. That's what a pointer stores. A pointer stores an address. So here's how you do it. Very simple syntax. When you create your pointer, when you create your pointer, you don't have to. You could create your pointer and set it to null, and then in the next line you could malloc. But here's the standard syntax. You're creating your int pointer to a type int, and then you'll notice that you call malloc, and in here we're saying malloc, we're gonna create 100 bytes for malloc, and then we're gonna cast it to an int pointer. Because malloc only returns a address, you have to cast it to an int pointer, because that address is storing an int pointer. This is the standard way to do it. Now, you're requesting 100 bytes of memory and assigning it to the address of the memory block to p number. P number is going to point to the first int location at the beginning of the 100 bytes that were allocated. So what this means is, since integers are 4 bytes apiece, it can hold 25 int values. And again, this is assuming that you have 4 bytes. Now, depending on the system that you're running, they may be larger, maybe smaller. So you should see the problem with this. This code's not going to work on different systems because you're allocating based on an assumption, based on the assumption of the int size. So it's not really good to use malloc in this manner with a constant number, 100. What you want to do is you want to use the size of operator. So it would be better to remove the assumption that ints are 4 bytes. Instead, if you want to allocate room for 25 integers, inside the malloc argument, specify the number of integers you want to allocate, and then multiply that by the size of the integers. And this will make the code much more portable. This code will now work on different systems, different operating systems, different architectures. You still cast the return value, the address, because it has to be pointing to a type int. So you say int star. The only difference here is you use the size of operator. Size of operator is really important when you're allocating memory using malloc or using calloc or realloc. You always want to use the size of operator for the type that you're allocating, and then multiply that by how many particular numbers you want. So if you want to store 25 ints, you do 25. So the argument to malloc above is clearly indicating that sufficient bytes for accommodating 25 values of type int should be made a variable. Also, as I mentioned, notice the cast. This converts the address returned by the function to the type pointer to int, an int pointer. Malloc returns a pointer of type void. That's what it makes it so useful, right? It returns that address, but it's a void pointer. Remember, we talked about void pointers and why void pointers are useful, because now you can have a function that can take different parameters and it can return a void pointer. Now you're seeing the power of returning a void pointer. But to use it, to actually assign data to it, to dereference it, you have to cast it. Right? If we didn't want to cast this, we could say void star p number. We don't cast it, but then we would have to eventually cast it once we wanted to dereference it. But that's why we have to cast for malloc. It's returning an address and you want it to point to a int type, and it's returning a void type. You can request any number of bytes. However, it is dependent on your system and how much memory you have on your system. So if you try to create or try to request a ton of bytes, or there's some limitation, it could fail. And when it fails, it returns a value of null. Malloc will return null. And this is good because pointers, when pointers are pointing to null, it means that they're not pointing to any memory. So you can't corrupt or change any memory inadvertently. So it's always a good idea after you do a malloc to immediately check for null before you use it. Just like it is when you assign data, or just like it is when you dereference a pointer. You want to make sure that you're actually pointing to something. So here we're allocating some memory for p number, our pointer, and then we're saying if not p number. Remember the null is a 0, so you can just use a not on it. You don't have to actually compare it to null. You can compare it to null. It makes it more readable, maybe makes it more explicit. But you can just say not p number, and that's actually saying not 1. And null is 0. So this will check for null, and if it is null, that basically means that memory was not able to be allocated. If you're not able to allocate memory in your program, you're in trouble. And so what you should usually do in this code to deal with a memory allocation failure is you should abort. You should call exit. You should get out of your program, because if your program can't allocate memory, your program's hosed. So usually you call an exit or an abort if you can't allocate memory. You can also, at least when you do this, you can display a message, terminate the program. It's much better than allowing the program to continue when we're not able to allocate memory. Because then you may continue, you may try to use that memory. It's going to be null, so the program's going to crash anyways, but you're not necessarily going to know why. You'll have to look at the call stack. It will take a lot longer to debug that error. Releasing memory. Now, I mentioned that since the programmer is responsible for allocating the memory, you have to get rid of the memory when you're no longer using it, because memory is a vital resource, especially on embedded systems. You shouldn't be using memory if you don't need it. So you have to release the memory. You always want to release the memory when it's no longer required. Memory that you allocate on the heap will be automatically released when your program exits, which is good because it does do some cleanup. But it's much better to explicitly release the memory when you're done with it, even if it's just before you exit. It's cleaner. Always do it free, or always release the memory after you allocate it. You want to follow this rule. This is a stringent, strict rule. Always release memory if you allocate it. A memory leak occurs when you allocate some memory dynamically and you do not retain the reference, so you're unable to release it. Maybe you're out of scope for that reference. You don't release it. That's called a memory leak. There's memory allocated, but it's no longer being used. This often occurs when you're in a loop and you're allocating memory in a loop. You're in the loop, you allocate this memory, you use it inside the loop, and then you jump out of the loop and you no longer release it. Each loop iteration is allocating it. So to free memory that you have allocated dynamically, you must still have access to that address. So usually you want a free memory when you're done using it, and usually in the method that you allocated it. However, if you are passing that memory to another function, and then it's that function's responsibility, but usually you want to release the memory in the function that you allocate it. To release the memory for a block of dynamically allocated memory whose address you have stored in a pointer, all you have to do is call the free function. This is in the standard lib as well. You just pass in the pointer to the free function. And usually after you pass in that pointer, you want to set it to null, because that's saying that you have no memory allocated for it. The free function has a formal parameter of type void star, so you can pass in any pointer type, and it will work. You don't have to actually cast it or anything like that. As long as P number contains the address that was returned when the memory is allocated, the entire block of memory will be freed for further use. Other programs can use that memory. Your program can now use that memory. Significant when you're on an embedded system. And then, as I mentioned, you always want to set the pointer to null to signify that that pointer is no longer pointing to anything. That memory has been freed. There's another nice function called calloc. This has a couple advantages over malloc. It's very similar to malloc, but what it does is it allocates the memory as a number of elements in a given size. And it also initializes the memory. That's the difference, initialization. I talked about the importance of initialization. That's why you always want to initialize data. You want to initialize data so that you understand that there's data in there that you're expecting. When you uninitialize data, there could be data in there that you don't have any clue about. So always initialize your data with something. And calloc is a little bit better because it does it for you. It takes two arguments, it has two parameters, the number of data items for which space is required, the size of each data item. It's declared in the standard lib header. You call it just like you call malloc. Looks pretty much the same way. In this example, we're creating an integer pointer, and we're allocating 75 integers of size of int. So it takes two parameters. It's a little cleaner because you don't have to actually do a multiplication. In malloc, you had to do 75 times size of int. Here, you just say 75. You're creating 75 ints, and the size for each int is 4 bytes, or whatever the system returns from the size of operator. But again, what the significance of this is, it's going to initialize all that data as well. The return value could be null if it's not able to allocate that memory, which in turn you should abort. But it's very similar to using malloc, except the big plus is this initialization. All of the ints are initialized to 0, and that's a really big deal, big advantage. It's also a little bit easier to use with the two parameters. Let's talk about another function called realloc. The realloc function enables you to reuse or extend memory that you previously allocated using malloc or calloc. So this is a way to dynamically change how much memory is allocated while you're running. So you could initially create so much memory, and then you realize that that's not enough memory. Well, what you can do there is you can just call realloc, and this will reallocate memory. It expects two argument values: a pointer containing an address that was previously returned by a call to malloc. So you have a pointer that has some memory allocated, or calloc, and then the size in bytes of the new memory that you want allocated. So this will allocate the amount of memory you specify by the second argument. That's the second argument. It transfers the contents of the previously allocated memory, referenced by the pointer, so it automatically knows how much memory you had previously allocated because you pass in the pointer. And then it will actually add to that, the newly allocated memory. And it returns a void pointer to the new memory. So you have to recast it when you call realloc, just like the other ones. It returns null if you weren't able to realloc, which again is probably a fatal error and you should abort. The most important feature of this operation is that realloc preserves the contents of the original memory area. You're just extending that memory. It may be fragmented because you may not have been able to do it in sequence, but you still have all that memory that you can assign to now. Data. Let's look at an example. In this example, we're going to use malloc, and then we're going to realloc the memory. And then we're going to free it. So here we're creating a character pointer. We're not initializing it to null. We probably should be. But it's not pointing to, it doesn't have any memory allocated to for what it's pointing to. It has memory allocated to store the pointer, which is just an address, but if you try to go to that address, your program would be hosed. So what you do is you call malloc. Here we're saying malloc 15. We should be doing, this will create 15 bytes for a character pointer. We cast it because it returns a void pointer. So stir is a pointer now that has memory allocated for what it's pointing to. We then can use stir copy to pass in some data to what it's pointing to, a string, and we print out the string and the address. Well, then we realize that what we allocated, 15 bytes, is not big enough. Right? So then we call realloc, and we pass in the pointer, which is stir, and we want to realloc 25 more bytes. And then that returns a void pointer, so we have to cast it again. Now, we're still going to have in memory JSON. So now we can call stir and concatenate it, and we concatenate to the string com, so now it will be json.com. And then we print it out. And then last but not least, probably the most important thing of this feature, so we don't have, or for this slide, so we don't have a memory leak, is we call free. Always call free when you call malloc. So let's take a look at this example inside code blocks. Okay, here's our code example inside our code blocks editor. And the first thing you should notice is we're including the standard lib header file because that's where our malloc functions and our realloc functions are in, as well as our free function. Also, because we're using some stir functions, concatenation and copy, we're including string.h. Now on line 8, we're going to create our character pointer. It has no memory allocated for it. We should initialize this to null because it's not pointing to anything yet. On line 11, we call malloc. Right? And we should probably say 15 times the size of char in case the size of bytes of char is different. And then we cast it into a character pointer because malloc returns a void. We then copy it. If we tried to copy this and we didn't do anything on line 11, the program would crash because we have no memory allocated for what string points to. We then just print out the string and the address. Now we call realloc. We need to store more data than 15 bytes, so we're going to realloc with 25 bytes. And we probably want to do, again, size of char to be consistent. We cast this, and then we concatenate onto our existing memory location that contains JSON, com, and we're going to print out json.com. And then last but not least, on line 20, we free that memory up, which is really important. So let's go ahead and run this, and what you'll just see is that when we print it out the second time, we have the concatenation. So our first string, we have memory allocated, and it's an address 000C29.118. Then we created a new address by reallocating and taking the existing size of the pointer that we passed to it as an argument. So 000C0CD8 actually has more data allocated to it. The existing data in JSON and 25 more bytes. And so what you notice is the concatenation works. Because when we reallocated, we put the contents JSON in that memory, and we just extended it. So a lot of advantages to using these malloc and these calloc and free and realloc calls. You want to use these, you want to understand these. Pretty simple functions to use. So in our last slide, let's just go over some guidelines. You want to avoid allocating lots of small amounts of memory. It's not efficient. When you allocate memory on the heap, it does have some overhead with it. And if you allocate small blocks of memory, it's going to have much more overhead than allocating fewer larger blocks. So allocate the memory that you need, but don't do it every 2 statements, with reallocation. Do large chunks. Only hang on to the memory as long as you need it. Memory is a scarce resource. When it's on the heap, it's even more scarce. So when you're finished with a block of memory, call free. Always ensure that you provide for releasing memory that you've allocated. Decide where in your code you will release the memory when you write the code that allocates it. Make sure you have access to that pointer. If you need to make the pointer global, then you need to do that. But usually wherever you allocate it in that function, you should release it in that function. If you have other functions releasing memory for you, you're then assuming that function, it's just not good because there's too much coupling and dependencies there. The person that creates it should be the person that deletes it. Don't put the responsibility onto other functions and such. Make sure you do not inadvertently overwrite the address of memory you've allocated on the heap before you have released it. This will cause a memory leak. So if you try to write too many bytes to it, or if you have overflows, you may have issues. So be especially careful when you're allocating memory within a loop, okay? Because this can cause problems and buffer overflows. I hope this was helpful. Dynamic memory allocation, a big deal. I'll give you a challenge that helps you become more familiar with this, but make sure you understand this concept. Thank you. Hello, welcome back. This will be our last assignment, our last challenge for our pointer section. In this challenge, I want you to understand how dynamic memory allocation works. So you're going to need to malloc a string. It's going to be pretty basic, but it will get you understanding this whole concept of dynamic memory allocation. What are the advantages of dynamic memory allocation? Well, it means that you can allocate enough memory when you need it. You don't have to waste memory, and if you need more memory, you can reallocate. This assignment is just going to have you using malloc. So in this challenge, you're going to write a program that tests your understanding of dynamic memory allocation. I want you to write a program that allows the user to input a text string. So you're going to need to use scanf. You can also use getS. We haven't talked about it a ton, but getS or fgetS on the standard input stream will allow you to read a string that contains spaces. Remember, scanf, it's only going to read the string up to a space. If you use getS, you can read multiple strings separated by spaces. Either way is fine though, scanf or getS, either way. You're going to have the user enter a string. The program's going to print the text that was inputted. And what that may seem very easy, but the difference here is that the program's going to utilize dynamic memory allocation. You can also have the user enter the limit of the string they are entering, and then you can use that for malloc, so you know how many bytes to allocate. You should create a char pointer only, a character pointer, no character arrays. I want you to malloc allocate memory. Remember, when you create the character array, the memory is automatically already allocated for you based on what the size that you put in to the brackets. And again, a big disadvantage is that is now what if you try to enter something larger than what you put in the size? You have to recompile. It's static. That memory gets allocated at compile time. Dynamic memory gets allocated when you're running the program. And so you can determine how much memory you want to allocate based on what the user enters. So again, ask the user to enter a number for the number of bytes you want to allocate for the string. Then ask the user to enter the string in, and you have to correctly allocate memory and then pass that character pointer into scanf, fscanf or getS, and then basically just display the text that was entered. And then lastly, do not forget about the all-important free function. You always want to release your memory when you're done using it, right? And you want to make sure you do that so that other programs can utilize that memory. Memory is a scarce resource, okay, especially in embedded systems, real-time programs. So don't hog the memory. Release it. Good luck, and I'll provide a solution in the next lecture. Thank you. Hello and welcome back. In this lecture, I want to provide a demonstration for our previous challenge, which was getting you to understand how to allocate memory dynamically using malloc. We're just going to do some simple reading from the keyboard and then displaying a string, but we're going to use it with dynamically allocated pointers, character pointers. So let's bring up code blocks and create a new project. And we're just going to name this one dynamic memory allocation example. And the first thing you need to do when you're going to utilize dynamic memory allocation is you have to make sure you're including standard lib. Luckily, when you create a project in code blocks, it will automatically include it for you. But the reason we need to include standard lib is because malloc, the malloc function is in there. And malloc, remember, is the main function to allocate memory. You also have calloc. Calloc is really important because calloc will do some of the nice calculating of how many bytes you need, because that's two parameters. But the real good thing about calloc is it initializes all the data to zeros if they're ints and so forth. Really nice function. You have realloc. Realloc will extend memory that's already been allocated. So you pass it in a pointer. From that pointer, it determines how much memory is allocated for it, and it copies everything that was in there to a new memory location. And then you also specify how many more bytes you want to allocate, just adds it to the new memory location. Really nice feature. But remember that when you're allocating memory for integers using malloc, you have to determine how much memory, you want to allocate bytes, but you usually want to use the size of operator, right? So here, let's get to that. In my main method, I'm going to create a integer, and I'm just going to say that's just going to be size. The user is going to enter the size of how many bytes they want to allocate at runtime. So that's going to store the size. The other thing I want to create is I want to create a char pointer. And this is just going to be text. And I'm going to initialize this to null because it's not pointing to anything right off the bat. Now, first thing I want to do is I want to ask the user to enter the size. So I'm going to say printf. I'm going to say enter limit of the text. And they're going to enter a number for how many bytes want to be allocated, really be the number of characters. And then I'm going to read that in by using scanf. Scanf, the first parameter is the type of the format specifier for the type of the data. So it's going to be %d because I'm reading in an integer. And then remember, scanf takes a pointer. We now know that functions that take pointers, you need an address to pass in. So if I'm going to pass in size, size is not an address unless I use the address of operator. So I'm going to use the ampersand and I'm going to say size. That's going to read in the number of bytes. Once I have the number of bytes, I can now allocate memory for it using the malloc function. And malloc is going to return a void pointer, and the pointer is going to be the first address for that newly allocated memory. So you can assign it right to text. Because remember, text is a pointer. We want to point text to this new address that's being returned. Because malloc returns a void pointer, we have to cast it. The type of data that we're pointing to is a character, so we want to say char star. Right? And then we can call the malloc function. The malloc function takes a number of bytes, right? And so the number of bytes, if you just passed in the number of bytes, it's only going to allocate that many bytes. But depending on the type of the data may be 2 or 4 bytes. So if you wanted to allocate 10 characters, you want to make sure that you multiply 10 characters times the size of char. So now we're going to say n times size of. The size of operator is often used in the malloc function, because it's machine independent and it will tell you how much you actually need to allocate. Now, this is more relevant when you have integers. Remember, integers, depending on the system that you're on or the architecture that you're running, integers can be represented by 4 bytes, 2 bytes, usually 2 or 4 bytes. If you were to say, I want to store one integer, so I'm just going to create 4 bytes of memory, well, that might not be correct, because what if it's 2 bytes? So you always want to do how many integers or how many characters you want to create, and then multiply that by the size of the character on your system. The size of operator will give you the number of bytes a char occupies. So if you want to create 10 chars, you say 10 times size of char. If you want to create 10 integers, to store 10 integers, you say 10 times size of int. That's really important. Now with the calloc function, you don't have to do that. Calloc actually takes 2 parameters, and the first parameter is the pointer, I think, and then the second parameter is the size of bytes. So if you say 24 ints, then all you do is you have to pass in just 24 and it'll automatically allocate it for you. So calloc's a really nice tool to use because you don't have to do this multiplication. So for calloc, the first parameter is the size. So if you wanted to create 10 ints, you would just pass in 10. And then the second parameter is the size of the bytes. So you don't have to do the multiplication. It saves you a little bit of the step. Now that we allocated memory, you want to make sure that text isn't null before you try to dereference text. So you always want to wrap this around a not text. And that will say it's not null. Or you can just do explicitly and say if text is not equal to null. Always want to do that because it's very, very dangerous to try to dereference a pointer. You have anything could happen. You might be able to write data into it. It would just write it somewhere else in memory, so it would screw up your program, or you may have a segmentation fault and the program may crash. But as long as you're able to allocate that memory, you can now actually read in some data. You can use getS or you can use scanf here, but what you want to do is you want to print out, enter some text. And we also want to add line feeds here so they're easy to read. And we'll use scanf since that's what we're familiar with. And scanf is just going to read in %. Actually, I'm going to show you a trick. I'm going to use scanf to read in the next character so it pauses, and then I'm going to use getS to read in the text. And getS is just another function. Usually you can use fgetS. You just have to set it to the input stream. But getS is going to read from the standard input stream, which by default is the keyboard. And getS is going to takes a pointer. So all we have to do is pass in text because it's already a pointer. We don't have to put in the address of operator. And the nice thing with getS is that you can read in multiple strings separated by spaces. Once we actually read in getS, we can just print it out. So we can say inputted text, if inputted is a word, %s, \n, and then comma text. Text is a pointer, printf takes a pointer, we don't have to dereference it. This is going to give you, actually do want to dereference it, sorry about that, because if you just display text, text is going to display the value of the pointer, which is going to be an address. We actually want to display the value of what text is pointing to, right? And then we're done, right? Oh, nope, we definitely are not done. We want to call our free. We want to free our pointer. Even though when we exit, the memory is going to be free, we still want to make sure that we free it. And then we also probably want to just for safekeeping, we want to set text equal to null. So let's go ahead and build this and see what happens. And I do have a problem because I'm not reading in the right variable. N is undeclared, so here I'm not using the right variable. I want to use size. And it looks like we're good. So here we go. The one difference here is you don't have to dereference the text because text is a character pointer. You only have to dereference if it's in pointer and so forth. So you can just, when you use the %s, it automatically knows to dereference the character pointer. That's one difference when you're using character pointers versus other pointers. The other pointers you have to dereference to get the value. Because you can't actually copy strings to string arrays and so forth, you would never be able to do star text equals. You'd have to always use the star copy if you want to copy text, because you can remember from the lectures you can't actually assign data to an array, and a character pointer is an array. So here this looks correct, no reason to dereference it. We want to build this and then we want to run it. And you'll notice we put the limit of the text. So say we put in 5, 6 for JSON, and it prints out input is JSON. And you can play around with this program, but again, the takeaways from this include standard lib when you're doing malloc. Right? Initialize your pointers, your character pointers to null. Do a scanf, use the ampersand because size is not a pointer. When you're mallocing, malloc returns a void pointer, so you have to cast. You always want to, inside your malloc, do the size of operator for what you want to allocate for, times how many actual characters or integers. This is more applicable to integers and primitive data types. Technically for characters, you can just do size. That should work fine. You always want to check for null. Make sure it's not null when you go to use a character string. And then we just enter some text stored in our getS and print it out. And then last but not least, we always want to free our pointers so that we can give that back to the heap. Hope this helps. Thank you. Hello and welcome. We are in a new section. We're going to be talking about structures. This is a new concept in C that allows you to group items together, similar to array but more powerful. I want to talk about what a structure is, how you can create, and how you can use a structure. So structures in C provide another tool for grouping elements together. Again, I mentioned they're similar to an array, but they're actually a bit more powerful. If you're familiar with object-oriented programming, if you program in Java or C++ or any object-oriented language, it's kind of thought of as an object, but only with data members, no actual behavior, no methods. So it's a powerful concept that you will use in many C programs that you develop, because you can group different items together in a single name, and those can represent essentially data attributes. So for example, Say you want to store a date inside of a program. A date usually consists of 3 variables, month, day, and year. You would create those 3 variables to store that data. For example, you'd say int month equals 9, day equals 25, year equals 2015. Suppose your program also needs to store the date of purchase of a particular item. Well, you'd probably have to go and create 3 more variables for each date that you use in your program. So you can see how this can get very repetitive and you end up creating a lot of variables. But what you should notice is these variables are logically related. They're all dates. They really should be grouped together. They should almost be their own data type, and then you should be able to create them and access the different elements. You shouldn't have to create 3 separate variables for every single date. So again, this is where it comes into relation to objects and a class that has 3 data attributes. So it would be much better if you could somehow group these sets of 3 variables together. And this is precisely what the structure element does in C. It allows you to group these different elements together with a particular name. You can then create different variables of that name and access the elements in that name, the different data attributes. They're really called members. So how do you create a structure in C? It's very, very simple. Structure declaration describes how a structure is put together, what elements are inside the structure. And we usually refer to these elements as members. Okay, because you first have to define the structure or declare the structure, describe what is inside the structure. And so you can do that with the struct keyword. The struct keyword enables you to define a collection of variables of various types called a structure that you can treat as a single unit. Very, very powerful. So by using this struct keyword, all you have to do is provide a name, and this is usually referred to as the tag name. In this example, we have a tag name of date. But you see the keyword struct. That's the keyword that tells the C compiler that this is going to be a specific function. This is going to have specific functionality that allows you to group elements. So struct is the keyword followed by the tag name, and then you have the left curly brace and the right curly brace followed by a semicolon to end. And then inside there, you can define any types of variables you want. You can even put pointers in there. And those are called the members of the struct. So this is a statement again. It defines a date structure that the C compiler will understand. It tells the C compiler what this date structure is going to contain. 3 elements, month, day, and year. There is no memory allocation for this declaration. Again, what you're saying is this is a structure that exists. I haven't started using it yet. I just said this is how it's going to be defined. This is going to be the date structure, and this is what it consists of. The variable names within the date structure, the month, the day, and the year, those are called members or fields. Members of the structure appear between the braces that follow the struct tag name, date. So tag name, date. Very, very simple syntax to group these elements together inside of a single name, which is date. And you notice it's different from an array because there's no indices. You're not actually specifying a size. It's not the exact same data type. You can have different data types and you can have many different ones. So how would you utilize this structure? Well, the definition of date defines a new type in the language. You can really think of it as another type, just like an int, a double, or a float. Except this type you defined. You can almost think of it as an enum, except an enum only holds 1 value. This date structure can hold 3 values, but it is another data type. Variables can now be declared to be of type struct date. So that's exactly what you would do. You could create a new variable called today, and it's going to be type struct date. And today is essentially going to be able to hold 3 values. And then if you need to declare more dates, you can create more variables of that same type. And so you no longer need to have 3 separate variables for a purchase date, 3 separate variables for the current date, 3 separate variables for a billing date. You can have 1 variable or 2 variables of different instances of that actual struct. Again, hopefully you notice how powerful this can be. So this above statement declares a variable to be of type struct date. Purchase date. Memory is now allocated because you declared the variable. Memory is allocated for this structure. Memory is allocated for the 3 integer values or the 3 members of each variable. So that memory is going to be allocated. And also, the reason it's going to be allocated is because there's no pointers in there. If there were pointers in that struct, you would have to allocate memory for that pointer. But since this today date struct, it's a very simple struct. I'm starting off slow. It contains 3 ints. Those members are automatically allocated for you. But make sure you understand this distinction from the previous slide and this current slide. There's a difference between defining a structure and declaring the variables of that particular structure type. All right, defining the structure, again, is just telling the C compiler, here's a structure, and this is the data that's inside of it. But actually, declaring a variable of that particular structure type is saying, I'm going to start using that structure. I now have memory allocated for the 3 elements in our example, and I can access those elements and set them. So how do you access the members in a struct? So now that you know how to define a structure, and now you know how to declare structure variables, you now need to know to be able to understand how to refer to those members of struct. Right? You have to access them. If you couldn't access them to see the values or set values, it would be useless. So a structure variable name is not a pointer. So you need a special syntax to access the members, because pointers usually contain just the value of an address, right? And if it's not a pointer, then you're going to need some special syntax. You can refer to a member of a structure by writing the variable name followed by a period. It's usually called like the dot operator. And then after that dot operator period, you follow the name of the member variable inside of that struct. The period between the structure variable name and the member name is called the member selection operator, also referred to as the dot operator. There are no spaces permitted between the variable name, the period, and the member name. To set the value of the day in the variable today to 25, I would just do something like this. The name of the variable, which is today, and then I would say dot, no spaces in between either side, and then I would specify the name of the element inside the structure definition, which is day. And then I would assign it just like I assign any other integer. I would use the equals assignment operator, a literal constant here, and the semicolon. Very, very simple. If I want to assign the year, I would say today.year, and I would say equal 2015, for example. And when I want to access the member values, for example, if I wanted to access the member value of month to see if it's equal to 12, I would still use that dot syntax, that member selection operator. So you can use the member selection operator to access the members' values. And when you access those member variables, you can use them just like you use other variables. You can use them in arithmetic operations. If they're ints, you would follow the rules of that data type. So in this case, we can actually compare that int to 12 just using the equals equals inside of an if statement. And then, for example, if it was equal to 12, we could say next month equals 1. That would maybe a local variable that we would assign. So let's look at an example. Here we're defining a struct called date. We have 3 elements, integers, month, day, and year. We know that we're defining it because we have the struct keyword and we have those curly braces. And then also notice that right curly brace has a semicolon to end the definition. At this point, no memory is allocated for the structure. In the next line, we actually declare a variable of that type. So we're now allocating memory for a variable named today that contains 3 elements essentially, month, day, and year of type int. We can assign data to those 3 elements inside that struct today by just using that dot member access. So today.month equals 9, today.day equals 25, and today.year equals 2015. If we then wanted to print it or access that data, we would access it the same way after we assigned it. We would just use that member selection, today.month, today.day, today.year. And again, we can perform arithmetic operations on it because it is an int. We would use %d, or if we want to format it to 2, we could say %2i or %2d. So this is pretty straightforward syntax. Very easy to create and define structures and then use them, and then access them using the dot member selection operator. How about structures and expressions? Well, you just saw that I was able to access data and use it in an arithmetic expression, and it's no different. So when it comes to the evaluation of expressions, structure members follow the same rules as ordinary variables do. If you have members inside that struct that are integers, you can do the same rules of any other integer. You can apply additions, subtractions, and so forth. If it's a character buffer, you can only do the rules of character buffers. Can you add and minus character buffers? things like that. Usually not. So floats, doubles, all the different data types, you would just follow those same rules when you use those members inside of expressions. So here's an example. I say today.years divided by 100 plus 1. Perfectly valid because year is an int, no different than using a regular variable of type int. You just access it differently by using that member selection operator. Now there are variants. There are different ways to define the structures. The one thing great about C is its flexibility, and C allows you to define a structure in many different ways. So you may see different syntax when you define a structure. The first example that I showed you is really the one you should follow. You should always have a tag name, and you should define the structure in one place of your code and then declare variables of it in another. But C being it as it is, it's very flexible. You can actually define structures and declare variables in the same line, and you can also define anonymous structures or no named structures. So there's a lot of flexibility. It's valid to declare a variable to be part of a particular structure at the same time that you're actually defining the structure. You can put the name of the variable at the bottom. I'll show you how to do that. Include the variable name or names before the terminating semicolon of the structure definition. And you can also assign and initialize values to those variables in the normal fashion that you assign any variables. So let's look at that. A variation of defining a struct, doing it in the same same time as you're defining it, you can declare a variable. So in this case, we defined our struct date, but we also created a variable called today. Because at the ending right curly brace, that's the name before the semicolon. That is doing both the creation of the variable of type date struct and the definition of the struct date. Very nice. So in this above instance, you're creating a variable of the structure. We refer to that also as an instance of the structure. It's called today. It's declared at the same time that the structure is defined. So today is a variable of type date. We did it all in one. And you could actually, right after you do the today, you could actually initialize those variables by using the brackets and then saying month equals 5, day equals so on forth, so forth, just like you initialize any other integers. Now, again, another way you could create a structure is you could create an unnamed structure. This is a little bit more limited because you can't do much with it, but you don't have to actually provide a tag name. Remember, the tag name is at the top right after the struct keyword. In the previous examples, the tag name was date. But you don't have to provide that date. If all of the variables of a particular structure type are defined when the structure is defined, then the name can be omitted. And what this really means is you're only going to use the structure one time and one time only. So we could just say struct int day, int year, int month, and then declare the variable in the same thing, but you'll notice there's no tag name there after the struct keyword. This is just one struct we're going to use one time, so we create the variable today, and then we're never going to use it again. And that's really the disadvantage of it and the limitation. You really never want to do this unless you have some kind of local struct that you use once. But you can't define further instances of this if you define the structure this way, as a no-name structure, an unnamed structure. All the variables of this structure type that you want in your program must be defined in the one statement. You could create more than one variable. You could do the today, comma, and then another variable, so you could create multiple variables. You could initialize multiple variables. But this way is a bit limited because you can't, after that variable declaration at the bottom, you can't create any more variables. So there's three ways to define different structures. One way is to define the structure with a tag name and not creating the variable. You create the variable in a separate instance where the memory would be allocated. Another way is to create the variable and the structure at the same time where you would have a tag name, and that would allow you to create other instances or other variables of that struct type later in your program. Or this third option where you could create an unnamed struct with no name and just the variable at the bottom. And again, you can initialize all of these whenever you create either of the variables just using the curly braces and so forth. So now initializing structures. Initializing structures is very similar to initializing arrays. The elements are listed inside a pair of braces with each element separated by a comma. No new stuff to learn here really. The initial values listed inside the curly braces must be constant expressions. You can't use variables. Looks just similar to an array. Here we're creating a today variable of type struct date, and we're saying that the first member is equal to 7, the second is 2, and the third is 2015, which corresponds to the month, day, and the year, because that's the order of how they were defined in the struct. So just like an array initialization, Fewer values might be listed than are contained in the structure. You don't have to provide all three. You could just provide two. And that would initialize the month and the day, and it would not initialize the year. You could also, so this would set the date.1.month to 12, date1.day to 10, but it gives no initial value to date.year. You can also specify the member names in the initialization list. This way you don't have to actually have any order. You can put them in any order you want, and you're not dependent on that. So you could do something like .member equals value, and struct date, date 1, you could say .month equals 12. Right? So the initial syntax of this is setting the member inside the curly braces with the dot, and then just assigning the value. .month equals 12, comma, .date equals 10. You need that dot. That dot is important, so don't forget about that dot. You don't need the instance before the dot. So this is just going to set the year member of the date structure variable today to 2015 in this next example. So here we just say, because remember you can omit some of the other member variables, and in this case we're omitting the month and the day, so we're just going to set the year to 2015. In the previous case we actually omitted the year and just set the month and the day to 12 and 10 respectively. We can also do assignment with compound literals. Well, what exactly is a compound literal? You can assign one or more values to a structure in a single statement using what is known as a compound literal. I believe this might only be in C11. But here we have today, let's assume that we created a struct date today variable, and then we're actually putting inside the parentheses struct date, and inside the curly braces saying 9, 25, 215. And this is a compound literal. This statement can appear anywhere in the program. So as opposed to actually initializing or assigning values using the dot member, you can put this anywhere in the program after you've actually already initialized the today's struct. It's not a declaration statement. This is a compound literal assignment. The typecast operator is used to tell the compiler the type of the expression. So you need those things in parentheses. That's a cast, struct date. The list of values follows the cast and are to be assigned to the members of the structure in that order. It's order dependent. So it's listed in the same way as if you were initializing a structure variable. Again, the advantage of this is you don't have to assign each member variable individually on separate lines. You can do it all in one line and say, okay, this is the new value for this variable today. You can also specify values using the dot member notation, as I mentioned. You would just have to do it in one line like this, or on separate lines. And this way it sort of looks like the initialization, but you're still doing the compound literals. The advantage of using this approach is that the arguments can appear in any order. So just like previously. Again, the key in the difference of these assignments is it's not happening in the initialization. You're doing it somewhere else in the program to assign new values to that type. So a lot of good information in this lecture. We talked about structs and how powerful they are and how we can group different elements or different variables into a single name. We define that structure. There are various ways to define a structure. And then we also need to declare a variable. Once we have that variable, we can access assign data to that structure using the dot member selection operator. And then we also discuss some of the different notations and different ways of doing things as well as initialization. We're going to use structures quite a bit. I'll have a couple challenges that help you get familiar with this syntax, but this is just the start of the structure. We also have to talk about nested structures, how you can use pointers in structures, and things like that. So good luck. This is going to be a fun and exciting section. Thank you. Hello and welcome back. We're going to have our first challenge for structures. Let's begin. This is going to help you understand structures, how to declare them and initialize them. So I want you to write a program that declares a structure and prints out its content. We should know how to declare a structure, right? We use the struct keyword, and then we have the tag name, and then inside the structure we can put different elements. So I want you to create an employee structure. That would be the tag name, with 3 members. A name, which should be a character array. It doesn't have to be a character pointer. A hire date, which is an int, and a salary, which should be of type float. I want you to declare and initialize an instance of the employee type. So you should use the struct, and then you're going to have to know how to initialize members in a struct. I then want you to actually read in from the console 3 inputs, the name, the hire date, and the salary, and then store it in the same structure type of the one that you previously initialized. But before you store it in the type that you initialized, I want you to print it out. So you create your first structure, your only structure, you initialize it, you print out the contents, and then you read from the keyboard 3 more instances of data and put that in the employee type and then print that out. All right, so this isn't a pointer, so when you read it in from the input, you're going to have to use the address of operator, things like that. But the rest is pretty straightforward. But this will get you familiar with, again, creating a structure, defining it, and then initializing it and creating an instance of it. When you define the structure, you can define it outside of the main method so that it can be used by any other function. That's typical standard convention. So good luck. This should be pretty straightforward. We'll have another challenge to get a little more detail. We'll pass a structure to a function and so forth. But this is just going to get you started. Thank you. Hello and welcome back. In this lecture, I want to provide a demonstration of a solution for our previous challenge. So what I want to do is I want to show you how you can declare a structure, also define a structure, its contents, and then initialize it, and then read in some data and print it out. So this will get you familiar with the basics of structures. Here we have code blocks. I'm going to create a new project, and I'm just going to name it something simple, console application. Let's name it basic structure example. And this will create our main force. We know all about this. It will include 2 files as well. And we're going to delete the hello world. So I wanted you to create a structure of type employee or name employee with 3 elements: a name, an employee ID, and a salary. Actually, I think I wanted you to create a name, a hire date, and a salary. So to create a structure in C, all you have to do is use the struct keyword, and we want to define it outside of the main so that we can use it in other functions. It's a global definition, but it's no big deal because you can still create the instances or the actual variables inside each function. So we say struct, and then we provide a tag name. If you remember from the lectures, the tag name is actually optional. You don't have to provide a tag name if you're just creating a local structure with just a single variable. But since this is going to be used in multiple functions, we're going to provide a tag name. We're going to provide the tag name of employee, and then we're going to have our left and right curly braces. It automatically adds the semicolon for us. We could create a variable instance in the same at the same time we're defining the structure by just putting a variable name here, but we're not going to do that. So here I want to just create a name. It's going to be a character array. I'm just going to place it as 30 characters. I'm also going to have a hire date. I think I said the hire date should be an int, but you could make it an int or a character array. I'm going to put it as a character array. And we'll make that just 15 as well. And then our salary, which will be a float. So what we're doing here is we're creating this nice structure. Structure is great because you can group things together in a single variable, and you can also use it with arrays, and you can store a lot of elements. But it's nice that we now have this employee structure that has data associated with it. Now to actually use the structure, you have to create a variable instance of it. So here we're going to just create a structure employee type. All we have to do to create a structure employee type is use the struct keyword followed by the name, which is employee, and then an instance or variable name. And here we're saying we have an employee Mike, and we're going to actually have the second parameter. We're going to define it as a date inside quotes. So we're just going to say 7/16/2015. And then the last thing is their salary, $76,909. They're making pretty good money. And then we want to print this out. You'll notice that on line 14, we didn't create a pointer. So in order to access this employee struct, all we have to do is use the dot modifier or the member access. And then we just use the format specifiers for each variable type, which is %s, and %f. So this is pretty straightforward. To print out the data inside the struct that we already initialized, we can just print out some line feeds and format specifiers. Again, the way that you access the structure variable is you just use the dot, and that will give you the element inside of it. And we initialized it with the curly braces with commas separated the variables. So let's try building this and see what the output is. It should be exactly what you think it would be, which is what we initialized it to. We do have an error. We don't have an employee ID. Got to make sure I use the right ones. This is a date. I had different variations of this program, decided to use a date, and it's also going to be a %s. So now when we build, hopefully we're okay. And we are. So when we run this, we're going to get out Mike, ID, I got to change that, date 7/16/15, and then our salary. It'd probably be nice to do some formatting here. We want to change this to hire date. And we probably just want to say .2 for our format. And now we run it, the format, the data output looks a little bit better. $76,909, $716. Everything looks good. So now let's read in from the keyboard some of the values and store it in the struct. We can still use the same instance or the same variable name. Here we're just going to tell the user to enter some information. So we're going to say printf, and we'll just add some line feeds. And we're going to say enter employee information. And we'll end it with a line feed, a semicolon, and then we're going to say printf name and end it like that. And then we're going to get the actual name. We're going to use getS since we used it a couple times already. GetS, well, no, let's use scanf. We're going to say %s, and that is going to read in the employee name. So all we have to do here is employee.name, and this is a character array, so we don't have to provide the address. And then we're going to say printf. After they entered their name, we're going to say printf, and we'll add a line feed. And then this time we're going to say hire date. And then this time when we do a scanf, we're going to do a %d, or actually %f for float. And then this time we need the address of operator because this is not a pointer. And the scanf function does take a pointer, so we just need to say employee dot employee ID. Or I'm sorry, hire date, right? Or date. And then we want to print out the salary. Tell them to enter their salary. I want to have a line feed for that. And we want to use scanf to read in, and the date is in %s, and the salary is a %f. And then here is where I want to say, and the date is wrong again. Don't need the ampersand for the date because that's a character buffer. I need the ampersand for the salary. Just like that. We could probably add some line feeds so it's a little bit easier to read. Put some comments in there. And then we just want to print out the information. We can print it out just like we did before, so we could copy and paste lines 16, 18. Just do a Control-C, Control-V. And now we're good. Let's try to build and see where we're at. So it's first going to, when it runs, it's going to output the information that we hard-coded or initialized. And then we're going to enter some information. So for my name, I'm just going to say Jason. The hire date, I'm going to put 8, 9, 10. And the salary, I'm going to put 32,000. And it prints out Jason, 8, 9, 10, 32,000. So this is just a simple example of how you can create structures, first defining them globally, and then creating an instance of it or a variable type of it, and then printing out the information and entering information. Keeping aware that we need to use the ampersand, the address of operator, when we input data, and in other instances, we don't need to do that for the character array. I'll provide a solution for this as a zip file. Good luck, and please ask questions if you need to. Thank you. Hello and welcome back. Let's continue our discussion on structures and talk about how they're related to arrays. We talked about how structures are similar to arrays and that you can store more than one value, but they're different because you can have different data types and you can group them that way. But you can also actually have like arrays of structures. So you've seen how useful structure is in enabling you to logically group related elements together. We've seen that. We know how to define a structure with different elements using the struct keyword, using a tag name. And we also know how to create a variable of that type. Because what a structure is, essentially, is it's a new type of data that you can use. And then you can access elements of a struct using the member selection operator. Well, what about if you want to create multiple structures that is inside of an array? You can do that. So for example, it's only necessary to keep track of one variable instead of 3 for each date that is used by the program. That's the advantage of a structure. If we wanted to handle 10 different dates in a program, we'd only have to keep track of 10 different variables instead of 30. Because remember, the structure contains 3 variables inside of itself. 10 different variables is still kind of a lot, so it's really not the optimal way to go. You'd probably want to create an array, because you'd have 10 types of the same, just like you'd have 10 ints the same. They'd just be a structure type. So a better method for handling the 10 different dates involves the combination of 2 powerful features of the C programming language, structures and arrays. You can use them together to make it even more powerful. So it's perfectly valid to define an array of structures. The concept of an array of structures is a very powerful and important one in C, so pay close attention. Declaring an array of structures is just like declaring any other kind of array. You specify the type, it just so happens it's a structure type. So if you want to create an array of structures that are named date, you would say struct date, and then the variable name, and then you use the brackets, just like you use the brackets for other arrays. You have to specify the size. So in this case, if we're creating 10 instances or 10 elements of the date struct type, we would say 10 inside those brackets for the sign. So this would define an array called myDates, which consists of 10 elements. Each element inside the array is defined to be of type struct date, which contains 3 members. So essentially what you're doing is you're storing 30 different sets of data, 30 different data elements. To identify members of an array of structures, you apply the same rule you use for individual structures. You follow the structure name with the dot operator and then with the member name. Referencing a particular structure element inside the array is quite natural. To set the second date inside the myDates array to August 8, 1986, all you have to do is you specify the name of the array, myDates, and you specify the index. We're specifying here the second date. Remember, arrays are 0 based, so we say 1, sub 1. And then if we want to access elements of that array element or members of that struct for that element, we say dot month. So this is going to give us the second element in the myDates array, the month value for that struct type. And here we're going to assign it the value of 8. And then if we want to access the day, we're also going to assign the day 8, right? Because it's August 8th. And then finally for the year, we would say dot year equals 1986. This is how you can assign to the second element of the myDates array the 3 different variables because it is of type struct, date struct. So really, you should notice that it's really not any different. The only difference here is you have a dot. Normally you would just say myDates sub 1, and that would be it because you could only assign 1 variable depending on the type of that array. But in this case, you can say sub 1 with 3 different variables because those are the 3 elements inside the struct. Initializing an array of structures. Initialization of arrays containing structures is similar to initialization of multidimensional arrays. Remember, with multidimensional arrays, we would follow the specific syntax with curly braces on the outside and then curly braces on the inside representing each row. The curly braces on the inside were actually optional, but it made it much more readable. And so I like to follow that convention. In this example, we're creating a myDates struct of type structure date. It's going to be of size 5, and then we're going to initialize only the first 3 elements. And so we do it just like a multidimensional array. We have those curly braces inside. And so the first element in the myDates array, which is sub-0 index, we're going to say the month is 12, the date is 10, and the year is 1975. And then we're going to do the same for the first element. We're going to say 12/30/1980. And for the third element, we're going to say 11/15/2005. And because we didn't supply the other 2 elements in the myDates array, those are not going to be initialized to anything. So this will set the first 3 dates in the array myDate to 12/10/1975, 12/30/1980, and 11/15/2005. The inner pairs of braces are optional, just like in a multidimensional array, they're optional as well. But again, it makes it easier to read, easier to follow with those inner braces. I would follow that convention. So you could do this if you want to get rid of the braces, but it's a little harder to follow because now you just have commas separated by commas, and or elements separated by commas, and it can get very confusing if you're doing a lot of those. You have to map that correctly. You say, oh, I'm in the fourth element for my fourth comma. Okay, that's going to be the second element of the array. It's harder to follow. So use those inside curly braces. If you want to initialize just the third element of the array to a specified value, you can specify myDates sub 5. You're still creating the array here. You're still declaring the variable and setting the size to 5. But inside the curly braces, you're saying 2 inside brackets, and you're going to initialize 2 to 12/10/1975. So you'll see the square brackets that represent the element that you want to initialize, then the assignment operator equals, and then inside the curly braces, you're initializing the month, day, and year for the elements inside the struct. So you can specify exactly what element you want to initialize as well. If you want to just set the month and the day of the second element of the myDates array to 12 and 30, you can do something very similar. You just do a comma to separate each attribute. You don't want to actually set the year, so you wouldn't be able to use those curly braces. You could say dot month equal 12, sub 1 dot day equals 30. And again, this syntax looks very similar to initializing struct variables elsewhere. The only difference here is because it's an array, you have to specify the index of the array. But similar syntax. What about structures containing arrays? Elements inside the structure that contain an array. It's also possible to define structures that contain an array as a member. This might be useful. It's the most common use is to set up an array of characters inside a structure, right? We use char arrays quite a bit, right, for strings. So it would be very common for a structure to contain a string, essentially, a character array. So suppose you want to define a structure called month that contains as its members the number of days in the month, as well as a 3-character abbreviation for the month name. Well, that's where we could use a character array. We could say struct month. We know how to define a structure. Again, this is not allocating any memory. This is just saying this is how the structure is defined. These are the elements that are contained inside of it. Here we're using the struct keyword. We say the name of the struct, the tag name is month, and then we have that left curly brace, and then we specify the elements. We have one element, which is integer, represents the number of days. We have a semicolon at the end. And then we have a character array. Character name sub 3, so it's size of 3. Because it has 3 characters. And then we end the structure with the right curly brace and the semicolon. But remember, characters are arrays, right? And they're closely related to pointers as well. We know that by now. But you can easily have structures contain arrays by just putting them as a member element. And so this sets up a month structure that contains an integer member called number of days and a character member named called name. Member name is actually an array of 3 characters. Pretty straightforward. So how do you actually access it? Well, first you'd have to create your variable, right? The variable would create memory for the elements inside the struct. And then you'd want to just set the proper fields inside the a month variable, the character array, right? Because that was the name of it, right? We had name and number of days. Here it's called name, and the example it's called a month. Well, a month is the variable type, and then name is the element type, so that's correct. So here we create a struct. It's of type month. The variable name is a month. We don't initialize it with anything. We immediately set a month number of days of 31. We use that dot member selection operator. And then when we want to assign to the character array, we can't assign directly to a character array. You'd have to do a stir compare or something if you wanted to assign everything. And you could do that. You don't have to use these indexes. You could say stir copy a month.name, comma, and then JAN in double quotes. Or you could do it this, where you access the elements of the array via the index. Here we're saying a month.name because we have to access the name member variable, or member element. And then inside the brackets, we specify the index of the array. We're assigning the first character in the array to J, second one A, third one N. You would see this syntax if you were doing ints and doubles and floats. Normally, when you have a character array, you'll use the stir copy function and assign everything with double quotes. You can also initialize the variable to the same values by doing something very similar when you declare the variable. just inside the curly braces, you have, because it's an array, you can have inside inner curly braces and then the single quotes around each character. And you can set up 12-month structures inside an array to represent each month of the year. So now we can create a month's variable, which is an array of size 12 of type struct month. And that can represent each month. And then we can, for each month, we can spend the number of days and then abbreviations for the month. So utilizing these two powerful concepts of arrays and structures is very, very useful. Structures can have many elements, so they can actually be a structure of arrays, and elements inside the structure can be an array. And we're going to next talk about how we can use structures to contain other elements like pointers. But you'll see that structures can store any type of data and many different types of data. And it's very, very useful to use with the array concept. Hope this was helpful. Again, we'll have a challenge that kind of demonstrates some of these concepts and bring up some examples inside code blocks later. Thank you. Hello and welcome back. More on structures, particularly nested structures. Nested structures, structures inside structures. That's what that means. So C allows you to define a structure that itself contains other structures as one or more of its members. So pretty neat concept here. You can have structures inside of structures. So you've seen how it's possible to logically group the month, the day, and the year into a structure called date. We've been sticking with this example of date. Well, what about if we want to actually group time, the hours, minutes, and seconds, into a structure? That seems like that would be useful as well. So here we would have a structure called time, and it's very similar to date. It contains 3 elements. We know the name of the structure is time because it follows the struct keyword. That's the tag name. And then inside the curly braces, we define our elements, our data types, and names of our variables. And we know now that we can also put an array in there if we wanted. But in this case, we don't need an array. We just need 3 integers. We end the structure with the right curly brace and the semicolon. What about, though, in some applications, you may want to actually group both the date and the time together. It would make sense, right? Because the date and the time are logically organized. They're logically together, right? They're logically grouped. So you could set up a list of events that are to occur at a particular date and time. And so this might be a very useful case where you'd want to use a nested structure. So you have a convenient way to associate both the date and the time together. We can define a new structure called, for example, date and time. This would contain as its members 2 elements, a date and a time, which are both structures. So we now have a nested structure. We have a structure named date and time that contains 2 other structures. Something like that. And the syntax is very similar to creating other structures. The only thing different here is inside the actual structure as the element names, you have the struct keyword, the name of the struct, and then the variable name. So in this case, we're creating a date and time struct, and we have 2 structs. One's of type date, one's of type time, with 2 variables, sDate and sTime. The first member of the structure is of type struct date, and it's called sDate. The second member of the date and time structure is of type struct time, and it's called sTime. Variables can now be defined to be of type struct date and time. We don't have to create separate variables for date, separate variables for time. We can create one, and that structure is going to store both the date and the time. We would do that just like this. We would use the struct keyword, specify the type of the structure, date and time, and then the variable name. In this case, they're going to store events, so we say event. When we want to access the members in a nested structure, again, pretty straightforward syntax. All you have to do is reference it like any other member. You have to use that dot member selection operator. So we'd use it pretty much a number of times. So if we have a structure named event and we want to get the date, we say event.sDate because that's a member of that date and time struct. Now, if you want to reference a particular member inside of sDate, again, you would use the period followed by the member name. That would be tacked on the end. So this below statement is going to set the month of the date structure contained within event to October, and it's going to add one to the seconds contained within the time structure. So we say event.sDate and then another dot because we want to access the element of the sDate variable. We want to access month, and we're going to assign month 10. So there's multiple dots there. And all this is saying is you have a struct named event, And because of our declaration before, we said it was of type date and time. Inside there, you have a struct, which is just a date struct. You want to access of that date struct the month member. So you say dot month, 2 dots. And then if we want to change the seconds increment by 1, we can just say plus plus. We can use that incrementation operator, plus plus event, dot stime dot seconds. We have to include those 2 dots. And seconds is an integer, so it's just going to add 1 to it. Very straightforward. The event variable can be initialized just like normal structures. If you want to set the date in the variable event to February 4th, 2015 and the time to 3:30, you would say struct date and time event. You would create it just like normal, and then you'd have those curly braces to specify the different structs initialization members. So in the first curly braces, we're going to initialize the date. We're going to initialize the month to 2, February, the day to 1, and the year to 2015. And then we end the curly braces and we put a comma after those curly braces. And then the second, which is kind of it looks like a multidimensional array initialization, we say the time is going to be equal to 3:30 with 0. So 3 hours, 30 minutes, 0 seconds. You can use the members' names in initialization just like all of our other initialization rules. This would be beneficial because you wouldn't have to specify the order. And here we just create the event, and then inside the curly braces we use the dot operator. We say dot month equals 2, comma dot day equals 1, comma dot year equals 2015. And that is only going to specify the date initialization. If we wanted to specify the time initialization, we just again use the dots for each member name, dot hour, dot minutes. And we could switch the order around, right? We can say dot seconds equals 0 first, and then dot minutes equals 30, and then dot hour 3 would be last. The order does not matter. And then we end it with a semicolon and the right curly brace. Now that we know we can have nested structures, what about an array of nested structures? Now we're really getting into it. Yeah, it's possible. You can set up an array of date and time structures, and date and time contains 2 structures inside of it. You would just do it just like another normal syntax. You have to use those brackets to specify the size of the array. When you declare the actual structure name, you have to specify it of type date and time, just like any other structure. The array events is declared to contain 100 elements of type struct date and time. The 4th date and time contained within the array is referenced using the usual index, sub 3, or index 3, or subscript 3, inside those square brackets. So to set the first time in the array to noon, you would say event sub 0 dot stime, because remember stime is pointing to the time struct, and then you have to access the element in the time struct, which is hours, so you use another dot, and you say 12. It looks very similar to the previous declaration, or assignment I should say, but instead it has that array index, 0 inside the square brackets. If events was not an array, and you just wanted to access the single structure, or the hour structure of the time, you would just get rid of the brackets. So the arrays do not really complicate anything. You just have to be really familiar with those square brackets and the indexes. Here we're setting the minutes to 0, event sub 0, so we're setting that first element, and then we're setting the seconds to 0. Now, if we want to declare a structure within a structure, you can define the date structure within the time structure definition. So this is another category of flexibility. We don't have to necessarily have the date and the time structure defined somewhere else. We can define those structures right in our date and time structure. So here would be an example of just defining the date structure inside there, inside the time structure. So here we have a nested structure, but we actually defined it inside the definition of time struct. So we say struct time with the tag name, and then inside the curly braces we say struct date. That's perfectly valid. And you'll also notice that at the end of the struct date, before the ending semicolon, we're creating a variable called DOB. And then after we create the struct date and its elements in a variable DOB, we specify the elements of the time struct, hours, minutes, and seconds. So that is perfectly valid. Now you should probably notice the limitation of this. Struct date is only going to be defined in there once with a variable named DOB. You will not be able to use the date structure anywhere outside of this unless you use it inside time. You will not be able to use date by itself. So the declaration of the date struct is enclosed within the scope of the time structure definition. Scope refers to how you can access things. Because the date structure is in the scope of time, you cannot access it unless you create a time variable, time struct variable. You can't just say struct date my variable name because you don't have access to that. So date does not exist outside of the time struct. It's impossible to declare a date variable external to the time structure. The only time you can ever use a date structure variable is when you create the time struct, and it will automatically create a DOB variable for you. So this is somewhat limited, but you would use this in a case where you only need the date when it's associated with a time. The date should never be by itself. Then you would do it this way. So another neat concept, a concept of providing a structure inside of a structure. Very, very basic, and the syntax is pretty simple. You'll get used to this pretty easily. Adding the array to a structure that contains a structure, you just use the square brackets in the index. Nothing really changes there. And then you can change the format a bit. If you only want a local nested structure, you can define it right inside the other structure definition. So we're really becoming experts here with our structure type. I want to talk about the last couple concepts. Particularly, I want to show you how you can create pointers inside of a structure, which is useful. And then we'll do some challenges and exercises, and it will really get you really familiar with this structure concept. Thank you. Hello and welcome back. In this lecture, I want to talk about using pointers and structures, how they're related. We can have elements inside of a structure be a pointer, and then we can also make our structures themselves be pointers. Two very useful concepts. So structures and pointers. C allows for pointers to structures. So when we create a variable of type structure, we can create it as a pointer. Pointers to structures are easier to manipulate than structures themselves. So again, it's sort of a notational thing, makes things a lot easier, and it's also more efficient. In some older implementations of the C language, a structure cannot be passed as an argument to a function, but we know that a pointer can. So this is another reason why you want to have a structure be a pointer when you declare it, because then you can pass it around in older versions of C. You can pass it as an argument to a function. Even if you can pass a structure as an argument, passing a pointer is more efficient. We know that that's more efficient. We've talked about this in the past, how passing a pointer can be more efficient. In this case, it's even more efficient because if you're passing in a entire structure, if the structure is large and it contains a lot of elements, you're copying all the elements in the structure to that parameter. If you're passing in a pointer, you're just copying the address. Okay, so it's even more important with pointers as arguments that are structures because structures can be large. So many data representations use structures containing pointers to other structures. You're going to see this a lot in all of your C programs, structures that are pointers. And for the reasons we mentioned, the fact that you can pass them as parameters on older versions of C, and it's also more efficient because we do everything by pass by value, which is copying. Much more efficient to copy an address than copying all the elements of a large structure. So declaring a structure as a pointer, pretty straightforward. When you define a variable to be a pointer to a struct, you just use that asterisk after the type of the data, right? And we said that structures are really a new type. In this case, we have our date, our ever important date structure. We just say struct date and then you use the asterisk date pointer. And you'll probably want to initialize that to null. Because remember, when you say struct date pointer, struct date pointer, that does not allocate any memory it creates memory to store the actual pointer, right? It's not creating memory for the data inside of it. So you could either assign to this date pointer the address of another struct date, or you could allocate memory for it somewhere else, or you could initialize it with some data that way as well. So the variable date pointer can be assigned just like other pointers. You can set it to point to today's date with the assignment statement. So if we already had a declaration of today's date, we would just use the ampersand to get the address of it. So we create a normal date struct, and it's today's date. So that would create memory for the three elements. And then we create our pointer, and we just assign it the address of the other date. Pretty straightforward. We've done that with regular data types. It's no different when you do it with structures. You can then indirectly access any of the members of the data structure pointed to by date pointer. Right? So we would need to do something like this, right? If you wanted to access the element of the date pointer structure, you'd have to dereference it first, right? And so it'd probably be useful to put it in parentheses so it's very straightforward. You have to dereference the date pointer to get the value of what today's date is pointing to. the value of the address of today's date, which it's pointing to, in order to set particular values. So you would dereference it and then do .day equals 21, and that would assign 21 to your date pointer. Now, the above is just saying whatever today's date is pointing to, we want to access that value and set the day to 21. In this case, the parentheses are required because the asterisk has a higher precedence, or the dot has a higher precedence than the asterisk. If you didn't put the parentheses in there, it gets screwed up because it would try to do the dot first before it actually got the pointer to the pointer to the data. So it would try to access data with a null pointer, essentially. And so by dereferencing, you're getting the value. Now, when we use structs as pointers, if we wanted to test the value of month stored in the date structure pointed to by date pointer, we could do something like this, right? We dereference the pointer, put it in parentheses so it takes precedence over the dot, and then we say dot month equals 12. It's perfectly valid syntax. But it is kind of a little cumbersome. So C has its own syntax, so you don't have to dereference everything and put it inside a parentheses for structures. When you want to access what the structure is pointing to, you don't have to dereference it this way. There's a special operator that exists in C for structures of pointers, and it's the dash greater than. It's a dash followed by the greater than sign, and this allows you to not have to dereference the pointer. So instead of doing $x inside parentheses and then .y, you can just say x dash greater than y. Because x is a pointer, you don't have to dereference it, and you want to access the element inside that structure, whatever you're pointing to. So you're going to see this syntax all over the place. You're not going to see the parentheses and the dereference. It's perfectly valid, but you're typing in more characters. It's much more efficient to just say x dash greater than y. So the previous if statement up here, instead of dereferencing inside the parentheses, all you have to do is say if date pointer dash greater than month. And it's somewhat intuitive, right? Because the dash greater than is sort of saying it's pointing to something. And so date dash greater than month. And so date pointer is a pointer, and that's why I use the dash greater than. Now, if that was a nested structure, you would do the dash greater than to the structure, and then you'd have to do a dot after that to access the elements of the nested structure. But because date pointer is a pointer, you have to use the dash equals, or dash greater than. So here's an example. We're creating our struct date. We have 3 elements. Then we're creating our pointer, date pointer, and we're creating just a regular variable today. We assign to our pointer the address of today, and then to assign actual elements of the struct, we just use that dash greater than, and then we can print it out. So let's look at this in code blocks to see how this works. So we're going to put this example in here, and typically when you define structures, you define them outside of a function, because then you can use them in any function. It's kind of like a global, but remember that when you define the structure, you're not actually creating any memory. So you still create the variables as local variables or pointers, but the actual definition is outside the function. So if you want to use it, you can use it in any function. So here at the top, we've created a new struct of type date, or named date, and it contains 3 integers. We end it with a semicolon. We then create a couple variables inside the main. One, which is just a normal variable, struct date today, and then one that's a pointer. We know that it's a pointer because it has the asterisk before it. We know that a pointer, when you create a pointer, it only allocates memory to store that address for that value of that pointer. So we'd have to actually assign it an address, which we do with ampersand today, because we've created, and that's actually created a memory port. So now date pointer is going to point to whatever today is, with the address of today. We can then start assigning data to it by using this dash greater than. Very useful. And just assign a data like anybody else, just use the assignment operator. And then when we print it out, you'll notice we don't have to dereference it to print it out. To print it out, we can just actually say the data types for the format specifiers, here %i or %d, same for integers. And then we just use dash greater, because that is actually doing the dereferencing, remember? Now we could change this, and this would be valid. We have to put it in parentheses, and then we'd have to say the dot month. Either way is fine, but get used to the dash then greater because it is better syntax. And now when we build this, you'll see it prints out the date pointer's values and they're all set to 9/25 in 2015. So it says today's date is 9/25/15. It was formatted to print out that way. It's pretty straightforward stuff. Just remember that dash greater than. That's a new syntax for pointers to structs. But everything else here is just normal. We know that pointers have to have store addresses, so we know we have to either allocate dynamic memory or we have to assign it an existing struct. Let's go back and talk more about structs and pointers. Now let's talk about structures that contain pointers. We know how to create a pointer for a structure. We could allocate memory for that pointer if we didn't want to assign it an existing address of an existing pointer. But you can also have elements inside a structure that's a pointer itself. So a pointer also could be a member of a structure. We don't have to use that character array. So we could say struct, we could name it in pointers, and then we could use, here in this example, we have two integer pointers, P1 and P2. Perfectly valid syntax to do that. So a structure called in pointers is defined to contain two integer pointers. First one is called P1 and the second one is called P2. You can define a variable of type struct in pointers just like normal. Struct in pointers pointers. Okay? The variable pointers can now be used just like other structs. Pointers is not a struct. Pointers is not a pointer. It's int pointers. It contains two elements inside its struct that are pointers, but pointers itself is not an actual pointer. Right? So pay attention to that. It's a structure variable that has two pointers as its members. That's different. So if we want to access the elements inside the pointers variable, which is an int pointers, we don't use the dash greater than, right? Because pointers is not a pointer, it's a struct. We would use the dot to access P1 and access P2. So in this example, we create our structure, we create a variable, it's not a pointer, called pointers, and then we create two integers, I1 equal to 100, and I2, which is not initialized. Now P1 and P2 are pointers, right? So they have to contain valid memory addresses where the addresses have been memory allocated. And that's what int I1 and int I2 is doing. When you declare the integer variables, memory is being allocated for those integers. And so by assigning the address I1 and I2 to P1 and P2, that's perfectly fine. Because I1 and I2 have memory allocated for it because they're integers. Now, if the integer pointers were not integer pointers, but they were character pointers, then you'd have to allocate dynamic memory. So now we just are using integers, so we assign the addresses of the two integers to P1 and P2. We can now say star pointers.p2 equals 97, negative 97. Why do we have to dereference it there? Because pointers.p2 is what we're referencing. Pointers.p2 is a pointer. We're not accessing an element of a struct there. We're dereferencing all of pointers.p2. And we're going to assign that, the value of that, whatever that's pointing to negative 97. So notice the difference there. We're not creating a structure pointer. We're creating a regular variable pointer, but it contains two elements that are pointers. So if we want to assign to those two elements inside of the structure, we have to dereference them using the indirection operator. And that's what we do there. And then in our two print statements, again, we want to print out the values of what P1 is pointing to. So we dereference it, same with P2. And then we want to also print out, again, the values, what pointers is pointing to. So in that first one, we're saying I1 equals %i, comma, pointers.p1 equals %i. So the first one inside the double quotes is just printing out that actual text. It's not dereferencing anything. After the comma is where we're doing the dereferencing. We're first printing out I1, which is 100, and then printing out pointers P1, which would be 100. And then I2, which is going to be, I2 is actually going to be negative 97 after we assign it to P2. So what about character arrays or character pointers? We looked in the previous lecture, we talked about how you can create a character array as an element inside of a pointer. But what about character pointers? You know, should we do something like first and last have character arrays, or should we just do something like first and last with character pointers as elements? What is the better option? Well, we'll see. It's really, again, a notational thing, but there are advantages to using the pointers. So when we create pointers to characters inside of our elements, it's usually a little bit better. But you need to understand what's going on here when you create an element, an array element, char array as an element, or a pointer as an element. Both are valid, but there's a big difference. So if we say struct names VP, and we say Talia and Summers, and then we say struct pointer names. So remember, struct names contains the character arrays. Struct pointer names contains the pointers. And we here are initializing the pointers equal to Brad and falling jaw. And then when we print them out, we're going to print out the first element, which is a character array in VP, and then the first element of Trez, which is a pointer to first. So the struct names variable Veep. What's happening here is the strings are stored inside the structure. The structure has allocated a total of 40 bytes to hold the two names. They're character arrays. That's what's happening when we create character arrays inside of a pointer. We're allocating 40 bytes to hold those two names. Okay? 20 and 20. For the pointer names variable, Trez, where we have two pointers first and last, these are strings that are stored wherever the compiler stores string constants. The structure holds the two addresses because they're pointers. Pointers contain what? Values that are addresses. So all it's going to do is allocate two pointers inside that structure. That's 16 bytes for most systems. Pointers are usually 8 bytes or 4 bytes. The struct pname structure allocates no space to store the strings because it's only allocating space for the pointers themselves. Pointers have values that are addresses, right? The address that it's pointing to, there's no memory allocated for that. So when you create those two pointers, there's no memory allocated for those two pointers. It allocates no space. So it can be used only with strings that have had space allocated for them elsewhere. Whenever you have pointers inside of a structure, you have to use malloc or calloc. Otherwise, they could be stored wherever string constants is stored. And that's the big difference. So the pointers in pname structure should be used only to manage strings that were created and allocated elsewhere in the program. You do not want to assign data to that unless you have dynamically allocated it or that has been allocated somewhere else. Maybe by an existing struct or something. But typically you're going to want to malloc those pointers. Again, very different. You're allocating 40 bytes for these two character arrays inside the name struct. For the pname struct, you have two pointers. There's no memory allocated for that when you create a variable of that type. It's just creating memory for the two character pointers, which is 8 bytes each. To actually allocate memory for what first and last are pointing to, you have to do a malloc. So one instance in which it does make sense to use a pointer in a structure is to handle strings, is if you are dynamically allocating that memory. That's usually when you use it. Because other primitive data types, they're automatically going to allocate the memory for you. So you want to use a pointer to store the address. This has the advantage that you can ask malloc to allocate just the amount of space that is needed for a string. We talked about the advantages of dynamic memory allocation. When you create things statically at compile time, you're only going to create a specific number of bytes. What happens if you need more bytes? You're screwed. Your program's not going to work. You have to go back and recompile. With dynamically allocated strings, you can readjust. You can create just as much memory as you need, which makes it much more efficient in the program. So you're going to use malloc on any pointers created inside of a struct. So in this case, you have a struct named name count. You have two pointers, character pointers, fname and last name. And then you have an int, letters. The two strings inside here are not stored in the structure. We only create memory for the pointers, which contain addresses. We want to create memory for fname and lname for what the pointers are pointing to. So we want to store that in a chunk managed by dynamic memory allocation, which is using malloc. The address of the two strings are what's stored, not what they're pointing to. So addresses are what string handling functions typically work with, which is good, and that's why you want to use pointers in there. Because then you don't have to, then you can just pass them around a lot easier. So here's an example. We have a function called getInfo. It takes a pointer. Okay, and we can pass that pointer around very easily. Now we also are going to create another, or for our pointer array that we're being passed to it, we're going to allocate memory for it. So you'll see that we create a character array called temp, and then we store some data in that temp array. We ask the user to get something. We're not familiar with the sgetS, but it's the same as the getS, save scanf a little. Then we allocate memory for fname inside that pointer. And we do that just like we allocate memory for any character. We call malloc, we pass in the number of bytes, in this case the stir length of temp plus 1 for the null terminator, and then remember malloc turns a void star, so we cast it to a character star. But this is critical right here. This malloc call is necessary for any structures that contain pointers. Now, we passed this pointer in, and the pointer never had a memory allocated for it. So we're allocating memory inside here. We can then do our copy very easily. We can copy temp to fname of our structure PST. That was passed in as a parameter. And then we can have them enter their last name. We can malloc more memory for their last name and then store it in the last name struct variable. This is what you're going to need to do when you have pointers to characters inside your structures. You have to do the malloc. Because again, those pointers only store the address. They allocate enough memory to store an address, not enough memory to store a string. So whatever that address is pointing to, you have to allocate memory for that. And you do it just like normal with the malloc. The only difference is here you use the dash greater than sign to access the actual element inside that struct, which is a character pointer, so you can assign it to it. And that's doing a dereferencing. So you'll want to play around with this stuff. This is very common for character pointers inside structs. We're going to have a challenge where you're going to need to do this. But play around with this code. Go inside code blocks. Start allocating memory for strings or character pointers inside of structs. And see how you then can use stir copy to actually put data inside there. But you first have to allocate the memory before you assign. If you're doing constants like in the previous example, who knows where that memory is allocated. So again, a lot of important concepts presented in this lecture. This idea of a structure that is a pointer. And this new syntax where you can use the dash then greater than as opposed to using the indirection operator. Very nice. And then actually having elements as pointers and how you have to allocate memory for character pointers. Thank you. Hello and welcome back. Last thing I want to talk about concerning structures is how they're related to functions. How you can pass structures as an argument to a parameter in a function. And how this is more efficient as well. So structures as arguments to functions. After declaring a structure named family, in this example we're going to create a named family, how do we pass this structure as an argument to a function? So we have this structure called family. We have a bunch of character arrays in here, name, father and mother, and then we have an int age. That's our structure definition. We know it's a structure because the struct keyword is there, followed by the tag name. We have our curly braces and so forth. Now, how do we actually pass that structure to a function called siblings? Well, you would do it just like you declare the structure. You would say the type as the parameter name. Right, it's really straightforward. So in this case, we have Boolean siblings. Siblings is returning a Boolean, and it's taking two parameters, two struct parameters. You have to identify the struct type, which is type struct family. Now, in more advanced C, you could actually do a type def on this struct and name it something else, and you could shorten the name here, but we haven't talked about type defs. That would probably even be better. But this is really how you would need to do it, is you would have to define the entire type, which is struct family, and then the variable name, just like any other parameter. So here we're passing in two parameters, member1 and member2. They're both of type struct family. Then inside of our function, if we want to access members, we access members just like normal. Member1 and member2, they're not pointers, so we don't use the dash then greater than. We only do that on the pointers because we need to dereference them to see what they're pointing to. Because they're not pointers, we can just do dot. So member1.mother, member2.mother. Member1.mother and member2.mother are character arrays, so we can pass them, and character arrays are pointers essentially. So we can pass them to the stir compare. Stir compare is going to return equals if they're the same. So what we're doing here is we're checking if member1 mother and member2 mother are the same. And if they are, we're going to return true. Because if they both have the same name, and that really would be the last name, then they're siblings. Pretty straightforward. Easy to pass arguments to functions as long as the function declaration has that type struct in there. So this function, again, two parameters, each of which is a structure of type family. What about if we want to have pointers to structures as function arguments? And I mentioned earlier, this is better to do because we are doing pass by value in C. When you do pass by value, you copy. If you have a structure that contains a lot of data, a lot of large structures as arguments, you have to copy everything in that structure to the actual function. So that could take some time to copy those large structures over. Well, if you have a pointer, all you have to do is copy the address, which is much quicker. So pointers to structures are used as parameters and functions to avoid memory consumption and the time it takes to copy of all the structures. Now, if you have a small structure, no big deal, but definitely want to use pointers in structures that are big. So in this case, what do? You still specify the name of the type of the structure. You just put the asterisk beforehand. Very simple. And if you didn't want any of the data inside the structure to change, you could use constant before the structure type. If you didn't want the address to change, you would put the constant after the struct family pointer. But here we're doing the same thing, but now we're going to access it differently, right? Because now that it's a pointer, we can use the dash greater than, right? That new symbol to access instead of using the dot. We don't have to use the dot here because remember pointers you have to dereference first, so you'd have to put it in parentheses. It's more syntax to dereference the pointer. Then you'd have to put the dot outside the parentheses because it has higher precedence. Much easier to use the dash then greater than. Dash then greater mother, dash then greater than mother. They're both pointers. They can be passed into stir compare. If they're the same, return true. Otherwise, return false. Pretty straightforward. You can also use the const modifier, as I mentioned, if you don't want to allow any modification of the members of the struct, what the struct is pointing to, then you put the const before the pointer. You could put the const actually before family as well. In this case, family has a type def. So here, it would really be const struct family or struct family const pointer. And then again, acts is the same way. You're not modifying anything, so you're good to go. Compiler's not going to complain. You can also use the const modifier if you don't want to allow any modification of the address itself. Any attempt to change these structures will cause an error message during compilation. So here you would say family star and you'd put the constant after the star. And what this is saying is you can't change the value of p member, right? The address of the value of the pointer, which is an address. But again, this is not very useful because when you pass by value, you're actually passing in a copy of the address. So this is redundant. You don't need to do this, but you can. And here again, you wouldn't be able to change the address of what p member is. And in this case, you're just accessing the data anyways to see if they're equal. The indirection operator in each parameter definition is now in front of the constant keyword, right? That asterisk. It's not in front of the parameter name. You cannot modify the address stored in the pointers because it's after the asterisk. If it was in front of the parameter name type, then you wouldn't be able to modify the actual what it's pointing to. Right? If we had that indirection operator in front of the parameter name, what that would in the constant before it, that would mean you wouldn't be able to modify what it's pointing to. This is just saying the address. So you cannot modify the address stored in the pointers. It's the pointers that are protected here, not the structures to which they point. Just like constant and other pointer parameters. No difference with structs. If you want to return a structure from a function that's a pointer, the function prototype has to indicate this return value in the normal way in the declaration. So here you'd have to say struct date my fun, pointer or not pointer, it doesn't matter. This is a prototype for a function taking no arguments that returns a structure of type date. Very easy to return a structure from a function. And what is this? What is the value of this? Well, now we can return more than one element or one data item from a function. If you're returning a struct, you could return 10 values, 10 different data items. How cool is that? The struct allows you to return more than one from a function. Very, very valuable. So it's often more convenient to return a pointer to a structure as opposed to just the structure. When you return a pointer to a structure, it's created on the heap. Okay, because all pointers are created on the heap. This means it's going to be around a little bit longer, and this means you can delete it and manage it at arbitrary times. So in this example, we're creating a struct named funds. It contains a character array named bank, contains a double, another character array named saved of a particular length. Fun length, just assume fun length is equal to 50, and then it has a double save one. We have a function called sum, which takes that structure as a parameter. And all we're doing is inside that is we're returning the bank fund from the first structure plus the save fund. And that's going to return the amount that they have in their bank. Now, we're returning, in this example, sum is just a double, right? We're not returning a pointer. We're just taking a pointer as a parameter. And so in our main function, we're creating a structure variable called stan of type struct funds. We're initializing it with some values, and then we're printing out the total of calling sum. And we just pass this structure like we pass any variable. We don't have to dereference it. It's not a pointer. We don't have to really do anything special. We just make sure that in the function declaration we have that struct type there. But everything else looks normal. Couple reminders. I mentioned earlier that you should always use pointers when passing structures to a function. Why? Because remember, older versions of C did not allow, don't allow structures to be passed, but they do allow pointers. So you can avoid any kind of backward compatibility. If you're using an older version of C, your program is going to work. So just passing in that single address is also more efficient because of time copying. But if you do this, if you do pass in a parameter that's a pointer to a struct inside of a function, it does have less protection for your data. So some operations in the called function could inadvertently affect the data in the original structure. And this is where you want to use the const qualifier, right? And you'd use the const before the actual type, not after the asterisk, and before the parameter name, before the type. The advantage of passing structures as arguments: the function works with copies of the original data. It's safer than working with the original data. So that's really the only time you want to pass a structure as an argument that's not a pointer. And the programming style tends to be a little bit clearer. The main disadvantages of passing structures as arguments, as opposed to passing a structured pointer as an argument, is older implementations might not handle the code. It wastes time and space. And it's especially a waste for when you have large structures where you have to do a lot of copying for each member. So keep this in mind. For the most part, you want to pass in pointers to structures. Much more efficient and saves time. Programmers use structure pointers as function arguments for reasons of efficiency, and they use constant when necessary. And this is the combination that you want to do. If you're worried about the protection, just use the function pointer for efficiency, and then use the const so nothing gets screwed up inside the function. Just like really normal pointers, more or less. But with pointers, it's even more important with the efficiency because of large structures. Passing structures by value is most often done for structures that are small. And those are kind of the rules you want to think about. Okay to pass a structure that's not a pointer as long as it's small. Again, some important concepts related to structures and passing pointers as parameters, arguments, and returning pointers as well. Now we can actually start implementing some of this. We provided many examples. We understand the concepts. We understand the syntax. Now I want to present you with a couple of challenges that has you actually doing this. Has you memorizing the syntax, that now if you ever want to create a structure in the program, you know how to do it like the back of your hand. So we're going to have a couple challenges in our next couple lectures to get you familiar with all of the stuff we talked about concerning structures. Thank you. Hello and welcome back. We have another challenge for you. This challenge is going to be about structures again. It's going to get you familiar with elements in a structure that contain a pointer. So you have to allocate memory for that element. It's also going to get you familiar with declaring a structure as a pointer, and also passing a structure as a pointer to a function. So mainly structures and pointers in this challenge. So you need to write a C program that creates a structure pointer and passes it to a function. Create a structure named item with the following members: an item name, which should be a character pointer, a quantity, which should be an int, a price should be a float, and the amount should be a float. The amount that's stored in the structure is going to essentially be the quantity times the price, because that would be the total amount. I want you to create two functions. I want you to create a function named readItem that takes a structure pointer of type item as a parameter. Should be a pointer. We know the advantages of functions taking pointers as arguments as opposed to a regular structure, mainly being they're backward compatible. Previous versions of the C compiler didn't work with structures. And it's also a lot faster and more efficient when you pass a pointer to a function because you don't have to copy all the elements. You just copy the address. So we're going to have functions that take as parameters pointers to structures. This read item is going to take one. What this function should do is it should read in from the user a product name, a price, and a quantity, or an item name. The contents read in should be stored in the passed in structure. So you're passing in a pointer to a structure, you want to store it in there. I want you to create another function named print item. This also takes as a parameter structure pointer of type item. This function will print out the contents of the parameter. So you're just going to do some printfs. That will be pretty basic. In the main function, you want to declare an item, basically an item of the pointer structure, or declare an item and a pointer of the structure, because then you can assign to the pointer the item, the address of the item. And then you also need to allocate memory for the item name pointer. So remember, the item name element inside the structure is character pointer. That means you have to allocate memory for it. If it was a character array, you wouldn't have to. But remember, when you have an element as a character pointer, all it does is create memory for the actual address, the value of that pointer. It doesn't create memory for what it's pointing to. So if you assign a literal constant to it, it could be anywhere in memory. So you want to allocate memory for that item name element inside the structure. The item pointer should be passed into both the read and the print item functions. So it's, again, what this challenge will help you with is understanding pointers, how to use them as a member inside of a structure, and then also how to pass them around. And you'll have some practice with doing some mallocs as well. And then don't forget, whenever you do a malloc, you have to do a free, so make sure you add that to your program. So good luck. I'll provide a solution in the next lecture. As far as mallocing the size, you can just pick an arbitrary size, such as 30 characters or something like that. You don't have to read it in. Okay? Let me know if you have any questions. Thank you. Hello and welcome back. I would like to provide a solution to a previous challenge in this lecture, a demonstration of how you can have pointers as elements inside of a structure and also pass around pointers to functions that are structures. So let's bring up code blocks, create a new project. This is going to be a console application. And we're going to name this structure pointers example. And so if you remember, for the requirements for this was basically just a product type structure that stored an item name, a quantity, a price, and an amount. And the item name was going to be a character pointer. You were going to have an amount that basically just multiplied the quantity and price. And then we had two functions that will take as parameters pointers to a struct. So the first thing we're going to do is we're going to create our structure. And I mentioned this earlier, but it's good to create the structure globally, because if you want to use it in multiple functions. Creating the structure is really defining it. You're not allocating any memory, so there's no harm putting it globally. And they usually go inside the header file anyways. So to create a structure, we just say struct. We're going to call this item, and we're going to have 4 elements. We're going to have a character pointer, which we're just going to call item name. We're going to have a quantity. We're going to have a float for price, and we're going to have a float for the amount. And that's how we can define our structure. Pretty basic. Now, inside of our main function, we're going to want to create a variable for the structure type and also a pointer. So the first thing we want to do is we just want to say struct item with the name of the structure, and then we'll just call this item. And this is just creating a non-pointer. This is going to allocate memory for the 4 variables and elements inside the structure. And so we want to create our pointer now, and we can just say struct item. We're going to say p item, because we usually name our pointers with the prefix p. So we say the asterisk, and we say p item. And then in the next line, we just want to assign to our pointer item our item. So we need to use the address of, and we say item. All right. And so here we have memory allocated for our 4 elements in our structure for our pointer. We don't have any memory allocated for our character pointer, which is our item name. So that would be the next step. Now you may ask, why do we need to create the item struct? We don't really. We could just create the pointer, and the pointer is only going to create memory for that struct item pointer. It will allocate memory for the int and floats, but we still have to do the item name allocation. I just like doing this because this is usually the good practice. If you typically what you would do with the first item struct is you would initialize it, and so you would have some initialization. But we don't need to do that. So the first thing we want to do is allocate memory for our item name. So we can basically use a special operator to access elements if it's a pointer. Remember, for structures that are pointers, you have the dash then greater than symbol that you can use to access the elements. Otherwise, you'd have to dereference the pointer to access the elements. We could do something like this inside parentheses. We could dereference the pointer, so we'd have to do something like star p item and then use the dot to access elements. This is perfectly valid to do something like this, but it is kind of extra syntax that you don't really need. So C has special syntax that you can use whenever your structure is a pointer. If you want to access the elements, you can basically just say the name of the pointer, which is p item, and then use the dash then greater than. And in this case, we want to allocate memory for item name, so we're going to assign it what is returned from the malloc function. Remember, the malloc function returns a void pointer, so we have to cast it to a character star. But we can just call malloc, just say malloc, and then the size of the bytes that we want to create. In this case, we'll just say 30, and we'll multiply it by the size of char, just in case char is a different size on different computers. And this is going to allocate memory for our item name. We need to do this because item name is a pointer inside the structure. It doesn't have memory allocated for it when you assign it to another structure. Okay? So we have to do this. Now the first thing you want to do after you've allocated the memory is check the memory. So we do want to check for null here. We're just going to say, if p item, if it's null, that would say it's null. Otherwise you'd say if not, you could just say return. Or exit would probably be better. Exit the program if we weren't able to allocate memory. And you could pass it in a -1. Otherwise, we want to read in an item. So we want to create a function. The function that we're going to create is called read item. Let's put up a function declaration up here above the structure. It's just going to be reading in data into the struct that we pass to it. It's not going to return any data, so we can just say read item, and it takes a struct. And that's going to be a pointer. So it's a struct item, asterisk, I. Now we could make this a constant, so the value's going to change, but we are changing the values. But we could say constant struct. That would be, the values would not be able to change for that pointer that it's pointing to. If we did the constant after the asterisk, that would say the address can't change, or right before the asterisk. Something like that after the name. That would say the address can't change, but that's redundant because we're passing by copy value. We have our read item, and while I'm up here, I might as well do my print item. That's just going to be the function declaration, function prototype. Here it's going to be very similar. Also take a pointer. You can have a space if you want after the asterisk or not. Now we can define our read item below our main method. And this is just going to read in values of item and then calculate the total amount. So we can say void read item, have our pointer. And inside here, we just want to use some scanfs, really. We're going to print out some messages to tell the user to enter information. So we're going to say enter product name. Whoops. And then we're going to read it in, so we're going to say scanf. And we have a pointer to a struct, so we can access it using the dash then greater than. We want to read in for scanf, the product name is a character buffer, so we want to say %s, and then we're going to say I. We're going to store it in the item name. And we could go back and use the IntelliSense. Just go to item name. We don't have to use the address of operator because it's a character pointer. We then want to print out and get the price. Probably want to add some line feeds in here. enter the price. We're going to store that in the structure. So again, the price is a float though, so we're going to say %f, but we're going to also access it because it's a pointer. We still want to use the dash sign greater than, except this time we're going to say price, and we need to get the address of it, so we're going to put an ampersand in front of it because price is not a pointer. And then we're going to do the same thing for the quantity. So quantity is an integer, so we can say %d. We still need to get the address of it, but we want to store it in a different element. We want to store it in the price or the quantity, qty. Now that we've stored or asked the user to enter 3 items of information, now we can actually calculate the amount, store something in the amount. The amount is just the quantity times the price. So we still want to access the structure using our correct syntax, and we want to assign it, we want to cast it, we want to assign the quantity times the price. And that's the read item function. Takes the structure pointer, and so when we modify this pointer inside of the read item, it's going to get modified outside of the function. Right? So whatever structure we pass into this function is going to get modified. It's going to store all the items, the item name, price, and quantity, and amount. So that reads in the data. At this point, you'd want to test, and you probably want to compile and test before this. But we can now call the read item method up in our main and pass it in our structure that we created. So we can say read item, and we can just say p item. We don't have to pass in the address because it's a pointer, so we just pass in our structure. And then the next thing we can do is we can print it out. And what this will show you is that the data is saved. P item is being modified inside the function, and it's being saved outside of the function. The main function actually has saved those values. So we can say print item, passing in the pointer again, and then we can define the print item function. Print item is pretty basic. It's a void. It doesn't return anything, so we say void, and we say print item. Takes a pointer, so we just say struct item star I, whatever you want to name it. And then we just print out the data for the structure that was passed in. So we would do something like printf name %s, I item name, I price, I quantity, and I amount, and then we format the data. What's the last thing we have to do in the main after we printed out the data? The really, really important free function. We got to call free because we want to free the memory that we allocated for the item name. So we can just say free p item and then access the item name. We don't want to free the entire structure because the entire structure will be deleted on the stack when the function returns. We just want to free what we mallocked. We only mallocked for item name, so we free that. And then we return from the main. So let's go ahead and try to build this. And we do have an error. Let's see, it says struct item star, but so we had a mistake where the functions were defined above the structure, but the function is taking a parameter as a struct type. So we have to have the structure defined above where we're using it. So I move the functions down to lines 12 and 13. Now we're able to compile. Let's go ahead and run this. And let's see what we get here. We had one more error. You have to make sure you check p item for null. If you just say if p item for true, it's always going to be true. So you can either check to say it's not true with the not symbol, meaning it's not null, or you can check to see if it is null. So I just added the null there. So now when we run it, we should be good to go. We can enter the product name. We'll say cereal, and we'll say the price is $1.99, and we'll say we have 5 of those. And now we print it out, and we say cereal, $1.99, 5. The total amount is $9.95. The price, though, I don't like how the price is printed out, so let's fix that. In our print item, we can just say for price dot 2f floats. Now it will look a little bit better. And we run it. We'll get a little bit of better format. Four of them, and now it looks a little bit better. And everything's good to go. So again, basic program using structures and pointers. We created the structure at the top. We have a member that contains a pointer. It's very efficient to do that because we can just copy in addresses as opposed to character arrays. We have our two function declarations, read item and print item, that take pointers to structs. And then we create the pointer and assign it to a regular structure inside of our main. We allocate memory on line 22. We make sure the memory is allocated successfully. If it wasn't, we exit the program. And then we call our two functions that take pointers to structures, pass them in. And then last but not least, we free the memory and then we exit the program. And the functions are pretty straightforward. You take that pointer, you access the pointer using the dash and greater than. And you get the address of it for scanfs that don't have that are not pointers as elements. And that's basically it. I'll save this program. You can take a look at it. Let me know if you have any questions. Thank you. Hello and welcome back. We are in a new section. This section is all about file input and output, writing and reading from files. We're going to concentrate on text files, but we'll talk about binary files a bit as well. In this lecture, I just want to provide an overview, tell you what a file is, and tell you how it's good use for storing persistent data. So up until this point, all the data that our program accesses is via memory. Right? We're familiar with this concept of variables, structures, whatever it is, arrays. All the data that your program uses is in memory. And the reason that it's stored in memory is because memory is really fast. And you can access it quickly to perform calculations. You're doing the fetch execute cycle, all that stuff. So the scope, but it also is limited because the scope and variety of our applications, if it only uses memory, it's going to be somewhat limited. We know that memory goes away when the program goes away. And so that can be very limiting. All serious business applications require more data than would fit into main memory. Main memory is also very small, right? Nowadays you can get a lot of memory, 16, 32 gigabytes, but in the past, and especially on embedded devices, you don't have as much RAM. And as a result, your applications are very limited because of space and size. You really only want to store variables and things like that in main memory. It also, because main memory goes away, when the program goes away, you can't have any data that is stored persistent across reboots. So it all depends on the ability to process data that is persistent and stored on an external device such as a hard disk drive, these big programs. So you want to have this ability to store on the hard drive. It's a little bit slower, but you can store a lot of data on there, and big programs need to store a lot of data. C provides many functions in the header file standard.io.h for writing to and reading from external devices. You don't have to write your own code to read and write the files. But you can see the advantage that applications offer that have the ability to store data for a longer amount of time. A lot of advantages. The external device you would use for storing and retrieving data is typically the hard drive, the disk drive. However, the header file functions that we're going to talk about, you can use on any external storage device. So you could use it on a USB drive. You could use it on any external device that stores data. Okay, an SSD drive, anything. With all the examples up until now, any data that the user enters is lost once the program ends. This is referred to as volatile memory. Whenever you hear that term volatile memory, it means that the memory is not persistent, or the data is not persistent. It goes away when the program ends or if the machine reboots. So if the user wants to run the program with the same data, he has to enter it again each time so that it gets restored. It's very inconvenient. It limits programming. And again, this is volatile memory. When you store stuff in files and you store it on the hard drive, this is permanent storage. It's still there even when you reboot the machine or when your program is not running. That's referred to as non-volatile memory because it stays around. A file can store non-volatile data and is usually stored on the disk, or nowadays a solid-state drive, an SSD. It's a named section of storage, and the standard IO.h is a file containing the use of information in order to be able to read and write to those files. But we're going to use this concept of writing and reading data from a file for permanent storage. And you're going to notice how your applications become much more useful, much more robust, much more scalable, because now we have the ability to store large amounts of data. And we also do not have to worry about the data going away whenever the program ends or the computer reboots. So it's going to be very, very advantageous to use files. A file inside of, on the Linux operating system or Windows operating system is stored a certain way, but as far as C goes, the programming language, it's just a sequence of bytes. And each byte can be read individually. This corresponds to the file structure in Unix, but it doesn't necessarily, it only makes a difference when you're reading text files in Windows, because you may have extra characters that you have to worry about concerning size. But it's just a sequence of bytes. So if you have a text file and it has more bytes, you can still read those bytes. You just have to understand what those bytes are representing. So here's what a file looks like and how we're going to read it and write to it using the C programming language. It's just a series of bytes with different offsets. Okay. The beginning of the file would be byte 0, and then you can always find different positions in the file. Could be 4 bytes into it, could be 100 bytes into it. And then you have the end of file, and the end of file is usually marked with a special marker called EOF, for end of file. So a file has a beginning and an end, and a current position. The current position is defined so many bytes from the beginning. The current position is where any file action will take place. You're going to write or you're going to read at that position. And we're going to also talk about some functions where you can move around to move the current position. Anywhere you want in a file, even at the end, if you want to read at the end or write to the end. There are two types of files. There are text files and binary files. A text file is data written as a sequence of characters, organized as lines. Each line ends with a new line. And the text data can vary from system to system depending on how characters are interpreted. So for example, on Windows in DOS, every line has a carriage return and a line feed, so a \R and a \N. And so when you read the data or write the data, you have to understand this because the format's a little different. But on Linux, you don't have a \R. And so you have to understand how the text data is written, even though it's organized by lines and it's a series of bytes. Binary data is written as a series of bytes exactly as they appear in memory. So examples of files that have binary data are files like image data or music encoding. Binary files are not readable if you were to try to bring them up in a text editor because they are just bytes. We're going to concentrate on text files in this section, but you can write any data you like to a file. You can write it as a series of bytes and how they appear in memory, or you can write it as text. But once the file has actually been written, it's just going to consist of a series of bytes, even if it's represented as text. You can view text files in an editor, which makes it more readable. You have to understand that the format of the file in order to read it. And this is what I mentioned with if you're running on DOS, Windows, or Linux, where Windows may have extra characters when it writes data. So a sequence of 12 bytes in a binary file could be 12 characters. It could be 12 8-bit signed integers or 12 8-bit unsigned integers. Binary files are especially tricky because they just store what's as they appear in memory. So in binary mode, each and every byte of the file is accessible. But in order to read something from a file, you have to understand what's in there as far as data and how it's stored. And it may depend on what system you're running on, and it's going to also depend whether it's text or binary. Streams. C programs are automatically open on 3 files on your behalf. A stream can represent a file, but a stream is a more generic term that can represent any kind of input. So it could represent the keyboard, it could represent the console, it could represent a file, it could represent a socket if you're used to networking. Streams are a more generic term. And there's 3 streams that are opened up automatically for you in the C programming language. One is the standard input, and this is the normal input device of your system. Usually by default it's the keyboard. We've been using the standard input when we do scanf, but you could actually use scanf to read from files if you change the input stream. Maybe you change the input stream to a file. Standard output, this usually displays on the screen, usually via the console. Standard error is also on the screen, but you usually have to redirect it in order to see it, using like the ampersand 3 or something like that. But these are the 3 outputs. I mentioned standard input is the file that is read by getchar and scanf. Standard output is used by putchar, puts, and printf. We've mainly been using printf. You can also redirect files on the system to be recognized as a standard input or output. This is redirection. This is an operating system concept where you can redirect data. Send the output to a file, for example, or send the input get input from a file as opposed to standard output. This is where you can use the less than or greater than symbols. The purpose of the standard error output is to provide a logically distinct place to send error messages. So it's kind of separate. Even though it's displayed to the screen, to access it, you have to have special command. A stream is an abstract representation of any external source or destination for data. This is why it's more generic than, say, a file. The keyboard, the command line on your display, files on a disk, those are all examples of how you work with streams. Streams are going to be much more important when you start studying C++. The C library provides functions for reading and writing to or from data streams. So you can use the same input-output functions for reading and writing any external device that is mapped to a stream. Right, so that's why I mentioned you can use scanf to read from the keyboard. You could also use scanf to read from files. It all depends on what the input, where the stream is pointing to. And so the functions are very, very useful and very, very flexible to do this. And so this is just a high-level overview of what a file is and why we would use it, how it is persistent data. It's non-volatile memory. It stays around. We're going to use it, and we're going to use the standard IO header file to read and write to it when we need to store data for our program. And our programs end up being a lot more robust, a lot more usable, a lot more flexible. So in our next lecture, we'll talk about actually implementing this using the functions in the standard IO header. Thank you. Hello and welcome back. In this lecture, I want to talk about accessing files. So files on disk have a name, and the rules for naming the files are determined by your operating system. You may have to adjust the names depending on what OS your program is running. If your program is running on Windows versus Linux, the directory structure is different as well. So if you use / or /, you have to adjust this in your program. But for the most part, the names are relatively have the same naming rules and so forth. But there is the chance that you'd have to adjust it. A program references a file through a file pointer or a stream pointer. Since it works on more than just a file, you can actually, we mentioned this earlier, but the standard IO functions work on any device. So it's called a file pointer, but it really can be it really should be referred to as a stream pointer. You associate a file pointer with a file programmatically when your program is run. So what you end up doing is you'll create a pointer inside your program. It will be of type file, and that's going to represent the file when you read and write to it. We use these file pointers as a more effective way to actually point to the files as opposed to the name, right? Because the name can be a little bit different. The pointer will represent what it's actually pointing to. And you can reuse the pointers to point to different files on different occasions, which again was represented by the file name. A file pointer points to a struct of type file that represents a stream. You can actually go and look at the file struct to see everything that's inside of it, but it contains information such as whether you want to read or write or update the file, the address of the buffer in memory where you're storing data, a pointer to the current position in the file for the next operation. We mentioned the position is important because that's where you're doing your writes and reads. And you can set all this information inside the structure by using input and output file operations. Right? The input and output file operations, when you open a file, it's going to actually specify whether you want to read or write. And then also when you can change the current position by using other methods like seek and so forth that we're going to talk about. If you want to use several files simultaneously in your program, you have to create a separate file pointer for each file. You can only reuse the file pointer if you're reading and writing at different times. There is a limit to the number of open files you can have at one open time. You can look at the limit in the standard IO. There's a constant defined fopen max. It all depends on, again, what operating system you're running on. But you usually do not want to create and open a ton of files at once. Writing and reading the files is an expensive operation because you're writing on the hard drive. It's not as fast as writing to memory, so it takes time, and it can cause your program to be less responsive. So you don't want to have 10 files open and writing at 10 files at the same time. To open up a file, this would be the first step that you do before you read and write. So you want to associate a specific external file name with an internal file pointer through a process referred to as opening the file. The way that you open a file in C is you call fopen function. This will return the file pointer, which you can then use for reading and writing. And again, the file pointer is going to point to a specific external file that's on the disk. Fopen is going to take the name of the file. The fopen is what you'll usually do, what you have to do before you do any reading and writing. It's usually your first operation. And as with most of these functions, they're all defined in standard IO.h. Here is the definition of the fopen call. You'll see that the return value is a file pointer. It's all caps, the file structure. So all caps file. You'll then notice that it takes a couple of parameters. It takes a name and a mode. And don't worry about this restrict. That's just more C11 stuff. It really just takes a character pointer to a name and a mode. The first argument of the function is a pointer to a string that is the name of the file. So that will be inside double quotes. You can specify the name explicitly or use a character pointer that contains the address of the character string. So all this is saying is you could create a character string and assign it a literal text and then pass in the string to the function, or you can put in inside the double quotes right inside the function call. You can obtain the file name through the command line as input from the user as well, or define it as a constant in your program. It depends. If it's always the same file you're reading and writing to and the name doesn't matter, you can just refer to it as a constant. If your program is more flexible, it can get input from the user to say what you want to read or write to. The second argument to the fopen function is a character string that represents the file mode. This specifies what you want to do with the file, whether you want to read it, whether you want to write to it, whether you want to append to it. File mode specification is a character string between double quotes, and I'll show you some of the ones that we're going to end up using a lot of. Assuming the call to fopen is successful, it will return that file pointer, all caps. And then you can use this file pointer to call other input-output functions in standard IO header. And we're going to go through those when we go through reading and writing. Or you can also get the position using that pointer to change the position of where you are in the file. If the file cannot be opened for some reason, fopen is going to return null. So what this means is, before you start doing any reading or writing, make sure that the pointer is not equal to null. Another if check. Here are the file modes that I mentioned. The file modes, remember, are the second parameter to the fopen call. This is what specifies what you want to do with the file. And it's all inside double quotes. So if you do a W, that means you want to open the text file for writing. If you do an A, that means you want to open the text file for appending. All writes are to the end of the file. If you do an R, it opens up the text file for reading. If you add a plus to any of these, it will basically create the file if it doesn't exist. So if you open up a W plus file, it will open it up for update, and it will truncate the file to 0 if it exists, or it will create a new file if it doesn't exist. With the other ones, it's going to write or read, and the file has to exist. Same with A+, it's going to open it up for appending, for an update to the end of the existing file, or create the file if it doesn't exist, and the R+ will open up the text file for update. It's not going to create the file there because it will be empty. So the reading is just for both reading and writing when you see the R+. A little different than the other pluses where they're actually creating the file if it doesn't exist. Write mode. If you want to write to an existing text file with the name myfile.txt, you would create your file pointer, all caps, set it to null, initialize it to null, and then you would maybe create your file as another character pointer, myfile.txt, or you could pass that in as the first parameter. And then you just say fopen. Fopen, file name, and then W inside double quotes. That opens the file for writing, and it returns a file pointer. That's why you have pfile on the left of the assignment. You then want to check to make sure pfile is not equal to null, because if it's null, if it failed to open for any reason, maybe the file name was wrong or it didn't exist, then you wouldn't be able to write to it. So you always want to do the if check and print out some information if it doesn't open. This code will open up the file, and it will associate the file with the name myfile.txt with your file pointer's pfile. The mode W means we can only write to the file. You cannot read from it. If a file with the name myfile.txt does not exist, the call to fopen will create a new file with this name. And that's for fopen with the W option. Right? And so when we saw in the previous modes, W plus will create the file if it doesn't exist, but it also truncates the file to 0. That's the difference with the W. The W will create it if it doesn't exist, but it's not going to truncate it to 0. Okay. So this is a standard way for opening up files using that W inside the double quotes. If you only provide the file name without any path specification, so that's what we did in this example. A path, remember, is the name of the directories. If you don't provide the name of the directories, it's going to assume that that file is in the current directory wherever the program is executing. If you want to actually open up a file somewhere else where it's not actually located in the program's directory, then you have to specify the entire path. That's called the absolute path. When you provide no path, it's usually the relative path. It's relative to where the program is running. So you can specify either one, the absolute or the relative path, just to make sure you know where it's located and you're doing the right one. Relative paths are usually better because then it's not dependent. If somebody were to move that file, it's not dependent on where it was moved. And you can actually do a relative path and you can go back directories. So you can do a // and that's relative to where the program is running. You're just going back a couple directories. When you use an absolute path, it would actually be something like C: program files if you're on Windows. And if that file ever moved, the program would not be able to open it. So on opening a file for writing, the file length is truncated to 0, and the position will be at the beginning of any existing data for the first operation. Any data that was previously written to the file will be lost and overwritten by any write operations. Okay? So again, without providing the plus on it, it just means you can't read and write. This is write only. W is write only. W plus means you can read and write. Append mode. If you want to add to an existing text file rather than overwrite it, you can specify the A mode. This is appending. This positions the file at the end of any previously written data. If the file doesn't exist, it creates a new one. The example here is you just change the second parameter to be an A inside double quotes. It will add to the end of myfile.txt. And do not forget that you should always test the return value for null each time. You always want to do the if p file is not equal to null. When you open a file in append mode, all the write operations will be at the end of the data in the file in each write operation. All write operations append data to the file, and you cannot update the existing contents in this mode. It's all at the end. In read mode, we can open up the file to read a file. We just use the R inside double quotes. This is read only. You cannot write to the file. If you do R+, you would be able to read and write. So it looks like the other calls. You just do an fopen, pass in the name of the file, and then R in double quotes. That returns a file pointer. It will also position the file to the beginning of the data. If you're going to just read the file, it must already exist. You're not going to read an empty file. So there's no option of creating the file if it doesn't exist. It will just be empty. Or you would get back the file pointer would be null. If you try to open a file for reading, it doesn't exist, it will return the null pointer. If it does exist and it's empty, you just return no data. You always want to check the value returned from fopen. Again, reiterating that for the second time, it's important because if it's a null pointer, your program is going to crash, it's going to do something bad. Renaming a file. We know now how to open a file. Opening a file is the first operation. You specify the mode and the name of the file. That gives you back the file pointer, which you can now use to do other things with. Renaming a file is sometimes important. It's very easy. You just use the rename function. It takes an old name and a new name as constant character pointers, and it returns an int. The integer that's returned will be 0 if the name change was successful and non-zero otherwise. The file must not be open when you call rename. Otherwise, it's going to fail because it's in use. You can't rename a file when it's in use. So what you can do here is you can just say rename, pass in the old file name and the new file name. In this example, we're using a path to a file in Windows. And that you know it's Windows because I C:. You also notice that the backslash is there twice. The reason for that is because the backslash is a special character in C, right? \n is a line feed. \r is a carriage return. So the backslash has special meaning in the program. So if you want to actually use the backslash for a path in a directory, which is what Windows does, you have to provide 2 of them. And so here we're renaming a myfile.txt located in the temp directory. We rename it to myfile_copy.txt in the temp directory. And if that is not equal to 1, it will fail. We just print out an output that says it failed. Otherwise, we print out successful. This is going to change the name of myfile.txt in the temp directory to myfilecopy. If the file path is incorrect or the file does not exist, it's not going to be able to rename. You can also close a file, and you'll want to do this whenever you open a file. So when you're done with the file itself, you want to tell the operating system to free up that file. Remember, there's a limit to how many files you can have open at any given time. You can do this by calling the fclose function. Fclose accepts a file pointer as an argument. Remember, the file pointer represents the file. It returns an EOF. EOF is an int, EOF, it returns EOF if an error occurs. EOF is a special character called the end of file character. It's defined in standard IO.H as a negative integer. It's usually equivalent to -1. If fclose was successful, it will return 0. So you can check for EOF for unsuccessful. You just say fclose, pass in the pointer. You can then set the pointer to null. And the result of calling fclose is that the connection between the pointer, the P file, and the physical file is broken. P file can no longer be used to access the file for reading, writing, or appending, or renaming. If the file is being written to, the current contents of the output buffer are written to the file to ensure that the data is not lost. So you don't have any problems with data integrity. You're not going to actually close the file if it was being written to in another thread. So it's thread safe. We haven't talked about threads. That's more an advanced concept. But it's where you can have multiple execution points in your program. It's good programming practice to close a file as soon as you have finished with it. Just like it's good programming practice to free memory when you're done with it. Same for closing files. It protects against output data loss. You must also close a file before attempting to rename it or remove it. It has to be closed. It can't be opened. How about deleting a file? You can delete a file by invoking the remove function. This is also declared in standard IO.H. All the file operations are declared in standard IO.H. You can always go look at this header file if you want, wherever the C header files are installed. So you just say remove, name of the file. Here you don't have to use the file pointer. You can just say, because the file doesn't have to actually be open to remove it. The same with the rename, right? Because you don't actually want the files to be open, because the rename or the remove will fail. It's going to delete the file that has the name myfile.txt from the current directory. This is providing a relative path. It's going to look for that file wherever the program is executing. Otherwise, you need to provide an absolute path. The file cannot be opened when you try to delete it, just like rename. You should always double check with operations that delete files. You could wreck your system if you do not. A delete is a very expensive, very hazardous operation. Deleting files can cause problems, so be careful. All the information in this lecture had to do with accessing files, how you can open up files, which is what you need to do before you read and write, and also how you can delete and rename files, and then closing when you're done using them. Everything is based off that file pointer, so understand that file pointer and the structure it contains. Pretty useful stuff. The standard IO header contains all the great information. Next couple lectures, we're going to talk about reading and writing to text files, actually adding data or deleting or removing it, or adding or reading it. Thank you. I hope this was helpful. Hello and welcome back. In this lecture, I'd like to talk about how we can read text from a file. For now, we're going to concentrate on reading text files. So if we want to read characters from a text file, we're going to use a couple functions. First one is going to be fgetC. This will read a character from a text file that has been opened for reading. Remember, we always have to open up the file before we can perform any file operations on it, unless it's a rename or a delete. And then the file it cannot be opened. But if we want to do reading and writing or appending, we have to open that file. We know that we can open up files with different modes. In this case, for reading, we'd have to open up with an R or an R+, and then we can start calling fgetC. The fgetC function takes the file pointer as its only argument, and it will return the character read as type int. So here an example, we create an mchar type int, and we say fgetC pfile. It's going to read a character into the mchar variable with pfile as a file pointer. All right, think of pfile already been opened, return to file pointer. The mchar is of type int because EOF, which is our special character, our end of file, that's returned if the end of file has been reached. So we can always check that integer to see if it's EOF, and if it is, we don't want to read anymore. We don't want to call fgetC anymore. The function fgetC, which is equivalent to fgetC, is also available. So getC is almost the same as fgetC. You just want to use fgetC. I think it has some more protection in it. With getC, it requires an argument of type file star and returns the character read as type int. It's virtually identical to fgetC. The only difference between them is that getC may be implemented as a macro, and we don't even know what a macro is now. So we're going to stick with using fgetC as our function to reading characters. You can read the contents of a file, again, when necessary. You can use this rewind function, which positions the file that is specified by the file pointer to the beginning of the file. So you can use rewind if you want to read again. Just say rewind and then the file pointer. Pretty basic. So here's an example. You have to include the standard IO header whenever we do any file operations. In our main function, we're going to create our file pointer. Probably want to initialize this to null, and we're going to create an integer. First thing we're going to do is we're going to open up the file using the fopen call, and we're going to specify the name of the file, and we're going to specify that it's for reading. That will return our file pointer. So now our FP pointer is pointing to a valid file. If it was unable to open file.txt, it's not in the right path or whatever, it's going to return null. So you want to check for null, make sure FP is not null. If it is null, exit the program. Otherwise, when you usually read characters, you're going to have them inside of a loop. So here we're saying while C equals F get CFP. This is reading a character from our file, passing in the file pointer to F get C, which returns an integer. Remember, we can jump out of the loop if that integer returned is the end of the file, because we don't want to read past the end of the file. Otherwise, we can just print out our character using %C and C. Last thing we want to do is we want to close the file. We then want to set our file pointer to null, and we can return. Let's try utilizing this, creating this inside of code blocks. So here's our program inside code blocks. It does exactly what it says. This program's not going to work unless we have a file on disk wherever the program's running. So first, if we build this, it should build okay. You should create an executable somewhere on your hard drive. I've been putting all of my projects inside my downloads directory. So if I go to my downloads directory and I go to the project name, which this is just a test project. So wherever you're storing your projects, mine's in test. If I go to test, you'll see that inside the bin directory, inside debug is your executable. Here is where you create your file if you had a relative path. So here I could just create a new file, and we could have it as a text file, so I can just create it as a text document, and it has to be named file. And then I'm going to put some information in it. I'm just going to put in some data such as hi, this is JSON, line feed, okay, nope, so forth, and I'm going to save it. This file has to exist in order for this program to work. So I created the file. Now when I run it, hopefully it will read what I just added to it and print it out. It says error in file, opening file, no such file directory. And that's probably because I have it in the debug folder, and this is not running in debug. So let's try running it in debug. And I think it would probably work now. We can say debug, start. This will look for the executable in the debug directory, hopefully. We want to make sure it's run. Still not there, so you have to make sure you know where the executable is. Let's try somewhere else. Or better yet, I could just run the executable inside the debug directory, and it should find it there. So if I double click here, it actually doesn't pause. It just it jumps out. So what you can do for that is, instead of returning, you can say system pause, I think it is, and it won't exit the program until you've run it. So let's now try it. So now it paused. It didn't execute the program. And what you saw was, hi, this is Jason. It was able to find the file, print it out okay, print it out nope, and then it paused. Otherwise, when you execute the program, it prints the data so fast and exits the program that you're done. So that's how you can test it. Not sure where it must be stored where the executable is stored, where it's running from. It must be running from somewhere else in your project directory. I'm not sure where it's running from. We might have to we could try moving the file to where the source code is. It might be running it from here. So here, we'll put it in here, and now we'll try running it from the IDE, and maybe it will work. We don't build, we run it, and it was able to find it. So it looks like we have to put the file inside of where the source code is. So as long as we put that file.txt inside the project file, it will be able to see it. So quick example of how you can open up a file and read single characters. Not the most efficient way to read from a file, because usually you want to read strings. But this will open it up. You see the fopen call, and you notice the while loop. That's important. Let's go back and talk about how we can read strings from a file, which is much more efficient. So that's reading a single character. How about reading a string? You can use the fgetS function to read from any file or stream. This will read a string. It takes a character string as the first parameter, the number of characters you want to read, and then the actual file pointer. So this function is going to read a string in the memory area pointed by the stir. So you have to actually pass in the buffer where the data is going to be stored. And that's a pointer, so you'd have to allocate memory for it. And then it's going to read from the file specified as the third parameter, which is the file pointer. And then the end chars is going to say how much data to read. So if you put end chars as like 10, it's going to read in 10 characters unless it hits a line feed first. So it's going to either read an entire line or it's going to read the number of characters that you specify in the second parameter. The end of line is specified by the \n, that whichever occurs first. If a new line character is read, it's retained in the string, and a null terminator will be appended to the end of the string. So if you actually specified more characters, it would read up to the line feed and then jump out. And then it gets that new line character and puts a null character at the end of it. If there's no error, fgetS is going to return the pointer, which is the first parameter. It's going to return a pointer which gets returned from the function, and then it's also going to populate the stir pointer as the first parameter. If there is an error, null is returned, and then reading the end of file causes null to be returned. That means you read all of your strings. So let's look at an example. Here we have our main, and we're creating our file pointer, creating a character string. Here this is a pointer. We didn't allocate any data for it. We just create a character array. We opened up the file for reading only because it's R. We said if it's null, jump out. Otherwise, we just say fgetS. We read in 60 characters, or if the line feed is before that, a line feed will come up, and then it will print it out in what's ever in the stir buffer. So stir is that first character that's passed in. And then we close the file pointer, set it to null, and return 0. So let's again take a look at this inside of our CodeBlocks IDE. So the only thing that's changed in this program is really lines 14 to 17. We're using fgetS to read our string in, and then we have a stir buffer. So we've also need to create a character array up here, which is our stir. And we want this to contain 60. We're reading in 60. We'll add a line feed, so it's going to read in 59 and then add a line feed to the end of it. So we could say 61. And then the fgetS is going to be in an if statement, and it's going to read in each string until it either hits 60 characters or a new line, and it's going to print out that string. You'll notice that's not a while loop, so we're not reading to the end of the file. We read the end of file, we get a null. So if we build this, we want to make sure we have our quotes correctly. Whenever you copy from PowerPoint, it messes up the quotes. And we want to make sure we created our variable C is not used. That's okay. So let's go ahead and run this. And you see, hi, this is Jason. So actually read in an entire line of text from the file. It read in the first line. So you would call it again and read in the second line. If you change the number of bytes read, say we just want to read 10, it would read in 10, and then it would return those 10 as opposed to reading the entire line. So here we just have it, hi, this I. So it's going to read in number of characters, your second parameter, or until it gets a line feed. And it stores that in str. str is a character array. We print it out. fgetS. fgetS is a lot more efficient for reading because we're not reading a character in at a time. We're reading in more data. Reading a character in a time is not as efficient. So now we know how to read in single characters. We know how to read in strings until they read a new line or a number of characters. But you can also read in formatted input from a file. So we have getC, fgetC, fgetS, and now we have another function called fscanf. This is formatted input. Formatted input is data specified by, like, has a delimiter or has specific format associated with it. This fscanf function takes a file pointer stream and then a format. The format is just like the printf format specifiers that you use. So if you want to read in integers or doubles, you can specify data inside the file that are integers and doubles, and it will read that until it sees just like the scanf, until it sees a white space character. So the first argument to the fscanf function is a pointer to a file object that identifies the stream. We have to know what file we're reading from. The second argument to the function is the format. This is a C string that contains one or more of the following items: white space character, non-white space character, format specifiers. The usage is the same as the scanf and the printf, but instead it's from a file. So inside the double quotes, you can put in text, you can put in white space or non-white space characters, but the format specifiers is how you're going to store the data, how you're going to read in the data. And then you specify variables that you want to read it into. So the function returns the number of input items successfully matched and assigned. So here's what it looks like. You'll notice that the main is creating 3 character arrays, stir1, stir2, and stir3, just 10 bytes each. We create an integer called year, we create a file pointer. The first thing we do when we open up the file, in this case we're opening it up for reading and writing, but we're not going to actually write anything to it. We're just going to display what we're reading from it. We check to make sure the file pointer is not equal to null, and then here we're actually putting something in the file, fputS. We haven't talked about that yet, but this is writing something. Focus here on the fscanf. The fscanf is going to read in formatted data. And so what it's going to do is it's going to read in 3 strings separated by spaces. And so you see the %s space, %s space, %s space, %d. Then we're saying where we're going to read them into. Our 3 characters array and then our year. And we have to specify the address operator for our year. But the data is formatted a specific way when it's written. And when you read in something that's formatted, you have to understand the format of the file, how it's written. Here we know that the file is written by separating strings by white space. Right? So that's how we're going to read it in. And so we can read it in with one call, fscanf. We can use our format specifiers as our second argument, and then variable number of arguments for each, separated by each comma, to specify the data we want to read it into. And then we just print out that data, the 3 strings in the year, and then again we close the file. And so these are the 3 ways you can read in data from a file. You can either read in characters, you can read in strings, or you can read in formatted data. And you'll notice the formatted way of doing it is very similar to scanf. You use format specifiers, variables to read into. We'll have a challenge on reading data, which will get you more familiar with this. It's pretty basic. You're going to do your open calls, you're going to use your file pointers, and you're going to use those 3 functions. Thank you. Hello and welcome back. We have our first challenge for doing some file writing and reading. Specifically in this challenge, we're just going to read in some characters, get you familiar with the fputC function. So what I would like you to do is, I would like you to write a program to find the total number of lines in a text file. So you need to create a file that contains some lines of text. You're going to have to create a file. Remember, this file has to be placed in either where the executable is, and then you can double click the executable and run it in the same directory as that. Or if you're running it from the integrated development environment, you're running it from code blocks, then you can put your text file inside of wherever your source files are located, wherever you saved your project inside your C source file. So you'll have to create a file before you can actually write this program, because you need to read and write some data inside that file. You're going to need to open your test file up, right? We're going to need the fopen call. This is going to get you familiar with the basics. You need to use the fgetC function to parse characters in a file that you get until you hit the EOF, the end of file. So if it's end of file, you can increment the counter before you reach the end of file. That's how you're going to be able to count the lines. So you can just create a local variable for the counter. And what you want to do to display is you want to display as output the total number of lines in the file itself. Right? So this is going to be a basic program that gets you familiar with the basics of file input and output. Specifically, always want to open up a file using fopen. We're going to get familiar with that file pointer. We're going to have to close our file, and then we're going to use that important fputC function. So your while loop, you're going to have to create a local variable that's just a counter, and as you're reading in each character, you can compare the character to the line feed that's returned. And if you have a line feed, then you want to increment the counter so that you count each line. Whole purpose of this function is to count the number of lines in a file. So good luck. We'll be using the basics here, and I hope this gets you familiar with using a file pointer and opening a file in FKIT-C. Thank you.